back to our channel. So from today I'm going to discuss to you about one more subject called compiler design. So in today's session we'll discuss about the introduction to compilers, and in the further sessions we'll see the concepts of this particular compiler design. Now coming to the compiler, so what is meant by this compiler? So this compiler is also known as language translator. Language translator. So that means which will convert from one language to another language. So for example, it is a compiler. So the input for this compiler will be the high level language. The high level language. Right? And the output of this compiler will be the low level language. Low level language. So low level language is also known as object code. Object code. So this is the language which can be understood by the computer. So we can't write the instructions which the computer understands, that means either zeros or ones. So that's why we will write the instructions in our own language, which is in English sentences. So that language we call it as a high level language, and this high level language can't understand by the computer. So that's why we are using some language translator, a compiler, which will convert the high level language to the low level language. So the steps are, first we need to write the instructions. So these instructions will be given to the compiler. So in this compiler, it will check the rules, whether the instructions are written based upon the rules set by the compiler. So some set of rules will be given by the compiler, some set of rules. So it will check whether the instructions are written according to that particular rules or not. So if any instruction was not equivalent to this set of rules, that means if any instruction violates this set of rules, automatically it will raise an error. It will raise an error. So these errors are known as syntax errors. Syntax errors. Right? So the compiler will return the syntax errors. So once the errors are rectified, automatically the object code will be generated. That means which the system can understand. So this is also in the form like this, right? So this is the source code. This is known as the source code. We call it as a source code, which is in a high level language, which was written by the user, and that will be given to the compiler, and finally we'll get the output as an object code, right? So in our further concepts, we'll see how this compiler was designed, right? So what are the steps to convert the source code to the object code? So all these concepts will be covered in our further sessions, right? So this is the concept of compiler, and there is one more translator, language translator called interpreter, which is different from the interpreter. So which is different from the compiler, because what is the difference means the compiler will take the complete source code as an input. So it can give multiple errors. It can give multiple errors at a time, but interpreter will execute a line by line. The instruction by instruction will be converted into machine code. Instruction by instruction or a line by line conversion will be done. So at a time we will get only one error in the interpreter. We get only one error in the interpreter. So unless you solve this error, so next it doesn't consider the next line or next instruction, right? So apart from this compiler is a language translator. Now I hope you understood this working of this compiler. In the further sessions we'll go in depth how the compiler will it will convert the source code to object code. In this session we'll discuss about one more topic in compiler design. So that is a basic language processing system. So in the previous session we have discussed about the introduction to compiler. So in that we have seen that compiler, what exactly the compiler will do. So the compiler will take the high level language as an input and it will give the low level language as an output. So how this process will be done is called this language processing system. So first the input will be the source code, that means the instructions written in the high level language. So this is the source code, we should call it as a source code, and this will be given to the preprocessor. Preprocessor. So in any language there will be some instructions that can be executed before the code is given to the compiler. So for example, in C language, consider C language. So in C language there are instructions like macros or defining a constants. Defining constants. So like this, these instructions must be executed before giving the code to the compiler. So these processes will be executed by the preprocessor, and after that we'll get the preprocessed code. Preprocessed code. So it is not mandated that every code will be having these macros and defining a constant, but if our instructions are having these macros or defining a constant, so those instructions will be executed in the preprocessed stage, and we'll get the preprocessor code and that will be given to the compiler. Now it will be given to the compiler. So the compiler will execute this pre-processed code and it will generate the assembly code. Right? It will execute the assembly code. Assembly code. Okay, so this assembly code will be given to the assembler. So assembler is also a language translator, so it will translate the assembly language to the low level language, machine level language. Right? So this assembler will consider this assembly code and it will convert it into the machine level code. So that means the output from the assembler will be object code. So object code itself is a machine code, so which can be understood by the computer only. Right? And this object code will be given to a linker. So linker is a process which will link all the DLL files as well as some these object codes and to form the executable code. So here it will link all object codes. That means if there are any multiple codes, it will link all those codes or libraries. So if you are including any libraries in our program, so all those libraries will be linking, and DLL files. So it will link all these things to form executable code. So the output from the linker will be the executable code, right? So executable code, and this executable code will be given to the loader. This executable code will be given to the loader, and this loader will load the exe code, executable code, to memory. So every instructions will be executed by the processor itself, right? So this executable code will be loaded into the memory and it will wait for the processor to get executed. So this is the process of converting the high level to executable code, execution of a program. Right? So first the source code. Source code is nothing but the instructions written by the user in a high level language. And first the stage is a pre-process stage where the pre-process instructions or pre-process directives will be executed, and from that it will be given to the compiler, which will convert into an assembly code. So this assembly code will be again given to the language translator called assembler, which will convert this assembly language to machine code or object code, and this will be given to the linker here. All linking will be done. So if there are any multiple object files and DLL files or libraries, so all these files will be get linked to form an executable code .exe, right? So here it is called .exe. So this .exe file, that means the executable code, will be loaded into the memory to get executed, and this process will be done by the loader. See, the first phase is lexical analyzer. So where the complete instructions will be divided into different tokens, right? So here the instructions will be divided into tokens, right? And from this, the output of these tokens will be given to syntax analyzer. And here it will construct the parse tree. And the same parse tree will be given as an input to the next semantic analyzer. So here the tree will be modified. And the main thing is the type checking will be done. Type checking or type casting. So that process will be done, and this parse tree will be modified accordingly. So parse tree will be updated, right? Based upon the type checking, the parse tree will be updated, and the same thing will be given as an input to intermediate code generator. So in this intermediate code generator, so a temporary variables will be taken and the instructions will be evaluated, right? The temporary variables will be used, and some sort of a code will be generated here, and from that again it will go to the code optimization. And by using this code optimization, and the temporary variables, the code written by using these temporary variables will be optimized. based on computation or memory, right? So we can reduce the memory requirement, or we can reduce the number of computations, right? So in order to, by reducing those things, we will optimize the code which is given in the intermediate code generator. And this optimized code, from this optimized code, we'll go with the code generation. And here, by using the 3 address code, the instructions will be given. Right? So by using this 3 address code, the instructions will be returned. So this is the phase. Right? The first one is a lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and the code generation. So for all the things, only one thing is input. So that is symbol table. So from this symbol table, the instructions will be given as an input to all these phases, all these 6 phases. So these are the 6 phases need to execute by the compiler, right? So here the symbol table means, for example, the instruction is some C is equal to A plus B. You can see here C, A, B are IDs. So here in the symbol table, it will maintain all the tables, right? So ID, so this is one ID, right? ID1 is equal to ID2 plus ID3, right? So ID1, right? And ID2, see, this is A, ID3, this is a B, right? And is equal to and the plus other operators. So the instruction details, the details of instructions will be maintained in the symbol table, and from this symbol table, the instructions will be given as an input to the lexical analyzer. And in any phase, if any error occurs, so that will be given to the error handler. So here there is one more thing is there, that is an error handler. So I will just erase this one. I will write down the error handler. So because if there are any errors in any one of the stage, right? So that will be handled by the error handler. So error handling mechanism, right? So this error handling will handle the errors if any error occurred. So that we'll get the syntax errors. So once the syntax errors are rectified, then it will move with the next stage, right? See, so lexical analyzer, the tokens will be given, or we can say it as a lexenes, and here it is a parse string, and updated parse string. We can also call it as a syntax string, right? And here it will use the temporary variables for the instructions. And here it will be optimized code, optimized based upon the computations or memory. In both the cases, it will be reduced. And here we get 3 address code, that instructions will be written as 3 address code. So this is the phases of compiler, 6 phases. So lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimization, and the code generation. So let's stop here. Hope you understood. From the symbol table, the input will be there, and if there are any error in these stages, automatically that will be written, that will be taken by the error handler, right? And see, so these are called nothing but syntax errors. So whatever the errors we got during the compilation are called syntax errors. So we can simply rectify those errors. It's very simple to identify, and we can also easily solve those errors. So let's stop here. So hope you understood these phases of compiler. So in the next session, we'll see one example, and we'll take one instruction, single instruction, and we'll see the output from each and every phase. So how the instructions will be compiled. So we'll take only one instruction, and we'll see how the instructions will be compiled. So grouping phases of compiler. So in our previous session, we have discussed about what are the different phases of a compiler. And all these phases will be categorized into 2 passes, right? So here, phase, we are talking about 2 different terms. One is a phase, which are nothing but a units or stages that a program runs during compilation. So whenever we compile a program, so that particular unit or a stages, that means the program, the source code will be running towards a different stages, right? So we have seen 6 main phases. One is a lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, and a code optimizer, and the target code generator. So these are the 6 different phases where the source program will be converted to a machine code, right? So next we are grouping all these 6 phases into different passes. So we are calling it as a passes. What are meant by passes? So how many times the program, so here the program means a source code. The program compiles or runs. Okay, so how many times the compiler runs the source program? So these are the passes and these are the phases. So here we are having 6 phases. 6 phases. So we named it as a lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and target code generator. So 6 phases. And here passes means we are reducing the compilation time. So these are of two types. So one is single pass compiler, or one pass compiler, or you can also call it as a one pass compiler. Whereas the second category comes under two pass compiler, or multi-pass compiler. So now we'll see what is a single pass compiler and what is a two pass compiler or a multi-pass compiler. Now, coming to the single pass compiler, coming to the first category, single pass compiler. So here all the 6 phases will be grouped into a single category. Okay, so all phases will be grouped into single category in a single form, right? So whenever we give the source program, whenever we give the source code, first a lexical analyzer, the source code will be given to the lexical analyzer, and from that it will go with the syntax analyzer, from that it will go with the semantic analyzer, from that it will go with the intermediate code generator, from that it will go with the code optimizer, and from this it will go with the target code generator. So these are the different phases involved, right, in order to compile any of the source code. So we know that a compiler will convert the source code from one language to another language. Usually this source code will be in a high level language, and the output of the target code generator will be the machine level language. So these are the different phases, okay, whatever the thing we have discussed. So all these phases will be grouped into a single category. It is called as a single pass. So the complete program will be given as an input. Okay, the complete program will be given as an input to this compiler, right? So this one pass compiler, right? So that is a single pass, only one time. The complete program will be given a single time, right? So every line of the code will be executing in all these phases, different phases. So what will be the output of each phase? I have explained in our first session. So different phases of this compiler, right? So I'll post the link in the description. So just go through that link. Now coming to the multi-pass, or we are simply saying it as a two pass. So the name itself indicates here all the phases will be grouped into two categories. Right? And these two categories we call them as a two passes. Here categories we call them as a two passes. So the first pass usually call it as a front end. It's called as a front end, and it's also called as an analysis pass. Okay, so what happens here? So this is completely depends upon source code, and independent upon target code. So whatever the target, that is no problem. I mean that is not an issue for this particular pass, right? So that mainly depends upon the source code, not the target code. So which code the compiler should be translated. So that doesn't need here. The first pass is always a front-end analysis and front-end pass or an analysis pass. So where the analysis will be done only on the source code. So here the second one is called a second pass, and this is called as a back-end pass. Quite reverse or quite opposite to the first pass. So this is completely synthesis pass. Pass. So what happens? This mainly depends upon target code, not on the source code. So to which we have to be converted, to which the source code should be converted, and independent upon source code. So it doesn't depend upon the source code from which the code has been generated, right? So these are the two different passes. So the complete phases which we have seen will be categorized into two different passes. The first three phases, so lexical analyzer, syntax analyzer, and the semantic analyzer, all these three phases comes under the front end, because those three, in all the three phases, that depends upon the source code. And the output from this first pass will be the intermediate code generator. So some sort of intermediate code will be generated, and from that intermediate code, the next second pass will be started. So that means the code optimization and the target code generation will come under this second pass. So the first pass will be having the three phases, and the output of first pass will be the intermediate code generator, which will be the mediator between the first pass and the second pass. And the second pass will be two phases, that is a code optimizer and the target code generator. So I'll write here. So if this is a source code, so that will be given to lexical analyzer, and then syntax analyzer, and then semantic analyzer. So these three phases will be the first pass. This is a first pass or front end, or we can call it as a analysis pass. Okay, the output of this one will be intermediate code generator. Intermediate code generator will be the output, and from this code generator it will go with the code optimizer and code generator. And all these two comes under the second pass or backend or synthesis part. Okay, and from this we'll be getting the target code. So from the source code, first it will be given to the first pass or front-end path or analysis pass, where the three categories, that means the three will be implemented, both the lexical analyzer, syntax, and the semantic analyzer, and it will generate some intermediate code, and from that it will again gives as an input to the second pass or a backend pass or a synthesis pass, where the code generated called optimizer will be happens, and from there we'll get the target code. So this is about the multi-pass compiler or a backend pass compiler or the two-pass compiler, right? So in order to reduce the complexity, the complete phases were divided into two categories, that is one front end and the back end. And these passes, we call it as a one pass and a two passes. Okay, phases and passes both are different. And again, in the passes, we are having a one pass and two pass. Coming to the phases, we are having 6 phases.
Hello friends, welcome back to our channel. So in today's session, we'll discuss about the follow set and first set in compiler design. So first of all, let us know the importance and why we are finding the first and follows and where it will be used. So here, the first and follow sets are used in lexical analysis phase, and the first and follow sets are used by the parser to apply the correct production rule. And before calculating the first and follow set, make sure that the grammar doesn't have the left recursion. So if there is any left recursion in our grammar, first we need to remove the left recursion, and then we need to calculate the first and follow set. So let us see the steps to be followed to calculate the first set. And here consider alpha as terminal and beta as non-terminal, right? So if the production is in the form x tends to epsilon, then the first of x will be only the epsilon. And if the production is in the form x tends to alpha, that means only terminal, then the first of x will also be the terminal itself, only the terminal alpha. And if x tends to alpha followed by beta 1, beta 2, that means non-terminals, terminal followed by the non-terminals, then also the first of x will be the terminal itself, right? And if the production is in the format of x tends to beta 1 and beta 2, that means the set of only non-terminals, then the first of x will be the first of beta 1, if it doesn't have epsilon. If it doesn't have any epsilon, then only the beta 1, the first of beta 1 will be the first of x. And if there is an epsilon, so first of x, right? So then the first of beta 1 without epsilon union and first of all the remaining, so beta 2, beta 3 and so on, right? So you have to repeat the same process. Until you get the first of last, that means without the epsilon. So don't worry, so we'll see a few examples so that if you are having any still doubts, that will be clarified. So just remember this one. So x of epsilon, then the first of x will be the epsilon, and x of terminal, then first of x will be the terminal. And if the production is in the format of x tends to alpha, beta 1, beta 2, that means a terminal followed by n number of non-terminals or terminals, then the first of x will be the terminal itself. And here, if the x tends to non-terminal, set of non-terminals, then first of x will be the first of non-terminal 1 if it doesn't have the epsilon. If it is having the epsilon, then you have to consider the first of beta 1 without epsilon union first of all the remaining non-terminals. Again, you need to repeat the same step. Okay, so repeat same for this particular one. That means again you need to find the set of non-terminals. First of set of non-terminals. Again, repeat the same process. Right. Now we'll take one example and we'll solve. So let us take this example. S tends to A, B, D, H, B tends to C, C tends to B, C, and epsilon. These are the two productions for C. And E is also having two productions. One is G and epsilon. F is having two productions, F and epsilon. Now first we need to write first of S. We need to find first of S, and similarly first of B, similarly first of C, and first of D. Let us write all the things which we need to find out. First of E and first of F. We need to find all these things for this particular grammar. First, let us know whether this grammar is of left recursion. Left recursion means whatever the non-terminal on the right hand side, the left hand side production should start with that particular symbol. So here we are not having any left recursion, right? So we are not having any left recursion. So directly we can find out the first. So let us see this one, E and F. So these are the individual productions. So E tends to non-terminal, F tends to E tends to terminal, and F tends to terminal, and E tends to epsilon, and F tends to epsilon. Now you can say, so see, if x tends to epsilon, the first of x is epsilon. If x tends to a terminal, then first of x is terminal. So apply the same thing. So f of E is equal to G comma epsilon, because these are the two productions for E. So one production is E to G, another production is for E to epsilon. So we need to consider this one and consider F. So F tends to F and F tends to epsilon. So one is a terminal, another one is an epsilon. So simply you can write F and epsilon. And now you can see C tends to BC and epsilon. So C tends to BC. Here it is a terminal followed by the set of non-terminals. Now, so we can simply say the first of C can be B and epsilon, because C is also having two productions, BC and epsilon. C tends to epsilon, so first of C will be having epsilon, and C tends to BC. That means in the previous thing we have observed that if X tends to alpha, beta 1, beta 2, that means the production starts with the terminal followed by the non-terminals. Then the first of X will be the terminal itself. So B followed by a non-terminal. So we can simply write it as a B. And here you can see it is also a terminal followed by a non-terminal. So simply we can say it as a C, small c. Okay. And here coming to the S, here also a terminal followed by the non-terminals. So simply we can say it as A. Coming to the D. So D is having two non-terminals, E and F. So what we have to do? The first of E, right? So whether it's having epsilon or not, you can check. E is having epsilon, right? So we need to consider first of E without epsilon union first of F. So simply you can say EF means first E is having the terminal, so G, apply the G, and it is having epsilon, so apply epsilon on in place of E. So it has been gone, so the production is only F. Now we need to find the production for F, right? So what is the production for F? It's a first of F. It's a first of F. First of F means F comma epsilon. So F comma epsilon. So these are the first for given following grammars, right? Now we'll see one more example. Here you can observe the example: S tends to A tends to AB and AD, and B tends to B. So first let us check whether it is having the left recursion. So this production is having the left recursion. A tends to AD. A tends to AD. So this is having left recursion. So we need to remove the left recursion. So I have already uploaded the video how to remove the left recursion. I will post the link in the description section. You can just follow that one. So after removing the left recursion, the productions will be like this, right? Now find out the first of S and first of A, first of A dash, and first of B. Now coming to here B. So B is having only terminal. So first of B will be a B. And coming to the A dash. So it is terminal followed by the non-terminal and epsilon. So simply you can write it as D comma epsilon. And A, first of A. So here also it starts with the terminal, right? It starts with the terminal. So we can simply use A. And S tends to A. Only one non-terminal is here. So we can simply write it as first of A, right? S is first of A. So first of A is A. So this is a first set for all these productions, right? So let us take one more example here. Consider this one, and first of all find out whether it is having the left recursion or not. So here in this we are not having any left recursions, right? So we are not having the left recursion. So find out the first. So first of S, and we need to find first of L, and we need to find first of L dash, first of L dash. So coming to the S, we are having, this is a terminal, right? Other than the uppercase letters, everything will be the terminal. So parenthesis is a terminal, right? Terminal followed by the non-terminals. So obviously it will be left parenthesis and A. It's a terminal, so we can simply write it as A. And coming to the L, so first let us fill with the L dash. L dash is also having a terminal followed by the non-terminals. So comma and epsilon, comma and epsilon. Now let us consider the first of L. So first of L is S. So yes, whether observe S is having the epsilon or not. If it doesn't have the epsilon, simply the first of S will be the first of L. So here S doesn't have any epsilon. First of S doesn't have any epsilon. So simply you can say the first of L, S will be the first of L. So this is how we can find the first, right? So once again I will repeat the steps. So let us assume that alpha is a terminal and beta is a non-terminal. If the productions are in the form of X tends to epsilon, then the first of X will be the epsilon, and X tends to terminal, then the first of X will be the terminal, and X tends to terminal followed by the non-terminals, then also the first of X will be the terminal. And if the production is of the form X tends to a set of non-terminals, then consider the first of X will be the first of beta 1 if it doesn't have the epsilon. If it having the epsilon, then first of X will be the first of beta 1 without epsilon, and union the first of all the remaining things, and repeat the process, same process, until it doesn't have the epsilon, right? So this is the procedure to find out the first set. Welcome back to our channel. So in today's session we'll discuss about how to calculate the follow set in compiler design. So first let us see why we need to calculate the follow set and where it will be used. So the first and follow sets are used in lexical analysis phase, and the first and follow sets are used by the parser to apply the correct production rule. And before calculating the follow set, we need to calculate the first, and then we need to make sure that the production should not contain the left recursion. If the productions are there, if the productions contain the left recursion, we need to eliminate the left recursion, and we need to calculate the first and follow sets, right? Now let us see the procedure to be followed in order to find the follow set. So the first step is consider star in a follow set of start symbol. So for any start symbol, consider dollar as a one set value, right? And next, let us consider alpha as a terminal and beta as a non-terminal. Then if the production is of the format X tends to alpha followed by beta, that means here we need to follow that the non-terminal should be searched on the right hand side. So this follow will search non-terminal, this is most important, non-terminal on right hand side of the production, right? So you can see the follow of beta. So beta is on left hand side, sorry, right hand side, right? Then there is no other non-terminal or a terminal after the beta. So then simply you need to write follow of x. So once again I'm repeating, if the production is of the format x tends to alpha beta, where beta is a non-terminal, and we need to follow the we need to find the follow of beta, and here after beta there is no other symbols, either terminal or non-terminal. So that's why simply we need to assign the follow of x to the follow of beta, right? Then if the production is in the format x tends to alpha y beta, where y and beta are non-terminals, so let us take y and beta are non-terminals, and simply if you want to find the follow of y, so simply that will be the first of beta, where beta is also a non-terminal beta, and if epsilon is not in first of beta, if the epsilon is not in first of beta, if epsilon is there, then simply apply this epsilon in terms of beta, right? So that we'll get the first of beta without epsilon union the follow of x, So simply you need to apply the epsilon here, and if there are any other non-terminals, again you need to repeat the same process. If there are no non-terminals here, simply it will be the follow of x, right? See, so let me explain one example. So now let us consider the example. So first we need to find out the first. So this already done in the previous video. So now we'll find the follow. So follow of S and follow of B, follow of C, follow of D, follow of E, follow of F. We need to find all these things. First let us find the follow of S. So search S on right hand side, right? So there is no S on right hand side. So S is a start symbol, so we need to include $. And coming to the B, so search B in the right hand side. We are having the production this one, so only this production we are having. So simply you can say A, B, D and H. So what is the follow of B? Say D. D is a non-terminal. So simply we need to consider first of D if the first of D doesn't have the epsilon. So first let us check the first of D. So first of D is having, first of D is having G, F and epsilon. Write down G, comma F and epsilon. Now apply the epsilon on D. So A, B, epsilon, H. So this will be A, B and H. Now what is the follow of B? It's a terminal. So if it is a terminal, simply write down the terminal. Okay, if it is a non-terminal, we need to consider the first. If it is a terminal, simply consider the terminal. And see here, follow of C. So find the C on RHS. C on RHS. So what is the C on RHS? You can find this one and this one. So after the non-terminal C, there is no other terminal or non-terminal. So then we can simply follow the follow of B. So it will be the follow of B. So follow of B is nothing but G, F and H. And coming to the D, find out the D on right hand side. So here we are the production A, B, D and H. So what's the follow of D? It's a H. That's a terminal. So simply you can use the terminal itself. And follow of E. So here we are having E. So E and F. So follow of E is having F. F is a non-terminal. So then we have to consider first of F. If it doesn't have the epsilon, first let us find out first of F. So first of F is having the epsilon. So apply the epsilon here. So applying the epsilon here, so E and epsilon, so that is nothing but E. So E doesn't have any other terminal or non-terminal because we are finding the follow for E only. So then automatically it will be having the follow of D. So what's the follow of D? H. And follow of F. So follow of F you can observe only here it is there. So after the F we are not having any terminals or non-terminals. So simply the follow of F will be the follow of D. So follow of D is H. So this is how we have to find out the follow. So if there is an epsilon, simply apply the epsilon and again consider the follow of that particular remaining. And if the follow of a non-terminal is a non-terminal, then again you need to apply the first of that particular non-terminal. Right? Now we'll see one more example. So let us see. So in this example we have find out the left recursion and we have removed the left recursion. So these are the productions after removing the left recursion. Now we need to find the follow. So follow of S and follow of A and follow of A dash and follow of B. So if follow of S, so S is a start symbol, so it's simply $, include the $. So find out the S here, so there is no S available, so simply consider this one. And follow of A, so there is no A here, only in this production. And A doesn't follow any other terminal or non-terminal. A is the last production, last terminal, last non-terminal, right? So then simply the follow of A will be follow of S itself. So follow of S is $. And consider A dash. So A dash is also a last terminal, last non-terminal. So after this A dash, we are not having any terminal or non-terminal. So that's why we can simply say that follow of A dash will be the follow of A. So follow of A is dollar itself. Coming to the B, so we are having a B here. So A, B, and A dash. So this will be first of A dash. First of A dash. What is the first of A dash? D and epsilon. So simply consider D and apply the epsilon in this production. A, B, epsilon. So that will be AB. So now we need to follow the B. So B doesn't have any other terminal or not terminal here. So we need to simply give the follow of A to follow of B. So D and dollar. So this will be the follow of given productions, right? And consider one more. So here you can see there is no left recursion. So we need to follow of S, follow of L, and follow of L dash. So if it is yes, see, first we need, if it is yes, we are having S of L dash, right? And also here. So first let us consider the L and L dash. First find out the L and L dash. Follow of L. So you can see L is here. So follow of L will be the right parenthesis. Right parenthesis. Right? So coming to the follow of L dash. So L dash is the last one. So there is no terminal and not terminal after the L dash. So the follow of L dash will be the follow of L. So follow of L will be right parenthesis. Now consider the S. So both productions we are having this one. So yes, L dash. So that means we need to consider it as first of L dash. So first we need to include dollar because S is a start symbol. First of L dash is comma. So here you can see comma and epsilon. Comma and apply the epsilon here. So yes, epsilon. So that is simply yes. Okay. So there is no other symbol after the non-terminal yes. So simply we can follow the follow of L here. If you consider this one S L dash. So L tends to yes L dash. So L we are applying epsilon on L. So L tends to yes. So there is no terminal or non-terminal after the symbol yes. So that's why follow of yes will be follow of L. What's the follow of L? Right parenthesis. So right parenthesis. So follow of yes will be dollar, comma, and right parenthesis. So like this we need to apply the follow. So if the follow of a non-terminal will be having a terminal, so simply that terminal will be the follow. And if the follow of a non-terminal will be the non-terminal, so what we have to do? We have to find out the first of this non-terminal, and if it doesn't have the epsilon, if it having the epsilon, apply the epsilon on the production and find out the new production and find the follow of that particular new production. So like this we need to find the follow of this particular grammar. So
compiler, construction, tool. So we know that a compiler is a translator which will translate from one language to the another language. So that we have seen in the introduction part, right? So usually the high level language will be converted into machine level language. So this high level language to the machine level language, so it involves in a different phases, right? So around 6 phases we have seen. So the program will be moved towards 6 phases and finally we'll get the machine code. So in order to construct this compiler, this translator, so there are different tools available. So we'll see what are the different tools that are being used for constructing a compiler. So the first one is a scanner tool. Scanner tool. So first I list out all the tools and then we'll elaborate it, right? Scanner tool, parser tool, syntax, directed, translation engine. And the next one, data flow analysis engine, the code generator, and the last one is compiler construction toolkit. Right? So these are the different tools which are available during the construction of a compiler, So first coming to the scanner tool. So for this scanner tool, the input will be the program which we are giving is in a high level language that can also be given as a instructions, a grammatical instructions is an input, and the output, so I write here, for everything we'll write input and output so that it will be good. So input and output. So for this scanner tool, the input will be the program and the output will be the lexical analyzer. That means it gives the tokens. Okay, the complete program will be scanned for different tokens which are available. So we know that a token is an individual unit of a program. So it finds or it scans the complete program, complete instructions, and it will return some tokens. So the example tool for this scanner is a Lexical tool. So there is a tool called a Lexical tool which will scan the complete program and it will send or it will give the output as a tokens. And coming to the parser tool, the name itself indicates it will create a parse tree. It will generate a parse tree. So for this, the input will be the tokens, different tokens, and all these tokens will be analyzed whether they are syntactically correct or not, and then they will be producing or generating the parse tree. Parse tree. Right? So the input for this parser tool will be the tokens and the output will be the parse tree. So once the parse tree has been generated, the next one, syntax directed translation engine. So it will be having a lot of functions which will walk through about this parse tree and it will generate the intermediate code. So whether that is correct, whether they are syntactically and semantically correct, then automatically the intermediate code will be generated. So the input for the syntax directed translation engine is a parse tree. So the complete parse tree will be analyzed in every part. Okay, so it will be having a lot of functions. So it will generate the intermediate code. It will generate the intermediate code. And the example for parser is YACC tool. So in our further sessions we will be discussing about this tool. Okay, don't worry, just remember the tools. So this is a Lex tool and a YACC tool. And here the parse tree will be the input for the syntax directed translation engine and the output will be the intermediate code. And now the next one is a data flow analysis engine which will take this intermediate code as an input. This intermediate code as an input and it will produce the optimized code. So it will eliminate the unnecessary instructions, okay, unnecessary instructions, and it will make the code as an optimized, that means the best code. So the output will be the optimized. So this data flow analysis engine will be acting as a very important thing in the code optimization, optimized code. So once the code has been optimized, that means the best, and that will be given to the code generator which will generate the machine code. So the input for code generator is optimized code, and the output will be the machine code. Right? So all these things we have seen in the phases, different phases. But here, these are all the different tools which are available to generate the tokens, to generate the parse tree, to generate the intermediate code, to generate the optimizer code, and to generate the machine code. Right? So, and the last one is a compiler construction toolkit. So here the name itself indicates it's a toolkit. It's a combination of these tools. Okay, so it is an integration and a combination of all the above tools. So it may be integrated with the 1 or 2 tools, or it may be integrated with the 2 or 3 tools, or more than 2 tools. Right? So this is a combination of compiler construction tools. So if we combine 1 or 2 tools, then we can call it as a toolkit. Okay, toolkit. Right? So these are all the compiler construction tools. So scanner tool, parser, syntax directed translation engine, as well as a data flow analysis engine, code generator, and a compiler construction toolkit. So hope you understood about these compiler construction tools. Lexical analyzer. So what is the role of lexical analyzer? Right? So in our previous session we have discussed about different phases of a compiler, and then we have seen the grouping of different phases into different passes, 1 pass compiler, 2 pass compiler, and then we have seen a different compiler construction tools. Right? So now we'll go with the first phase, that is a lexical analyzer. So what are the roles? So first, before going to the roles of lexical analyzer, so what is the input for this lexical analyzer and what is the output for this lexical analyzer? So the input for the lexical analyzer is the program. It's a program which is written in high level language, so, right? And we know that the compiler input is the main aim of compiler is to convert the high level language to the machine level language. So obviously the input will be the program, and that will be given to the lexical analyzer, which is the first phase of a compiler. So it will be given to lexical analyzer. Then what will be the output of this lexical analyzer? So the output of this lexical analyzer will be tokens. So which will be the input for the second phase. Okay, so the tokens, and also it will be maintaining the symbol table. So this lexical analyzer will also maintain a symbol table. Okay, so now we know the input is program and output will be the tokens. I write here output. Now exactly what is a token? So this token is a group of characters. A group of characters. Okay, and this is a small individual unit of a program. Small individual unit of a program is called token. So there are different kinds of tokens, and these tokens are categorized in different ways. So categories. The first one, keywords. So every compiler will be having a few keywords. That means the result words are given by the compiler which have the specific functionalities. And similarly, identifiers. So which identifies the memory location. Okay. Similarly, operators. Operators. So usually operators we know for computing purpose, right? So we have seen a lot of operators in C programming. So like addition, subtraction, multiplication, division, bitwise operators, logical operators, okay, assignment operators, all these comes under these operators. And next is separators. Separators. Separators means by separating a different identifiers in a program. So for example, if we want to declare two variables, what we will be declaring? So int some a comma b. Okay. So this is a small statement we are writing to declare two variables. And now this will be a token 1 and this will be a token 2 and this will be a token 3 and this will be token 4. So this individual unit of a program, we call it as a tokens. And see this comma, this one also a token, right? So this is called a separator. Usually we can write it as a 4 and this is a 4 and this will be the 5. Okay, 3, 4, 5. Right? So this separators means separating one instruction with another instruction. So usually we use a separator semicolon to end the instruction. So semicolon will come under the separator, and as well as in order to differentiate two different variables, we are using a comma. So comma will also come with the separators. And also some symbols. We will be using some symbols. Okay, we'll be using some symbols in our program. So you can say the curly braces. These are the symbols which we are using to represent a block, and parentheses which represent usually for a function. Okay, so these will be called as a symbols. So all these grouped together, we call it as a tokens. Okay, all these grouped together, we call it as a tokens. So the collection of tokens, arranging the tokens in a grammatical format will give some instruction to the computer or a compiler, right? So tokens are this one, and from a program, we should get the tokens as a result. And the group of characters, see one more concept, a group of characters which represent token is lexeme. Lexeme. Okay, lexeme means it's a group of characters which represents the token. For example, we are saying this int as a token. So int will be one lexeme. And similarly, A is one lexeme, B is another lexeme, comma, semicolon, and parenthesis, open parenthesis, close parenthesis, I mean curly braces, open parenthesis, close parenthesis. So all these comes under lexemes, right? A group of characters which represents the tokens, okay, which match the pattern of a token is called a lexemes. So this symbol table will be having the lexemes and the corresponding tokens. Okay, so lexeme and token. The symbol table will be having a two fields, lexeme and token. So we'll see one by one. So now it will be processed, the input program will be given to the lexical analyzer and it will be processing the input and it will give the tokens. So what happens here is a question. Okay, so we are giving a program here. For example, let it be some C is equal to A plus B. This is the instruction of one program, I mean in a program. So output will be C is equal to A plus B. So these are the group of tokens. All these are the different tokens. How many tokens? So 5 tokens are there. These are 5 tokens. For example, if you are having a semicolon and you have to include the semicolon also. Okay, semicolon. So it will be a total of 6 tokens. So we are giving the input and we are getting these tokens. And what happens in this lexical analyzer? How the instruction will be converted into tokens. So that we'll see one by one. So the immediate step. The first thing is giving a program, that means a sentence or an instruction given to the compiler. So what happens here, the first role is it will remove all the comments and the white spaces in the program. So we know that if we write any program with a comments, and those comments will not be executed by the compiler. You can observe that. So you might be having an experience with that, right? So we are supposed to write some comments in the program by giving some titles, okay, and that will not be implemented, or that will not be executed by the compiler. So because the first step, it will eliminate comments. Whatever the comments we have written in the program, those comments will be eliminated. And also any white spaces, the extra spaces, okay, any extra spaces will also be removed, okay, and unessential symbols, okay, which doesn't obey the rules of the compiler. So all these things will be eliminated from the instruction. That's the first thing happens. And the next one, after eliminating that, so the instruction or program, or instruction will be divided into tokens. So this usually we call it as a tokenization. So division of the complete instruction into different small units or small parts. So usually we call it as a tokens. Now after that, what happens? So the grouping of tokens will be happens. So the tokens will be categorized. So grouping or classifying, okay, grouping of tokens will be done. That means, so what comes under the operators, what comes under the identifiers, what comes under the separators. So like that, the complete tokens will be classified. And then the next one is all the tokens, each and every token will be validated. So the next is each and every token will be validated. That means, so we know some rules given by the compiler to represent the tokens, right? For example, take the identifier. So we know some rules that we have to follow in order to give a name for the identifier, right? So it will check whether the complete rules have been followed, right? Whether the identifiers are valid identifiers or invalid identifiers. So that will be done here, right? So there will be few valid identifiers and invalid identifiers. And finally, after completion of that, tokens will be generated. So a list of tokens will be generated. And also it will maintain some symbol table. Okay. So for example, so some valid tokens and some invalid tokens in a program, right? So valid tokens are, we know the keywords, just now we have mentioned keywords, identifiers, operators, separators, some symbols, some special symbols. And invalid identifiers or invalid tokens will be spaces, macros, escape sequences, etc. So all this comes under the invalid token. So this will be done in this particular step. Okay, so each and every token will be validated. So it will group what are the valid tokens and what are the invalid tokens. Now we'll see an example and we'll see all these things. So I'll erase this one. Hope you understood the difference of valid and invalid. So for example, let us take some int main, int a comma b. Okay, and I write a small program. Okay, let us take this one, c is equal to a plus b, and close it. Okay, small program. Now we can say, let it be. I'm writing here comments. So addition. So what happens here? The first one, it will eliminate the comments. So these comments will be eliminated. The first step. Second step, program instruction will be divided into tokens. What are the tokens here? So int main parenthesis open close c is equal to a plus b colon, and also let us write here c is equal to, I write here a plus b. Okay, yes. So these are the different tokens in our program. So int main open parenthesis close parenthesis So curly braces, C is equal to A plus and B. So this is the second step. This is the first step. We have eliminated the comments, and this is the second step. And the next one, grouping of token will be done. What are the groupings? So you can say this is an identifier, this is a parenthesis, or we can say it as a symbol. Okay, and this is also a symbol, and this is a keyword, and this is a symbol. This is an identifier, this is an operator, it's an identifier, this is an operator, and this is an identifier and also close the parenthesis, that will be a symbol. So grouping will be done here. Grouping will be done. And then each and every token will be validated. So it will check whether there are valid tokens or invalid tokens. So it will check all the things, and definitely that is a valid token. And then a list of tokens will be generated. So this is a complete list of tokens. And there is a concept of symbol table. So whenever whenever the program is divided into token, that will be reflected on the symbol table. See, the symbol table will be having the two things, as I said, one is a lexeme, another one is a token. Okay, so this one is a lexeme and this one is a token. Right? So A is a lexeme, which represents the token. And what type of token this one? This is an ID, identifier. So ID means identifier, right? So identifier is a token. So this is a simply this we can say it as a symbol table. See, this is a symbol table, right? For this program, these are the different tokens we got. Okay, so in how many tokens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So total 11 tokens were there in our program. So don't worry about the logic, okay? For a simplification, for your better understanding, I have written only one statement. So don't give in the comment that C, A, B are not identified, okay? They are not being declared here. So you can also declare that, but the number of tokens will be more, okay? That's it. So don't worry about the declaration and all the syntaxes. Just if the program consists of only single statement, these will be the identifiers, right? So there are total 11 tokens. And also we have missed about the semicolon, yes. So we have also missed the semicolon. This will be the separator. This will be the separator. So total 12 tokens are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So total 12 tokens were there. So a simple example for getting the tokens. So this will be the last one. Okay. So last step is a list of tokens will be generated. And also it will find the errors. It will also send the errors. So usually if you are trying to execute any C program, so first we will compile that. So before creating the bytecode itself, we will be getting some syntax errors. So here itself the errors will be displayed. So what kind of errors? So if there are any spelling mistakes, for example, if you are using only in, okay, instead of int, okay, instead of int, if you mention it as a in, so that will be some sort of spelling mistake, okay, because we are not having an in keyword, okay. So this one will be the one error. Okay, and appearance of a special character. So typo mistake. If typo mistake, there is some A, B, C after the curly braces. Okay, after this curly braces, if there is A, B, C, this is nothing but a appearance of unnecessary symbols. So that will also be deleted. So unessential symbols or unessential characters. So after the completion of curly braces, these are the unessential characters. These will also be removed. Okay, and unmatched string. Unmatched string. So usually in our C programming, so the string will be represented in the double quotations. Okay, so if you open the open quotes, and definitely we have to close the double quotes. So in this absence of double quotes, this is nothing but unmatched string. So this is also one type of error. And also exceeding the length of identifier. So that depends upon the language. For example, if you go with the C, so the maximum length of the identifier should be not more than 32 characters. So when you are trying to give any identifier with a length which beyond the 32, definitely it will raise an error. And that doesn't happen in Python. Okay, so that depends upon the language. That depends upon the language. So all these kind of errors will also be displayed during this lexical analyzer. Okay, we usually call them as a compilation errors or a syntax errors. Right? So these are the roles of a lexical analyzer. So we have seen how the input will be processed and how we are getting the tokens as an output. So this is the first phase of a compiler which takes the program instruction as an input and tokens as an output. So here we have seen everything. We have taken one example and we have taken this is a symbol table. So symbol table will also be generated here, right? So lexemes and the corresponding tokens will be available in the symbol table. So in our previous session, we have discussed about various phases of a compiler and how we have grouped them into parsers, and also we have seen a few compiler construction tools. And coming to the first phase, that is a lexical analyzer, and also we have seen the role of lexical analyzer, which is the first phase of a compiler. So we know that a lexical analyzer will take the program as an input, or simply we can say a set of instructions as an input, and it will produce a list of tokens. And these tokens can be categorized as operators, okay, identifiers, keywords, special symbols, separators, etc. etc. So this will be maintaining in a symbol table. So all these things we have discussed in our previous session, right? Lexeme and token, corresponding token. So all these things we have discussed in our previous sessions. Now we'll see how the instructions will be converted into this list of tokens. Okay, so with the help of input buffering. Now let us take an example. So int main. Okay, so this is a small example. Let us take an example. So like a is equal to or simply go with the int a comma b. A is equal to a plus b. Okay, so this is a small program, and now we need to identify the tokens. So first we know that the complete program, so this we call it as a program. So where it will be saved, this will be in the secondary memory. Okay, in the secondary memory. So whatever the data we are storing, that will be stored in the secondary memory. So while execution, what happens? This secondary memory will be, the data from the secondary memory will be retrieved towards the main memory, because the processor will execute only the information which is available in the main memory. So in order to convert the program into tokens, it requires to read each and every character from the secondary memory. Right? So it reads every character from main memory. Okay. So first the program will be copied into the main memory. So from the main memory, each and every character will be retrieved, and that will be identified. I mean, the control will identify the tokens, the category of tokens, right? So here, let us check. For example, it is a memory, right? So the complete information, let us take this information up to here. So I, N, T, space, M, A, I, N, open parenthesis, closed parenthesis, and again, sorry, this is a curly brace, open curly brace. So let's take this one. So the complete information will be loaded into the main memory in this way. Each and every character will be read. So here there will be two pointers. So the first one is begin pointer, or we can also call it as a Lexeme begin pointer. Okay, Lexeme begin pointer, and the another one is a forward pointer. Okay, so let us assume it as LBP, Lexeme begin pointer, and the FP is a forward pointer. So initially both Lexeme begin pointer and the forward pointer will be pointing towards the same location. So for example, so this is a forward pointer and the position of Lexeme begin pointer. So this is a position of Lexeme begin pointer. So the Lexeme begin pointer will remain same until it identifies the complete Lexeme, one Lexeme. Okay, and forward pointer will be keep on moving towards the right side for every control to read each and every character. So initially it will read I, and then this forward pointer will be moving forwards towards here, and again it will read N, and again the forward pointer will be moving towards here, again T, and again it will be forwarded towards the next one. So here it is a space. So whenever the forward pointer points towards either space or any other special symbol which doesn't meet the requirement of Lexeme, then it stops forwarding, right? And whatever the characters read so far, that means int, it will be stored in a symbol table. So the Lexeme, so this is a symbol table. So here it will be a Lexeme, and here it will be a token. So whatever the information read so far, int, so this will be treated as a keyword here. And now whenever the forward pointer points towards the space or a special symbol, then immediately the Lexeme begin pointer will be points towards the next one. So that means one lexeme has been completed. Now the begin pointer points towards the starting position of the next lexeme. Now again the forward pointer will be keep on going here. So this is a forward pointer. So then next m, and afterwards the forward pointer will be incrementing 1. So again it will be here m a, and then that forward pointer will be moving towards here fp. So ai, and again the forward pointer moves towards here, and it is m. Again the forward pointer points towards here, and you can see it is having a special symbol. So then again it stops. Now this main will be stored into the lexeme, and again the lexeme begin pointer will be pointing towards the next lexeme. So the next one is a parenthesis. Next forward pointer will be moving towards this one, forward step, right? Again there is a special symbol. Again the process stops, and this will be moving towards the symbol table. It will check whether it is available in the symbol table or not. If it is available, then it will be ignored. Nothing will be happen. If it is not there, that will be stored in the symbol table. And again, the lexeme begin pointer will be pointing towards here, LBP. So then next one is this one. Again, the forward pointer will be moving on this one. So again, it is a special symbol. So this will be again loaded into symbol table. So like this, each and every character of a program will be retrieved from the main memory. So because in order to execute anything, the processor will execute only the data in the main memory. So that data should be loaded from the secondary memory to the main memory. So for this retrieval, it will be using some system calls. In order to retrieve the data, it will be using some system calls to read the data. So if our program is having some 100 characters, what happens? It requires some 100 system calls. It requires some 100 system calls. So it is somewhat an overhead problem. Okay, it will be focusing on more system calls, right? So time taking process also, and overhead problem also. So in order to avoid that, so there is a concept called input buffering. So we'll use a buffer where a block of characters can be read in a single system call, using a single system call. So for example, so here, in this case, in the current situation, every character was being read, right? So how many number of characters are there, that many system calls will be used to read the data. Now some buffer will be used. The concept will be same. The beginning pointer and the forward pointer, the concept is same. But instead of reading each and every character continuously, so it will take some block of memory. So block of memory, so which we call it as a buffer, which can read a few characters at a time. Okay, with using a single system call. For example, so let it be some 6 characters. So first 6 characters will be read with a single system call, and then it will be processed with the next one. So these are the single 6 characters, for example, I am saying. So all these 6 characters has been retrieved with a single system call. So previously it required some 6 system calls in order to read all the 6 characters. So that doesn't happen here. So here that is called the concept of input buffering. So here the input is a program. Okay, input is a program. Output will be the tokens, different tokens. So here we are reading the input from the program. So in order to read the input, we are using some buffers. In order to convert the input towards the tokens, we are using some buffers. And here there are 2 types of buffers, single buffer and 2 buffers. So 1 buffer and 2 buffer. So 1 buffer and another one is 2 buffer. So as the name it indicates, 1 buffer means it uses only 1 buffer to read all the characters. Okay, so here the problem is, see, if it is a 1 buffer, so this is a 1 buffer. I am explaining about the 1 buffer. So that means only 1 buffer will be available. For example, let us take these 2 statements. So I, N, T, A, comma, B. Okay, so there is a problem. So what about the semicolon and then again the next statement? So immediately after completion of this buffer, the next colon will be here. So I will be replaced and semicolon will be placed. So overwriting will be done. There will be some sort of overwriting, because if the input size is greater than the buffer size, then obviously the data inside the buffer will be overwritten. Okay, so for example, so the buffer size is some 10 characters, and the input size is some 15 characters. What happens? So first 10 characters there will be no problem. So 11th character will be placed in the first position again. So that means whatever the character available in the first position will be replaced with the 11th character. So some sort of data missing may be possible here, and also there might be a chance of having the complete token also. For example, let us take the same thing, this one, int main. For example, if you consider int main and we are taking here, so int m a I. Okay, so what about the n? What about the n? So n will be placed here. N will be placed here, but here, so what happens? The lexeme is incomplete. MAI, the lexeme is incomplete here. So there might be some sort of inconsistency. So for this problem, we are moving on with the two buffers. So in these two buffers, so as the name itself indicates, two different buffers will be available. See, two buffers will be available with a n size. So different sizes will be there. So let it be buffer 1 and let it be buffer 2. Okay, so coming to these two situations. So whenever the first statement, so you go with here I, n, t, space, a, comma, b, semicolon. For example, let us take one more. Okay, let us take one more. So what happens? So whenever we want to stop reading, so the end of the buffer will be placed here with the help of EOF. So EOF is nothing but the end of file, which represents the end of the buffer. So whatever the characters read after the EOF, immediately the buffer 2 will be start filling. So same situation. So here also there will be beginning pointer and the forward pointer. So this will be keep on moving, and whenever the forward pointer points towards this EOF, immediately the forward pointer will be next pointing towards the starting position of the second buffer. So this EOF is an end of file, or also we can call it as sentinel characters. So we'll use that EOF in order to recognize the buffer is end. Okay, the buffer is end, so that we have to start filling in the second buffer. So the control doesn't know about anything. So we are only giving the some sort of sentinel character like EOF. So whenever the file pointer moves towards the EOF, immediately the file pointer will start filling the characters, the next characters from the second buffer. And here also it will start filling here. So what is the next solution? I mean next statement. So a is equal to a plus b, and this is a again end, so we can go with the EOF. So whenever there is a EOF, again the file pointer will point towards the first position of the buffer 1, because buffer 2 has been completed, right? Buffer 2 has been completed. So if the file pointer points towards the end of file for the buffer 1, next pointer will be on the starting of the buffer 2. And if the file pointer points towards the end of the file of buffer 2, the next character should be read at the first position of buffer 1. So like this, the characters will be read from the program. So each and every character will be read into a buffer, okay, with a single system call, and from this the complete symbol table will be developed. Okay, so it contains the different tokens of the program. So input is a program and output will be the symbol table. So where we will be getting all the tokens, a list of tokens, right? So hope you understood. So previously, in the absence of buffer, in order to read each and every character, then if there are n characters in the program, it requires a n system calls to read the data from the secondary memory to the main memory. And in order to avoid that, we are going with the buffers. We are taking some buffer, which is a block of memory where a group of characters can be read using only one system call. So that will be implemented with the two things. One is a one buffer and a two buffer. As the name indicates, one buffer means only one buffer will be there, and the two buffer means there will be two buffers, and one will be having one sentinel character or end of file, so which represents the end of that particular buffer, so that the file pointer will start filling the characters from the second buffer. If the file pointer points towards the end of the file of the second buffer, it indicates the file point. It is the end of the second buffer, and the character should be read into the first buffer. Right? So this is how a program can be sent to the lexical analyzer, and by using this input buffering, the complete symbol table will be developed where we can get all the tokens, list of all the tokens. Specification of tokens. So whenever the term called as a tokens, that means we are discussing about the lexical analyzer, the part of the phase of lexical analyzer. So because the output of the lexical analyzer will be the tokens, as we discussed in our previous sessions, right? Now here the question is, how can we specify a token? So mainly this token can be specified by using a regular expression. So by using this regular expression, any token can be recognized. Right? For example, if you consider an identifier, the compiler will decide the rules of identifier. What are the rules? So we know that the rules are identifier should start with either underscore or a symbol, but not the numericals, and followed by it can have any number of alphabets or any number of numericals, right? And except underscore, it should not accept any special symbols. So these are the some rules we are given, and if all these rules have been matched with the lexeme, then we can say it as an identifier. So we are just extracting each and every lexeme from the programming instruction, and we are checking with these regular expressions, and if it satisfies, we are considering it as a tokens, whether they are comes under the identifiers or keywords or operators, etc., etc. So the main specification for recognizing this token is a regular expression. And how this regular expression can be achieved? So with the help of a language. With the help of language. So how the language can be represented? With the help of set of strings. Set of strings. And how these strings will be represented? So it is a set of alphabets. Set of alphabets. And how these alphabets can be represented? These are nothing but symbols. These are nothing but symbols. So this is the hierarchy, how we can specify a token. So we in order to specify this token, we should know about the symbols, and by combining a group of symbols, we call it as a alphabets or strings, grouping of alphabets, and grouping of these kind of strings we call it language, and we'll decide the regular expression for this particular language. Right? Now we'll see one by one. So what is a symbol? So the first one is a symbol. So if you are watching this session, you might be learned about the automata theory. So in that automata theory, we have learned everything. So these are all the similar terms, so not similar, the same terms which we have used in the automata theory. So usually it is called as a ATFL or theory of computation, or FLAT. In some universities it will be calling as FLAT, formal languages and automata theory. Right? So once again we'll revise. If you are not aware about this one, so please visit that one. I'll post in the description section. So please visit that one. And even in this session also, you'll be understanding what about the symbols, alphabets, strings, etc., etc. So here the symbols are, anything can be considered as a symbol. For example, 0, it's a numeric symbol. 9, it's also a symbol. Small a, capital A, at the rate, dollar. So all these are the different symbols. Okay, different symbols. And usually all these we can call them as a alphabets. That means a single symbol, we call it as a alphabets. So you can know that 0 and 1 will be the binary alphabets. Okay, small a to z, these are the lowercase alphabets. Similarly, some capital A to capital Z, these are the uppercase alphabets. So some 0 to 9, these are the numerical alphabets. Numerical. Similarly, at the rate, dollar. Okay, all these are some symbols, special symbols. Right? So all these comes under the alphabets. Individual symbol, a single symbol, we call it as an alphabet. Now, alphabets. And now, what is a string? So a string is a group of characters. We are calling it as characters, and here we could call it as an alphabets. So, coming to the second category, that is strings. Strings. So strings are a group of alphabets. A group of alphabets. So more than one alphabet, we can call it as a string. For example, so let it be A, B, C. This is one string. Similarly, A, 1, 2, C, 4. This is another string. So A, B. So one more string. Okay. So like this, we can combine a group of characters and we can call. So here, usually the characters can be called as an alphabets. Okay. So a group of alphabets, we call it as a strings. And here we can perform a few operations on strings. So what are those operations that can be performed on strings? So the first one is a prefix. Prefix means, so the starting letters of the string, starting alphabets of the string. That means we can usually call as a leading alphabets. Okay. So for example, A, B, C, D. So this we call it as a prefix, and this we call it as a suffix. The last characters. Okay. The last characters we will call it as a suffix, and the first characters we call it as a prefix, because see, if you consider this A, B, C, D, so these are a group of characters and we can say this as a string, right? So consider this as a string. That means we are prefixing this particular string with this particular A. So that's why we are calling it as a prefix. For example, one more, A, B, C, D. If you consider this one, C, D as a string, then A, B will be the prefix, because the string is started with the A, B. So like that, the prefix means starting characters. Starting characters. Okay. So here, for example, if you consider the string as, see, I'm writing my name Sundeep. So if the string is Sundeep. Okay. Now the prefix will be, see, first one is an empty string. Okay, first one is an empty string. For example, here the empty string is represented as an epsilon. Okay, empty string is represented as epsilon. So we can say that epsilon is nothing. Okay, epsilon is a nothing. So if you write this one, it doesn't sense difference if you prefix with an epsilon. Yes? Yes. So epsilon dot Sundeep is nothing but Sundeep itself, because this is an empty string. And don't use this, don't imagine that this is a product. So if epsilon represents the length 0, then 0 into string is 0. So that's not a 0. So if you consider x as a string 1 and y as a string 2, if you write string 1 plus string 2, which is a concatenation, that becomes x and y. That becomes x, y. So here, even though we are writing x, y, it doesn't represent that it's a product. It is a concatenation. So always the concatenation will combine the strings. So here also the epsilon dot Sundeep. So here what is the prefix? For example, if you consider this as a string, what's the prefix? Obviously epsilon. And the same thing, you can represent it as Sundeep concatenated with epsilon. So it also does not change anything, right? So obviously, if you consider this as a string, what will be the prefix? So whatever the characters we are writing here. So this is the characters. If you consider UNDEP as a string, what is the prefix? It is a yes. If you consider NDEP as a string, what is the prefix? SU. If you consider DEP as a string, what is the prefix? SUN. So like that, the prefixes will be like this. Okay, all the leading characters, the characters starting from the string. So if you consider the part of string, the remaining strings on the left side will be the prefix. And similar to prefix, there is one more operation called suffix. Suffix. So quite opposite. That means ending characters. Ending characters. For example, if you consider the same thing, so let it be the string. So ending characters. So here again the string. Let us take the same thing. Okay. Now suffix. What is the suffix? What is the suffix? You can say that if you are writing this one, so if you consider the complete name as a string, what is the suffix? Epsilon. Okay, these are the ending characters. If you consider Sundeep as a string, what is this one? Epsilon. Epsilon will be the suffix. And if you consider the complete epsilon as a string, what is the suffix here? Sundeep. So obviously, coming to the prefix and suffix, the first two elements will be the epsilon and the particular string. And see now here, if you consider p as a substring, okay, this one as a string, what's the suffix? It's a p. And if you consider this one as a substring, SUNDE, then EP will be the suffix. And if you consider only SUND, then EEP will be the suffix, and it will be move on. So this is nothing but a suffix. The ending characters or a trailing characters, we can call it as a trailing characters, leading or trailing. So leading, we call it as a prefix, and trailing we call it as a suffix. And now there is one more operation, that is a substring. Substring. So here we have to consider both the leading and trailing characters. That means a combination of prefix and suffix. So how the substring will be calculated? So you can say again here the string is the same thing. See Sundeep, and consider once again we'll take the same thing, epsilon into Sundeep dot epsilon. You can write it, no issue, no? Right. Then the substring will be, so if you consider UNDE as a string, okay, so we have to eliminate the suffix and prefix. So eliminate the suffix and prefix, you can write it as, so here the substring will be UNDEEP. That means the string which is available in between the prefix and suffix. Okay, so in between, I'm writing shortcuts B by W, right? It's a between, in between prefix and suffix, prefix and a suffix. So that will be the substring. So here you can observe, see, the first thing we'll see. So here, if you observe epsilon and epsilon will be the prefix and suffix, you can simply write it as a Sundeep. Okay, and if you imagine S and P as a suffix and prefix, it will be UNDEEP. And if you consider SU as a prefix and P as suffix, then obviously it will be NDE. Okay, So here up to E only, right? So if you consider S and EP, so S as a prefix and EP as a suffix, then it will be UNDE. So that means, and there will be a lot of substrings. There will be a lot of substring. Okay, so you can also go with the SUN as a prefix and EEP as a suffix, then the substring will be only D. Okay, so in this way we have to calculate the substrings also. And similarly, the next operation is concatenation. Concatenation. So concatenation means adding two different strings. So just now we have seen if X is a string 1 and Y is a string 2. So if you concatenate S1 plus S2, that means both the strings, then we'll get the product, that means XY. XY. We'll get the XY as a product. So that is the concatenation. Usually it will be represented with a plus symbol. This is not an arithmetic addition. This is a concatenation if we perform this plus in between the strings. Just remember that. So this is the second level. Now we have to move on with the languages. What are the different languages? So what is meant by a language? So a collection or a set of strings from the alphabets is called as a language. We'll write here. So next one is language, which is nothing but set of strings. Set of strings from the generated from alphabets. From alphabets. For example, if the alphabet, we usually call it as a sigma, sigma is equal to alphabets A, comma B, and this language, the language L will be all the strings which are generated with the help of these alphabets. That means A, B, AB, AA, AAA, ABB, BB, okay, ABA. So whatever the strings we are generating from these alphabets, everything comes under the language. So this is a language. Okay, now we want to know the operations of this particular language. So the operations. So first one is a union. Union. So we know that a union operation will combine both the languages. For example, if S is having some language, some A, comma B, and T is having some language called C and D. Okay. Now the union operation S union T will be the combination of both languages A, comma B, comma C, comma D. That means whatever the alphabets available or whatever the strings available in this particular language and whatever the strings available in this particular language, both comes with the union operation. So union, right? And the next one is an intersection. The next one is an intersection. So intersection here is nothing but a product of two different strings. So for example, the same thing we take S is equal to A and B and T is equal to C and D. So then S intersection T will be a product of the combination of both S and T. See, A product with C, A product with D, B product with C, B product with D. So this is somewhat different, and this we call it as an intersection. So combining both the languages, the product of both the strings. Okay, so this is an intersection. The next one is a closure. Closure. So usually we call it as a clean closure. Clean closure. So clean closure means it is represented from 0 onwards. Okay, so there are two things. One is a clean closure, another one is a positive closure. So starts with 0, and here it starts with 1. Okay, and one more example, one more difference, it represents with a star. It represents with a star. And here it represents with a plus. With plus. So make a difference. So if it is having a star, then it is called as a clean closure. And if it is having a plus, it will be calling it as a positive closures. So I represent this one. So it can be written as sigma star union from 0 to infinity. Okay, 0 to infinity. L naught. Sorry, here you can write it L. Okay, L. So which is nothing but simply so L naught, comma L1, comma, L square, comma, L cube, comma, and so on, L of infinity. Okay, L of infinity. And here we will be getting it as a 1, comma. If L is having the alphabets A, comma, B, then it will be, so all these are the unions, different unions. Okay, so, or if you consider it as an A for simplification, so it will be A, and so on. This will be the thin closure. And if it's a positive closure, then plus U1 to infinity L. That means, so what will be getting? So L1, L2, L3, and so on. So that means we will get A. So that's the difference. It will start from 0, and here it will be starting from 1, and here it will be represented with a star, and here it will be represented with a plus. So these are the different operations that can be performed on the languages. So union operation, intersection operation, a clean closure, and the positive closure. Right? So hope you understood these languages. Now we'll move on with the regular expression. So just now we have seen, if we define a language, okay, we can set a pattern. So if the lexeme identifies with the pattern, then we can say it as a token. So the next one is a regular expression. So usually it will be having some pattern match. So pattern matching. Okay, pattern matching will be there. I'll tell you one example. For an identifier. Right? And we know that identifier should start with either underscore or alphabet. So the first should be either underscore or alphabet. That can be A to Z or capital A to capital Z. So always it starts with this one. Followed by multiple. We can have A to Z, capital A to Z, 0 to 9, underscore. Right? So this matches an identifier. This shows that it should only start with either alphabet, underscore, or lowercase alphabet or an uppercase alphabet. And here you can simply use a star. That means it can repeat multiple times. Okay, and followed by multiple alphabets or multiple alphanumeric. So it can have multiple alphabets or multiple digits or any underscore symbol also. Right? So this type of pattern matching will be there, and based upon this pattern matching, the regular expression will be worked. And one more thing here. So see, the union of R1 and R2. Here R1 or R2, assume that both are the different regular expression. This will also gives a regular expression. And similarly, closure. Both closures of R1 and R2 will also gives the regular expression. So we can combine. Okay, union. We can union the regular expressions, and we can get a final regular expression. So simply imagine that regular expression means a pattern match. So which should satisfy by the lexeme. So if it's satisfied by the lexeme, then it will be categorized into some tokens. Right? So these are the different ways we can specify a token. So a token can be specified majorly by using the regular expression, and regular expression will be represented with the help of languages, and the language will be formed with the help of set of strings, and a string will be formed with the help of symbols, or we call it as alphabets. Right? And we have also seen some operations on strings as well as operations on some languages. So how the tokens can be recognized, and this can be done in two ways. So the first one is by using a transition table, and the second one is by using transition diagram. So these are the two ways how we can recognize different tokens. So you might be knowing about the automata theory. There you will be knowing about these transition diagrams. So which will be represented with a circle and edges. So circle represents some states, and the edge represents the different possibilities to change the state. Right? Now coming to the transition table. First we'll see the transition table. So in our previous sessions we have seen the output of the lexical analyzer, which is the first phase, is a list of tokens which will be arranged in a symbol table. Right? Symbol table. So the same symbol table we can call it as a transition table. So what will be available in this transition table? So the lexeme and the corresponding token will be there in the transition table. So in order to create the transition table, first we need to identify the different categories of tokens in the statements. So first the transition table, we are going to deal with this. Okay. So what happens here? The grammar or statements will be like this. So the statement can be written as, okay, so if some expression then some sort of statements to be executed. If expression, some statement, or if expression, then statement, and we will also write in the else part. So this is a simple if and this is a if else. So statement else, one more statement, else one more statement, or the statement can be null, that is an epsilon, null. So what is this expression? So usually what we call it as an expression, expression means if there is any operator in between two different operands, then we will call it as an expression which will be evaluated. So here it can be represented as the term followed by some relational operator and followed by one more term. So usually we are calling this term as a operands. Okay, so how these terms will be represented? Term can be represented as an identifier, or it may be a number. Directly we can give a number, right? An identifier or a number. So identifier means we will be getting both keywords as well as a constants. Sorry, not a keywords, variables and a constants. Both we call it as an identifier. So we are calling it as an identifier or it's a number. Okay. So now take the transition table. So which is having two different parts. The first part will be the lexeme. So first it will eliminate all the white spaces that we have seen in our previous session, right? First it will be eliminating all the white spaces and it will be only considering this lexemes. Okay, and here the corresponding token. So coming to here, the lexeme is a if, and the token will be the same. So token will also be the keyword, right? Similarly, if, else, or then, else, all comes under the keywords. Right? Then symbols. Okay, symbols. Here you can write what is the relational operator. Relational operator can be less than, greater than, less than or equal to, greater than or equal to, and usually not equal to. Okay, not equal to. So here we can simply write it as less than, greater than, less than or equal to, greater than or equal to, and not equal to. So all these comes under. See, all this comes under relational operators. So we can simply write them as an operator. Operators. So in a similar way, whatever the statements we are using in our program, from that statement we have to represent as a grammar, and from this particular statements or a grammar, we are finding out the lexemes and followed by the corresponding tokens. And this we usually call it as a transition table. And also we can include this ID and number. ID and numbers. Okay, those comes with different identifiers which will be having some sort of pointer towards the memory. Okay, because we know that identifier or the variables or constants, we say that these are the alternate names given for the memory location. So which points to the memory location. So like this is one way. By using the transition table, we can recognize the different tokens with the help of a different grammar or statements. And the next one is a transition diagram. See, transition diagram. So I'll tell you, so we'll see how the transition diagram will be, and we know that the name itself indicates the transition diagram, so which represent the diagrammatic, that means a picture representation, right, of anything. So usually we will use a circle with a start symbol and states, different states, and circle inside the circle, double circle, will represent it as a stop or end state. End state. So this can be called as a start state, and this will be the end state. And the arrow marks will be representing the edge. Okay, edge or possibility to change. Possibility to change from one state to another state. So by using these representations, these notations, we are going to draw the transition diagrams. For example, if you want to draw the identifier, the transition diagram for this identifier, for example, it will start with the start symbol. So let us start it with the start. Okay, and always the diagram should start with the letters. Okay, the keywords or identifiers. Sorry, identifiers or means variables or constants, anything. It should start with the letters. So it will start with the letter, right? So after that, it can be a possibility of both letters and digits. So you can have a loop, self loop, and here a letter or digit. Okay, and also we can go with the plus. Okay, that means a more number of digits. So okay, here we are representing the loop, self loop, so it can be more, and then followed by any others, and which will give the end state. Okay, so this will be the transition diagram for identifier, because that identifier should start with only the letter. Okay, so we are using, it will start with the letter, compulsory it will start with letter, and followed by, it may be a combination of alphanumeric, that means a more number of letters can be having or more number of digits can have. So that's why we are giving a self loop. Okay, it can have multiple letters and digits, and finally it will move on with the third state, that means the final state, because we are representing with a double symbol. And similarly, one more example, the relational operator. See, it will start, the transition diagram will start with the start symbol, and if it is less than, then the second state, okay, then it can be, yeah, so it can be is equal to, which is the third one, okay, and which ends with the others, or simply we can say this will be the final state, and this is nothing but less than or equal to. And there can be the second one, second possibility, which can be greater than symbol, which will be not equal, and another one, others or epsilon, see, which will be just a less than symbol. So this is a one more transition diagram for the relational operator less than, and once again, let us 6, it is a greater than. Then see, what is this one? One possibility is less than or greater than or equal to, and another one, others or epsilon, which gives only the greater than symbol. And there is a one more possibility, which is equal to, so which simply gives the others, and which gives the end state, which is nothing but is equal to. So you can observe less than or equal to, less than, not equal to, greater than or equal to, greater than, equal to. So the relational operator can be represented by using this transition diagram in this way. Okay, so this is the second method to represent the tokens. Okay, so for example, if it is an ID, we know that it should start with a letter, and the next one, it can be letter or a digit, and it can be plus. That means it can have a more number of letters and the digits, but it should have only it should start with only the letter. So you can represent this within this particular pattern matching, or else you can also represent A to Z, capital A to capital Z, and again A to Z, capital A to capital Z, 0 to 9, and here you can give a plus. So that also specify the same thing. So the identifier should start with either small letters or the capital letters, and followed by n number of small letters and capital letters and the digits. That means alphanumeric. So by using these two, transition diagram and the transition table, the tokens will be recognized. Okay, so hope you understood. So Lex tool. So what is the Lex? So Lex stands for lexical analyzer, and this is nothing but a program that generates lexical analyzers. Okay, right? And so sorry, this is a tool that provides the lexical analyzer, and this lexical analyzer is a program. It is a program that generates tokens, right? So Lexic is a tool that generates the lexical analyzers, and whereas the lexical analyzer is a program that generates the tokens. So obviously these tokens are the output of the first phase in the compiler, that is a lexical analyzer. So for this we have to write a program in a Lex. Okay, so the step 1 is writing program in Lex language. Okay, similar to our C, there is a language called Lex language. And the second one, Lex compiler execution. So in order to change the language from one form to another form, we are going to use some compilers. So in similar way, here we are using the Lex compiler to convert the program which was written in Lex to C. So here the input is Lex program and it generates an output in C program. So for that we are going to use a Lex compiler. And the next one, the third step, is a C compiler. C compiler execution. So now the output of the Lex is a C. Now what happens? We need to execute the C in C compiler. So what we'll be getting? We'll be getting some object code. Object code. So here the input will be C program and output will be object code. Object code. And finally we are giving, and this usually we call it as a lexical analyzer. Lexical analyzer, and we have to give some input bits for the lexical analyzer so that we will be getting the sequence of tokens as an output. So the next one is executing object file. So here the input will be a stream of bits and the output will be tokens, a sequence of tokens. So this is the process done for getting the sequence of tokens. So first the program will be written in a Lex. So here we will be using a different text editors in a Linux, right? VI, Vim, Gedit. There are a lot of text editors available. So with the help of those text editors, so we can write the program in this Lex language. So there is a structure for this Lex program also. We'll see in our further minutes, right? So the program should be written in the Lex language, which it will be having the extension of .l. Extension with a .l. So similar to our Java, C and Python, so the Lex language program is also having the extension .l. And here we know it is a .c, we'll be getting the .c, and the object code it will be .out, a.out. Okay, out, right? So usually this will be given some input to this a.out, so that we'll be getting the tokens. So just I will show you the representation of these points. See, the first step, writing the program in Lex, and then input for the Lex compiler. So here I am taking here, it is a Lex compiler. So here the input is lex.l, so which is nothing but a Lex program, and the output will be C program. C program, right? So let it be some lex.c. So it will be converted, right? And that will be given for this one, right? So the same thing will be given to the C compiler now. C compiler, and here it is lex.c, and we'll be getting the output as a.out or something object code. Okay, this is a lexical analyzer, and in this case, so the object file will be here. Okay, the object file will be here, and the input will be a stream of bits, and the output will be sequence of tokens, a sequence of tokens. So this is the process. Now we'll see how the Lex program will be written. That means a structure of a Lex program. Okay, now let us check. Structure of a Lex program. So this Lex program will be having the 3 sections. So 3 sections. So what are those sections? The first one is definition section. Definition section. Okay. So here we are supposed to give all the definitions of macros or declaring the variables. Anything will be written here. So defining or declaring. So here the declaring the variables will be done. Declaring of either variables or constants. Okay, variables or constants. Similarly, including any header files. Similarly, sir, any macros. Everything will be written in this definition section. So, see, these are the points, 3 points. Right? So, how it can be written? How the declaring of variables, how the header files, and how the macros will be included. So, these will be included in between. See, mod curly brace, and here we need to write the definitions and close it. So in between the percentage and the curly braces, here we are supposed to write the definitions. For example, we can write here include stdio.h, the header file, or else we can write int a comma b, or we can also declare any preprocessor directives. Okay, so declaring a constants, we can give a declaring a constant here. So everything will be done here. So that should be in between percentage curly brace and percentage curly brace. And this is called the definition section. So the first section is a definition section. And the next one, and the second one is a transaction rules. Transaction rules. So here we are supposed to write some regular expressions and followed by whatever the actions to be taken if it matches with the given regular expression. So that usually represented in between percentage and percentage. And here we need to give the transaction rules. We have to mention all the transaction rules. So in between percentage and percentage. And these transaction rules will be in like P1 and curly braces action 1, P2 curly brace action 2, and followed by. So here P1, P2 represents the regular expression. Okay, so this P1, P2 represents regular expression, and here the action represents whatever the action to be taken if the instruction matches with this particular regular expression. So these kind of transaction rules, whatever the transaction rules, those rules should be given in between two percentages. So that we call it as a transaction rules, and this is the second section in Lex program. And the third one, am I using this one? And the third one is a user subroutines. The third one, user subroutines. So that means the user defined functions. Okay, so here you can write it as int main and followed by the code. Okay, followed by the code, or else so int check prime, and whatever the code we can write it. So these type of user defined subroutines or user defined functions should be written there. Okay, so here the main function which we are writing in C will comes under the user defined functions, because whatever the logic that should be a compiler should execute, we are writing itself, right? So main function is always the user defined function. So all those user subroutines or sub procedures, sometimes we can call it as a procedures, some we can call it as a subroutines. So the user defined subroutines or user defined functions should be written under the third section called user subroutines. So these are just an example for that. Okay, so there are three sections in a structure of Lex program where we have to write the instructions. The first one is the definition. So I'll write here itself. Okay, all the three sections I'll write here. So structure of Lex program. So we can go with a percentage. So here it will be definition section and followed by double percentages, and here we have to write it transaction rules in terms of P1 and action, P2 and action, etc. And within the double percentage we have to write it. And the third section is the user subroutine section. Subroutine section where we are supposed to write all the subroutines, user defined subroutines. So this is the structure of Lex. Okay, so definition, transaction rules, and user subroutines. So this we are giving as an input, so that we are getting the sequence of tokens as an output. And this will be given to the Lex compiler, which will be converts this particular program. So that extension of Lex program is .l. So this program will be given to the Lex compiler, which will convert it into a C program, and again we are giving the C program to the C compiler. We are getting some object code or a machine code, so or a lexical analyzer, so where it takes some input as bits and it will return the output as a sequence of tokens. So this is all about our Lex tool, and this usually we call it as a language specifying the lexical analyzer. So language specifying lexical analyzer. So this is the language, that is a Lex language. Okay, so language specifying lexical analyzer. So Lex is the language, and through the Lex language we are writing some programs. So before going to the parser's introduction, so let us recollect the previous one. So we have seen so far the first phase of the compiler design, that is a lexical analyzer. So which takes the source code as an input and which produces or which gives the sequence of tokens as an output, and also it will create a symbol table which consists of all the lexemes and the corresponding tokens information. And coming to this concept of parser, so this is also known as syntax analysis. So this is the second phase of compiler design. So this parser is syntax analysis. So which is the second phase of our compiler, right? So the input for this second phase, the input will be the output of lexical analyzer. So what is the output of lexical analyzer? So a sequence of tokens. A sequence of tokens. And what will be the output for this? It's nothing but a parse tree. A parse tree. So the syntax analyzer will be there, or syntax analysis. So which gives the tokens as an information and which will produce parse tree. And from where we'll be getting this one? So we'll be getting this one from lexical analyzer. From lexical analyzer. So for this we'll be giving the source code. Source code, right? And it will create a symbol table. So it will create a symbol table which will be also using by the syntax analysis. So it will request for another token. So it will retrieve tokens one by one and it will generate a parse tree. Okay, so this process we also call this syntax analysis as a parsers. Okay, this syntax analysis is also known as a parser, the second phase of a compiler design. And it will also check the syntax, whether the keywords or identifiers were written in a syntactic way, whether they are syntactically correct. If they are not, then the error will be raised. Okay, so this parse tree can be generated in two ways. And the process, okay, the generation of this process, okay, generating the parse tree is known as parsing. Parsing, right? So this parsing can be implemented with two ways: top-down parsing and similarly bottom-up parsing. Okay, bottom-up parsing. So whenever we call it as a tree, definitely there will be a root node from where the tree has been generated and the leaf nodes where the tree has been ended. That means further the node cannot be expanded. That we call it as a leaf node. For example, let us consider some nodes A, B, C, D, E. So the node from which or from where the tree has been started, so this is called as a root node. And see, D, E and C can't be expanded further, right? So these are the last nodes. So these we call it as a leaf nodes. Leaf nodes. So whenever we are calling it as a tree, definitely there will be a root nodes and the leaf nodes. So coming to the top-down approach, top-down parsing, so the name itself indicates the parsing will start from the high level of the tree. So usually we can call it as a high level, right? So the parsing will be started with the high level of the tree. I'll write here, right? So top-down. So parsing starts from high level or root to leaf node. Root to leaf node. So it will start from high level node to leaf node. So in this process, it will follow the leftmost derivations. Leftmost derivations will be used. And it should not contain any ambiguity in the grammar as well as the left recursions in the grammar for the top down. Okay, so no ambiguity and left recursion. So already you might be knowing about this ambiguity and left recursion for any grammar because we have covered the same thing in automata theory. So if not, don't worry. In our further sessions, we'll see one by one. So how to remove the left recursion if it is available. Okay, if it is not available, then no need of doing anything. So if grammar contain the left recursion, so how can we remove the left recursion? So that we'll see in our next session. And coming to the bottom up, the second category is a bottom up parsing. In this bottom up parsing, the parsing starts from leaf node to root. Leaf node to root. Okay, and here obviously it will be using the rightmost derivation. So in the top-down approach, we are using the leftmost derivation. So in order to create a tree, but here we are using a rightmost derivation in order to create a tree. So this will be the output of syntax analysis. So syntax analysis output is a parse tree. Is parse tree. So which will be giving as an input to the next phase, that is a semantic analysis. So the third phase. So far we have seen the first phase, lexical analyzer. Now we are going to see the second phase. What happens in the second phase? So now we are having the sequence of tokens after end of the first phase. So with the help of this sequence of tokens, how this sequence of tokens will be converted into the parse tree. So that we'll see in our further sessions. So that will happen in our second phase, that is a syntax analysis. As the name itself indicates, it will also check the syntax, whether the tokens have been following the registered syntax or not. If not, the errors will be raised. So what is this bootstrapping process and where it will be used? And mainly this bootstrapping process will be used in designing of a compiler. So it will be used in designing of a compiler. Designing of a compiler. So here another way is, we can say it will be used in a compiler development. So compiler development. See, here we know that a compiler will convert the one format of language to another format of language. For example, high level language to the low level language. So you can say, just recalling the working of any compiler. So this is a compiler, and here we are supposed to give the source program. Okay, source program. And what we'll be getting? So we will get the another format of this program, right? So that we will call it as a target program. For example, target program. So usually, if you consider any C language, the source program will be .c file, okay, which is a high-level language, and coming to the target program, which is an object code. Object code. That means a machine understandable code, right? So for that transformation of one language to another language, we are going to use this compiler. Now, this compiler was also designed by using some programming language. That means using some sort of instruction codes. So this we call it as a implementation language. So there is one more language, right? Implementation language. So source program or source language, target program or target language. So how the compiler was designed? The compiler was designed with a few instructions which we call it as a implementation language, and this can also be the high level language, right? So for example, C program is given to the compiler. C program is given to the compiler where we will get some machine code, okay, machine code. So this compiler can be implemented by using or designed by using C or C++ or Python, etc., etc. So some programming language should be used while designing this kind of compiler, right? So who will execute this compiler? Okay, so the compiler was designed by using any one of these programming languages, but these languages are also not able to understand by the machine, right? So this code should also be compiled. Means compiler should also be get compiled. Okay, hope you understand. Don't get confused. So source program we are compiling so that we are getting some object code because the system doesn't understand the machine code. But here the compiler was also designed by using any one of the different programming languages. So the computer doesn't understand these programs also. That means the compiler should also be get compiled. Okay, so this process is called as a self-hosting compiler. Okay, the compiler compiling itself, that means the code itself is called as self-hosting compiler. So this bootstrapping process will be useful for creating these kind of self-hosting compilers. See, which is called as self-hosting compiler. The name itself indicates self-hosting. That means the compiler will be get compiled of its own code. Okay, its own code. So that's called a self-hosting compiler. Now we'll check. For example, and usually any compiler design will be categorized with or characterized with 3 different languages. So categorized with 3 languages. Any compiler design is categorized with 3 languages. So just now we have seen, one is source language. Usually we can represent it as a S, okay, capital S. And what is the result? The target language. Target language, usually we represent with a T. And the third one is the implementation language. That's what we have seen, right? So implementation language. Implementation language, which will be represented with I. So how these languages can be represented? So we are saying yes, and we are getting T with the help of I. Okay, that's what we have seen. So if you observe, so this is the diagrammatic representation of all these 3 languages, which we call it as a T diagram. So because it looks like a T structure, right? The alphabet T. So that's why we call it as a T diagram. And this can also be represented as, say, this is a source program, which will be converted to T. So T, and with the help of I. So this kind of thing can be represented with a notation STI, source program converted to target program with the help of a compiler which has been designed with the implementation language. Right? So for example, we are saying C converted to machine code with the help of C compiler. That means the compiler was also designed with the help of C language. So this is also a T diagram. Okay, you can erase the arrow marks. This is one compiler. So this can be represented as C machine code with the help of C. So this can be written in this way. Right? Yes. So let us see one example of this particular bootstrapping process. What happens here? For example, if I want to convert some language A to language B with the help of some C++. See, this is a T diagram I have taken. This is a T diagram. That means the source language is A, okay, any language. Then target language is B, and the compiler language is a C++. So for executing of A and B, that means by using the C++ compiler, we are going to convert the source language from A to target language B. And to do the process, C++ code is not being understood by the system. So we have to execute this one also. So for that purpose, we are going to do C++ to the machine code with the help of C compiler, right? So we are executing this particular compiler. That means we are converting this particular C++ to the machine code, right? So because the system only understands the machine code. So the compiler has been developed by using C++. So first we have to convert the C++ to machine language. For that also we have to use some compiler, because that's also a transformation of one language to another language. So that, for example, let us take a C. Okay, C program. Now the compiler was designed in C. Even C is also not understood by the system. So again we need a transformation from C to another language. Again there will be a one more compiler which can convert C to some machine code. So with the help of some assembly language. So now you can see we are converting the C to machine code. For that we are using a compiler which was designed using assembly language, and still the assembly language was not understood by the system. So again we need to convert the assembly language to machine code. Again we have to use one more compiler. So let us take this one. So assembly language to machine code. Again machine language. Okay. Now you can see we are converting the assembly language to the machine code with the help of machine code. And this process we call it as a bootstrapping. Okay, with the help of one programming language, we are translating the normal source program to the complicated program. We are translating the complicated program, which further will be responsible for one more complicated program, to convert one more complicated program. So you can observe initially we are using the C++ compiler, and later in the second step we are using C compiler to convert the C++ code to the machine code. And the third step we are using some assembly language to convert from C language to machine code. And again the fourth process, in the fourth step we are using some machine language compiler which converts the assembly language to the machine code. So this process we call it as a bootstrapping. Okay, so this main bootstrapping is also used to create cross compiler. One more term, right? Cross compiler. So what is this cross compiler? What is this cross compiler? So cross compiler is a compiler which produces the object code which runs on the other machine. Okay. Now, for example, let us take some C language. Okay, and we need to convert it with the machine code. And here we are using some C++. Okay, and this is a source. This is a source. And what is the target? So I need to change the environment. So I need to convert C to machine code. And the compiler should be C. And this is the target, my target. So this is a source. That means I want to convert the C program to the machine language using C++ compiler. I'm having this one. And my target is the C program should be converted to machine code by using the C compiler. So what happens? There should be one more compiler should be there which converts the C++ to C. So which can complete C++ to C by using some compiler, right? C compiler. So this compiler is called as a cross compiler. So which takes the source program and which gives the target program. Okay, see what happens. So this will be the cross compiler. Okay, you can combine all these three so that we can get the complete picture. For example, this can be represented as C, C, M, C++, and C, M, C. Okay, so we can get this one. So I'm just erasing this one. Hope you understood this bootstrapping process. And by combining all these two together, we can say a C, M, so C++, and here we will be getting the C++, C, which is a M, and C, M, and sorry, this is C. So this we are creating, right? C. So this is the combination. So you can see this is the source, this is the target, and this is the implementation. So we are using one more compiler which creates a code for another machine. Okay, so this is done with the C++ and this is done with the C. In order to conversion from C++ to C, we are using one more compiler which converts the code from C++ to C. Okay, which runs or which produces the code for another machine. This is another machine. So you can consider it as a machine 1, and this is a machine 2, and this is a cross compiler. Simply we can say it as a cross compiler. Okay, so hope you understood. So just remember one thing in the cross compiler. So these two portions should be equal. These two portions should be equal. So this and this should be equal. Excuse me. So this portion we call it as a cross compiler, and the bootstrap process will create or will use these kind of cross compilers. So previously we have seen, right? So in order to execute one compiler, that should be translated to another language by using one more compiler, right? So this is a complete overview about the bootstrapping process in compiler design, and mainly that is used in a compiler development. So we are saying that compiler, we are designing a compiler, but the compiler is also developed by using some programming language instructions. So that should be also be converted. That means also to be compiled. So the compiler has to compile itself, right? So that process we call it as a self-hosting compiler, which is nothing but a bootstrapping. Derivation tree, and the same is also known as parse tree. Parse tree, right? So in this trees concept, this derivation tree consists of 3 nodes. So first one is a root node, or we can call it as a root vertex or root node. So which is nothing but a start symbol of our CLT, start symbol. Okay, and also this would be known as the non-terminal. Okay, non-terminal. And the second one is leaf node or leaf vertex. Leaf node or leaf vertex. That means these are nothing but terminals. Okay, and the third one is intermediate nodes. Intermediate vertex. So these are all non-terminals, a set of non-terminals other than the start symbol. Okay, these are all the non-terminals. So if you consider any context-free grammar, so is there any string which accepted by this context-free grammar can be derived by using some derivation, and that can be graphically represented by using this derivation tree, right? For example, Let us take some context-free grammar. S tends to some B, S, B, or A or B. So let us take this example. Okay, and we need to construct the derivation tree for a string. B, B, A, B, B. So we need to construct the string. So construction of a string means this string is accepted by this particular context-free grammar. So we need to derive the string from these production loops. Okay, we need to derive the string from these production loops. So let us start with the start symbol yes. So in yes, we can substitute B, yes, B. So B, yes, B. Okay, so the first B was done. And again, yes can be substituted with B, yes, B. So again, once again, I will go with this one, B, yes, B. Okay, so from the start symbol, we are just substituting the production rules and deriving the string. Because this string is an accepted string by this particular CH, context-free grammar. So we are supposed to derive the string from these production rules. So you can observe here, B, B. So this one also HU, B, B. Okay, and also at the end we have HU, B, B. Now A. So you can also substitute yes with A. So if you substitute yes with A, so you can observe here, so it will be B and it will be B, and here you can observe B, 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 B. So this is the required string. Okay, this is the required string. So first of all, yes, we have substituted B, S, B, and again in the S we are again substituting B, S, B, and in the S we are substituting A, so that we got this particular string. Right? So if the string is accepted by the context-free grammar, then we can derive that string by substituting the production rules. And based upon this derivation, so this is called a derivation, right? This is called the derivation. And from this derivation, we can easily construct this derivation tree. So what is the start symbol root vertex? That is a start, yes. Right? This is the start symbol. And yes, by yes we are substituting the another production, that is SB, SB. So it will be having the branches B, S, B. So this is a B, S, B. So here you can observe B are nothing but a terminals. So if it is a terminal, automatically it will be the leaf vertex. So there will be no expansion, right? There will be no branches. And S is a non-terminal, so it is an intermediate. So we can expand yes again, right? Again, in order to get the given string, yes should be again divided into B, yes, B. B, yes, B. So again you can observe B are the terminals we can't expand. So these are the leaf nodes. Now again we can substitute yes. So in order to get the given string, S should be substituted with A. Right? Now I will expand this one with A. Now you can observe A is again this terminal. So we can't expand it one. Now just read the leaf nodes from left to right. So you can observe here. So B, B, A, B, B. Right? So B, B, A, B, and B. So this is a string. You got this string, right? So in order to draw the derivation tree, so it would be very easy if you derive the string from the production rules. So from this derivation, so we can simply write the derivation tree, right? So hope you understood. First we need to take the string which is accepted by the context-free grammar, and we can directly, so here the strings that are accepted by this context-free grammars will be many. So for example, if the string is B, A, B, this is also accepted string. This is also accepted string, right? So we can also draw the derivation tree for this one. So B, yes, B, and here it will be A. So you can observe here B, A, B, right? So we need to read the leaf nodes from left to right in order to get the string. So here we are reading from left to right. So from leftmost. So B, A, B. So this is a string. So we can consider any string and just derive the string by applying the productions, and directly from that derivation we can simply draw the derivation tree. So we'll see one more example for this derivation tree. So consider the one more example. So this is the production rules, right? So this is the context-free grammar. So S tends to AB or epsilon, A tends to AB, and B tends to SB. And the string is here. So we need to construct the derivation tree for this one. So before constructing the derivation tree, first let us derive the string from the production rules. So I will write this one above. I think it's useful. Yes. AB or epsilon. Right? Now let me start with yes. Yes. So yes can be substituted with AB or epsilon. So I will just write A, B. And now first we need to get the terminal A. So in order to get the terminal, so A can be derived as A, B, B. Right? This was HU. And again we need to get A. So in order to get A, here you just write S, B, and B. So now this A is, sorry, yes, A. A, S, B. Right? And again, so if you want to get A, just we need to apply S as A, B, B, B. And again now, instead of A, So we need to get this one, right? So A, instead of A, we can write A, B, 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 and B. Right? Now, you can observe here, 2 A's have been achieved. Now we need to get a B. So instead of B here, you can write it S, B, 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 and B. Okay? So, you can observe here, we have to get a B. So instead of S, we can simply apply epsilon. So this will be A, epsilon B, 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 and a B. So you can simply avoid the epsilon, A, B, capital B, small b, and a capital B. And again, so this was achieved. Now again we need to get a B here. So instead of getting, for getting B, now again substitute this one, A, B, and B can be written as SB. Again you can write SB, B, and a B. Again you can apply the epsilon, A, B, epsilon B, B, and B. So avoid the epsilon, A, B, 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 and B. Right? Again, you need to expand this B. So we have achieved this one. Up to here we have done, right? Lastly. So this will be done. I'll write here. So A, B, 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 and a B. Right? So instead of B again, I am just substituting here A, B, 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 yes. Sorry, this is BS. Sorry, SP. Okay, yes, B. So right now A, B, 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 epsilon B. So simply we can avoid the epsilon. So simply we will get this one. So this is the string. So this string was derived from the star symbol. Okay, simply we are deriving the string from the star symbol. So just represent the same derivation using the derivation tree. So start with symbol S. Start with symbol S. Okay. So yes, first we have given A and B. Next, A is again divided into AB. So A, B. Right? And again B is divided into S into B. So we need not change this one because this is a terminal, right? So S and B. Right? We need to change B. Again, this S is divided as AB. So once again, A, B. Okay. And again A is divided as AB. A, B. Okay. Now again B is divided as SB. Yes, B. Right? And now see, this B is again divided as SB. Yes and B. And here we have given some epsilon. We have given some epsilon. And here also we are giving some epsilon. And you can see A, B, 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 and here again B is divided as S and B, which is nothing but epsilon here. So this is the derivation tree for this particular context-free grammar to achieve the string for 2 years followed by 4 weeks. So you have to read the string from left to right, all the leaf nodes from left to right. See A, and what is the next one? A, what is the next one? Epsilon, B, 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 epsilon, B. Right? So A, epsilon, B, B, epsilon, B. So from reading from left to right, we are achieving this particular string. So this process we call it as a derivation tree. So this is called a derivation, and this is a derivation tree. So if you derive the string from the production rules, then it will be very easy to draw the derivation tree. And this derivation tree is also known as parse tree. Parse tree. Okay, derivation tree or a parse tree. So 3 nodes will be there. One is a root node, another one is a leaf node, another one is an intermediate node. So root node is a start symbol. Leaf nodes are terminals and intermediate nodes are non-terminals. Right? So hope you understood this derivation tree and the derivation. So leftmost derivation tree and the rightmost derivation tree. So in the previous session we have discussed about the derivation tree or a parse tree. So where we have to derive the string from the production rules. And in that we are just substituting the production rules to get the required string. And we have constructed the parse tree or derivation tree. So there we have seen the 3 vertex, that is a root vertex and the leaf vertex or the intermediate vertex. And the string will be completely with the terminals. And by using the production rules, we are supposed to derive the complete string. And today we'll go with the left derivation tree and right derivation tree. So simply I will write it as a types of a derivation tree. Types of a derivation tree. So here it is a leftmost derivation tree and rightmost derivation tree. Right? 2 types of derivations. So what is the difference between these things, rightmost and leftmost? So if you are deriving or constructing the derivation tree, we are supposed to substitute the production rules, right, one by one. Now, in the leftmost derivation tree, the derivation will be done. Derivation will be done from leftmost non-terminal in production rule, right? So I will tell you an example, so don't worry. So the derivation will be done from leftmost, right? We need to substitute the production rules from the leftmost non-terminals. And coming to the rightmost, so the same, the derivation will be done from rightmost non-terminal in production rule, right? So we are moving from leftmost to non-terminal to the terminals, and here we will move with the rightmost. Example, let us take the productions. E tends to E plus E, and again E tends to E into E, where E tends to A or B or C. Okay, so this is the example. So we need to construct the rightmost derivation tree and the leftmost derivation tree for this particular grammar. And here the terminals are the terminals are plus star A, B and C. All these are the terminals. And non-terminals are E. Okay, only one non-terminal, that is E. So let us derive the thing. Okay, first let us derive the string. So for example, the string is A plus B into C. So this is the string. So we need to derive this string from this particular grammar. Now we'll see, I will start with E because E is a start symbol. So here we need to go from the leftmost. So E can be substituted with this production or this production, right? So I will go with this production. So E can be substituted with E plus E. Okay, so here we have to derive the string from the leftmost. So in this production or in this expression, we have to first substitute with the leftmost. So what is the leftmost? Here E is the leftmost. So first we need to substitute the production for E and then this E, because this is the leftmost. Okay, now leftmost E, according to the given string, first one is A. Okay, A plus B into C. So this I will replace with A plus E. Now you can observe the leftmost non-terminal. So here the leftmost non-terminal is this one. Okay, previously we are having two non-terminals. Among these two non-terminals, the leftmost non-terminal is this one. So first we need to substitute this one. And the next, after getting the result, now again check for the leftmost non-terminal. So this is the leftmost non-terminal. Now according to the string B into C, so this will be given as A plus E into E. So I will substitute E into E. Now among these, what is the leftmost? What is the leftmost? So this is the leftmost. Now replace this E with B into E. Again, from this, what's the leftmost? This one is the leftmost because only one non-terminal is there, right? So A plus B into, what's the E value here? C. C is a non-terminal, right? So we have derived the given string. From the leftmost non-terminal. Okay, by substituting the leftmost non-terminals. Now coming to the rightmost non-terminal, so take the same thing. So E. So I will substitute the same production here. E plus E. E plus E. Now, what we have to do? We have to derive the given string from the rightmost non-terminal. So among these two, what is the rightmost? This one is the rightmost. First, I have to substitute this one. So E plus, what we have to get? B into C. That means we can take this production E into E. So E into E. Now, so what is the next thing? Again, we are having some three non-terminals, right? Three non-terminals. Among these three non-terminals, we have to substitute the terminal. We have to substitute the non-terminal from the rightmost. So what is the rightmost non-terminal? This one. So just give here C into E plus E, right? Now among these two, what is the next non-terminal? Rightmost. Rightmost means this one. So substitute here B into C plus E. Now what is the rightmost non-terminal? Only one terminal is here, so we can substitute here A plus B into C. So you can observe here, we have derived the same thing. By using the rightmost derivation tree. Okay, by rightmost derivation. So here we are deriving the string from the leftmost non-terminals, and here we are deriving the string from the rightmost non-terminal. So simply you can draw the tree. So E is a start symbol, is a root vertex. From this we have divided into E plus E. Okay, and again we have derived the leftmost, right? So here we have given A, right? And this one we have derived again E into E. Now among this one, again we have to derive this one B, and here it is C. Now read the leaves from the left to right. So A plus B into C. So automatically we got this tree. Now just draw the tree for this. So I am taking E, and from E it was derived E plus E, and now rightmost. Okay, rightmost means this one. So again I have derived from here E star E, and now you can see this one a C, this one a B, and this one A. So even though both trees are common, so we have derived the string from the rightmost non-terminal here and from the leftmost non-terminal here. So here also you can observe here, just read the leaves from left to right, A plus B star C. Right? So in both the cases we are getting the string. We are deriving the string, but only the difference is we are applying the production rules, substituting the production rules from the leftmost non-terminal and here from the rightmost non-terminal. Right? So hope you understood this one. Let us move on with the next second example, and so that if you are still having any doubts, so it will be clarified. Now let us see the second example. So let us take this grammar, and the string is this one. So we will derive the string from the leftmost derivation using the rightmost derivation. So if you derive the string, automatically we can simply draw the diagram, right? So let us see the derivation first. Okay, after that we can simply construct the derivation tree. So let us take the leftmost derivation first. It will start with S. Okay, so S can be substituted with T 0 0 T. So here the terminals are 0 and 1. Terminals are 0 and 1, and non-terminals are S and T. Non-terminals are S and T. So we need to derive this string. Okay, we need to derive this string. First, let me consider S. I will start with the start symbol S, and S is substituted with the T 0 0 T. Right? Now, first, in the string, first symbol is 1. So you can replace. So it will be derived from the leftmost. Okay, leftmost means this one. First we need to derive this one. So we can apply T with 1T because the string starts with 1. So 1T 0 0 T. And now here you can observe. Now from these two non-terminals, what is the leftmost? So this T. Now you can observe this one. So first one, next one, it is 0. So we can replace the T with 0T 0 0 T. Okay. Now see, in our string there is a 3 zeros. So you have to substitute T so that we have to get the resultant 3 zeros. So automatically we can simply apply this epsilon. So this T is replaced with epsilon, right? So because this is the leftmost non-terminal in the given string. So 1 0 epsilon 0 0 T. So this can be written as 1 0 0 T. Now among this one, only one non-terminal is there, this one. Now what is the result? The next one is 1. So this will be substituted with 1T. So that 1, sorry. So 1 0 0 0 1T. Again we need to get 1. So again this will be substituted with 1 0 0 1 1T. Again we need to get one more T. So again this can be written as 1 0 0 1 1 1T. Now you can observe here the complete string was achieved. 1 0 0 0 1 1 0 0 0 1. Now simply replace this T with the epsilon so that 1 0 0 0 1 1 1 epsilon. So finally we get the result 1 0 0 0 1 1 1. So this is the required string. So we are deriving this particular string. Okay, we are deriving this particular string by applying the leftmost derivation. So we are just substituting the non-terminals which are on the leftmost, okay, in the string. Now the same thing we can derive by using the rightmost. So let us start with the S. And in the S we can represent T 0 0 T because there is no option, right? Only one production is there. Here among these two non-terminals, so as it is a rightmost derivation, we have to consider the rightmost non-terminal. So because this one, we need to consider this one, right? We need to consider this one. So you can simply use C 0 0. Okay, so in the string you can observe here there is a 0 0. So 0 0 is there. So we need to get one more 0. So simply you can go with the 0 T. Okay, so T 0 0 0 T. T 0 0 0 T. So among these two non-terminals, again this one we need to create this one. So this can be replaced with 0 0 0, and next one is 1. So 1 T. So T 0 0 0. Okay, and this T can be again considered as 1 T because another one is there. And again rightmost, we are deriving the rightmost, right? Again you need to consider this one, and T 0 0 0 1 1 1 T. Now you can observe here. So the string is ended with 3 ones. So here also the string ends with 3 ones. So simply you can apply the epsilon here so that we get T 0 0 1 1 1 epsilon. So which is nothing but T 0 0 0 1. So now there is no rightmost terminal. So there are no more than one non-terminal, right? It is having only one non-terminal. So we need to substitute this one. So the string will start with 1. So simply replace T with 1T 0 0 0 1 1 1. And you can observe here the string is 1 followed by 3 zeros and 3 ones, and here 1 followed by 3 zeros and 3 ones. There is an extra non-terminal. So simply you can replace this T with the epsilon. So the T with the epsilon 1 epsilon 0 0 0 1 1 1. So simply the result is 1 followed by 3 zeros and 3 ones. So we have generated this string, we have derived this string, required string, using the rightmost derivation, So here we are deriving the string from the leftmost derivation. That means substituting the leftmost non-terminals. Here we are applying from the rightmost non-terminals. Right. So before going to this topic, let us know about what is a left recursion. So in our productions, there might be a chance of getting three types of recursions: left recursion, right recursion, and a normal recursion. Right. So here, a recursion can be done in three ways. So one is normal recursion, left recursion, right recursion. Right. So coming to the normal recursion, if the production is having similar to this one, right? So A, S, B. Okay. So whatever the variable or a non-terminal which is on the left hand side of the production is repeated on the right hand side of the production, then we call it as a normal recursion. Right. So calling the same thing. So as we know in the programming language, recursion is calling the same function itself. So that is called a recursion. So here we are just giving the non-terminal which is on the left hand side on the right hand side. So this type of production we call it as a normal recursion. And coming to the left recursion, so on the right hand side, if the non-terminal is on the leftmost, then it is called left recursion. See, for example, if it is in this format. So if it is in this format, then we call this production as a left recursion, right? So in this observe, you can observe here in this production right hand side, we are having a combination of non-terminal and the terminal, and the non-terminal place is on the leftmost, and the same thing is on the left hand side. Okay, so in the production we are having some left hand side tends to right hand side. And if you use the same non-terminal here, so we know that LHS will always be the non-terminal, and the same non-terminal appears on the right hand side, and that is also the position of this non-terminal on the right hand side is the leftmost, then it is called the left recursion. And here, if the same non-terminal is on the right hand side, rightmost, is called a right recursion, right? So this type of production we call it as a right recursion, because here on the right hand side we are using the same non-terminal, but the position of this non-terminal is on the rightmost, right? So this is the different types of recursions. And here, during parsing, so we have constructed the parse tree. So in this parsing, this can be done in two ways. One is top down and bottom up. Top down and bottom up. So coming to this top down parsing, this left recursion is not suitable. Left recursion is not suitable. Right? So there is no problem with the normal recursion and the right recursion. So if it is a left recursion, it is not suitable for the top down parsing. So that's why we need to remove the left recursions from the production, right? So now we'll see the procedure how we can remove the left recursion. So let it be the left recursion A into alpha, right? So A tends to A into alpha. So if the left recursion is like this, A tends to A or B. So you can observe this example. So on the left hand side we are having the non-terminal A. On the right hand side also we are having the non-terminal in the production. And the position of that non-terminal is on the leftmost, so that's why this is called a left recursion. So we call it as a left recursion. So we need to remove this left recursion because it is not suitable for the top-down parsing. So in order to remove this one, create a one more non-terminal, so A dash, and give the production which is not in a left recursion. So here this production is not in a left recursion. So use this one B A dash, sorry, A tends to B A dash, and replace the A dash as. So other than the recursion, give the another string. That means either it can be having a more than one terminal or more than one non-terminal, or a combination of terminal and non-terminal, whatever it may be. So here this is the recursion non-terminal. So other than this, use this one A dash or epsilon. So you can simply use this process to remove the left recursion. So once again I'm saying, so if the production is in the form of A, capital A and small a, so here capital A is a non-terminal and A is a non-terminal. And if it is the production is in this format, simply use a new production A dash. Okay, give the new non-terminal A dash. So A tends to, so B is not in a left recursion. So B into A dash, B into A dash, and A dash tends to, other than the non-terminal which is giving a left recursion, write down all the content. So A and A dash with epsilon. So use this formula to remove the left recursion. Right. So let me give you examples so that you will be understanding more. Right. See, let us consider these three examples, and we'll remove the left recursion. So here you can see A is the non-terminal which is on the left hand side. So we need to check whether it is available in the right hand side and the position of that particular non-terminal is on the leftmost. So you can observe here A, okay, A. So that is on the leftmost, right? And here also it is A which is on the leftmost. So we need to remove the left recursion for this particular production, and here also you can observe B is a non-terminal on the left hand side and on the right hand side B is a leftmost non-terminal. So we need to remove the left recursion for both the productions. First consider this one. So A tends to A, B, D, capital A, small a and A. So if you observe here, what we have to do? So other than the left recursion, write down the productions. So A tends to A. So this is a production which doesn't have the left recursion. So A dash, and write down the A dash as other than the left recursion, the non-terminal which appears in the left recursion, write down remaining. So here we can have the BD, so B, D, A dash, and here other than the left, the non-terminal, write down the A. So A dash and epsilon. So this is the way we can remove the left recursion. Coming to the second one, consider the second one, B tends to BE or B. So you can observe here, for this also the left hand side, whatever the right non-terminal is available, the same non-terminal is the leftmost position in the right hand side, right? So we need to remove this one. So what to do? First write down B tends to, write down the production which is not in the left recursion. So this B dash. So use another non-terminal. Now B dash, and other than the non-terminal which is available in the left recursion, write down the remaining string. So here E, B dash and epsilon. So this is the production after removing the left recursion, right? So coming to this one, and see, consider whatever the capital letters are there, those are called as a non-terminals. Other than that, everything will be a terminal. So here you can see E is E, T, F. All the three are the non-terminals, and terminals are plus star and ID, plus star and ID. Now you just observe. So here it is a left recursion. Here there is a left recursion. So we need to remove the left recursion for both the productions. And the third one, F tends to ID. Generating the terminal. So we need not focus on that one. First, let us take this one. E tends to E plus T or T. So consider the production which is not in a left recursion. So T. So E tends to T, E dash, and E dash tends to. So write down the string other than the left recursion non-terminal. So other than this one, the string is plus T, E dash and epsilon, right? So this is the productions after removing the left recursion. Coming to the second one, consider this one, T tends to T star F or F. So consider the same thing. So T tends to, write down the production which is not in the left recursion. So F, T dash, create one non-terminal. So T dash tends to, write down the string other than the left recursion non-terminal. So star F, T dash and epsilon. So these two are the productions after removing the left recursion on this. And finally, we can simply go with F tends to ID. So this is F generating the terminal, so we need not focus on that one. Coming to the third example, you can see here. So this is called an indirect way we can remove the left recursion. So consider this one. So A tends to B, A, and C. So here C is a terminal, right? So here we are having this production which is having the non-terminal, and it's a left recursion, because on the left hand side we are having a non-terminal A, and in the right hand side also we are having a non-terminal A which is at the leftmost. So this production is only the left recursion. So in such case we can simply write it as A tends to, we have to write the productions which are not in the left recursion. So here B, A is not in the left recursion, so B, A dash or C, A dash. Okay, now you have to write the production for A dash tends to. So whatever the left recursion production is there, other than the non-terminal, write down the everything. So here A into A dash and epsilon, into A dash and epsilon. So these are the productions after removing the left recursion for this particular production. Now, if you want to represent, if you want to replace this one, okay, so just apply the A, substitute A in this one. So we'll get B tends to, so B, and apply this one, A. So B, A dash, B, okay, C, A dash, B, and C. Sorry, I think it's D. Right? So hope you understood. This is one thing, and again substitute A value. Okay, substitute A production in this production, right? So I'm substituting so that again we are getting the left recursion, right? So now you apply the left recursion, remove the left recursion. So B tends to, what we have to do? We have to write down the productions which are not in the left recursion. So here you can see C, A dash. Sorry. So C is a terminal here, right? C, A dash, B, B dash, and D is also the production which is not having the left recursion, so D, B dash. Now we need to write down the production for B dash, B dash tends to, so whatever the string that is available in the left recursion, so except the non-terminal remaining, you have to write the remaining string. So first go with the B, B dash, and except B, so A dash, B dash, epsilon. So this is the productions after removing the left recursion for B. Right? So this type of, we call it as an indirect left recursions. Okay, first we need to find out this one and substitute the same thing here so that we'll get a one more left recursion. So before we are not having the two left recursion productions, right? We are having only one left recursion production. After substituting a value here, we are getting the one more left recursion production. So after that, we have to remove the left recursion. So hope you understood this one. So this will be useful in the next concept. So just practice more problems for removing the left recursions. So in our previous session, we have seen the elimination of a left recursion, so which will be not suitable for performing the top-down parsing. Similarly, this is one more case. So if the grammar is in the form of left factored, then that production rules or the particular grammar will not be suitable for top-down parsing. So here the left factoring is the process of transforming the left factored grammar to the grammar which is suitable for the top-down parsing. So this is a process, right? So it is a process of transforming left factored grammar, left factored grammar to the grammar that is suitable for parsing, particularly top-down, right? Top-down parsing. So now the question is, what is this left factored grammar, right? So we are saying that if the grammar or the production rules are in a left factored, that will be not possible for or not suitable for this top-down parsing. Now we'll see what is the left factored grammar. So which type of grammar we will call it as a left factored grammar. So I'll write here left factored grammar. So we know that a grammar will be a set of terminals and the non-terminals. So usually the terminals will be considered as a uppercase characters and the non-terminals will be considered as a non-terminals will be considered as a uppercase characters and the terminals will be considered as a lowercase characters. So we know that the grammar, right? So if the production rules or the grammar will be having the common prefixes, then we will call it as a left factored grammar. So here the production rules having common prefix, then there will be a problem which production should be taken for parsing. So there is a dilemma of choosing the particular production for expanding the production, right? So in such cases we'll be using this, and in such grammar we will call it as a left factored grammar, right? So not able to decide which rule should be used for expansion, because every rule will be having the common prefixes. For example, if the grammar or the production rules are in this format, so alpha beta 1 or alpha beta 2 alpha beta 3 and so on. For example, if the production rule is in this format, okay, so here you can see alpha can be, and this alpha can be terminal, non-terminal, set of terminal and non-terminal. So anything it can be, right? So this alpha can be either terminal or non-terminal or a set of terminal and non-terminal. That's a combination. So if all these rules having the same prefix, right? Whereas beta 1, beta 2, beta 3 is completely different. Okay, beta 1, beta 2, beta 3 are completely different. That can be also either terminal or non-terminal or the combination of both the terminal and non-terminal, right? So here the alpha is a common for every production rule. So this type of grammar we call it as a left factored. So in order for expansion, we are supposed to have some sort of dilemma of not to decide which production rule should be taken for the expansion. So here we have to convert this left factored grammar to the grammar which is suitable for the parsing, top-down parsing. That means we have to eliminate this left factored grammar similar to our left recursion, so which we have discussed in the earlier sessions. So what we have to do? See, for example, if this is in this format, the production is in this format, take a one more production, right? So take the common prefix alpha, a dash, and go with the a dash, move on with the remaining one, beta 1 or beta 2 or beta 3 and so on, right? So we can convert the complete production, that means a left factored grammar, by using these two. So write down the common prefix into a new production, I mean new terminal. Okay, so new one, and expand this a dash to all the remaining part of the production rule. Okay, so hope you understood this one. And also we can write in different way. See, this is a first case. This is the first case. Okay, and if the production rule is in this format, A goes with the alpha beta 1 or alpha beta 2 or gamma 1 or gamma 2 or and so on. That means you can see only two production rules were having the same prefix, whereas gamma 1, gamma 2 are not having the same prefix. You can see alpha. This is a common for only this one. Now you can expand only this one. So A tends to alpha, A dash, or go with the remaining one, gamma 1, gamma 2, and etc. And expand A dash tends to beta 1 or beta 2 or and so on. So this is the second case. This is the second case. Okay, so this is a case 2 and this is a case 1. So here we are having all the production rules having the same prefix, but here only some of the production rules are having the same prefix but remaining are unique. So then that should be written in this way: the same prefix, common prefix, into a new non-terminal and followed by all the remaining unique productions. Okay, so you will be understanding if we solve any example. Now we will move on with an example and I'll explain it. So see, let us solve this example. So you can observe this is a production rule, and here we are, both the production rules were starting with the same prefix. So you can consider it as an alpha, and this is nothing but beta 1, and this is an alpha, and this is a beta 2. So we know that a plus is also one terminal, right? So minus is also one terminal. Now how we can write, so consider it as a A. So E is equal to, so that means E tends to the common prefix which is a T followed by a new non-terminal. So what is a new non-terminal? You can write it anything. So I'll write it E dash. So E dash can be written as the remaining part. So plus E or minus E. So this is the grammar, so which has been eliminated the left factored grammar. So this is a left factored grammar because the production rules having the same common prefix. So this we have eliminated by using this one. Okay, so hope you understood this one. Now we'll move on with the next one more example. So take one more example. Here also there are three production rules. Okay, now you can see A. So all these three production rules were starting with the same prefix, and also we can move on with the set of terminals. See, yes, you can also observe A is also having with a one more prefix. Okay, two production rules were having the common prefix, or if you take A, then all the three terminals were having the same prefix. So you can move on with the either, right? So let us take with the one terminal, one common terminal, because which is a common prefix for all the three production rules. Now how we can change it? So A tends to the common prefix A, and let us write it as X as a new. Okay, X as a new. Now X can be written as the remaining thing. So AB or BC or AC. Okay. Now again, see, this is a left factored grammar. This production is a left factored grammar because you can observe A. Okay, it's not mandatory that every production rule is having the common prefix. So that's what we have seen. So this is in the format A tends to alpha beta 1, alpha beta 2, gamma 1. So you can see only two productions are having the same common thing. So this is in this format. Now what we have to do? So X tends to common thing A and Y tends to write on the, sorry, also this one BC, right? So which doesn't have any common prefix. Now you can write it y is equal to b or c. Okay, so this is the nothing but this is the elimination of left factored grammar. So this is the original. Now you can say, so the result is a tends to ax and x tends to ay and bc and y tends to bc. So this is the final output which eliminates, after eliminating the left factored grammar, right? So hope you understood. So it is not mandatory to have all the productions with the common prefix. So that's the second case. So previous example is for a first case, only one, all the productions are having the common prefix, and this is the second case. Now we'll see one more example, right? So let us see this one more example here. So we are having the 3 production rules, and among these 3 production rules, the 2 production rules are having the common prefix. Now what we have to do, so this is a common prefix and this is a common prefix. Now t tends to, let's take the common prefix int and followed by a new production which is a, or, and this doesn't have any prefix, common prefix, so we can write it here in this way, right? Int a and inside the parenthesis e. This is one production. Now we expand a. Now you can see the star t is a one production, and from this production what remains? Nothing. That can be represented as an epsilon, right? So if completely written here, then it will be the epsilon. So this is a grammar after eliminating left factored grammar. So this is a common thing is int. So I have taken int and give the new production, write down the new non-terminal a and followed by the gamma 1, which doesn't have any common prefix. So the same thing I have written here, and then we have to expand the new non-terminal a tends to, write down the remaining terms in the production. So star t, as well as here we are taking the complete prefix, so it will be epsilon, right? So hope you understood. And this process, see, now you can understand. It's a process of transforming left factored grammar. So this is a left factored grammar. So transforming this left factored grammar to the grammar that is suitable for parsing. So this left factored grammar is not suitable for parsing, similar to our left recursion. So that's why we are eliminating this left factored grammar. Okay. So hope you understood this one. We have seen 3 different examples in different cases, for case 1, case 2, and for getting the epsilon here. And now, so consider this production and solve and eliminate the left factored grammar and transform to the grammar which is suitable for top-down parsing, and post the result in the comment section. Hello friends, welcome back to our channel. So today we will see one more concept in compiler design, that is a category of top-down parser, that is recursive descent parser. So it is a recursive descent parser. So in our previous sessions we have seen the introduction to parser and what is the input of the parser and output of the parser, and what are the different categories or different types of parsers, top down and bottom up. And also we have seen, so in order to go with the top down parser, there should not be the left recursion for the grammar as well as the left factoring in the grammar. And if the grammar contains, that means the production rules contains any left recursion or the left factoring, first we have to eliminate that, because those left recursion and the left factoring are not suitable for top down parsing. So here this is a category of a top down parser. And as the name itself indicates, it will be using of recursive procedures. So uses recursive procedures, either directly or indirectly, recursive procedures. So need not worry, I'll take one example, the grammar, and let us design the parser. And then there will be no backtracking. So here, particularly in the top-down approach, so top-down parsing, there will be 2 methodologies, that is by using the backtracking and without using the backtracking. And this is a process where we are not using the backtracking. So no backtracking will be implemented or used, no backtracking will be there. Right? So this is the main thing of recursive descent parser. So before constructing this one, first let us see the rules which we have to follow in order to write this parser, recursive descent parser, for a given grammar. Okay, and one more thing, so there should not be a left recursion and a left factoring for the grammar. So no left recursion and left factored grammar. Right? So then only we can easily implement this recursive descent parser. That means a top-down parsing. Right? So here we'll be taking one input and we are going to parse that input.
So for that we are going to use some input pointer which points towards the starting position of the input and keeps on going. That particular pointer will be incremented by 1 until it reaches to the complete end of the particular string. So that we'll see with an example. So before that we have to write down the rules for parsing using this recursive descent parser. So the first rule, rule 1. So if the input is a non-terminal, so here the production rules or the grammar will be in a combination of terminals and the non-terminals, right? So the first one, if the input is a non-terminal, if the input is a non-terminal, so that non-terminal should be expanded. So that's why, so here we have to write, so then write a procedure. So here if it is a non-terminal, then we have to write a procedure, right? So procedure or a subroutine, we can also call it as a subroutine, or we can also call it as a recursive function, okay? And the same function calling itself, either directly or indirectly, right? So that we have to do. So the first one, if input is a non-terminal, then we have to write the procedure. And then R2, rule 2. Now if the input is a terminal, if the input is terminal, what we have to do? So we have to compare that particular terminal with the input string, and if both are equal, then simply increment the input pointer to a forward level. So what we have to do? So first one, compare a terminal with the input symbol. If both are equal, okay, then increment input pointer. So we can forward it. Okay, we can forward it to the input pointer. Next, R3. What's the rule 3? So we have checked whether the input is, that means we have done when the input is non-terminal and when the input is a terminal. Now we have to see the next one, that is if any non-terminal is having multiple productions. Okay, if any production or a non-terminal will be having a multiple productions. So if any non-terminal having multiple productions, what we have to do? So we have to write the complete procedure, all the procedures, okay, I mean all the productions in the same procedure. Okay, so then write all the productions in single procedure. So we are writing some recursive procedures here, right? So while writing the recursive procedures, if any non-terminal points towards the multiple productions, then we have to write the complete all the production information in the single procedure. And one more thing, the last one, it doesn't have any main functions or any declarations. Okay, so no main and no declarations. So directly we can write down the procedure. Okay, so these are the rules for recursive descent parser. So we have to take one example, and we can write down the procedure by using all these 4 rules, and then we have to take one input string, which can be whether that string can be parsed with the given grammar or not. Okay, that we'll see in just now, right? So let us take an example and let me explain about this process. So let us take an example. These are the given grammar, and here we are having a different non-terminals and also terminals, so production rules. So what is the first thing we have to check is whether this grammar is having any left recursions or left factoring. So obviously this grammar has not having, this grammar was not having any left recursions and left factoring. So this is the grammar after eliminating the left recursion and left factoring. So first you check whether the taken grammar is having any left recursion or left factoring. And if you are not aware about that, how to eliminate the left recursion and left factoring, I'll post the video links in the description. So once go through that links and solve a few examples so that you will be getting a confident how to eliminate the left recursion and the left factoring, and what is the left recursion and left factoring. Right now, see this is the grammar we are taking. So without the left factoring and the left recursion. So this is suitable for top-down parsing. So always the top-down parsing should be started with the starting symbol. What is the starting symbol here? E.
Okay, so we have to start with the starting symbol itself because it is a top-down parsing, and from the starting symbol we have to expand the non-terminals until we get the terminals. And now, see, starting from this one, write down the procedure for each and every production here. Okay, so that we will be getting the number of procedures is equal to, I mean, how many number of procedures we have to write means in our grammar how many non-terminals, just count the number of non-terminals, so that many procedures will be getting. Okay, so you can observe here one example. So see, F tends to E or ID. So here this production, this non-terminal is having two productions. So we have to write the complete thing. So the information regarding these two productions in a single procedure. Now we'll go with the writing the procedures. So first one is a non-terminal. Okay, write down the procedure for E. Right. So procedure E. Left parenthesis and right parenthesis, because usually we are representing any function by using the left parenthesis and right parenthesis. So I am also writing E, left parenthesis and right parenthesis, so that will be the procedure. Now see, the first one is a terminal. What we have to do if the input string is a terminal? What we have to do? So we have to write down the procedure. Simply call the procedure T. That's it. Next, E star. E star is also one more non-terminal. So write down here. So in order to represent a star, I will write down E star. E star, right? So two terminals. So this is the only procedure we have to write for production E. Okay, this is a procedure for production E because it is having only two non-terminals T and E. So if these are non-terminals, automatically we have to call the procedures. Now write down the procedure for the E star. Write down procedure E star. What we have to do? So we are having the input symbol, right? So that is a terminal. So write down if the input string, the input from the input string, whatever the input string is equal to the symbol plus. If it is equal to plus, what we have to do? So simply we have to write increment the input string, input pointer. So the input pointer should be incremented. After that, what is there here? Terminal. So if it is terminal, what we have to do? We have to call the procedure. So simply call the procedure T. And afterwards E star. Once again, this is also a terminal. So again, we can simply write E star. Call the procedure for E star. Okay, and close. Okay, whether this procedure has been completed? No, because so here E star is also pointing towards the epsilon. So that should also be written in the same procedure. So if input is plus, this one, else it will be epsilon. So you are taking it as E star. Okay, having two productions. Two productions. One is plus T E star, another production is epsilon. So if the input symbol is not plus, automatically the input symbol will be epsilon. So here we can write it as else, simply return. So this is the procedure for E star. Hope you understood now, right? So here we are having two different productions, and the complete two productions should be written in a single procedure. I have written in a single procedure. Now come to the next one, T. So we have to write down the procedure for T. So procedure T, what is that? The two are non-terminals, F and T star. So call the procedures F and T star. Right? So that is a T. And again, now there is a one more production T star. So write down the procedure for T star. Procedure for T star. So what is there? So there we are having some terminals. So again, write down the same procedure. If the input from the input string is equal to star, what we have to do? So simply increment the input from the rule 2. Okay, from the rule 2 we have written. And then if it is a terminal, what happens? Call. Again terminal, T star. Again call. So close it, and you can observe here similar to this E star, it is also having a one more epsilon, that means one more production. So we have to write down that production in the same procedure. So here we can write it as else. So as it is epsilon, we are writing it return. And if it is not an epsilon, again we have to write down the if or if else or else if ladder. Anything we can write it. So close this one. So this is the procedure of T star. And again we are having one more thing. That is a production for F. So we have to write down the production for F. So procedure F. So how we have to write? So first there is a terminal parenthesis. So simply write it as if input is equal to left parenthesis. What we have to do? If it is a left parenthesis, so simply increment the input. Okay, then again there is a terminal, so non-terminal. So call the procedure, and again we are having one more terminal. So again write out if input is equal to right parenthesis, simply input plus plus. Okay, so the production ends here, so you can end it, and here also you can end it. Okay, and once again there is a terminal. So previously we are having some epsilon, but here we are having a terminal. Again we have to check here. So here this production ends, and here again we are checking if input. You can also write else or else if whatever it may be. So I am writing here input is equal to id. If it is id, what I have to do? Again input plus plus. So close this procedure here. Close this procedure here. So this is the procedure for terminal. So how many procedures we are getting? So 1, 2, 3, 4 and 5. 5 procedures we have written. Now count the non-terminals in the production. So 1, 2, 3, 4 and 5. So here we are having some E, T, E star 3 and T star and EF. So total 5 procedures, 5 non-terminals. So we have written some 5 procedures. And now let us check by taking one example. Let us take an example for ID plus ID and finally give the dollar, which means that end of the string. So first ID. So remember always the parser starts with the start symbol because it is a top-down parser. What is the start symbol? E. So from here it will be starting. Now immediately after this one it will execute the T. So it will check for the T, procedure T. Here it will comes. So F will be called. Now the procedure F will be called here. Now if input is equal to left parenthesis, but the input is ID here. Initially the input is ID. So this condition is false. Automatically it will comes out from this condition and it will check for this condition. If input is equal to ID, yes, true. Then what we have to do? Input plus plus. So this will be incremented to this one. This will be incremented to this one. After ending this one, from where it will be called? Here. Okay, from here it is called. Now the control will come back to here. Now T star here. Input is equal to star, but here it is plus, not equal. So automatically it will comes to the else part return. So from where this function has been called? From this one. So automatically the control will go back to this procedure T. So from where this procedure T has been called? From here it is called. So directly the control will come to here. And E star. Now the E star will be taken. Now input is equal to plus. Yes, the input is equal to plus. What happens? Now it will be incremented. So the input will be incremented to this one. And T, it will be calling as T. Then control moves to here. F, again the control moves to here. So what happens? If input is equal to less than, no, false, comes here. Input is equal to ID, true, input plus plus. So this input pointer will be pointing towards the dollar. So from where it has been called? From here, T star. So it will come here. So control, if input is equal to star, here dollar, false, return. It go back to the calling function, so T. It go back to the calling function. Okay, here. Next E star, it will be calling here itself. Input is equal to plus, but here it is a dollar. Automatically false, return. It go back to the main function. So it completes its procedure. So this is an input string which can be parsed by using this procedure. And you can also take the same with one more thing, ID, star, ID, dollar. You can also take and check with this one whether our procedure has been correct or not. So ID here also. So irrespective of the input string, always the procedure, the top-down parsing will start from the starting symbol, that is E. So T, first the control will move towards T. F, it will move towards the F. So input is equal to less than, left parenthesis, false. So it comes out of the loop and it will check for ID, yes. So now the input will be incremented, so it will be pointing towards the star. Now it is the end of the procedure, it will move to the calling function. So the control will move towards the T and it will start executing T star procedure. So it will go with the T star. If input is equal to star, yes, star. So input plus plus. So the input pointer will be pointing towards the next internal. Next F, procedure F, it goes to the procedure F. So input is equal to left parenthesis, no, false, moves towards the next part. Input is equal to ID, true. So the input pointer will be pointing towards the next terminal or next symbol of the input string. So the procedure completed. So to where it will be going? So automatically it will go to the T star. Again T star. So again there's a recursive call. Okay. Now input is equal to star, but here input pointer is pointing towards the dollar. So false. Else, return. So from where it will be getting? So it was getting from T. And from here T, it was called from this one. E star. E star, if input is equal to plus, but here it is a dollar. So automatically It will come out from the if condition and return. So go back to the calling function, that is E, and that is the end of the procedure. So automatically this is also being parsed successfully. That means our procedure has been written perfectly. So always remember, this top-down parsing will be starting from the starting terminal, okay, starting non-terminal of the production. And prerequisite, that means before starting this top-down parsing, so first we have to check whether the grammar is having the left recursion and left factoring. If there, so we have to eliminate that left recursion and left factoring, then only we have to follow this procedure. Okay, we have to follow the 4 rules which I have given. If the first one is a non-terminal, write down the procedure. If the input symbol is a terminal, check the terminal with the input terminal, and if both are equal, then simply increment the input pointer. And the third rule, so if any non-terminal points towards the multiple productions, so simply write down the complete information about those productions in a single procedure. And the next one, the fourth one, is there will be no main function and no declaration part. So here we are not involved in any main function, any declarations. Okay, if you want to write any main function, you can write down the main function, but you have to make a call for the procedure E because it is a starting symbol. So you can write the main function, but in that we have to start the first symbol of the production, that is a grammar. Predictive parser. So in our previous session, we have seen one type of parser in top-down parsing. So that is recursive descent parser. Okay, and now we will see one more concept in the same top-down parsing, that is a predictive parser. So this is also a category of top-down parser, and here it doesn't require any backtracking, no backtracking, and we can also call this predictive parser as LL1 parser. LL1 parser. So here this L is used for parsing the input string from left. Parsing input string from left. And this another L represents leftmost derivation, right? So deriving the tree left with a leftmost derivation. It's a leftmost derivation. So, and this one represents, so at a time we are taking only one token. The processing will be done with a one token, right? So that's why we call it as a LL1 parser, right? So we'll see what exactly that this predictive parser or LL1. So you can also write it here LL1 parser. Okay, what exactly happens? So here there will be 3 components. So here this LL1 parser, the input will be the grammar, the context free grammar. So we can also call it a CFG, context free grammar, and the output will be the parse tree. Parse tree, right? So let us see. This is a parser, LL1 parser. So the output from this LL1 parser will be the parse tree. Parse tree. Then what is the input for this one? So the input for this one will be one stack which process this input string. So this is a stack, and it also takes the input from input string, and also it will take the input from the table called parse table. Parse table or parsing table. Okay, parsing table. So by taking the input from all these 3, we will be getting the parse table. So it will make use of the input string, the stack, as well as the parsing table. So finally we will be getting the parse table. Now we will see what are the steps need to be followed for getting the parse table. See, what are the first steps? So what is the input for this parse tree? We have seen this grammar, right? So the grammar, the context free grammar will be the input. So the step one will be, first we need to find out whether the grammar is having the left recursion, because we have seen the 2 things which are not so suitable in top-down parsing. There is a left recursion as well as a left factoring. So even in the previous session also we have seen some recursive descent parser. So where first we have to check whether the grammar is having the left recursion and left factoring. If there exists, we have to remove that left recursion and left factoring, right? So step 1, elimination of left recursion. Elimination of left recursion. Step 2. So once the grammar was eliminated with the left recursion, if there are any, the next step will be elimination of left factoring. Elimination of left factoring. So these are the basic steps while we are doing the top-down parser, because these two are not suitable for top-down parsing. So first we have to eliminate these things. So already we have recorded the session regarding how to eliminate, how to identify the left recursion and how to eliminate the left recursion. Similarly, how to identify the left factored grammar. So this is left factored grammar. Okay, that process we call it as a left factor. So we have to find out. We have also recorded a session how to find the left factor grammar and how can we remove that left factor grammar. So I'll post the same links in the description box. If you are not aware about that, first visit those things and then you can follow the same. Okay, so first two steps are elimination of left recursion, elimination of left factor grammar. And the next, step 3, we need to find the first and follow for the grammar. Okay, find first and follow for the grammar. Okay, so this video also has been recorded in our channel, so I'll post the same thing in the description. And step 4, filling up the parsing table. So we have to construct the parsing table, right? So construct parsing table. So by using this first and follow, we are supposed to create the parsing table. So we'll be taking all the non-terminals as a rows and the terminals as a columns, and we need to create one parsing table, so which can be used in this particular top-down parsing. And finally, step 5, parsing the input string. So we need to take some input string and we have to check whether that input string can be parsed by using this particular parsing table. And the final step, the step 6, construct parse string. Construct the parse string. So finally we'll be getting the parse string. So these are the steps we have to follow while creating the parse tree by using Predictive Parser, that is a LL1 parser. Right? Now we'll take one example, simple example, and then I'll show you everything. Okay, so the first 3 things already we have been recorded in our session, so you just refer those things and then you can easily understand this one. Okay, so let us take an example and continue, and let us construct the parse tree. So let us take this example. So this is the grammar we are having, and you can see this is the grammar or production rules after eliminating the left recursion and the left factored grammar. Okay, so now we are directly moving with the step 3, because the step 1 is identification and elimination of left recursion, that has already done, and the second step, the removal or elimination of left factoring, that is also already done. And the step 3 is we have to find out the first and follow for the grammar, right? So I'll write here the first and follow. So I'll erase everything. So this is a LL1 parser, LL1 parser. So the first of E. Okay, so first of E means move on with. So E is having the non-terminal T, so it will be the first of T. T is having the, so we have to check the first alphabet. Okay, so either it is a terminal or a non-terminal. If it is a terminal, we can directly post it in the first, and if it is a non-terminal, we have to go with the expansion of that particular non-terminal. So here you can see for E, the first alphabet is T, which is a non-terminal. We are moving on with this one. So again we are having a non-terminal. We are moving on this one, and this is a, sorry, here it is, I think. See, yeah, yes. So here we are having 2 productions for the same year. So in the first production, this is the starting terminal and this is the starting, right? So the first of E will be the left parenthesis, comma, ID. So 2 things are in the first of E. Similarly, we have to find out the first of the next one, that is E dash. So we have to find the first and follow for all the non-terminals. Okay, first of E dash. So what is it? Plus. Plus is the starting symbol, and again epsilon. So directly we can go with the plus and epsilon. First of T. First of T. Let's move on with the first of T. The first one is F, which is a non-terminal. Go with the expansion, and again we are having the left parenthesis as well as ID. So left parenthesis as well as ID. This will be the first of T. And similarly, first of T dash. So what with this one? The first one is a star and epsilon. So star and epsilon. Okay, so I'll post the link how to follow this first and follow, how to calculate the first and follow in the description. So go through that. There we have already solved a few examples. So once you practice with those examples, you will be confident how to calculate the first and follow, right? So here I'm giving a very less explanation about first and follow. Directly I'm taking it, right? So first of F, the remaining is F. So first of F, so which is a left parenthesis and ID, left parenthesis and ID. So this is the first of E dash, T dash and F. So we have to find out the first for all the productions as well as the follow for all the productions. So we'll also find out the follow. Follow of E is equal to, so go with the productions and find out which follows the E. So anything else here, so here we are having, so this is a starting symbol, E is a starting symbol, it should consist of dollar. Okay, dollar should be included, and other than dollar, anything else which followed by E. So here we are having the non-terminal E, so here the right parenthesis is followed by E, so then automatically the right parenthesis will be in E, follow of E. Okay, and the next one, follow of E dash. Go with the follow of E dash. Here we are having, so after E dash there is no other terminal or non-terminal. Then automatically we have to consider the follow of that particular production. So it will be follow of E only. Okay. So if E dash doesn't have any other terminal after, then whatever the production we are having, that follow will be coming to this one, right? So I'll write it the same. So dollar and this one. Okay. And here also there is nothing, and it will be coming with this one. And coming to the next one, follow of T. So find out follow of T. So any other E is there. Okay, E is there. So if E dash is there, right? So E dash is follow of T. So what we have to do, we have to consider the first of E dash. Okay, if there is no other terminal or non-terminal after this one, then immediately we can say the follow of that particular production. But here we are having E dash as a follow of T, right? So we are finding a follow of T. So T is followed by E dash, right? So we have to consider the first of E dash. First of E dash. So what is the first of E dash? Plus and epsilon, right? But the follow should not have this epsilon. So we have to place this epsilon. I'll write here. I'll erase. Okay. So plus T E dash is the thing, and this is the here. So we have to consider the first of E to this one, follow of T. Okay. So E dash first is plus and epsilon. So if you are having the epsilon, plus has been included, and substitute this epsilon in E place, E dash, right? So plus T epsilon. So what is the production? E dash is equal to plus and T. That's it. Plus and T. So now again consider what is the follow of T here. So there is nothing. So what we have to consider? The follow of E dash should be considered. So what is the follow of E dash? Dollar and right parenthesis. Hope you understood, right? So for example, previously we have taken the same thing, C, T, E dash, and we are finding the follow of E dash. So there is no terminal or non-terminal after E dash. So obviously, if in such case, we have to consider the production follow as E dash follow. And in this case, the another thing. So E dash is there, right? So we are finding the follow of T. So E dash is there. So we have to consider first of E as a follow of T. So what is the first of E dash? First of E dash. First of E dash is plus and epsilon. So plus is included, but epsilon should not be included in follow. So we have to substitute that epsilon in the E dash. So here we have done that. Okay. So we have substituted epsilon in E dash. So it becomes now. So E dash tends to plus T. So now again consider the follow of T. So there is no other terminal or non-terminal here. So that's why we are just placing this follow of E dash in the follow of T. Okay. Next, follow of T dash. Follow of T dash. So coming to the T dash, let us check. So where it has been. So we are having two things. So T tends to F T dash and T dash tends to star F T dash. Okay. See here T dash is there. So after T dash we are not having any terminal or non-terminal. So obviously we have to consider the follow of T. So what is the follow of T? Plus dollar left parenthesis. And coming to here, there is no terminal or non-terminal. Again we have to consider follow of T dash. So same thing will be appear. Now the next one, follow of F. Follow of F. Consider this production where F is there. So T tends to F T dash and T dash tends to star F T dash. Okay, so two productions. Coming to here, so what? I'll write here two productions. One is here and another one I'll write here. So T dash tends to star F T dash. So we are finding the follow of F. So what's the follow? T dash. So we have to consider first of t dash. So what is the first of t dash? First of t dash, star and epsilon. So if it is epsilon, we have to place the epsilon here, right? So t tends to f into epsilon, okay? So which becomes t tends to f. So here there is no terminal or non-terminal, we have to consider the follow of t. So follow of t is plus dollar and right parenthesis. And here also the same thing, we are having t dash, so we have to consider first of t dash. So star and epsilon, star already we have written, and epsilon place epsilon here, t dash tends to star f. So here there is no terminal or non-terminal, we have to follow the follow of t dash. Follow of t dash plus dollar and right parenthesis. So this is the first and follow for given production. Okay, so we have taken the first and follow of the production. Now we will see, this is the first, the third step. Okay, third step. And the fourth step is we have to find out the parsing table, construction of parsing table. I'll write here parsing table. So as I said that rows will be the non-terminals and columns will be the terminals. I'll write here the terminals. What are the terminals? So the terminals are plus, star, left parenthesis, right parenthesis, ID, dollar. Okay. Now the non-terminals E, E dash, T, T dash, and F. Now we have to construct this parsing table. So this is a parsing table, right? So we need to construct this parsing table. How we have to construct this parsing table, right? Now let us consider each and every production. Okay. So how many productions are there? 1, 2, 3, 4, 5. 5 productions, and here we are having one more production 6, one more production 7, one more production 8. So total 8 productions were there. So we have to use all these 8 productions to fill the parsing table. Okay. And with the help of this first and follow. With the help of first and follow. Now we'll check how can we fill this one. Okay. So just remember the 2 rules. If the production is in the form of A tends to alpha, okay, obviously the non-terminal tends to some combination of terminals and non-terminals. So here, if alpha belongs to, okay, epsilon, if it belongs to epsilon, then the result will be the follow of A. Okay, we have to map everything with the follow of A. And if alpha not belongs to epsilon, then go with the first of alpha. Okay, so we will get some symbols or some terminals for A and some terminals for alpha, right? So simply we can go with the M of particular A and followed by the follow of A, or M and A comma first of alpha, first of alpha. So we have to use this one. What is the M and this one? So this, the first argument in M represents the row number and the second one represents the column number. So we have to place this particular production in this particular place. So we need to follow these 2 rules. So one, if it is not alpha, if it is alpha. Okay, so is equal to, there will be no confusion if you write like this. Okay, if it is not equal to, if it is not equal to epsilon, then we can go with the first of alpha. Now we'll see one by one how we can write it. So let us take the first one. E tends to T E dash. So consider this as A and this as alpha. So alpha is not equal to epsilon. So consider the first of alpha, that is T E dash. So which is nothing but first of T. So which will be the first of T. Left parenthesis and ID. Now what we have to do? So E comma left parenthesis and E comma ID. So in these positions we have to place this particular production. So E comma left parenthesis, E comma left parenthesis. Here we have to write the production. E tends to T E dash, and similarly this one E to ID. E to ID also we have to write the same thing. E tends to T E dash. Okay, right? So hope you understood. Next, so this is all about our production. First production. Coming to the second one. Consider the second one. What's the second one? E dash tends to plus TE dash. Okay, there's a second one. We should not consider epsilon because epsilon will be the next another production. Now you can consider this as A and this as alpha, and here alpha not equal to epsilon. So simply we have to go with the first of plus T and E dash. So which is nothing but plus. The first is only plus. Okay. Now what we have to do? So we have to place at E dash comma plus. In this position we have to use this one. So E dash plus. So E dash plus. We have to put it as this one, right? So E dash tends to plus T E dash. Okay. Now that's all. The next one, next production is E dash tends to epsilon, right? So just consider this as one production, this is another production. So E tends to epsilon. So where alpha is equal to epsilon. So let it be, this is A and this is alpha. Now what we have to do, we have to follow of A. So that should be a follow of E dash. What's the follow of E dash? Dollar, I'll write here. Dollar and right parenthesis. So we have to copy it in E dash comma dollar, E dash comma right parenthesis. Copy the same one with E dash comma dollar. So E dash under dollar. So it should be E dash epsilon. And similarly E dash with right parenthesis. Yes, E dash with right parenthesis. Here also we have to give the same thing, E dash with epsilon. Same production. We have to write the same production here. Okay. Now consider another one. Third one. T tends to F T dash. So this is A and this is an alpha. So alpha not equal to epsilon. So simply we have to write it as first of F comma T. So first of F T dash. This is not F comma T. F T dash. So where it is a F, first of F. What's the first of F? Left parenthesis and ID. So where we have to copy T comma left parenthesis and T comma ID. So this production should be copied in these positions. T comma left parenthesis here. So what is the production? T tends to F T dash and T ID. T with ID. Yes. T tends to F T dash. So we have copied the same. Right. Now the next one. T dash tends to star F T dash. So this is A and this is alpha. So here what happens? Alpha not equal to epsilon. So simply what we have to do, we have to consider the first of star F T dash, which will be only star. So simply what we have to do, so we have to place this one in T dash and star. Place the production in T dash and star here. So it will be T dash tends to star F T dash. And the next one, next production, T dash tends to epsilon. So here alpha, so this is A and this is alpha. Alpha is equal to epsilon. So this is true. Now what we have to do? So we have to consider a follow of T dash. What's the follow of T dash? So follow of T dash plus dollar and right parenthesis. So where we have to copy T dash comma plus T dash comma dollar, T dash comma right parenthesis. In these three positions we have to follow, we have to place this T dash epsilon, T dash plus. So here we have to go with T dash epsilon, T dash dollar, T dash epsilon, T dash right parenthesis, T dash epsilon. Okay. Now the last production, F tends to, two more productions, E. So where consider this as alpha, this is A, and alpha not equal to epsilon, right? Now what we have to do, the first of E, so which will be left parenthesis. Okay, the first of E. So first of E will be always the left parenthesis. So left parenthesis, so where we have to copy F comma left parenthesis. So copy the same thing in F comma left parenthesis. So here F tends to E. And the next one, the last is F tends to ID. So this is A and this is alpha. So alpha not equal to epsilon. So obviously what we have to do, so we have to go with the first of ID, which is ID, right? So where we have to copy F comma ID. So copy this one in F comma ID. So here F tends to ID. F tends to ID. Okay. So like this we have already created the parsing table, right? With the help of first and follow we have created the parsing table. Now, so the step 4 has been completed. Okay, step 4 has been completed. What is the step 5? Now we have to take one input string and we have to parse that. Okay, we have to check whether the particular input string has been parsed with the help of parsing table. See, I'll erase this one and I'll take the 3 things here. So we'll be taking a stack, and here it will be input string, and here we'll be taking some action. So what are the productions we are going to take? Okay, now initially the stack will be empty and we will be inserting the dollar into the stack. We are inserting dollar into the stack. Okay, and the input string is, we can take any input string. I will take the input string as id star id, and the end of the input will be dollar, right? So we are trying to parse this one. So this is the input. This is the input, id star id dollar. So I will take the same thing, id star id dollar. So we have to check whether the string has been parsed, and if it is done, we have to construct the parse string. And action is nothing. Initially, the action will be nothing. Now what we have to do, we have to push the starting symbol, right? So dollar and push the starting symbol. So consider dollar is at the bottom. Okay, dollar is at the bottom, and top E will be on E. And now consider this one and pointing E with id. Pointing E with id. So from the parse table, find out the value in this particular column, E and id, and write down the production here. So E with id, we are having E tends to TE dash. So E tends to TE dash. Okay, now we can replace this E with TE dash. Okay, here the production is TE dash for the terminal, non-terminal E. So here we can replace this E with TE dash. Now what happens? We have to push the terminals, the production to the stack. So what happens? So first E dash will be pushed, next T will be pushed. Okay, so consider, because E dash here, first we have to take out the E dash. So E dash will be pushing into the stack, then T will be pushing into the stack. So now the top will be at T only, right? Now write down the same input string id into id dollar. Now T pointing towards id. Only consider the first terms. Okay, so T with id. So go with the T with id. ft dash. So T tends to ft dash. So here the T can be replaced with ft dash. Okay, so dollar E, T dash will be pushed first, then F will be pushed. Okay, hope you understood. So first T dash is pushed, then F will be pushed. Follow the same order. Don't write F T dash. It is a T dash and F. And consider the same input string. There is no change here. And F is pointing towards the ID. So F with ID, which is F tends to ID. F tends to ID. So you can, what we can do, we can replace F with ID. So dollar E T dash ID, ID into ID dollar, and what happens here? ID is, both are same, both are at terminals. So simply we can pop. In both the cases we can pop. So after performing the pop, what is the result? T dash, and here star ID dollar. Star ID dollar. Now the top is T dash and star. So check out the production, T dash with star. So what is the thing? It is a star F T dash. Sorry, I write the complete production. So T dash tends to star F T dash. So just push this production to T dash. We can replace the T dash with star F T dash. So dollar E, first T dash will be there, then F will be there, then star will be there. And here also star ID dollar. So now you can see star and star. Star and star, both are equal. If both are equal, simply perform the pop operation. Simply apply the pop operation. So what happens here after pop operation? E, T dash, F, ID, dollar. Now you can check with F with ID. F with ID. So it is F. F tends to ID. So replace this one. You can replace this one. So E, T dash, ID, ID, dollar. So both are equal. You can see both are equal. So if both are equal, what we are doing? We are doing the pop operation on both ends. So dollar E, T dash, and dollar T dash and dollar, right? So if both are equal, we are simply popping that one. Now check T dash with dollar, T dash with the dollar, epsilon. So T dash tends to epsilon. Replace this epsilon. So dollar E with epsilon, dollar, and E with epsilon means nothing but E. Okay. So dollar E epsilon dollar. Okay. So what happens? Nothing. E into epsilon means E only. Okay. So no action. So I am writing once again E dollar. Now E to dollar. E to dollar. Somewhere else we have done a mistake. See, yes. So here E dash. This is all the E dash, not E. Okay. See, here we have taken F T dash. So E dash, T dash, F. So everything E dash, we are getting E dash from this position. Commonly we have to write the E dash. So I forget to write E dash, right? Now E dash and dollar. So E dash and dollar we got E dash with the dollar got epsilon. So replace this one. So epsilon dollar E dash epsilon only here. So epsilon we are replacing E dash dollar. Okay. And again we got dollar both the dollars. If we are getting the input string dollar and the stack is having only dollar, so then we can say it is accepted. Accepted means the input string has been parsed successfully. The input string has been parsed successfully. Okay, so now we have to construct the tree. It's a top-down parsing. So consider these productions and construct a tree. So I'll erase this one, this first and follow, and I'll construct the tree. I'll show you. See, first production, E can be expanded with T and E dash. T and E dash. T is further expanded with F and T dash. F and T dash. F is expanded with ID. So which is a terminal. It can't be expanded, right? Now, pop, okay. T dash is expanded with 3 terms. One is a star, another one is F, another one is T dash. And star is also a terminal. We can't expand this one. And F tends to ID. So this is a ID. So this is a terminal. We can't expand more. T dash tends to epsilon. This is an epsilon. We can't expand. This is epsilon. And E dash tends to epsilon. E dash tends to epsilon. It can't be expanded. So you can observe the terminals here. Okay. So ID star ID epsilon epsilon. So if epsilon dot epsilon, it will be coming ID star ID epsilon. And ID into epsilon also ID into ID. So this is the input we have taken. So dollar we have to append at the end of the input. So we are getting ID into ID. Okay, so hope you understood. So we are taking this particular input and we are expanding. Right? So hope you understood. Now you can consider one more input as ID plus ID dollar and ID plus ID into ID star. So simply if you understand this concept, so try to find out the first and follow and construct the parsing table and try to parse these two strings, these two input strings, ID plus ID and ID plus ID into ID. So repeat the same procedure and comment me the result. So whether the strings has been accepted or not accepted, whether we can draw the parse tree for these input strings or not. So in our previous session we have seen the top-down parser, and in the top-down parser we have seen two parsers, that is recursive descendant parser and LL1 parser. And now we are going to see one more concept, that is a shift reduce parser, which comes under bottom-up parser category. So this is a bottom-up parser. Bottom-up parser. So that means we'll start from the leaf node and then we are just moving towards the start symbol, right? And see here it will be using the rightmost derivation. So in the top down we are using a leftmost derivation. Now we are using a rightmost derivation. So what are the inputs for this shift reduce parser? So the input will be the context free grammar and the output will be the parse tree. So whatever the category, that means either top down approach or bottom up approach, the input is same and the output will also be same. The working procedure will be different. So here the input is context free grammar and the output is parse tree. The output is a parse tree. So in order to convert this context free grammar to the parse tree, it requires two data structures. So one is input buffer or an input string, and the second one is a stack. So whereas in our previous session we have seen a LL parser where we have used three data structures, that is input buffer, stack, and the parsing table. And that parsing table is not required here. So it requires only two things: input buffer and the stack. So you can simply say input buffer, and this is a parser, and this is a stack, so which will produce parse string. Okay, so this will be the diagram. Right? Now, what are the different actions that can be performed while doing or while converting the context-free grammar to a parse string? Okay, or context-free grammar to the parse string. So the actions to be taken are, the first one is a shift action. Shift means shifting the symbol from input string or an input buffer to the stack. Okay, so shifting the input symbol from input buffer to stack. Second one is reduce. So if the top of the stack matches with any one, the left hand side of any one of the production, then simply replace with a non-terminal. So you can pop that particular production from the stack and replace it with the non-terminal from the productions. Okay, we will be having some productions, and from the production, if the top of the stack matches with the left hand side of any production, simply that can be replaced with the right hand side non-terminal. Okay, and the third one is error. Third one is a error. Okay, error means if in any case the symbol can't be shifted to stack, or the symbol can't be replaced, or any symbol's top of the stack can't be replaced, so then we can say it as an error. Okay, so that means if the input string can't be parsed from this particular parser, right? So that cases we call it as an error. And the fourth one, how we know, that is accept. So if the input string matches or parsed, the complete input string has been parsed by the parser, then we can say the accept. That means the top of the stack and input buffer, okay, having $, only $. Okay, if the top of the stack is $and the input buffer is having only $, then simply we can say it is accept. That means the complete input string has been passed. So initially the input buffer or input string should be appended with $. So this is the first one we need to remember, right? So the input buffer or input string we want to pass, so that should be appended with $. And the second one, top of the stack, push $, into empty stack. That means always the stack will be having $, at the end, at the bottom. That will be the last element. Okay, so these two rules we have to follow before starting the parsing technique. Okay, so these are the things, just remember. So there's a bottom-up parser. It uses the rightmost derivation. The input is a context-free grammar and output is a parse string, and it uses two data structures, input buffer and the stack, and it will be performing 4 different actions: shift, reduce, error, and accept. And before starting the parsing, before parsing any input string, we have to take care that input string should be appended with $, so which specifies the end of the string, right? And the second one, push $, into the empty stack. Initially we have to push $, into the stack, so that $, will be the last element in the stack. Okay, so now we'll see one example context-free grammar, and let us solve that. Let us take some input string and let us see whether that input string can be parsed by using that context-free grammar or not. So let's move with an example. So now let us take the example, the context-free grammar. E is equal to E plus E, E tends to E star E, and E tends to ID. So you need not bother about the left recursion and left factoring. Okay, so we have to bother about these left recursion and left factoring only when you are using the top-down parsing. So now we are going with the bottom-up parsing. You need not worry about the left factoring and left recursion. So directly we can consider those context-free grammar and we can parse the input string. Now let us take stack on one side and input string on the next element in the next side, and the action to be performed. So we have seen 4 different actions: shift, reduce, error, and accept. Now consider the stack. It's an empty stack. So what we have to do, in empty stack, $, should be pushed. So initially there is a $, and now the input string. This is the input string. Let us consider whether this type of input string can be parsed through this particular context-free grammar. Now I'll write the input string ID plus ID star ID. And what we have to do in the first step, we have to append the $, to the input string. So I am appending the $, here. Okay. Now what is the action we have to take? So symbol by symbol we have to shift to the stack. So the first one, shift operation. We are performing the shift operation. That means from the input string we are just shifting one symbol towards the stack. So the next will be dollar and ID has been shifted to stack. What's the remaining input string? Plus ID star ID dollar. Okay, now you can see, check whether the top of the stack other than dollar, which is available in the right hand side of the any production. So he can see ID and see this is the LHS left hand side and this is the RHS, which is the right hand side. Now we have to compare whether this ID is on right hand side of any production. Yes, we are having the ID in the right hand side of one production. So now what we have to do? We have to reduce with the production E tends to ID. Okay, now replace this ID with a non-terminal. So the production E. Okay, now remaining plus ID star ID dollar. What we can do? You can check whether it is available on the right hand side of any production. So there is no E on the right hand side. So there is E plus E and E star E, but there is no single E. Then excuse me. Again we have to perform the shift operation. Again plus will be moved to the stack. So E plus. So here what happens? ID star ID dollar. Check whether the stack elements are having on the right hand side of the stack. So there is no, right hand side of any production. E plus is not available. E plus E is available, but E plus is not available. Now what we have to do? Again, you can perform the shift. Once again we have to perform shift operation. So dollar E plus ID star ID dollar. So you can check ID. Okay, ID is available on the right hand side of any production. Yes, we are having. Okay, just keep aside. Plus and ID. So is there any plus and ID? No. E plus ID. Is there any E plus ID? There is no. So simply reduce with E tends to ID. So what happens here? Dollar E plus E star ID dollar. Okay. Now you can check whether E plus E is available. Yes, E plus E is available. Now what we have to do? Again we can reduce with E tends to E plus E. So simply you can write it here E and star ID dollar. So you can check whether E is available on the right hand side of any production. No. So simply we can write shift operation. So dollar E star and ID dollar. So check star is available? No. E star is available on the right hand side? No. Again we have to perform shift operation. So dollar E star ID dollar, and now you can check E star ID, there is not available. Star ID no available. ID available. So reduce with E tends to ID. What happens now? E star E. Okay, E star E. Now again it is a dollar symbol. So check whether E star E is available or not. Yes, E star is available here. So now we can perform reduce with E tends to E star E. So it becomes dollar E dollar, and now you can check. So a small correction. So previously I have said that whether the top of the stack and the input buffer having a dollar, then we can say it as an accent. But a slight correction, I'm extremely sorry for that. So if the stack is having the starting symbol, if the stack is having only the starting symbol and the input string is dollar, then it will be accepted. Okay, so I'm extremely sorry for that one. So small correction. So when the parse will be accepted means if the input string is completely parsed and only dollar is left, and the stack is having only the start symbol. So here the start symbol is E. So then we can simply write it as accept. So we can say that by using this context-free grammar, this particular input can be easily parsed. Now we have to construct the parse tree. How can we construct from bottom to top? So consider from here E, and E has been expanded with E star E. So E star E. Okay, move towards up. E is ID. So this is a ID. Move towards up. So E plus E. E came with E plus E. Go with up. This is a ID. Move towards up. E to ID. So you can say ID plus ID star ID. So only the leaf nodes. Consider only the leaf nodes. So I will round up with the leaf nodes. All the leaf nodes. Leaf nodes are nothing but terminals. Okay. Leaf nodes are the terminals which can't be expanded. Right. So here you can see ID plus ID star ID. So that is the input string we have passed. Right. So hope you understood this one. Clear? Yes. So I'll give you one more example. So you have to solve this and post the result in our comment box. Okay. Yes. This is a context-free grammar. One more example. S tends to TL, T tends to int or a float, and L tends to L comma ID hyphen ID. Here comma is also a production, right? It's also a symbol. And input string you have to pass is int ID comma ID. So why we have taken the same example? Because so our programming instructions will be in this format, int ID ID. That means int a comma b. So if we want to declare two variables, so that will be done with the help of int. Okay, some data type integer a comma b. So here we are replacing that a comma b with the identifiers id comma id. So the input string is int id comma id, and the context-free grammar is these three production rules. And check out, follow the same procedure, and check whether this particular input has been parsed through this context-free grammar or not. And post your result in the comment section and let me know that. Operator, precedence, parser. So this is also one category of bottom-up parser. So it is also a bottom-up parser. And also a category of shift-reduce parser. Shift-reduce parser. Right? So now we'll see what are the steps to parse any input string here. Right? So steps. So the first one, the production or the context-free grammar should not have any operator precedence grammar. So that's also a new term, right? So far we have seen the left recursion, left factoring, etc. So this is one more thing. So first we have to identify whether the production rules are not the operator precedence grammar. So productions should not have operator precedence grammar. So that means first we have to check whether that grammar is having some operator precedence. If it is, we have to eliminate that. Now the question is, what exactly means this operator precedence grammar? So precedence grammar, right? So if the production having adjacent non-terminals, if any production is having the adjacent non-terminals on right hand side, not left hand side, right? So on right hand side, and the second one, okay, production having epsilon. So if any grammar is having these two possibilities, then we can say it is an operator precedence grammar. So we have to avoid that one. So the first step is production should not have the operator precedence grammar. That means that production should not have any adjacent non-terminals on the right hand side and also the epsilons. Not having means, so production should not have, I'll just replace it, should not have adjacent non-terminals on right hand side, and production should not have epsilon. For example, if our production is in this way, E tends to E, A, E or ID, where A is plus or star. Okay, so you can check the first one. A production should not have adjacent non-terminals, but here we are having two different non-terminals, adjacent non-terminals. So that should not be there, right? So second one, production should not have epsilon. So this production doesn't have any epsilon, no problem, right? So first one, we have to eliminate this one by replacing A in this place. So E tends to E, instead of A we can give a plus, E plus E, or we can go with a star, E star E or ID. So this is the final productions without the operator precedence grammar. So if any production having the adjacent non-terminals on the right hand side, or any production is having some epsilon, simply we can say it as a operator precedence grammar. Okay, now if it is, we have to eliminate that one. So this process should be done first. So I write the same grammar here. E tends to E plus E, E tends to E star E, E tends to I. So the same thing we have taken as an example in our previous parsers also. So first one, we have to eliminate this one. And the second step, after eliminating, so we can say this is the production, this is the grammar which doesn't have any operator precedence grammar. And the second one, second step, we have to construct the parsing table. Construct parsing table. Okay, for all terminals using precedence of operators. Precedence of operators. So the second step is we have to construct the parsing table, so which will be having for all the terminals, only the terminals. So don't take any non-terminals. So here the terminals are plus, star and ID. Three terminals. So apart from these three, we should also add a dollar, because we are appending the dollar to the input string as a end of the string, right? So we have to consider dollar also. So preceding table for all terminals and dollar. Okay, end dollar. That's the second step. Third step, what we have to do? We have to take the input string and append dollar at the end of the string. So consider input string and append dollar at end of string. And the fourth step, what we have to do? We have to parse the input string, okay, with the help of parsing table. Now parse input string using parsing table. Okay, parsing table. And also we have to go with the shift and reduce operations. With shift or push and reduce or pop operations. By using two operations, we are going to parse. Okay, we are going to parse the complete input string using the parsing table as well as this shift and reduce operations. And the last one, construct parsing using bottom-up approach. So because this comes under the category of bottom-up parser, right? So we have to construct the parse tree with the help of bottom-up approach by using the bottom-up approach. Okay, so these are the steps we have to follow. First, we have to eliminate the operator precedence grammar, so that we have to check whether the grammar is operator precedence grammar free or not. If not, we have to convert it. And then we have to construct the parsing table for all the terminals based upon precedence of all the operators, including the identifiers. And consider the input string and append a dollar at the end of the string, right? In order to recognize the end of the string. And then parse the input string using parsing table with a shift or push and reduce or pop operations. So there we are going to use a shift and reduce operations. And construct the parse tree using the bottom-up approach. This is the final thing. So finally, we have to check whether any input string, we have to take some input string, I'll write here. So let us consider the input string as ID plus ID into ID. So this is the input. Okay. So we have to check whether this input string can be parsed by using this operator precedence parser for this particular grammar. Okay. Now we'll check one by one. So I'm erasing this one. I'll tell you how to do all these things. So the first step is we have to identify, or we have to check whether the productions of the grammar is having any operator precedence. So this grammar doesn't have any operator precedence grammar because no two non-terminals are adjacent. Right? There is no epsilon production. So automatically this is an operator precedence grammar free, context free grammar. Now the second one is we have to construct the parsing table for all the terminals. So let us consider the terminal. So plus star ID and also dollar. Similarly plus star ID dollar. So we have to consider this one. And then we have to construct the parsing table. Yes. Based upon the operator precedence. Okay. Operator precedence. Now you can check plus and plus. So both are having the equal precedence. So then we have to follow the associativity rule, right? So if both the operators in the same expression are having the same precedence, we have to follow the associativity rule. So associativity rule is from left to right. The expression should be evaluated from left to right. So this will be the left and that is the right. So plus is greater than plus. The precedence operator, right? So usually we'll be writing it as a greater than and dot less than and dot equal to. Okay, so A, B. So operator A is having the highest priority than B, and operator A is having the less priority than B, and both the operators are having the same precedence. Okay, now we'll check plus and plus. Obviously both are having the same precedence, so left to right we have to follow the associativity. The left one is a plus. Okay, so you can simply write it as a left and this is a right. So plus and star, which one is having the highest priority? Star will be having the highest priority. Okay, among plus and star, star will be having the highest priority. So plus is less than star. Okay, plus is less than star. Similarly, plus and ID. Remember one thing, among all the operators and identifiers, the identifiers will be having the highest priority, and dollar will be having the lowest priority, least priority. So that important. So identifiers having high priority than any other, right? High priority. Similarly, dollar having low priority, right? Now plus and ID, obviously ID will be having the highest priority, so plus is less than ID. Okay, plus is having the less priority than ID. So here we are specifying either less than or greater than. That implies plus is greater than plus, plus is less than star, plus is less than ID, plus is greater than dollar, because dollar is having low priority among all the things. So here we will be getting greater than. Okay, next star and plus. So star is greater than plus. Star and star both are having the equal priority. Then we have to follow the associativity rule, left. So greater than. Star and ID. Obviously ID will be having the highest priority. Star is less than ID. Star and dollar. So dollar will be having the least priority. So greater than. Then similarly ID. So ID will be highest priority for anything. So greater and ID and ID. So both are having the equal priority. So for the operators we'll be having some associativity rules, and here we are comparing two different operators. We can't say which will be higher, so you can left blank. Okay, you can simply left blank for any identifier to identifier. And ID with dollar, obviously greater than. Obviously it's a greater than. Now dollar plus, dollar is less than, dollar star less than, dollar ID less than, dollar. So if dollar and dollar we got, it will be the accept state. Okay, for dollar and dollar it will be the accept state. So when we are parsing the input string, whenever there is a situation like dollar with a dollar, immediately we can say it as an accept. So this is how we have to construct the parsing table. So here we are performing or we are filling the blocks with the help of operator precedence. Among the operators, which one is having the highest priority? So by using that operator precedence, we are filling the complete transition table or parsing table. So second step is completed. Third step, we have to consider the input string and we have to add some dollar at the end of the string. So I have taken the input string, so I write it here also. Input ID plus ID into ID dollar. So I am appending dollar at the end of the input string. So we have to check whether this string has been parsed by using this context-free grammar with the help of this parsing table. Right? So third step is also completed. First step, eliminating of context-free grammar in the eliminating of operator precedence grammar in the CFG, context-free grammar, and the second step, filling of the parsing table. Third one, input string, appending dollar. Fourth one, parsing the input string. So we'll parse the input string. So let us check. So two things. First I'll write here. So first one is a stack. So stack. So for pushing and popping or shifting and reducing, we are going to use the stack. And then this operator precedence, or a relation, or we can write it anything, relation. And the third one is the input string, and the fourth one is an action to be taken. So two actions, one is a shift and reduce, or push and pop. So what happens here? See, we have to compare the input string with the stack. Only the terminals, non-terminals, we should not take into consideration of non-terminals. We have to consider only the terminals. Now fill the input string ID plus ID into ID dollar. I will action here. Okay, so ID plus ID plus ID into ID dollar. And initially the stack will be having dollar. What we have to do is, first we have to compare the top of the stack with the input string. And input string is also be parsed from left to right only. The input string should be parsed from left to right. So first we have to compare this dollar and ID. So check out the relation in this transition table. Dollar with ID. dollar with ID, it is a less than symbol. That means dollar is having the least priority than ID. So we have to consider two rules. Okay, if top of stack is highest priority, top of the stack is having the highest priority, we have to use a pop operation or reduce operation. Remember, if input string is having the highest priority, then we have to use a push or shift. Okay, so two rules while parsing the input string. Top of the stack is high, pop. Input string is high, push or shift. Now you can check among these which one is having the highest one. So ID is having the highest priority. So that's what we have written here, right? Dollar is less than ID. That means ID is greater. So what we have to do? Push operation. So push operation, or we can simply write it as a shift operation. So what we have to do? Dollar and push it into a stack, and the remaining input string plus ID star ID dollar. Okay, now we have to check the top of the stack with the input symbol. This is the top of the stack and this is the input symbol. So ID and plus, go with the table. ID and plus is a greater than. It's a greater than. So now which one will be having the highest priority? Automatically the top of the stack will be having the highest priority. So if the top of the stack is highest priority, pop or reduce. So we can simply use a reduce operation. By using ID, we can change the ID. So we can check whether ID is available on the right hand side of any production. This production we are having. So reduce with E to ID. So replace this one. E plus ID star ID dollar. Okay, we have replaced ID with E, so we are reducing the stack. Now E with plus, is it possible? No, because E is a non-terminal, plus is a terminal, and this parsing table is having both the row and column with the terminals only. So simply we have to compare with dollar. If E is not there, dollar. Okay, so I mean the next top of the stack. Okay, so here the top of stack is dollar E. So imagine this as a stack. It is a dollar, it is a E. If it is a non-terminal, automatically this will be the top of the stack, because in the parsing table we have written completely with the terminals, not without any non-terminals. So we have to only compare the input with the terminal only. So dollar and plus less than. So obviously plus will be having the highest priority. If plus, that means input string is having the highest priority, we have to push. So obviously what is the next one? Push. So dollar E plus ID into ID dollar. So what happens? Plus and ID. Compare plus and ID. So plus with ID. Plus and ID, yes. Less than. So what happens? Again, this input string is having the highest priority. So again we have to apply the push operation. Push or shift. So anything we can write. Okay, push and shift. So what happens here? Now the stack will be having E plus ID also, and then here star ID dollar, star ID dollar. So now what happens here? This ID will be compared with star. So ID and star, which is a greater than. So top of the stack is high. Here top of the stack is high. So if the top of the stack is high, we have to apply the pop and reduce. So we can reduce with. So you can check ID, E plus ID, whether it is available on the right hand side of any production. No. ID is there. So reduce E to ID. So obviously we have to replace this ID with E. So dollar E plus E star ID dollar. Now E and star, again there is no possibility because E is a non-terminal. So we have to go to the next top of the stack, which is a plus. Plus and star, which is a less than symbol. Okay. So which one is having the highest priority? Input string. So if the input string is having the highest priority, push and shift. So simply you can push. See, you can check. E plus E star, and here ID dollar, and star and ID. Compare with the star and ID. Top of the stack and input string. Star with ID, it's a less than. That means ID is having the highest priority. So again we have to apply push or shift. Here also push or shift. So now we can push it here. So dollar E plus E star ID. Okay, and here it is dollar. Now we can check ID with dollar greater than. So that implies top of the stack is highest priority. If the top of the stack is highest priority, pop and reduce. So reduce, what we have to do? Check ID is available on the right hand side production. Yes, E tends to ID. So you can write here So dollar E plus E star E and dollar. Okay. Now you can check star with a dollar. Star with a dollar greater than. Okay, greater than. Star with a dollar. So see, first E with a dollar. So obviously this is a non-terminal. So if you have to check with the terminal, which is the top of the stack. Next one, star and dollar. Star with a dollar, it's again a greater than. So you can check top of the stack is greater. So pop and reduce. So what we can reduce, you can check. So whether E is there any on the right hand side production? No. So E star E, whether, so you can check whether star E is available in right hand side production? No. So you can check with the E star E available in the right hand side? Yes. So reduce to E tends to E star E. So what happens? So this should be replaced. So E plus E, and here it is dollar. Now E and dollar will be compared. But E is a non-terminal. So next to top of the stack is plus and dollar. So plus and dollar, it's again a greater than. So top of the stack is only highest priority. So obviously if the top of the stack is highest priority, again you have to reduce. So what we have to reduce? Again check whether E is available on the right hand side production? No. Plus E is available in the right hand side production? No. E plus E is available in the right hand production? Yes. So we have to reduce to E tends to E plus E. Okay, E tends to E plus E. Now what happens here? Dollar, E, dollar. You can check with the E and E. So E is a non-terminal. What is the next top of the stack? Dollar, dollar and dollar, dollar and dollar. Accept. So that this implies the complete input has been parsed successfully because the comparison was done between dollar and dollar. So it was accepted. So this has been accepted. Okay, so this is the process. So we have to compare, or we have to use the transition table which was filled with the help of operator precedence. And now from the bottom to top, bottom up approach, by using the bottom up approach, we have to construct the parse tree. So I'll erase this parsing table. Now we'll go with the first top, bottom to top. Bottom is E. E is expanded to E plus E. So E is expanded to E plus E. So I'll round up the terminals. And now again E is expanded to E star E. So E star E. Okay. Now E is given with ID. This is a ID. And then second E is with ID. Then the first E with ID. That's it. Now you can check ID plus ID star ID. So ID plus ID star ID. So you can check with all the terminals. ID plus ID star ID. So we got the parse tree with a bottom up approach. Bottom up approach. So we have approached from bottom to top. Bottom to top. Right? So this is called the operator precedence parser. So with the main motto is, with the help of operator precedence, we are constructing the parsing table, and with the help of parsing table, we are parsing the input string, whether it can be accepted or not. If there is no production to reduce, automatically it is nothing but an error. If there is any production, so we got here greater than, but it is unable to reduce with any one of the production from the context free grammar, that implies, so this is an error. So this particular string, input string, cannot be parsed. LR Parser. So this is a category of bottom-up parsing. So in our previous session, we have seen one category of bottom-up parsing, that is operator precedence parser. Now we are seeing the LR Parser. So we know that what is a bottom-up parsing. So it will start from the leaf node and it will start parsing and it will generate a tree up to the root node. And now this LR means, L means the input will be parsed from left to right, from left to right, and this R stands for, it will use the rightmost derivation, rightmost derivation, right? And also here we'll be having LR of K, where K is a look ahead, right? So how many symbols will be parsed at a time, right? So usually this LR parser is categorized in different ways. One is LR of 0, SLR, LALR, CLR. Okay, so LR parser, SLR stands for Simple LR Parser, and LALR stands for Look Ahead LR Parser, and CLR stands for Canonical LR Parser. Now we'll start with the LR Parser, a normal LR Parser, LR of 0. Okay. Now, what are the steps required to construct the tree? So here also we'll be considering some context-free grammar, and then we have to take some input string and we have to verify whether the input string has been parsed with the help of the given context-free grammar. So, step 1, consider the context-free grammar and apply the or convert the context-free grammar to the augmented grammar. So, convert context-free grammar to augmented grammar. So, how this will be happen, I'll let you know later, right? So, when we are going with each step, I'll tell you how to convert the normal CFG to this augmented grammar. And the step 2, in order to pass the input string, place a dot at the beginning of right hand side of the production. So, insert dot at right hand side of all productions. For every production, we have to write them. We have to use this dot symbol. Okay, this is the dot symbol. And the step 3, find out the canonical list options or list items. Canonical list items. So that also I'll tell you. So find canonical list items for all the productions. For every production, we have to find out the canonical list items. Step 4, we have to give the numbering for each and every production. Okay, so give numbering for all productions. All productions. See, if it is a top-down parsing, first we have to find out whether the given productions are having the left recursion or left factoring, and then we have to avoid, then only we have to use the top-down parser. But here we need not check everything. So consider the context-free grammar and apply all these things. So give numbering for all the productions. Okay, normal context-free grammar. Step 5. After giving the numbering for all the productions, now generate the parsing table. Okay, generate the parsing table. Generate parsing table with the help of canonical items and numbering of productions. Numbering of productions. So with the help of the step 4 and 3, we have to create or we have to generate the parsing table. So once the parsing table has been generated, now start parsing the input with the help of parsing table. So step 6. Step 6. Parse the input string. Parse the input string using parsing table. Using parsing table. Okay, we have to start parsing the input string. And the next one, step 7. So after completion of parsing, now generate the parse string using bottom-up approach. Generate parse string using bottom-up approach, because this is a bottom-up parser. Okay, bottom-up parser. So these are the steps we have to follow for generating the parse string. Okay, so first step, convert the CFG to augmented grammar, and second step, insert dot for all the productions on the right hand side. Step 3, find the canonical list items. Step 4, give the numbering for all the productions. Step 5, by using this canonical list items and the numbering of all productions, generate the parsing table. And step 6, with the help of parsing table, parse the input string. Consider one input string and you can parse the input string. And step 7, finally we have to generate a parse string. So these are the steps. Now we'll go with the one by one. So step 1 to step 7. Now let us take an example and we'll see how the parse tree can be generated by using this LR parser. See, I am taking an example here. S tends to A, A tends to A, and A tends to B. So this is an example. For this we have to construct the parse tree using LR parser. Okay, LR parser. So LR is this one also, right? Yes. So this is the given context-free grammar. Now we have to convert into augmented grammar. So conversion of augmented grammar means take a one more production which gives and which tends to the starting symbol. So here the starting symbol is yes. So take one more production s dash tends to s, and s tends to a, and a tends to a, and a tends to b. So this is the augmented grammar. So in order to stop or accept condition, we have to use a one more production, the extra production, which maps to the starting symbol, Now the third step is, so this is the augmented. Okay, this is the augmented. And the next step is we have to insert dot symbol at the starting of every right hand side of the production, every production right hand side. So the next one, s dash tends to dot s, s tends to dot a tends to dot a. So here small a is a terminal, capital A is a non-terminal, and again a tends to dot b. So this is the first step, second step, right? And now we have to find out the canonical items, canonical list items. So we have to expand by start parsing this dot from rightmost to the leftmost. Okay, now canonical list items. Okay, canonical list items. Now you can draw the flow chart. Okay, it will be very good. So flow, not a flow chart, it's a data flow diagram. Okay, so you can draw the data flow diagram, or simply you can write down the steps. So this is a simple production. So I'll do the data flow diagram. I'll go with the data flow diagram. First, take down all the things. Okay, all the productions with parsing about to start parsing. It's a dot with a dot. So I'll go with this one. S tends to dot s, and s tends to dot a tends to dot a, small a, capital A, and a tends to dot b. So this is a start symbol. So let us consider it as a I0. I0 means nothing but a states. Consider them as a states. I0 means 0th state. Now we have to find out for all the things. So you can see there are different possibilities from up to s, up to a, up to small a, up to small b. So you can go with you can expand this with the next level. So upon s dash upon s, so it will be s dash tends to move the dot symbol towards a one position. S dot. Okay, s dot. And now you can observe for this production, the dot will not be produced further. That means it came to the end of the production. See, for example, consider it as AA. This implies the parsing is going to be start from here. In the next step, it will go here. In the next step, it will be moving towards next one. So there is no other symbols, terminals or non-terminals to parse. So that implies that production has been parsed completely. Okay, so the same thing happens here. The same thing happens here. So simply you can say this will be the leaf node, because we cannot expand. So when it can be expanded means if there is any possibility to parse the further symbols. See, for example, this can be expanded further. This cannot be expanded further. This can be expanded, right? Because this dot represents parsing. Imagine dot represents a parsing. So for every step we are parsing each and every symbol and moving towards the right hand side, end of the production. Now next, if it is with a, s tends to a dot a. So whenever you got in this similar way, so for example I write here s tends to a dot a. So whenever you got this dot a, write down all the productions of a here. Okay, in this level. Now you got a dot a. So a dot a means whatever the productions we are having, we have to write down this in this particular level. So dot a. So dot a means a dot small a, capital A tends to dot b. So this is one more. And coming to the next one, if with a small a, so small a, you can see a tends to a dot a. Again we got same thing, dot a. So dot a means again we have to write all the productions of a. So write down all the productions of a. A tends to dot a, small a tends to dot b. Okay, and then with a b, simply we will get a tends to b dot. And here you can see this production we can't expand further. Now give the state numbers here. Okay, I0. Now this becomes I1, and this becomes I2, and this becomes I3, and this becomes I4. Okay, I4. Now expand this one. Expand this one. So this cannot be expanded, right? This cannot be expanded. So this can be expanded. So again, you can see there will be three options. One is with A, B, A, capital A, small a, small b. Now with the capital A, what happens with the capital A? S tends to A dot. A dot. So here it ends. Here it ends, right? Because the dot, the parsing has been sent to the last position. So it can't be further expanded. Now with A, what happens? A tends to A dot A. If it is A dot A, what happens? We have to take one more production, A dot AA, and A tends to dot B. Right? So you can see the same state repeating. Here we have given some I3. The same state has been repeated here. Okay, see, A tends to A dot A tends to dot AA, A tends to dot B. The same production. So you need not further expand this one. Okay, so simply upon A, it will moving on with I3. It will be moving on I3. Right? Now, once again, there is one more chance. It is B, that is A to B dot. So you can observe A tends to B dot. These are already generated with a state 4. So you can replace this with a state 4. State 4. Okay. Repeat the same process for this one, I3 also. So with A, it will be A tends to A dot. So it cannot be further because dot has been reached to the end of the production. And with also A, it will be A tends to see, it will be going with A dot A, and here again it's a dot A. We have to write on A, and A tends to dot B. So again you can see the same thing. Again you can see the same thing. Okay. So, here it is a capital A. Here it is a capital A. So capital A, parsing on capital A, parsing on small b, parsing on small b. And here parsing on capital A, parsing on small a, parsing on small b. Okay, after dot, whatever the symbol we are taking, that we have to do. So the same thing repeated, and again I will go with the same loop, that means same state I3. And again here on B, it will be A tends to B dot, which is nothing but I4. So again it will be I4. So go with the next level. So give the states and go with the next level. So I am giving the states. I0 given I1, I2, I3, I4, and this will be I5, and this will be I6. This will be I6. So no other production can be further expanded. So we have to stop here. So this is the canonical list items. Canonical list items with all the states from I0 to I6. If this I5 is further generated, that should be again expanded. Okay. So this should happen until there is no expansion of any one of the production. And all these productions should be parsed. You can see in I4, the third one has been expanded. The third one has been completed, parsed completely. And coming to the I5, the first production has been parsed successfully because started with the right hand side dot on the right hand side production, and now the dot becomes the last one. And I6 is the second one, second production, right? Now we have completed. Now we have to generate the parsing table. I generate the parsing table. So there will be two options. One is a action option, another one is a go to option. The first one is action option, another one is a go to option. So on the action option, we have to give all the terminals. On the go to option, we have to give all the non-terminals. So here on the action, what are the terminals we are having? So A, B, and take the dollar, because the input string, end of the input string, we are giving some dollar. And coming to the go to, we are having two non-terminals, S and A. Yes, A. Okay, this is a row. Now what about these are the columns. Now what about the rows? The number of states are represented as a rows. So we can go with the rows. So I'll write here because yes, I'll write here. So rows are states I0, I1, I2, I3, I4, I5, and I6. And actions are terminals. So A, B, dollar, and the terminals are yes, A. So these are the actions, and this is the go to. And now you can create the parsing table. You can create a parsing table with the help of canonical productions and the numbering of productions. So this is the okay. So I'm creating the complete grids. I'm drawing the grids because there will be no confusion about this. Okay. So there is a completely zigzag position. So don't worry about that. I just and give the productions. Give the numbering for productions, and this will be given as 1, 2, and 3. So don't go with the augmented grammar. So go with the original grammars and give the numbering for the productions. Now let us start. In the actions, we have to write it as a shift. Okay. In the goto, we should write it as a reduce. Okay. Now start. I naught. So here I naught on A. I naught on A goes to the I3. I naught on A goes to the A. Sorry. Yeah. I3. I3 means give it as a shift 3. Represent as S3. And I naught on B. On B it is I4. So we have to specify it as S4. We have to specify it as S4. Now I naught on S goes to I1. I naught on S goes to S1. So here give only the numbers. Okay, don't go with the shift or anything. So give the numbers. And see, I naught on A go to the I2. 2. So I give the number 2. I give the number 2. Now coming to I1. So I1 was not able to process next. Further. So S dot means the start symbol has been parsed. So I1 on dollar will be accept stage. Accept stage. I1 on dollar will be the accept stage. And I2 on A go to 5. I2 on A it goes to 5. I2 on small a goes to I3. I2 on small a goes to I3. That means S3. If it is actions, give the shift. I2 on B goes to I4. So S4. Next I3 on capital A goes to 6. I3 on capital A goes to 6. I3 on small a goes to 3. Again S3. I3 on small b goes to 4. S4. Okay. Now coming to I4. So I4 is last. Okay. So the production ends here. And is this just a start symbol? No. So what is this production number here? B dot. So that is the third production. So go with the reduce for I4. So it will be R reduce third one 3 and give the same for everything R3. Coming to I5 again this is the last, right? So which production has been ended and is the start symbol? No. So this is one production. What's the production here? Number 1. So I5 will be reduce 1. Reduce 1. Next I6. This is also last one. And check whether it is a start symbol. No, this is not a start symbol. Then what's the production number? A dot 2. Go with the R2. R2. Okay, so this is the parsing table. So we have generated parsing table from this canonical list items. Don't get confused. Fill the parsing table with a careful manner. Okay, so for all the possibilities, fill the actions. So if it points towards any other productions, go with the shift. And if it points, it moves with the terminal, then only we have to go with the yes. If it moves on the non-terminal, give the numbering, just a number. Now the next step is we have to take one string and we have to parse that particular string. Now, let us. I'll erase this one. Okay, I'll erase because hope you have noted this down. So I'll erase. And the next step is we have to pass this input string. We have to take the input string. So I'll take the input string as A, B, B. A and B, B. Now consider the string. So here let us consider it as a stack and input string and the action. See, this is also very important. So initially the stack will be empty and dollar will be pushed. Input string will be A, B, B, dollar. So we know that input string should be appended with a dollar because that gives end of the string. Now initially start with the initial symbol, start symbol. So where the start symbol is appeared, that will be in the starting state, that is 0. So from 0 we have to start. Okay, we have to start from 0 to state. That's the start symbol. So that's why I have kept here 0. Now see 0 on A, I0 on A, it's a 3. So what's the action we have to do? Shift. Shift input. Shift input to stack Okay, and place 3 because it is a S3. So what we have to do in our next case, what we have to do, $0, push this input symbol A, and what is the value here? 3. So I have to keep here 3. Okay, once again repeating. So 0 on A in the parsing table, 0th state on A gives a shift 3. So shift the input first towards the stack. So A will be shifted towards stack and place 3 because it is a third state, right? Shift 3. So 3 will be placed here itself. So always I'll write here shift with S3. I'll write in this way. Okay. So in order to avoid the place, I'll write in this way. So now the input will be A, B, B, $. Now again you can check with 3 and A. State 3 with A, shift 3. Again the same thing will be done. So shift with S3. So what we have to do? First we have to push A into stack. So $0, A, 3, again A, and again the symbol is 3. So again we have to give us 3 here, and it will be B, B, $. Okay, hope you understood. So again shift with S3. So A will be pushed into the stack and 3. So 3 will be placed here. Again now we have to go with the 3 with B. 3 with B. So 3 with B, it's a shift 4. Now again shift with S4. What we have to do? The next one will 0, A3, B4. Okay. Now the remaining input will be B $. B $. Now again go with the 4 and B. 4 with the B. See, 4 with B. Now it is a reduce 3. So reduce 3. So what is the 3 here? A tends to B. Okay, here 3 means a production. A tends to B. Now we have to replace this B4 with this 3, production 3. Okay, production 3. That means a reduce. That means we are reducing the stack to the productions. We are applying the productions to the stack value. So the next value will be 0, A3, A3. For B4 we are taking it as A, capital A. Capital A. So what about the number here? So there is no number. Now use 3 and A. 3 and A. Okay. So here B4 has been reduced with production 3 capital A. Okay. B4 reduced with third production capital A. Now there is no number here because here you can see we are comparing or we are getting the shift or reduce values with the help of state number and the terminals and non-terminals. And here we are not having any state number. So we have to check the 3 and A, reverse process. So 3 and A, it is 6. So give here 6. Give here 6. Now it will be B $. So check with 6B. State 6 with B or 2. Now again we have to go with the reduce 2. Reduce 2. So this is nothing but A tends to B, and this is nothing but A tends to A, small a, capital A. Now you can observe here. So forget about the states. It is small a, capital A. So everything can be replaced with this particular A. So what happens here? 0, A, 3, capital A. So this complete replaces with A. Now again there is no number. What we have to do? Again we have to check with 3A. So 3 with A, it is 6. Again we have to go with 6. And now B $. Check with the B and 6 and B. 6 and B. Reduce. 6 and B is reduce. Again we can reduce. Okay. So reduce 2. So again A tends to AA. So again what we have to do? Again we have to perform 0. What happens here? A3, A6. So A, 0 A, and here it is B $. Right? Now again there is no number. So again A0. A0 or 0 A, it is 2. We have to check with 2 and B. 2 and B. 2 and B is 4. Shift with S4. What we have to do? Again we have to place 0, A, 2, B and 4. B and 4. It's a $. It's a $. Now you can check with this one. So 4 and $. 4 and $. It's a R3. Okay, R3. So reduce 3. So what is the third production? A tends to B. Now what happens here? This can be replaced with $0, A, 2, A. 0 to A. Okay. So again 2A. So 2A. 2A. It's a 5. It's a 5. And it's a $. Okay, $5. So 5 and $, compare. So 5 with a $, 1. You can go with reduce 1. What's the 1 here? S tends to AA. Now what happens here? We have to replace it with dollar. AA can be replaced with 0 S. 0 S. Okay. You can see 0 S is 1. And this is a dollar. And now you compare with 1 and dollar. 1 with the dollar, it's an accept. 1 with the dollar is an accept. So like this, we have to perform the shift and reduce operations with the help of this numbering of productions as well as this parsing table. So actually the parsing table has been generated with the help of this numbering productions and the canonical items. So with the help of this parsing table itself, we can reduce. We can use a shift and reduce. Okay. So one thing we have to remember. So every time we have to compare the state with the stack of top of the stack. Okay. So hope you understood this one. Hope you understood. Now the last step. So this is the parsing of input string. Now the last step is a parse string. So what's the parse string? From bottom we have to go. So what's the bottom? Yes. Yes. Then S can be expanded with AA. So A. And this A is expanded with B. And this A is expanded with A and A. Again this A is expanded with A and A. See this one. And this A is expanded with the B. Completed. Now you can check A, B and B. So you can write out all the leaf nodes, that is A, B, B. That's the input string. Okay, so we are going from bottom to top. So previously we have started finding the expansion of generating the parse tree from top to bottom. Now in this case, we are using the bottom up approach. Okay, bottom up approach. From the bottom level, we are going towards the top level. So by using that, we have generated the parse tree. That implies the given input string A, B, B can be parsed with the help of this particular context free grammar. Okay, so this is how we can generate the parse tree using LR Parser. Okay, so this is the first category of LR Parser, LR0 Parser. So first step, we have to create the augmented assignment, and the next one, we have to insert the dot symbol on all the productions of the, right hand side of all the productions, and then we have to find out the canonical list items, and with the help of canonical list items, and the next step is give the numbering for the productions, and with the help of these two, that means numbering of productions and the canonical items, generate the parsing table, and use the shift and reduce here, and by using the parsing table, parse the input string using shift and reduce operations. So shift operation means shifting the input string towards the stack. Reduce means reducing the stack values with the non-terminals.
In today's session, we'll discuss about the SLR Parser to construct the parse tree. So before going to that, so let us see the introduction. So here, what we have to do means, first take the productions and first find out the LR of 0 items, and then construct parse table and consider a string generated from the productions or from the grammar, and parse the string. So we need to parse the string because we need to check whether the parse table is correctly generated or not, right? So finally, we need to design the parse string. So once the parse string was successfully generated, the string was parsed successfully, then we can design the parse string, right? So these are the steps we need to follow while constructing the parse string. So first we need to find the LR of 0 items for the given productions, right? So I'll explain with the Excel so that everyone can understand. So let us take the productions. These are the productions. E tends to E plus T, E tends to T, T tends to T star F, T tends to F, and F tends to parenthesis E, F tends to ID. Now, before finding the LR of 0 items, first we need to find the augmented grammar. So augmented grammar means adding one more production for the starting symbol. So here E tends to E plus T. So I need to introduce one more new production for the start symbol. I need to change the start symbol, right? So previously it was E tends to E plus T. Now I'm adding the production E dash tends to E and E tends to E plus T. So all the remaining productions will be same. So this production is newly added. Right? So this is called the augmented grammar. So first let us write the augmented grammar for the given productions, right? So E dash tends to E and all the remaining are same, right? all the remaining are same. Now the augmented grammar is ready. Now what we have to do? So we need to find the LR of 0 items. LR of 0 items. Now what exactly this item means? So we know the productions, right? So the grammar we call it as a production. Then what is this item? So an item means adding a dot at the beginning of the right hand side production, right? So for example, let us take the first. So E dash tends to E. So what we have to do? We need to add dot at the beginning of right hand side production. At the beginning of right hand side production. That means, so this should be written as E dash tends to dot E. E dash tends to dot E. So now this is called item, LR0 item. Now what we have to do? If the dot is having a followed by the dot is having a non-terminal, immediately after the dot we are having a non-terminal, then we need to write all the productions of that particular non-terminal. Write productions of non-terminal, right? Okay, hope you understood this one. So if the dot is having before the non-terminal, that means immediately the dot has having the non-terminal, then simply we need to write the productions of that particular non-terminal. That means we need to expand. Right? Now this is called the items. Okay, LR0 items. We need to process this one. Now let us check here. LR of 0 items. I'm writing here. So E dash tends to dot E. So dot, we need to add the dot on the right hand side production. Now after the dot we are having a non-terminal, we need to expand the productions, right? So what we have to expand? So E tends to dot E plus T, right? And also E tends to dot T. And again we are having dot after T. So we need to write down the T productions. T tends to dot T star F. See, simply remember that we need to add a dot after each and every production. That's called LR0 items. Then we'll find out the states, because in the construction of parse table we need to find out the states. Okay, we need to use the states. So that's why we'll find out the states. Now I will add the dot for every production. F tends to dot E and F tends to dot ID. So you can observe here. So this is a terminal. So it should be in a small letters. So you can observe here. So E dash tends to E. So for all the productions we have added a dot. Okay, for all the productions we have added a dot on the right hand side. So starting the right hand side production with a dot. Now we need to traverse this dot to the end of the production. So that will be calling as a final item, right? So if the dot is at the end of the right side of production, then it will be the item. Now let us consider this as a I naught, the state I naught, right? So I will highlight this one. So this is I naught. Now just simply go with the I naught. Go to I naught, and here you can see first one dot E, right? Dot followed by the E. Now that means we need to travel this dot towards the end of the production. So first I will travel I naught, go to I naught on E. So find out the E on the right hand side productions. You can see this is the one production, this is the one production. Just send the dot towards the right side of the production. So one step right side. So E dash tends to E dot, and again E tends to, okay, so just search the non-terminal on the right hand side only. So don't search for the left hand side, search for the right hand side. If you search for the right hand side, so these two are the productions where we are having E on the right hand side. So we need to move the dot towards the right hand side, one step right hand side. So E tends to E dot, and E tends to E dot plus T. And now observe whether the dot is followed by the non-terminal. So here the dot is at the end of the production. Here a dot is having a terminal. So just leave it. So give the state as I1. So we need not expand the terminal, non-terminal. So if the dot is followed by the terminal, okay, then if the dot is followed by the non-terminal, then we need to expand the non-terminals. So just take the another state. This is another state. Now simply go to I naught, and I naught still having the productions T, right? Now I naught on T. Let us travel the I naught on T. Now consider the T on the right hand side. So we are having these two productions. So similarly, just move the dot towards the right hand side. So E tends to T dot and T tends to T dot star F. So observe here, after the dot we are not having any parameter, any symbol here. Right? Here after the dot we are having the terminal. So we need not expand. So if the immediate symbol after the dot is a non-terminal, then we need to expand. Right? So just leave it and give the state I2. So because I0 is there, I1 is there. Now I2. So I will highlight the states and labels. Now, is it completed with I0? No. So there is one more thing, F. So I0 on F. So simply go to I0 on F. So what happens? So there is only one right hand side, that is this one, right? Dot F. So simply move the dot towards the right hand side. So T tends to F dot. T tends to F dot. So is there any other productions with a F on the right hand side? So here there is a F. So we need not process this one because dot after F, you need to consider this one. And yes, so simply stop it because here after dot we are not having any other symbols. So simply stop it. So give the state number 3, I3. So this is a I3, state I3. Now again go to I0 on completed F and there is a parenthesis, I0 on parenthesis. We can also process this one because dot parenthesis. Now we need to check whether we need to move the dot towards the right hand side. So F tends to parenthesis dot E parenthesis. Now you can observe after dot we are having a non-terminal. After dot we are having a non-terminal. So we need to expand this one. So write down all the E productions. Write down all the E productions. So if you write down all the E productions, simply you need to use, see, these are the E productions. These are the E productions, right? So we need to write all these things, E productions. And after writing this one, again you can observe after dot E is there, we have written the E production, and coming to this production, after dot we are having a T. T is also a non-terminal. Again, expand the T productions. So these two are the T productions. So I'm expanding these two productions. And after that, again you can observe dot T. So we have already expanded the T. So in the second production, dot F. In the second production, there is a dot F. So again we need to expand the F productions. F productions, right? Now in the F production you can see after dot there is a terminal. Here also there is a terminal. So leave it. So give the state as I4. Give the state as I4. Now after parenthesis there is a one more operation, that is the ID. Now go to I0 on ID. So ID is a terminal, right? So we need to write down the ID, this one. So move the dot towards the right hand side. So ID dot, right? So here you can observe after dot we are not having any symbols. So and we need not expand any other productions, and consider this one, and the dot is on end of the production, right hand side production. So this is called the final state. This is called the final state or final item. So I5. So let us give the label as I5. So take it. Right. So I will do the color, another color because of see, this is the final state, final item. Now after completion of I0, we have completed the I0, right? So I0 on E, I0 on T, I0 on F, I0 on left parenthesis, and I0 on ID. So in each and every case, we need to move the dot towards the right hand side. Then coming to the next, go to I1 on. So let us check with I1. So in the I1, the first production, dot is at the rightmost, okay, at the end of the production. Coming to the second production, so dot can be traveled, right? So on plus, I1 on plus. So here just move the dot E plus dot T. And observe here, after the dot we are having the non-terminal, right? After the dot we are having the non-terminal. So simply expand this one. So write down the T operations, I mean T production. In the T production, again we are having the F. So dot after dot we are having the F. So expand the F productions. Expand the F productions, right? Now give the state as I6. So just give the label, and again whether it was completed or not, let us check I1 on T, right? It was completed, right? Now move to the I2. So I2, first production is completed, right? The first production is completed, T dot, okay, dot is at the end of the right hand side. Now consider the second production. So go to I2 on star, I2 on star, right? Now let us check this one. So T tends to T tends to T star dot F, T star dot F. Again, observe. So dot after dot we are having the non-terminal. So we need to expand. So expand means we need to write the F productions. I will write the F productions here. Right? So that's the only production we can apply. So we'll give it as a I7. Give the label as a I7. Now after I2 was completed, go to the I3. So I3 is a final. Okay, I3 is also final state. So we can change it. Because in I3 only one production is there. In that production also dot is at the end of the right hand side production. So we can't travel the dot. Okay. Now go to the I4. So I4 we are having a lot of productions. I4 on E. So go to I4 on E. Go to the I4 on E. So we can observe we have to travel the dot towards the right hand side. So dot parenthesis dot. So dot will be moved E dot. So this production is changed to F tends to E dot. And again there is one more E on the right hand side. So you can change this one. E tends to so E dot plus T. And you can observe in these both productions we need not expand the non-terminals because after dot we are not having a non-terminal. So simply you give the state as I8. I will give the state as I8. Right? So like this we need to find all the states. So let us calculate all the things. Now just a second, I will write here itself. Okay, right. So I4 on E is completed. Now we'll check I4 on T. I4 on T. So go to I4 on T. So if it is I4 on T, okay, I4 on T, see here I4 is this one. T means here we are having only one production. So T tends to, okay, two productions. So E tends to T dot and T tends to T dot star F. Okay, so these are the two productions we are having a T on the right hand side. Okay, in the I4 T. So T dot and T dot star F. T dot star F. So here we need not expand any other non-terminals because after dot we are not having any non-terminal. So simply leave it and you can give the state, and before giving the state number you check whether these productions are repeated productions or not. And here you can see in the I2 the same productions has been repeated. E tends to T naught and T tends to T dot star F. So simply give the same state here, I2, same state number, because both are the same productions. Now I4 on T is completed. Now I4 on F. So simply go to I4 on F. So we are having only one production on the right hand side, F. So just expand this one. T tends to F dot. So only this one, we need not expand more because after dot there is no terminal or a non-terminal, and this is the final state. And let us check whether it was repeated or not. Yes, so this is repeated. This is a I3. So simply give the same state name, I3. Right? So consider whether it was completed or not. I4 on F is completed. Now again I4 on parenthesis, left parenthesis. We need to check with left parenthesis. So let us write here. So go to I4 on left parenthesis. I4 on left parenthesis. If you go to with the I4 on left parenthesis, you can see this one, expand this one. So F tends to move the dot towards the right hand side. So parenthesis dot E, close the parenthesis. Right? Now you can observe after dot we are having a non-terminal. So expand E, so that write down all the E productions. So these two are the E productions. Simply copy and write down the E productions. Right? So after writing the E productions, simply see. Again see, there is a dot, after dot there is a non-terminal. So T, expand this one. So write down the T terminals. So T productions. I'm writing the T productions. And here we are having again after dot F. That means again non-terminal. So write down the F productions. Right? And here we are not having any non-terminal after the dot. So just leave it. And now before giving to the state number, check whether it was repeated or not. Yes. So you can see here. So the same thing, I4 is repeated here. I4 is repeated. All the productions are same. So give the same name I4. Right? Now, so I4 on parenthesis completed. Now I4 on ID. We need to go with I4 on ID. So go to I4 on ID. So now just move the dot towards the right hand side. So F tends to ID dot. So this is also a final item. And check whether it was repeated or not. Yes, it was repeated. So this is I5. Right? So give the same state number I5. I5. So the process is simple. Just follow this one, and I4 is completed. Now go with the I5. So here we can't expand the I5 because I5 is a final state. Go to the I6. So yes, in the I6 we can do the process because so dot is not at the end of the right hand side production. So I6 on T. Let us start with the first one. I6 on T. So go to I6 on T. Now what happens here? So E tends to E plus T dot. Okay, E tends to E plus T dot. And again, T tends to T dot star F. So we are having a T on two productions on the right hand side. So we need to move the dot for the two productions. So E plus T dot star F. Right. So it was not repeated anywhere. So check once. So it was not repeated. So give a new state. So what's the new state here? I8. So it is I9. So this will be the I9. This will be the I9. Right. Now after that, so consider once again consider. Sorry. Right. Now I6 on T completed, and you can say I6 on F. So there is an I6 on F. So go to I6 on F. So what happens? We are having only one production on the right hand side with the F. So T tends to F dot. T tends to F dot. So simply after that we are not having any terminal or not terminal. Simply we need not expand this one, and this is a final item. And let's check whether it was repeated or not. Yes, it's a I3. It's a I3. So give the same state name I3. The same state name I3. Right. Again, consider I6 on F is completed. Now I6 on left parenthesis. I6 on left parenthesis. Go to I6 on left parenthesis. Right. Now consider this one. F tends to left parenthesis dot E. Left parenthesis dot E. So this dot will be moved towards its right. So left parenthesis dot E. Now you can observe again after dot we are having a non-terminal. So expand the E. So write down all the E productions. I will consider these E productions here. Right. And again we are having a non-terminal after dot, so that is T. Again we need to write the T productions. I will write down the T productions. Here after dot we are having F, again non-terminal. We need to expand the F productions. Right. So you can observe this is again it's a I4. This is again I4. So just give the name as I4. The state I6 on left parenthesis is I4. Again go with the I6 on ID. I6 on ID. So I will write here. So I6 on ID. So only one production is there. Right, with the ID on the left hand side, sorry, right hand side. So just change that one. F tends to ID dot. So is it repeated? Yes, it is repeated. Right, so it was repeated. That is nothing but I5. Okay, it's nothing but I5. So simply write down I5. I5. Now the I6 was completed. Now go to the I7. Again, I7 is having F, right? So we can process it. So go to I7, comma F. So if you process this one, right? If you process this one, so dot should be moved towards the right side. So T tends to T star F dot. F dot. So only one production is there where F is on the right hand side. Simply leave it and just check whether it was repeated or not. So there is no repetition. So give the state, new state. So where we have stopped I9. So this will be I10. This will be the I10. And I7 is completed? No. So I7 can also be processed with parenthesis and ID. Now consider go to of I7 with parenthesis. I7 with parenthesis. So parenthesis means this one. So simply process F tends to parenthesis dot E. So that means expand the E productions. So if you expand the E productions, write down the E productions here. So if you write down the E productions here again, we are having the T after the dot, so which is a non-terminal. Write down the T productions. Again, write down the T. After writing the T productions, you can observe there is a F which is a non-terminal after the dot. So again, expand the F productions. Right. So this is repeated. This is repeated. This is nothing but I4. I4. So it's nothing but I4. Give the same name. Right. Now after that. Is it completed? No. We need to process the ID also. I7 on ID. So I'll write here. So go to I7 on ID. So what happens here? ID. So the dot operator should be processed towards its right. So F tends to ID dot. ID dot. So let us check whether it was repeated. Yes, it's a I5. The state I5. It was a state I5. Right? Now I7 was completed. Go to the I8. So I8 can be processed because dot is not at the end of the productions. So I8 on right parenthesis and I8 on plus. We can move like this. So simply go to I8 on right parenthesis. I8 on right parenthesis. Now I8 on right parenthesis, you can see this production F tends to, so right parenthesis E, right parenthesis and dot. So E dot, right? So this is a final item, right? So it was not repeated. You can give the name. The state is I11 now. I11. The state is I11. Now again we need to process I8 with plus. Go to I8 with plus. So what happens here? You need to expand this one, right? So E tends to E plus dot T. So again, after dot we are having the T. After dot we are having the T. Expand the T productions, right? Write down the T productions here. I'm writing the T productions, and after writing the T productions, again we need to write the F, because after dot we are having a non-terminal. So write down the F productions here. We'll write the F productions, right? And you can observe whether it was repeated or not. So once you observe from the beginning, see here, these are the productions repeated. These are the productions repeated, right? So the state is, give the same state I6. Give the same state I6, right? So I8 is processed. Now I9. Go to the I9. Where is I9? The state I9. So in the I9, again we can expand with a star. I9 we can expand with a star. Now simply go with this one. So go to I9 with star. So only one production, because the above production was already, the dot has been processed towards the last of the right side production, right? So dot is at the end of the right hand side production. Now we need to process this one only. So star dot star. So T tends to T star dot F. T star dot F. So again write down the F production, because after dot we are having the non-terminal. So write down the F productions. So I'll write the F productions here and see whether it was repeated or not. We'll check. Yes, so you can observe here F I7 T star dot F and F productions, T star dot F and F productions. This is a I7, right? So this is the state. Now I9 on star completed. Go with the I10. So I10 is a final item. Okay, I10 is a final item. So you need not process it, right? And again I11. Go to the I11. I11 is also the final item. You need not process. Go with the I12. So there is no other state with I12. So we have already covered all these things. So we need to stop now, right? We need to stop. So the process is lengthy, but the procedure is very simple. The first thing, consider the productions and write down the augmented grammar by adding a new production for the start symbol, and consider the LR of 0 items. That means add dot on the right hand side. Start the right hand side production of every production with a dot. So E tends to dot E, E tends to dot E plus T, and E tends to dot T. Now consider the state as I0. Now we need to process I0 with all the terminals and the non-terminals, right? So dot E. So we need to process I0 on E, because the dot should be processed towards the last of the right hand side. Okay, end of the right hand side production. So it is dot E. So we need to process E. So find out the E on the right hand side. So E on the right hand side, we are having these two productions. Now just use these productions. That means just move the dot towards the one step towards the right side. Move the dot one step towards the right side. So E dash tends to dot E becomes E dash tends to E dot, and E tends to dot E plus T will be moving as E tends to E dot plus T, right? So observe whether there is a terminal or a non-terminal after the dot. So if there is a terminal after the dot, if there is a non-terminal after the dot, expand that particular productions. So here we are not having. So after dot there is no other terminal or non-terminal, and here we are having a dot. After dot there is a plus, that is a terminal. Leave it. Now consider this one. See, consider this example. So F tends to parenthesis dot E. So now dot after dot we are having a non-terminal. So we need to write the productions of this particular non-terminal. So expand this one. So write down the productions of this particular E. So these two are the productions of E. I have written these two productions of E. And again check whether again there is a terminal after the dot. So after the terminal dot there is a E. So we have written already. And in this production we are having T after the dot. So again expand T. So write down the T productions. We have written the T productions, and then again check. So there is a one more expansion, that is a dot F. So F is there after dot. So write down the F productions. You just follow the same procedure until you process all the states. Until you process all the states, right? So this is the first step. So we need to construct the canonical collection of LR of 0 items, right? So hope you understood this one. So after that we will construct the parse table. Now let us see the number of states, and we'll construct the parse table. So before constructing the parse table, first let us note down the final states, and we'll find the follow for all the non-terminals, right? So based upon that, we need to fill the parse table. So first let us write down the final states and the follow. So I will write in one more Excel so that it will be very easy for understanding. So here I'll write. So final states and reduced terms. Reduced terms are nothing but our follow, right? So see the final state first. Here you can observe the final state, that is I1. In I1 we are having the final state E dash tends to E dot. So the state we will call it as a final state when the dot is at the end of the right hand side production. So here we are having the right hand side production, E tends to E dot. That's one final state. I will write down that one. So E dash tends to E dot. E dash tends to E dot. So that is available in the state number 1. So I1. Next, coming to the state 2. So I2 is also having a final state, that is E tends to T dot. E tends to T dot. And then I3 is also having the final state. So that is T tends to F dot. Next, I3, I5. So we have already mentioned here. So I5 is having the final state F tends to dot ID. Sorry, ID dot. So the dot should be at the end of the right hand side production, ID dot. So after I5, so we are having I9. So I9 is having the final state E tends to E plus T dot, and after that 10. So I10 is having one more final state, T tends to T star F dot. So I think completed, or yes, one more thing is there, that is a F production. I11 we have I11 F tends to, in the parenthesis we'll use a E and dot, in the parenthesis E dot, right? So these are the final states. Now give the order based upon this augmented grammar, right? So this is R0, R1, R2, R3, R4, because these are the reduced terms. By using this one, we are going to reduce the grammar, right? So first E tends to E, that is nothing but R0, and next E tends to T dot, so that is R2. E tends to T dot, that is R2, right? Next T tends to F dot. T tends to F dot is R4, so R4. And next F tends to ID dot, it's F R6. E tends to E plus T dot, that's R1. And T tends to T star F dot, that's R3. And F tends to E dot, that's R5. Right? Now we had the final states and the corresponding reduced terms, right? Now we'll see the follow, right? So this is the initial state. E dash is an initial state, so this will be accepted state. Okay, this will be the accepted state, and coming to from the next one, we need to find out the follow. We need to find out the follow. Follow of E is equal to, follow of E is equal to, so I have already done this one, so just go through the previous sessions how to find the follow and find out. So I'm directly writing the result. So plus dollar and right parenthesis, right? And the next one, follow of T. Follow of T is equal to, so plus dollar right parenthesis and a star. Similarly, follow of F is equal to star plus dollar and the right parenthesis Next, follow of follow of E is the same, okay, and T, follow of T is also same. So we'll write the follow of E because this production is of E, so we'll just note on the same thing, we'll copy the same thing, follow of E here, and this is of T tends to T star F dot, so we'll go with the follow of T. So based upon these terms, we need to fill the parse table. This is F, so follow of F. So note down like this, right? Now we need to fill the parse table. The parse table will be containing two terms. One is an action, another one is a goto. So here the action means for the terminals and goto for the non-terminals. First, let me write down the states I0, I1, and so on up to I11. So total 11 states we are having, right? Total 11 states. And here, so we are having the terminals ID plus star left parenthesis, right parenthesis, and finally that dollar. And the non-terminals E T, F, right? So this is the parse table we need to fill. So how to fill this parse table? We'll see one by one, right? See, so check now. So all the terminals comes under action, and all the non-terminals will comes under go to, right? So always remember that the one with a dollar is an accept state. One with a dollar is an accept state, right? So now let us check according to this one. So come with order I naught on E, right? So I naught on E, it goes to I1. So I naught on E goes to I1. So if it is a non-terminal, just give the number 1. And I naught on T moves to I2. I naught on T, it moves to I2, that means 2. I naught on F, it is 3. So I naught on F, it is 3. Next, I naught on left parenthesis, it's I4. So if it is a terminal, use S symbol, S for shift, okay? So I naught on left parenthesis, I4. I naught on left parenthesis, it will be S4, right? So it's a fourth state. Here we need to use a shift, right? If it is a terminal, use the S symbol, yes. If it is a non-terminal, use the numbers, state numbers, right? And after that, I naught on ID goes to I5. I naught on ID goes to I5, so S5, right? And I1 on plus, here I1 on plus move to I6. I1 on plus move to I6, that means S6, right? Next, I2 on star moves to I7. I2 on star moves to I7, so it will be S7 because of its terminal. So I4 on E moves to I8. I4 on E moves to I8, so it's a non-terminal, so simply give the number. And I4 on T moves to I2. I4 on T moves to I2. I4 on T moves to I2, so give the number. I4 on F moves to I3. I4 on F moves to I3, so give the 3 as a number. Then I4 on left parenthesis I4. I4 on left parenthesis I4, simply go with the S4. And I4 on ID moves to I5. I4 on ID moves to I5, so it's a S5. And I6 on T moves to I9. I6 on T moves to I9, so give the number 9 because of non-terminal, right? I6 of F goes to I3. I6 on F goes to I3, so give 3 number. I6 on ID goes to I5. I6 on ID goes to I5, so S5 because of its terminals. These are the terminals. I6 on left parenthesis I4. I6 on left parenthesis I4. This is S4. And I7 on F goes to I10. I7 on F goes to I10, so give a symbol 10. Then I7 on ID goes to I5. I7 on ID goes to I5, so S5 because it's a terminal. And I9 on star. I9 on star gives to I7. I9 on star goes to I7, so S7. So this is a S7, right? I think, yeah. So I7 on left parenthesis. I7 on left parenthesis, it moves to I4. I7 on left parenthesis, it is a I4. Then I8 on right parenthesis I11. I8 on right parenthesis I11. So it is a S11 because the right parenthesis is a terminal, right? I8 on plus goes to I6. I8 on plus go to S6, right? So these are the terminals and the non-terminals, and these are the states. These are the states, right? So we are filling the shift. Shift is completed. So simply you can say yes for shift operation and R for reduce operation. So we need to apply only these two. Okay, shift and reduce. So we have completed the shift operations, and now we have to apply the reduce operations. So how to fill with the reduce terms? Simply go with here, right? So I2 is having the final state E, okay, so which is nothing but a R2. R2 means the production 2, right? So go with the follow of E. So because this is a E production, the follow of E. So fill the I2 on plus dollar and right parenthesis with R2. Okay, so this is the first. I mean, this is one final state. E tends to T naught. T dot is the final state, which occurs in I2 state, and this is the production number 2. So previously we can see E tends to T naught. E tends to T naught is the production 2, second production. Consider the productions, right? This is the second production. So we need to use a reduce 2. And similarly, so find out the follow of E so that whatever the terms we are getting here, you fill 2 corresponding to all these terminals with R2. So here you can see I2 on plus dollar and right parenthesis fill with R2. So I2 on plus is R2, I2 on dollar R2, I2 on right parenthesis R2, right? So hope you understood this one. Similarly, go to the next one. I3 on, this is a T production, and that is a fourth production, and find out the follow of T and fill the corresponding 3 corresponding with all these terminals with the R4. So I3 upon plus, go with the R4, and I3 upon dollar R4, and I3 upon parenthesis R4, and I3 upon star R4. Similarly, go with this one. Next, I5 upon star, it's a R6. I5 upon star R6, reduce 6. Okay, so I5 upon plus R6, and I5 upon dollar R6, and I5 upon right parenthesis, it's again R6. Then this I9, right? So all these are the, remember, all these are the final states. So these are the state numbers where we got this final state. Okay, final item, we can say it as a final item. So without confusion, I will write here, it's a final item, and these are the final states. Okay, these are the final states, and this is a final item, and this is nothing but a production number. These are the production numbers, right? Now we got with the R6. Now I9 upon plus, it is R1. I9 upon dollar R1, I9 upon right parenthesis R1, and similarly I10 upon plus R3, I10 upon dollar R3, I10 upon right parenthesis R3, I10 upon star R3, right? Similarly I11 upon star, it is R5, I11 upon plus R5, I11 upon dollar R5, and I11 upon parenthesis, right parenthesis R5, right? So these are the reduce operations. So we have successfully completed the parse table. We have filled the parse table. So once again, I'm repeating. So first, write down the follows, write down the productions. That means the final items. So where we got the final item. So once again, I'm repeating, the final item means the dot should be at the end of right side production. So just write down the final productions and write down the corresponding states where we got this final item. So here, from here, we can get the state number from where you got the final productions, right? So then corresponding, give the production numbers. So the starting productions, give the numbers for the starting productions and fill them with the production numbers, right? So fill them with the production numbers. Now simply use the thing. So find the follow for each and every non-terminal and fill the follow, right? So here, this is the E production, write down the follow of E. This is the T production, write down the follow of T. F production, find out the follow of F. E production, find out the follow of E. T production, find out the follow of T. F production, find the follow of F, right? So already we have discussed about how to find the follow in the previous sessions. So I will post the link in the description. So you just go through that and find the follow of all the non-terminals. And now use the table, create the table with all the states and two terms, that is the action and go to. Action consists of all the terminals and go to consists of all the non-terminals. Now upon the states, see, upon I0 on E, go to the I1. So upon I0 on E, go to the 1. So if it is a terminal, if it is a non-terminal, just give the numbers. If it is a non-terminal, give the S value, S followed by the state number. So S stands for shift. So once you complete these shift operations, then based upon the follow of these non-terminals, so the state upon the follow of this non-terminal, fill the reduce values. So R2. So for this production, this is the R2. So I2 upon plus dollar and right parenthesis, fill the R2. R2 means reduce, right? Similarly, I3 upon plus dollar parenthesis and star, fill the R4. So R4. So like this, we need to fill the parse table. Now the parse table has been completed. Now the next step is we need to consider one string generated from the productions, and we need to parse that string whether we are getting the correct answer or not, right? So finally, we need to apply the shift and reduce operations on the string so that we need to get the accept state. Accept state means 1 upon dollar. So this is the accept state. So finally, we need to get this accept state, right? So now we'll generate one string from the productions and we'll do the parsing, right? We'll parse the particular string so that we'll check whether the parse table is constructed correct or not. Now we'll consider a string. We'll generate the string from the given productions, right? So here with the given productions are so from the given productions, let us generate a small string, right? So first let us start with the E tends to E plus T, and in the place of E we can substitute T. So here we'll substitute T, so T plus T, right? And in the place of t, we can substitute f from the production. T tends to f, so f plus, again here also we'll substitute f, and in the f we can directly give the terminal id, so id plus id, right? Now let us consider this a simple string. So this is a string generated from these productions. So if you parse this string with the help of parse table, so it should be, we should get the accept state, right? So let us consider this string id plus id, right? Now let us consider, let us take the three terms. The first one is a stack, the next one is the input string, and the next one is a action, whether we need to reduce or a shift. Okay, so initially the stack consists of dollar and the input string id plus id, and at the end of the string dollar. In order to represent the end of the string, we'll take the dollar, right? So hope it is visible to everyone. There is no problem with that, right? So here let us consider right. So initially the stack value is dollar, right? And the input string is id plus id dollar, and initially there will be no action. So now let us start with the initial state. So I am pushing 0, the initial state, to the stack, and the string is same. And now we need to find out 0 upon id. So 0 is the top of the stack and input string is id. So just follow the parse table and take the action on 0 upon id. So what action it was, either reduce or shift. So according to the parse table, we'll find 0 on id. So this is a parse table we have constructed. 0 upon id, this is s5. S stands for shift and r stands for reduce. So if 0 on id, it is s5. So here s5, s5 means shift 5, right? Shift 5. So if it is shift 5, what we have to do, we have to shift the first term in the input string into the stack. So $0, what's the input string here? id. So push the id and then push the number, the state number, that is a 5, right? So hope you understood. 0 upon id is the shift 5, right? Shift 5. If it is a shift, just push the input string, the first element of the input string, to the stack, and then push the state number to the stack. So 0, id, and a 5. And here now the input string is plus id and dollar. Sorry. Okay, as this is Excel, so it doesn't accept the plus, right? So we'll, just for understanding, I'm writing some plus. Okay, so don't get confused. Plus is for representing the operator plus. Okay, plus id dollar, plus id dollar. So here now 5 on plus, 5 on plus. So go to the parse table. 5 upon plus, it's a reduce 6. It's a reduce 6. So r6. So what's the r6 here? Just go to the here. R6 is f tends to id. So here it is a f tends to id, right? R6 is a f tends to id. Now just observe, if the production f tends to id, whatever the production it may be, the reduced production. So on the right hand side, just count the number of elements. So if the count is 1, we need to pop the 2 elements from the stack. If the count of elements is 2, we need to pop 4 elements from the stack. If the count is 3, pop 6 elements from the stack, right? So 2 into number of count. So here this is a reduce operation. So reduce r6. R6 is f tends to id. See, r6 is f tends to id. On the right hand side, we are having only 1 element, so we need to pop 2 elements. Okay, we need to pop 2 elements. So here I will write the action. So push input string, then state number, right? Input string and state number. Here count number of elements on right hand side of production and pop 2 into number of elements, okay, from stack, right? So just for better understanding, I'm writing all these things. See, now remove the 2 elements, that is 5 and id will be removed. So $0, and now push the f, right? Push the symbol non-terminal 0 f. So here it will be plus id and dollar. And here what action you need to take? So 0 upon f. So consider 0 upon f because f on plus, there is no state number here, right? So the top of the stack is, it's a non-terminal. So we need to get the state. So find out 0 upon f. So 0 upon f. So 0 upon f, it is a 3. So give the action 3, right? Shift the 3. Now push state number to stack, right? Push the state number to stack. So next it will become 0 f 3, and here it will be plus id dollar, right? So here after that we need to consider and push LHS non-terminal on LHS to stack, right? Now right, now see, now 3 upon plus, 3 upon plus, so go to the past table, 3 upon plus, it's R4, right? R4. So let us check with the R4, T tends to F. So it is T tends to F. T tends to F. Now the same thing apply. Count the number of elements on RHS. On the RHS of production, we are having only one element. And pop 2 into number of elements from stack. 2 into 1, 2 elements from the stack. And push non-terminal on LHS onto stack. So remove this F and 3 because on the right hand side production we are having only one element F. So 2 elements to be removed from the stack. So $0 F, sorry 0, and push the non-terminal on the left hand side to the stack. So T, and here it will be plus id. Now here what action to be taken? So T on plus, there will be no element for this particular table, right? So we need to get the state number. So 0 upon T, find out 0 upon T. 0 upon T, it's a 2, right? So 2. Now push the state number to the stack. So it will become $0 T2, and here it is common plus id dollar, right? So 0 T2. Now 2 on plus, 2 on plus, again reduce R2. R2. What is R2? R2 is E tends to T. E tends to T. E tends to T. Now you can observe the same thing. First count the number of elements on the right hand side. So only one element. So we need to pop 2 elements from the stack. So $0. T and 2 has been removed, and push the non-terminal on the left hand side production to the stack. So E. And here again it is plus id and dollar. So here we need to get the state number. So 0 and E. So push the state number 0 upon E. So 0 upon E is a 1. So take 1. Now push the state number to the stack. So $0 E1. And here it is the same plus id and dollar. So G1 on plus. So 1 is the top of the stack and plus is the input string. So 1 on plus. So 1 on plus. It's a shift 6. It's a shift 6. So push the input string. First push the input string. So $0 E1. What's the input string here? Plus. Okay. And then push the state number. So 6 is the state number. 6 is the state number. Now the input string will be id and dollar. id and dollar. Now what happens here? 6 on id, right? 6 on id. So 6 upon id is again S5. So shift 5. So again same, apply the same. So first shift, sorry, S5, right? So 6 on id, let us check 6 on id S5, right? Now push the input string first and then the state number. So you apply the same thing, and after that just push the id input string and then the state number 5. Now the input string becomes empty. That means a $, right? The input string is $. Now 5 upon $. 5 is the top of the stack and $. So 5 upon $R6. So now you need to go with R6. What is the R6? So just above we have written this R6. So what is this? F tends to id. Yes, F tends to id. And same, count the number of elements on the right hand side. Count the number of elements on the right hand side of the production and pop 2 into that many count from the stack. So only one element is there. We need to remove the 2 elements. So it will be a $0 E1 plus 6. Okay, id and 5 has been removed. And push the non-terminal on the left hand side of the production to the stack. So F, and give the $. So there will be no element for F on $. So we need to get the state number. In order to get the state number, go with the 6 with F. So 6 upon F, it's a 3. So it is a 3, right? Now push the state number to the stack. So $0 E1 plus 6 F and 3, and it's a $. Now again 3 on dollar, 3 on dollar, it's a R4, that means a reduce 4. So R4 means here t tends to f. So if it is t tends to f, again we need to remove 2 elements from the stack, because on the right hand side of the production we are having only 1 element. So count the elements and remove the 2 into that many elements from the stack. So dollar, so 0, E, 1 plus 6. So f and 3 has been removed here. F and 3 has been removed, and push the non-terminal on the left hand side to the stack, so t, and it will be the dollar, and there is no element for t on dollar, so we need to get the state number. So go to the 6 upon t. So 6 upon t is a 9. 6 upon t is 9. So here go with the 9 and push the state number to the stack. Push the state number to the stack. So simply you just push it. So dollar 0 E 1 plus 6 t and 9 upon dollar. So 9 upon dollar now. Right? 9 upon dollar. 9 upon dollar. It's a R1. It's a R1. So what is the R1 here? Just go with this one. R1. It's a E tends to E plus T. So E tends to E plus T. Now you can observe the count on the right hand side of the production is we are having 3 elements, E, T plus and T. That means 2 non-terminals and 1 terminal. So what we have to do, we need to remove 2 into 3. That means 6 elements from the stack. 6 elements from the stack. So you can remove 9, T, 6 plus 1 and E. Total 6 elements. So these are the 6 elements. Okay, E 1 plus 6, T 9. All these 6 elements has been removed. So now the stack is having dollar 0 and push the non-terminal on the left hand side to the stack, so E, and go to the dollar. So E upon dollar we will not get any entry, so we need to get the state number. So 0 upon E, go with the 0 upon E. It's a 1. So it is a 1. Now what we have to do, push the state number to the stack. So it will be dollar 0 E 1 and dollar. Now go with the 1 with the dollar. So 1 upon dollar. It's a accept. It's a accept. Right? Accept. So what we have done, so we have started parsing the input string with the help of this parse table. Finally, we got this accept state. So if you got this accept state, that means our input string is parsed successfully, so that we can generate the parse tree. So we can also generate the parse tree, right? So once again, I'm saying, so first input stack will be, by default, it will be dollar, and the input string we have generated from the production. So we have taken one input string. So you can take any input string, right? So initially there is no action. So first let us start with the initial state 0. So push the 0 to the stack and 0 upon ID. Go to the parse table, 0 upon ID, it's a S5. So here we are doing 2 operations, the shift operation and the reduce operation. If you are using the shift operation, you need to shift the input string first and then the state number. So it is S5. So first we need to push the input string, that is the ID, and then 5. And now the input string becomes plus ID dollar. So here just observe, don't get confused. I'm writing in a words, plus in terms of words, because it's an Excel. So if you are using plus with the starting, so it will be calculating some formula. So that's why I'm representing the operator plus, the symbol plus with text. Okay, it's string. So plus ID dollar. Now 5 upon plus. So 5 upon plus, go to the parse table and check 5 upon plus. It's a reduce. If it is a reduce, go with the reduce number R6. So go to the here R6. We are having the ID. F tends to ID. So F tends to ID. So here we know that production will be having the left hand side and the right hand side. Left hand side will be having the non-terminal, and the right hand side will be having the combination of terminals and non-terminals. Now count the elements on the right hand side of the production. So if the count is 1, just remove 1 into 2. That means a count into 2 elements from the stack. Right? So if the count is 2, we have to remove 4 elements from the stack. If the count is 3, we have to remove 6 elements from the stack. So here, if you observe the count is 1, so 2 elements should be removed. That is ID and 5 has been removed. And after removal of this thing, the 2 elements, push the left hand side non-terminal of the production to the stack. Okay. And now observe F1 plus. So there will be no entry for F with a plus. So we need to get the state number. So just to follow the 0 upon F. 0 upon F. So go to the table and 0 upon F. It's a 3. So here the action is 3. So just push the state number to the stack. So just push the 3 to the stack. Now we got the 3 and plus. So now check 3 with the plus. So 3 with the plus R4. So reduce 4. So reduce 4 means again we are getting the production R4 T tends to F. So only one element is there. So 2 elements will be removed from here, and the leftmost non-terminal will be pushed into the stack, as well as, so 0 upon T, it is a 2. Now again 2 will be pushed into the stack. So this is how we have parsed the input string, and finally we got the accept. Okay, finally we got the accept. Now you can observe from this, the last step is construction of parse tree. How can we construct the parse tree? How can we construct the parse tree? See, let us start here. So consider from bottom up. So this is a bottom up parser, so bottom up. So consider the last production. This is the last production, right? So E tends to E plus T. Consider this one. E tends to E plus and T. Now next production T tends to F. So T tends to F, right? So these are the nodes. T tends to F. So next F tends to ID. So here F tends to ID. Next one E tends to T. So this is a E, right? E tends to T. Next T tends to F. Again T tends to F. F tends to ID. F tends to ID. Now you can see the leaf elements ID plus ID. So the leaf elements are ID plus ID. So which is nothing but our input string. Okay. So this is a bottom up. Finally, you need to construct the parse tree. So just go with the last terminal, I mean last production. So last production is E tends to E plus T. Consider from that one E tends to E plus T, right? And follow with the next one T tends to F. So remove T with F. Okay, F with ID. So F with ID and E tends to T. So E tends to T and again T tends to F. Again T tends to F and finally F tends to ID. So F tends to ID. So the leaf nodes you can observe ID plus ID. So this is how we can construct the parse tree. So you can take any string. You can take any string from the given productions and you can check with the parse table. Okay. So this is how we can construct the parse tree by using the SLR parser, right? So the first step we need to consider the LR of 0 items. Okay. First give the augmented grammar, go with the LR of 0 items, find out all these things and find out the states and then find out the follow of elements and find the final items and corresponding states and give the order of productions, and based upon all these things fill the parse table by using the shift operations and the reduce operations, right? And finally you need to construct one input string. You need to construct one input string and parse that input string based from the parse table, and finally we should get the result as accept. Okay, we should get the result as accept. Once you got the accept, now start constructing the parse tree from bottom to top. This is a bottom up approach. So start with the last production and move upon with the first production. So finally you should get the input string, right? So this is all about our SLR parser.
So usually we call it as a CLR1 parser. So in our previous sessions we have seen two bottom-up parsing techniques, that is LR parser and SLR parser. And now we are going to see this CLR, canonical left-right parser. Okay, so here C is for canonical. So we need to calculate the canonical list items and the input string will be parsed. Input will be parsed from left to right, and last one R is, it uses rightmost derivation in order to construct the parse tree. And finally this one indicates look ahead symbol. So we'll see what exactly means this look ahead and how to calculate this look ahead symbol, right? Yes. So as just now I have said that this is a category of bottom-up parsing. It is a category of bottom-up parsing. Okay. Now we'll see what are the steps involved in this particular CLR parser. So similar to our LR parser and SLR parser, so here the first step is we need to create or we need to generate the augmented grammar. From the given context-free grammar, we have to convert it into augmented grammar by adding one more production for the initial symbol, the start symbol. And the second step, I'll write here, okay, I'll write here. So step 1, so creating augmented grammar. And the second step is finding out the canonical list items. Finding canonical list items. That means LR1 items. So we have seen LR0, okay, LR0 items. That means LR parser. Now, what exactly means these LR1 items? So these LR1 items means LR0 plus look ahead. Look ahead symbol. Okay. For example, if we are having something like AA, okay. So here the augmented grammar will be dot AA, and afterwards we need to give the look ahead symbol, which is nothing but the first of the remaining terms in the above, right? So first of AA. So this is the look ahead part. This is the look ahead part. So this is the LR0. LR0. That means we are starting with the dot, okay, and the dot represents the parsing. So the parsing will be done from the beginning till the end. So for every iteration, the dot will be moving towards on the right side. So whenever it becomes here A dash, that implies the production is completely parsed. So this is the LR0, and this will be the look ahead. So don't worry if you are not getting clarity. So while solving a problem, you will get a clarity, no problem at all. So the second one is a finding of canonical list items. Canonical list items. So I represent it as LR of 1, which is LR of 0 plus look ahead symbol. And step 3, numbering of productions. So for the productions, just give the numbering. So this is a common step we have done in both the LR and SLR. And step 4, generate the parse table. Generate parsing table with the help of LR1 items and the numbering of productions. So with the help of step 2 and 3, just we have to create the parsing table. And once the parsing table has been created, step 5, we have to start parsing the input string. So we have to consider one input string, and we have to start parsing that input string. So parsing of input string. Parsing of input string. So once the input string was parsed successfully, then the last one is construction of parse string. And the two bottom up parsing, by using the bottom up parsing. Okay. So these are the steps involved in the CLR1 parser. So hope you understood this with an introductory part. Now we'll take the grammar and we'll solve it by using this CLR parser. Let's take an example. So whatever the example we have taken for LR parser, so the same thing I'll take here. So I'll take the productions. So S tends to A, and A tends to small a, capital A or B. Okay, this is the grammar we have taken. The input string is A, B, B. So we have to check whether the input can be passed with the help of this grammar or not. So the first one is the augmented. The first one will be the augmented, right? So I'll take one more. So step 1, I'll write here step 1, augmented. So S dash tends to S, and S tends to A, and A tends to small a, capital A, and A tends to B. I'll write each and every production separately. Okay. See, after this, we have to add a dot before the right hand production, right hand side of every production. So I'll write here S dash tends to dot S, and S tends to dot A, and sorry, A tends to dot small a, capital A, and A tends to dot B. So we need to find, the next step we need to find the canonical items, that means LR1 items, right, by parsing dot with the help of look ahead, right, with the help of look ahead. So that's most important. So the step 2 is we have to find out the LR1 items. LR1 item means LR0 along with the look ahead symbol. So first I write here S dash tends to dot S, and we need to find out the look ahead. So for initial state, the look ahead symbol will be dollar. Simply remember, it will be a dollar. Now here we are having a dot S, so we need to write down the productions of S. So S tends to, what's the production of S? Dot A, comma. Here we have to find out the look ahead symbol from the previous production. So now it will be first off. So after the S, we have to find out the first. So it will be only dollar. So no other terminals or non-terminals here. So it will be first of dollar. So obviously it will be dollar. So here again we are having a dot A. So we need to write down the productions of A. So A tends to dot small a, capital A, comma, first of. So after A, we have to find out A, comma, dollar. So first of A. So first of A means, you can see A is having two terminals, A and B. So the first of A will be automatically A or B. Similarly, there is one more production, A dot B. Again, the same will be applied for A, because the same lookahead symbols will be there for all the same non-terminal productions, right? So this is our first state, and from this state we are supposed to expand further. So we need to move the dot from left to right towards the end position. Okay. Now we can see on yes it will be s dash tends to s dot comma dollar. So is there any production with yes on the right hand side? No. So that will be the same. Second one, a s on a. So yes tends to a dot a dollar. So what happens here? Again we are having dot a, so we need to write down the productions of a. So a tends to dot a capital A, and the lookahead symbol will be same for all the productions. So a tends to dot b dollar. So this is a one more state. And upon small a tends to a dot a comma a or b. Again there is a dot a. So again we have to write down the a production. A tends to dot a comma a or b. A tends to dot b comma a or b. So this is a one more state. Hope you understood. So if you are having a dot after the non-terminal, we have to write down the complete production. That is called an augmented grammar. So upon b, a tends to b dot comma a or b. Okay. Now these are all the different states. So initial state is I0. Now it will be I1, I2, I3, and I4. 4 states. Now again we have to expand further. So we can't expand this further because the dot reaches to the end position of the right hand side of the production. So it will be remain same. This can be expanded because after dot we are having some terminal or non-terminal. So this can be expanded here. So upon a, s tends to a dot comma dollar. So any other a on the right hand side after dot? No. So this will be only one production. Upon a, it will be a tends to a dot a comma dollar, and here after dot we are having a non-terminal here. We need to write all the productions of that particular non-terminal. So a tends to, so what's the production? Dot a, and here it is a dollar, so just keep writing this dollar symbol. So dot b comma dollar. And upon b, and check whether it was repeated state or not. So if all these three productions are repeated, so then you can replace this with that particular state number. So check out here a dot a, yes a dot a, dot a dot a, dot b dot b. So both are equal. So let us check with the lookahead symbol. Here it is dollar, it is a by b. So lookahead symbol are different. So that will be the new state. We should not replace that with the state, right? So it tends to be a tends to b dot comma dollar. Again check with this one. Check with this one. You can check here. I4 is having the same production but different lookahead. So just reminds this will be the new states, which is I5, I6, I7. Okay, I7. And upon this one, upon capital A, we have to expand this I3, right? So upon A, what will be there? A tends to a dot comma a or b. Only one thing. So this becomes I8. And upon small a, you can see a tends to a dot a comma a or b. Write down the a productions. A tends to dot a by b, and a tends to dot b a by b. And now you can see all these productions are same. A dot a dot a dot b, a dot a dot a dot b, and lookahead symbol also same. So this will not be the new state. This will be the same state I3. So I3 upon a goes to I3 itself. I3 upon a goes to I3 itself. Okay. And similarly upon b, a tends to b dot comma a or b. See, these both are same. B dot a by b, b dot a by b. So upon b, it will go with the same state. Sorry, I4. And I4 can't be expanded. So we have expanded I2 and I3. Now check whether it can be further expanded. So I5 can't be expanded. I6, yes, I6 can be expanded. So I6 upon a, which will be a tends to a dot comma dollar, and this will be only thing, a dot dollar. So check whether it has been appeared previously or not. So here we got a dot, but the lookahead symbols are different. So that will be the new state, which will be I9. Now upon small a, it will go with the a dot capital A comma dollar, and here again dot a. We need to write down the a productions. So a productions. So dot a comma dollar. A tends to dot b comma dollar. So you can check whether it is same or not. So both are same. See, a dot a dot b. So lookahead symbols also same. So we need not move with the new state. It will be same. That means I6 only, the self state. And upon b, it will be a tends to b dot comma dollar. So I think it was also happened? See, A tends to B dot dollar, which is I7. So you can replace this one and simply go with the I7. Okay, and now I8 can't be expanded more. So we have already expanded each and every term here. Okay, so hope you understood. Now we have to give the production numbers. So 1, 2, and 3. 0, 1, 2, 3. So these are the original productions. I am giving 1, 2, and 3 as a production numbers. Now I will write the parsing table. The next step is a parsing table. So where we have to consider the terminals and non-terminals. So for the non-terminals, we are considering the shift operations. Terminals we are considering the shift operations, and non-terminals just we are writing the state numbers. So that we will be calling as a go-to, actions and go-to. So what are the terminals we are having? A, B, and dollar, and non-terminals are S and A. So these will be called as a actions, and this will be called as a go-to. And what are the states? 9 states. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I'll draw the table first, and then we'll fill the particular columns. So here we need to fill the parsing table based upon this LR1 items. These are all the LR1 items. So LR1. Now I not on capital S. So remember, if we are giving the terminals, we'll give a shift operation. We'll represent it as a S followed by the state number. And if we are moving on with the non-terminals, we are just giving the number. Okay. So I not on S, which is a non-terminal, moves to I1. So I write it as 1 here. And I not on A moves to I2. So it's a non-terminal. So I write only 2 here. I not on small a, it goes to I3. I write it IS3. B, I4, S4. So like this, we have to fill for all the states. Now I not completed. I1. So this is a starting symbol, and it is a last one, right? So 1 with a dollar is an accept. It's an accept. So while parsing the input string, when we get this 1 with a dollar, so that means it has been accepted. Now I2 on A is 5. I2 on A is 5. Sorry. I2 on small a it is 6. I2 on small a it is 6. I2 on B it is 7. It will be 7. And now I3 on capital A it goes to 8. I3 on capital A it goes to 8. I3 on small a it goes to S3. I3 upon B goes to S4. I4 is the end. Okay. So there is no, this is an end state, right? So if it is an end state, check with this particular production number. So A tends to B. What is the number of production? That is a 3. So that will be the R3, reduce 3. So where we have to put this R3? So look at symbol. Okay. So follow the look at symbol AB. So upon A and B, we have to give this reduce symbol. So I4 upon A and B. I4 upon A and B, it will be R3, reduce 3. In our previous parsers, we are supposed to write this R3 for the complete row. So that should not be happen here. So we have to fill this reduce operation only based upon the lookahead symbols. So here we are having A or B as a lookahead symbol. We have to place the production 3 in those 2 symbols. Now I4 completed. I5. I5 is also end state. So A, which one is a production 1? So reduce 1. Where we have to put, so first lookahead symbol dollar. So 5 on dollar, it is a R1. R1. And coming to I6. I6 upon capital A it is 9. I6 upon capital A it is 9. And I6 upon capital small a it is 6. I6 it is S6. B I7 7. And coming to I7, it's an end state. Again you can check A tends to B, which is the R3, where we have to place this one. Look at symbol dollar. 7 on dollar, we have to keep R3. 7 on dollar, it's an R3. Next, I8, this is also end. Which one? Second R2, where we have to place on the look at symbol AB. So 8 on A and B, we have to place R2. 8 on A and B, we have to place R2. And yes, I7 on A, I8 completed. Now I9 is also end. So what is the production number here? 2. Where we have to get 9 on dollar, it is R2. So here we have completed the parsing table for this particular CLR parser based upon the canonical list items, that means LR1 items. We are filling out or constructing the parsing table. So next we have to follow the next step, that is we have to parse the input string. Okay, we have to parse the input string. So I am erasing this particular diagram. Okay. we have to pass the input string right now. So how we have to pass? We have to consider so here I'll take it as a stack input and action we have to take. So the stack initially it will be a dollar and input A, B, B, dollar. Okay, A, B, B, dollar. So this is the thing we have taken as an input, and we have to place the dollar at the end of the string, so to represent that it is an end. Now, initially state 0. Initially the state 0. So you have to check with 0 and A. Compare 0 and A in the parsing table. 0 upon A it is 3. Shift yes 3. So what we have to do? We have to shift the input symbol into the stack and place the 3 on the stack at the top of the stack. So what we have to do? $0 A 3. And after removing A here, it will be A, B, B, dollar. Now again check 3 with A. 3 upon A from the parsing table. So 3 upon A, it is again S3. You can check. Again it is S3. So what we have to do? Again we have to shift the symbol towards the stack and place 3. So I will put here 0, A, 3, and after pushing here, the result will be only B, B, dollar. Now again check 3 with B. 3 upon B from the table. 3 upon B, S4. Again we have to shift S4. So again we have to shift one input symbol into the stack and place 4 here. So 0, A3, B4, and here it is the remaining string is B dollar, and now you have to check with 4B. So 4 upon B it is a R3. So now we have to reduce the elements in the stack. So reduce 3. So here 3 is a production. What is the production 3? A tends to B. Now you can replace this B with capital A. You have to replace this B with a capital A. So we are reducing here. So 0, A3, and reduce this B4 with A. Okay, B4 with A. Now see, A upon B, there is no matching here. So we have to map from a state number towards the terminal or non-terminal. But here how to get the state number? So B4 has been reduced to A. B4 has been reduced to A. Now check with the previous number. So 3 upon A. So 3 upon A it is 8. Place the number here. Okay, don't get confused. So after reducing 3 production, this B4, what's the third production? A tends to B. So B can be replaced with a capital A. So I am replacing this B4 with a capital A. Now here always we have to compare, or we have to check out with the parsing table from the state number with the terminal or non-terminal. But here we are not having any state number. So in such case, go with the previous state number and the top of the stack. So 3 upon A, which gives it as a 8. And it is a B dollar. So 8 upon B. 8 upon B. 8 upon B it is a R2. Again we can reduce. Reduce with a 2. So what is the second production? A. So you can check here. So I will write here. Here it is A tends to B, and here it is A tends to A, capital A. So A can be replaced with a capital A. A can be replaced with a capital A. So now we can check $0, A3, and this can be replaced with a capital A. Now again there is no number, state number. What we have to do? We have to go with the previous top of the stack and top of the stack. So 3 on A. Again 3 upon A is again 8. So we can write it 8. B dollar. So 8 upon B. 8 upon B. So what is the 8 upon B? 8 upon B it is a R2. Again we can reduce. Reduce to A tends to AA. A tends to AA. So what we have to do? We have to replace this one. So $0, and everything can be replaced with A, and that's it. So now there is no again number. So what we have to do? Go with the previous number. A upon 0. A upon 0 it is 2. A upon 0 it is a 2. Now B here. So we have to check with 2 on B. 2 on B it is a S7. So it is shift 7. So what we have to do? We have to shift it with the to the stack. 0, A, 2, shift the symbol, and 7. And it is $. Now you can check with a 7 upon $. 7 upon $, it is a R3. Reduce R3. What is the R3? A tends to B. So you can replace this B with A. So $0, A, 2, A. So there is no number. Again 2 upon A. 2 upon A. It is a $5. Now check with $5 and $. $5 and $. It's a R1. Reduce 1. So what's the first one? S tends to A. So A. So $. So this can be replaced with yes, and it is $. yes and dollar. Sorry, 0 yes and dollar. So 0 upon yes, 0 upon sorry, yes. 0 upon yes. What is the one? 1, and it is dollar now. So 1 upon dollar, 1 upon dollar, it is accept. So we can say that it has been accepted. The string has been accepted with the following grammar. So the input has been parsed successfully. Now the last step is we have to construct the parse tree, that to bottom up. So we can construct the parse tree from here. So yes will be expanded with A, and this A is expanded with a B, which is a terminal, and see, this A is expanded with A, and this is with again A, and this A is expanded with B. So you can check all the terminals of this tree. So A, B, B. So this is a parse tree from the bottom up, from the bottom to top. So in the same way, we have to calculate the CLR parser. Okay, so don't get confused. Only one thing, we have to find out the look ahead symbol, and based upon the look ahead symbol, we have to fill out the parsing table. So this is a parsing table. Okay, so the first step we have seen is finding the augmented grammar, and then the second step, finding the LR1 items. So LR1 items will be calculated with the help of LR0 items and the look ahead symbols, and the third one giving the numbering to the productions, and the fourth one filling out the parsing table, and the fifth one parsing the input string. So consider one input string, any one input string, and we have to parse that one. And the next is a construction of a parsing tree, parse tree. Okay, so with the help of this parsing of input string, so that to bottom to top. So that's why we call it as a bottom up parsing.
In our previous session, we have seen an example for CLR1 parser, so which is a category of bottom up parsing, and we have seen one example how can we construct the parse tree using the CLR1 parser. Now we'll go with the one more example, so where the parse tree can be constructed using the CLR1 parser. Okay, so some sort of complex productions, we'll take 5 productions and we'll take an example, right? See, as we discussed in our previous session, the CLR1 parser is a category of bottom up parsing technique, where C stands for the canonical list items, where we have to construct in our second step, and L stands for the input string will be parsed from left to right, and R stands for we are going to use a rightmost derivation while constructing the parse tree. And here the one inside the brackets indicates the look ahead symbols, right? So now we'll see the steps to construct the parse tree once again, and then we'll directly move on with the example. So coming to the step 1, we have to create the augmented grammar. So we have to insert a dot before the first terminal or non-terminal on the right hand side of every production, and then we have to create one more new production which points towards the starting symbol. So for that we are creating the augmented grammar. Like that we are creating the augmented grammar, and then the step 2, we are going to calculate the LR1 items. So these LR1 items are nothing but LR0 plus look ahead symbols. We know that LR0, how to find out the LR0. So for every step we have to move that dot towards the right hand side until it reaches to the end of the right hand side of the production. And the third step, we have to give a numbering of productions for the original productions. So other than the augmented grammar, we need to give some numbering starting from 1. So with the help of this LR1 items and the number of productions, we are going to construct a parsing table in the step 4. So once the parsing table has been constructed, then we have to parse some input string. We have to consider some input string, and we are going to parse that input string. We have to check whether that input string can be parsed for that given grammar. And if it is successful, then the last step is we have to construct the parse tree. That is up to bottom up approach, the bottom up parsing technique, right? So like this, we have to calculate, or we have to follow all these steps for construction of parse tree. Now we'll take an example. See, this is the example I have taken. So this is a grammar I have taken here. So S tends to L is equal to R, S tends to R, and L tends to star or L tends to ID, and R tends to L. And here I'm going to take the input string as, so we have to check whether this input string is passed or not. I'll take it as ID is equal to ID. And here, the terminals are, what are the terminals? Star is equal to and ID. Star is equal to and ID. And coming to the non-terminals, so S, L, and R. S, L, and R. Now we'll start. So the reason why I am using this screen recording means So our whiteboard is very small. So in order to calculate this LR1 items, so the board may not be sufficient. So I'm using the Excel. So definitely that will give you a better understanding of all the steps. Okay, right. So let me start this one within in an Excel. Yes. So first let me copy this original productions. So these are the original productions, and yes, I'll maximize with a 24 so that you can understand. Okay, so yes, yeah, this is a context free grammar. Okay, now what we have to do, we have to calculate the augmented grammar, right? So let's check it. So what we have to do, we have to take one more production, which is s dash tends to starting symbol, and the remaining is a common. So I'll leave one. Yes, so what better understanding, I'm doing all these things. So yes, this is the augmented grammar. Okay, now we have to calculate the canonical items starting with a, so we have to change that one. So we have to place the dot symbol for on the right hand side productions. So I'll go with the s dash tends to dot s. Okay, dot s, and similarly s tends to dot l is equal to r, and s tends to dot r, and l tends to dot star r, and l tends to dot id small, right, and r tends to dot l, right. Yes, now we have to find out the look ahead symbol. We have to find out the look ahead for everything. So as this is the starting symbol, the look ahead symbol is a dollar. Okay, dollar. Now we have to calculate the look ahead symbol for this second production, s tends to dot l is equal to r. So for that we have to find out the first of this one, first of this part, because for s we are finding out. So for this part we have to find out the look ahead first of this one. So obviously the first of this one will be first of dollar itself. So here the look ahead symbol will also be dollar. And coming to here, so this is also production, yes, so obviously it will be a dollar. And coming to the r, again you have to calculate after r, so that means only a dollar. So here also it will be, just wait, yes, yes. So for this L production we have to find out the productions first of this part, that means after L. Okay, so the first of this one is equal to n dollar, so obviously this will be is equal to or dollar, is equal to or dollar. And coming to here, this is also L production, obviously it will be is equal to or dollar. And coming to the R, you can see, so after dot here, so it will be the first of dollar, so the look ahead symbol will be dollar itself. Okay, so just remember we are finding out the S production. So in the above production, after dot S we have to find out the first of remaining things, and here we have to find the look ahead symbol for L production. So in the above productions, find out the first of after whatever the things we are having, either terminals or non-terminals, after the dot L. And coming to R also, we are going to find out the first of after the dot R, right? It's a dollar. So this will be the I naught. This will be the I naught, state I naught. Okay, so I'll use an yellow color. This is I naught. Now from I naught we have to expand everything until the dot reaches to the end of the right hand side production. That means we are parsing each and every production from starting itself to the end. So now we can go with yes, I naught with yes, first yes, I naught with yes. Okay, so for this we can write it as go to I naught with yes. Okay, so let us take this one. At the bottom we'll write the states. At the bottom we'll write the states. Yes, so yes, so this is a I naught, state I naught. Okay, in order to avoid the confusion, I am just giving all these borders and everything. Okay, see, so this is the augmented, right? Now go to I naught with yes. What happens? S dash tends to s dot, sorry, s dot, comma, look at symbol dollar. So you can check whether there is any other items with s dash, okay, with yes on the right hand side. Okay, you can check for s on the right hand side on every production. So there is no production with dot yes, so this ends. So this will be I1, the state I1. Okay, state I1, and this will be go to, and this will be state. So yellow represents the states. Okay, yellow represents the states. Now the second one, next, go to I naught with L. So you can check with these productions. The next one is dot L. Now we can move this one. S tends to L dot is equal to R, and the lookahead symbol is dollar. Okay, and also you can check whether there is any other production with L. Yes, we are having. That is the last one. So give here R tends to L dot comma dollar. Okay, so we have to check whether any production is having a L on its right hand side, immediate to the dot, immediate to the dot. That's important. So we are having these two things. Okay, now any other productions with a L after dot other than S tends to dot L is equal to R and R tends to dot L? No. So we can stop here, and it will be the I2 because no other, I mean, it's a new state. It's a new state. Okay, and this will be the green color. Go to. And next one, go to I naught on R. You can check. So here I naught with yes, I naught with L, I naught with R, I naught with star, and I naught with ID. Okay, we have to check all those things. And I naught with R, check whether any production is having R on the right hand side immediately after the dot. So we are having only one. So go with S tends to R dot, comma, look at symbol dollar. So any other production with the R on right hand side after immediate dot? No. So this will be I3, state 3, because this is a new state. Okay, we have to check whether this production is already parsed or not. So far that was not parsed. This is a new thing. So this will be the new state. This will be the new state, and the states are represented with the yellow color. Okay, so go to I naught yes, I naught L, I naught R, and then the next one, go to I naught with star, terminal, terminals. So coming to the terminals, oh, sorry. So coming to the terminals, you can check I naught with star. There is only one production where the star is on the right hand side, that too immediate after dot. So expand this one. Star L tends to star dot R, comma, is equal to or dollar as a look ahead. L tends to star dot R. So here you can see now the dot immediately after dot R dot there is a non-terminal. If there is a non-terminal, immediately we have to write all those productions here. So dot R, we need to write that productions here. R tends to dot L. So we need to go with R tends to dot L, comma, and give the same look ahead. Okay, is equal to or dollar. So you did not focus on this particular look ahead. You just focus on this particular look ahead. Okay, because so if you are writing the R, you have to check the look ahead symbol. I mean, you have to find out the first of this one. So we'll get a is equal to and dollar. Okay, so any other yes, again this production is having dot L, so we need to write all the productions of L. So from this grammar, what are the productions? L tends to dot star or, comma, is equal to or dollar. And again one more production for L tends to dot ID, comma, is equal to or dollar. So we are having a 4 productions here. So is there any other we can expand? So no, here there is a dot after star. So it is a terminal. We need not expand here. Dot ID. ID is also a terminal. We can't we need not expand. If there is a non-terminal after dot, we have to write all those productions of that non-terminal. So in all these states, now up to now we have calculated some 4 states: I0, I1, I2, I3. Among these, is this matches with any one of the state? No. So that's why it will be a new state, I4. We can consider it as a I4. So I'll give yellow color. The states will be represented in an yellow color, and this go-to represents with a green color. Yes. Now there is a one more thing, that is a I0 to ID. Star is completed. Now we have to write go to I0 to ID. Okay, just remember after dot, whatever the thing, either terminals or non-terminals, we have to expand. So here S, L, R, star, ID, and L already we have given, so that one. So that's why we are expanding. So go to S, I naught to L, I naught to R, I naught to star, and now I naught to ID. So if it is I naught to ID, just move here. L tends to ID dot, and the lookahead symbol is equal to or dollar. So you can check whether this particular production has been generated in any one of the state. No. So obviously this will be the new state, that is a I5. That's a new state, it will be I5. So I'll place yellow color, and for this I'll place the green color. Now we have parsed the I naught. We have parsed the I naught. Okay. Now we have to go with the another state. Okay, another level. So for simplification, I'll move this one to here, and this one to here, so that it will be easy for visibility. Okay, so for that purpose, I am just moving on the row side instead of column wise instead of row wise. So I'll move here. The first one is all the I naught. First one is all referred to I naught. Yes. So I'll give all the borders. So just for presentation, I'm doing all these things in order to avoid the confusion. So you'll be getting some sort of clarity. Okay, and I'm leaving one column. Yes. So coming to the next one. So that means we have to expand each and every stage. So coming to I1. So coming to I1, now we have to expand I1. So I1 cannot be expanded. I1 can't be expanded. So because so already dot has been sent to the end of the production. See, if you observe, the production is S dash tends to S. So the dot has been moved to end of this production. So we can't expand this one further. So that will be the final state. Okay. And coming to the second one, I naught, that means second state. So here the second production R tends to L dot. So this is also end production. So we can't expand this production. So we need to expand the first one, that is S tends to L dot is equal to R dollar. So in this step, we have to move dot towards the right hand side until it reaches to the end. So now you can go to I2 comma is equal to. Go to I2 comma is equal to. Now what happens? S tends to L is equal to dot R. So dot has been moved to right hand side with a look ahead dollar. And now you can observe after dot we are having a non-terminal. If it is a terminal, we can leave it. If it is a non-terminal, we have to write all the productions of that particular non-terminal. What are the non-terminal productions? R tends to dot L comma dollar. Again you can observe, again we are having a non-terminal. So with dot now after dot. So we have to write down all the L productions. L tends to dot star R comma, it's a dollar. And similarly one more production is there for L. L tends to dot ID comma dollar. Okay. So is there any expansion is required? No. So in both the productions after dot we are having only terminals. So we need not expand this one. And check whether this has been created in any one of the state here. Any one of the state. So no. So here you are having another. So there is no other state. We have defined this one. So this will be the new state, that is I6. I6. So this will be, I'll giving the green color, and this will be yellow color. Next, what we have to do again? Yes. So from I2 we are expanding this one, right? From I2, is there any expansions? No expansions. From I2 we are not taking any expansions. Coming to the I3. So I3, is there any expansion for I3? No, because dot has been reached to the end of the right hand side production. So we need not expand this I3. Coming to the I4, yes. So for the first production we can expand, because after star we are having dot, and after dot we are having R. So now the dot is not at the end of the right hand side production. So dot can be moved. So here we can write go to I4 comma R, capital R. So what happens? L tends to star R dot comma is equal to or dollar, is equal to or dollar, right? So yes, then is there any other productions we can expand here? No. So we can leave it, and this will be I7 because it was not created anywhere so far. So it will be I7. Okay, now I7. Again, I4 on L. We have to present I4 on L. So go to I4 on L. So we are expanding the state 4, right? So we are expanding the state 4. First production we have expanded, and now we are going with the I4 on L. So R tends to L dot, and look ahead is equal to or dollar. And here again you can see the dot has been reached to the end of the production, so we can't expand anymore. So check whether it has been created anywhere else. So S dot L dot, R tends to L dot, but you can observe the look ahead symbol is different. Here is equal to or dollar, and here is dollar. So it will be the new state I8. I8. Okay, so this will be this color, and I'll give it as a yellow color. Right now, again there is a third production which tends to star. So go to I4 on star. I4 on star. If it is I4 on star, expand this one. L tends to star dot R, and look ahead symbol is equal to or dollar. Okay, now you can observe after dot we are having a non-terminal. So what we have to do? So we have to write all the non-terminal productions. So R tends to dot L comma is equal to or dollar. So we have to repeat the same look ahead symbol. And again we are having a non-terminal after dot. So we have to write down all the dot productions. Okay, so dot L tends to dot star R comma is equal to or dollar. And again L is having one more production. L tends to dot ID comma is equal to or dollar. Okay, now you can observe, check whether it has been created anywhere else or not. So now you can check, see L is equal, L tends to star dot R. No, 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 yes. Star dot R is equal to or dollar. R tends to dot L is equal to dollar. L tends to dot star R is equal to dollar. L tends to dot ID is equal to dollar. So the same thing has been repeated here. So you need not go with the new state. So it will be the same state. So the same I4. Okay. So give the number I4 here. So I'll give here a color green for representing the go-to, and I4. It's not a new state. So I'll go with the one more state which is somewhat different. Okay. So same state. So some red color. This is a not new state. Now we have done with the go to I4 with a star. Now we have to go with the I4 with the ID. I4 with the ID. So let us check. Go to I4 with ID. So what we have to do? I4 with ID. So L tends to ID dot is equal to or dollar. So after here dot comes to the end of the production. So what we have to do? So we have to check whether it has been generated anywhere else or not. So check out with this one. L tends to ID dot. L tends to ID dot. Yes, here L tends to ID dot. But look, check with the look ahead whether both are equal or not. Here is equal to a dollar, is equal to dollar. Yes. So both are same. So what we have to do, if both are same, we need not go with the new state. It will be I5 because it is a I5. So it was generated at I5. So just write down the I5 here also. So I give here a red mark because it was not generated new. It was not a new state. It was a already generated state. So up to here we have completed this I4. Now we expand I5. Expand I5. So I5, whether we have to expand I5, so no, because I5 is the end state because the dot is at end of the production. End of the production. Now what we have to do? So we have to expand I6. So check whether we can expand or not. Yes, we have to expand because here we are having after dot R L star I. So repeat the same process here. So go to I6. So I'll write here I6. Yes. Go to I6 on R. I6 on R. Sorry. I6 on R. Now what are the productions now? You see, this is the I6. S tends to L is equal to R dot comma dollar. Whether it can be expanded further? No, because here the dot comes at the end of the production. Excuse me. So let us check whether there are any other productions with R. No. So just we can stop. And now we have to check whether it has been constructed anywhere else. L is equal to R dot. L is equal to R dot. So no. So it will be a new state which is I8 after I9. It is I9. And this will be of yellow color because the state's number, and this will be of green color. Now next there is a one more thing here, dot L. For L also it is there, so go to I6 comma L, I6 comma L. So here also R tends to L dot, R tends to L dot with a lookout symbol dollar. Okay, and this is also end state because the dot came to the end of the production. So now check whether there is this production has been done or not. Yes, so here it is. But along with this there is a one more production, so we need not write it here as I2, because if you write it as I2, state 2 is having two productions, but here we are having only one production. So we need to check with any other else. See, here we are having R tends to L dot, R tends to L dot, yes, but the lookahead symbol is different. Lookahead symbol is different. So this will be the new state. So here also there is no. So this will be the new state, which is I10, which is a I10, right? So hope you are understanding. And next, star is there. So go to I6 on star. I6 on star. So just go with the move the symbol. L tends to star dot R comma dollar. And after dot we are having the R non-terminal. Write down the productions of all the non-terminal R. So R tends to, here we are having this one state 0 dot L comma, it's a dollar. And again, sorry, here it is dot. Again, after dot we are having a non-terminal, right? So write down the productions of all that L. L tends to, so dot star R comma dollar. And again L tends to ID comma dollar. Okay, so sorry, dot ID, it is a dot ID, right? Now check whether it has been already created or not. So you can check, yes, here it is star dot R star L star dot star R dot ID. So both are equal, but lookahead symbol is different. You can check lookahead symbol is different. And also you can check here, this is also same, but lookahead symbol is different. And yes, there is nothing. So we have to create a one more state, which is I11. This is I11. After I10 it is I11. So I'll give it as yellow color the state number, and this will be the green color code. And then whether I6 has been completed? No, there is one more production with ID. So go to I6 with ID. So what happens? L tends to ID comma dollar, ID 10 dollar. Now check whether so because this is an end state, because dot has been reached to the end of the right hand side production. Now check whether it has been generated or not. ID dot, L tends to ID dot, here it is, but the lookahead symbol is different. And one more here also it is, but lookahead symbol is different. Is there any other? No, there is nothing. So this will be the new state, I12. So we have to repeat everything until all the productions, all the states has been expanded. Okay, so completed. I6 is completed now. So move on with I7. I7 is having only one production, that's also end state. I8, it's also end state. I9, it's also end state. I10, end state. Now I11, we are having a lot of productions. We have to expand I11 also. So I11 can be expanded, I11 with the R, I11 with the L, I11 with the star, I11 with the ID. Now start expanding, go to I11 with R. What is the production here we have to use? So L tends to star R dot and dollar. L tends to R star R dot dollar. So here dot comes at the end of the production. So we have to stop here. Now check whether it has been created earlier or not. Whether it has been created earlier or not. Okay, so check out here. Anything? Yes. So here L tends to star R dot, L tends to star dot R, but here it is lookahead is different. Okay, lookahead is different. So we should not move on with that. So it will be the new state, which is a I. After 12 it is a 13. After 12 it will be the 13. So that is a state. So I'll give the color yellow, and here for this go to, I'll give the color as a green. And now I11, we are expanding I11, so this is I11. Now it will be R. Go to I11 with R. L, sorry, R has been completed. Now L. Now you can check LR tends to L dot comma locate symbol dollar. Locate symbol dollar. So here also you can check it has, the dot has been came to the end of the production, so it can't be further expanded. Now we have to check whether it has been expanded or not, I mean already created or not. So here it is there, but along with this one more production is here, so we can't give this state as I2, and we'll check somewhere else. It has been R tends to L dot, R tends to L dot, but look at symbol is different, and here it is R tends to L dot dollar, R tends to L dot dollar. Yes, so it will be I10. We should not give it as a new state. We should not give it as a new state. So it will be I10. And now check whether it was completed. I11. No. Go to I11 to star. One more. Go to I11 to star. So again, I11 to star means L tends to. So what happens here? Star dot R, comma dollar. Now you can check after dot we are having a non-terminal, so we have to write all the productions of that non-terminal. R tends to dot L, and with a lookup symbol dollar. Again we are having a non-terminal after dot, we have to write down all the productions of L. So L tends to dot star, sorry, dot star R, comma lookup symbol dollar. And again we are having one more L, which is a dot ID with the lookup symbol, the same a dollar. Okay, so it has been completed. Now we have to check whether it has been created earlier or not. So you can check here itself, it is star dot R dollar dot L dollar. So it is I11 itself. Okay, so that's a self loop, right? So just give here I11. Give here I11. So I'm changing the colors. So I'll give some yellow color. So it will be a colorful document, right? Yeah. Now check whether it has been completed. I11 with R, I11 with L, I11 with a star, and once again I11 with ID. There is one more thing. Go to I11 with the ID. I11 with ID. So what we have to do? Again we have to check out L tends to ID dot, comma, it's a dollar. Okay. So what happened? Here also same. L tends to ID dot dollar. So it's also I12. So it was not a new state. So we have to give some red color because it was repeated. So this is also red color. It also repeated, and here it is green, right? So I11 completed. Now go with the I12. It's an end state. It can't be expanded. Go to the I13. It's also end state. It can't be expanded. So after the last state is the I13 itself, right? Now we can stop finding out this canonical list item. So these are all called as a LR1 items. LR1 items means LR0 along with the look ahead. So for every production we are giving the look aheads, right? So this is our second step. So first we have calculated all the augmented grammar for the given grammar, and then we are finding out the complete canonical items. So all these comes with the canonical items, list 1 items. Okay, now what we have to do, we have to construct the parsing table, or we have to give the numbering for the grammar, the own grammar, right? So numbering for the grammar, I'll give here numbering the productions. So these are the productions we had. So I'll give the numbering for these productions. The production number, I'll merge this one. Yes, wrap text. Yes. Yes. So this will be 1, 2, 3, 4, and 5. This is the numbering we have given. Numbering of productions. Okay. So I'll give some other color for this numbering of productions, and see for this also I'll give the same color because these are the different steps. And the next one, we have to calculate the parsing table with the help of these canonical list items and the numbering of productions. We have to calculate the parsing table. So coming to the parsing table, so first we have to write down all the terminals and the non-terminals. Okay, here I'll write all the terminals and non-terminals. So what are the terminals now? It is ID star and then is equal to, and also we have to go with the dollar, and then the non-terminals S, L, and R. So these four comes under action, and these three comes under go to. So here we need to mention the state where we have to go. Sorry, go to. And this completely we call it as a parsing table. Parsing table. Right? So here we need to give the states 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So total 13 states we have calculated. Total 13 states we have calculated. So this is the parsing table. I'll give here and this one. Yes, state. So this is the blue color, and these are the states. So I'll go with some other color. We'll give some other color, and states with yellow, because already we have generated some yellow color. So I'll go with this yellow color. Right now, so we have to fill this parsing table. Okay. Now here, remember, 0 means I naught, state number. 0 on ID, 0 on star, 0 on is equal to, 0 on dollar. If it is an action, we have to mention it with a shift. That means yes with state number. And if it is a terminals, we have to represent only the state number. Now, coming here. Yeah. So I naught on ID, I naught on yes. So let us take from here. I naught on yes. I naught on yes, it goes to I1. Yes is a terminal, sorry, non-terminal. So here we have to write it as a 1. Okay. Then next, I naught on L. I naught on L. So here I naught on L, it moves to I2. So here it is a non-terminal, we have to give only number 2. I naught on 3 R. I naught on R, it is a I3. So here we will do only 3. Just a second. So yes, I'll give a format painter because I'll apply for this particular table. Okay. Now I naught on star, it is I4. I naught on star, it is I4. So here we have to write it as S4 because it is a terminal. I naught on ID, it is 5. So I'll go with the S5. And I naught, yes, that ends. I naught on, yes, I naught with all we have created. Okay. Now go with the I1. I1 on, where is that? I1 on. So I1 with, there is no expansion for I1, right? So I1 itself is the end state, and this is a start symbol. So on dollar, you can see the dollar, look at symbol dollar. So 1 on dollar, it will be the accept. It will be the accept stage. Okay, so that will be the accept stage. I'll go with one more color. This is the accept stage. Now coming to the next, I2. What's a I2? Go with the I2. Yes, I2 is expanded. I2 is equal to, I2 on is equal to, I2 on is equal to, it goes to I6. Is equal to is nothing but a terminal. So I2 on is equal to, it is S6. Okay, I2 on is equal to is S6. And also you can check I2. Okay, it is having the end state here. See, L tends to L dot. Sorry, R tends to L dot. That means a end state. So now what we have to do is check the number of for this particular production. So S tends to, I mean R tends to L. R tends to L is a 5. So what is a look at symbol dollar? For particular dollar, I2 on dollar, go with the R5. R5, reduce. Okay, if it is an end state, we have to give it as a reduce and state number. Hope you understood. I2 is having the end symbol. Okay, I2 is having the end symbol. And further expansion. One is I2 on is equal to 6, we are giving S6, and also end symbol. So if it is an end symbol, look ahead symbol, go with the look ahead symbol. So we have to fill the column of I2 on dollar and give the production. Whatever the number given to this production, reduce with that particular production number. So R tends to L is a 5, production number 5. So it will be R5. Right? Now, good. So state 3. So state 3 is again, it is a end state, because here in this production you can observe dot is at the end of the right hand side of the production. So what we have to do? So we have to reduce. So check with the look ahead symbol, which is a dollar. We have to fill a 3 with a dollar here, 3 on dollar, and go to the production number. What's the production number? S tends to R. It is a 2. So here we have to fill with the R2. Okay. Next, go with the I4. I4. So coming to the I4, there are a lot of productions, and we have expanded that. So check out with that. I4 with a capital R, it goes to I7. So as we have discussed it just now, so if it is a non-terminal, we have to state only the state number. I4 on R, it will be 7, and I4 on L it is 8. I4 on L it is 8, and I4 on star it goes to 4 itself, and it is a terminal, so we have to write I4 on star it is S4, and again I4 on ID it is 5. I4 on ID it is S5. Now go with the fifth state, and it is an again end state. That means that the production has been ended because the dot is at the end of the right hand side production. So this can't be expanded. So now what we have to do, we have to check with the lookout symbol. So lookout symbols are is equal to n dollar. So we have to fill these two columns is equal to n dollar. What we have to fill? So just find out the production number here. L tends to ID. It's a 4, and we have to fill here with R4. R4. Right now, go with the 6. I6. So where is the I6? Yes, here it is the I6, and I6 is also having a lot of production. So we have expanded I6. So this is the I6 expansions. So I6 on capital R it is 9. I6 on capital R it is a 9, and I6 on capital L it is 10. So these are all non-terminals. We have to write only the production number. Okay, state number. And I6 on star it is I11. I6 on star it is I11. So it's a terminal. We have to give S11. I6 on ID it is 12. It is S12, S11 and S12. And coming to the seventh seventh state. So where is the 7? Yes, here it is a 7. So coming to the 7, again it is a last end state because dot is at the end of the right hand side production. Now check with the lookout symbol is equal to dollar. So we have to fill 7 on is equal to $. 7 on is equal to $. So what we have to fill? We have to find out the number of the production number. L tends to star R. It's a 3. So we have to fill R3 amount is equal to $. R3. And coming to the 8. So where is the 8? And 8 is also end because dot is at the end of the right hand side production. So check with the is equal to $. So we have to fill these two things on I8 state. So what check with the production number R tends to L. R tends to L is 5. So it will be R5 and R5. Right. Next 9. 9 is also end because dot is at the end of the production, right hand side of the production. So we have to check the lookout symbol and we have to fill out the $. 9 on $, because $, is the lookout symbol. And check out the production number L is equal to R, which is 1, and it is R1. It's a R1. And coming to the 10, this is also end. So because L dot, that means dot at the end of the right hand side production. Check with the lookout symbol, it is a $. So you have to fill 10 on $. Check out the production number at R tends to L, it's a 5 R5. You have to fill with the R5. Next coming to the 11. So 11 is having a more than one production, so we have expanded this one. So these are all the expansions. L1, I11 on R, capital R, it is 13. I11 on capital R, it is 13. We have to give only the production, the state number. And then I11 on L it is 10. I11 on L it is 10. So here we have to give 10. And I11 on star, this is a terminal. So we have to give S11. So self. So star it is S11. And on ID it is 12. So it is S12. And coming to the 12, it is again the last one, the end state, because dot is at the end of the right hand side of the production. So we have to check out the lookout symbol. Lookout symbol is $. So we have to fill 12 on $. So what we have to fill? We have to check out with the production number of L tends to ID, it is 4, it is R4. And coming to the 13, again the 13 is also end state because dot is at the end of the right hand side production. So we have to check with the lookout symbol $. So we have to fill this 13 on $. So find out the production number L tends to star R, which is 3, it is R3. So in this way we have to fill the parsing table. So now the parsing table has been completed. Now what we have to do? So the next step is we have to find out we have to construct the we have to parse the input string. We have to parse the input string. How we can parse? The first one we have to take it as stack and the input string, and finally the actions to be taken. Okay, so I'll expand this one. I'll expand the input string and the actions. So for that it requires only the parsing table. We can go with this parsing table. So here I'll match and I'll write input string. So parsing of input string. Parsing of input string. So which is ID is equal to ID. Okay, now yes. So I'll match this one. And initially the stack is initially the stack will be filled with $, and the input string ID, and I'll write equal to ID. So instead of symbol I'm writing equal to. Okay, don't confuse. And at the end of the string we have to include a $. Okay, and actions. So coming to this one, initially the top of the stack start with the 0. Now check out 0 upon ID. So 0 is a state number and ID is the input string. So from the parsing table, check out the 0 upon id. So whether it is having the actions or it is having some reduce. So 0 upon id, it is s5. So the action here is shift s5. So we have to shift the symbol from input string to stack and write down the state number 5. So the stack now will be $0 id and 5. So we have shifted id to the stack, and here it is s5. I am writing the symbol 5 because there is a I mean we are having this shift and reduce operations based upon the states and terminal and non-terminal. So we have shifted id and giving the state number, and the remaining stack is input string is equal to id and $. Now it is 5 with equal to. So 5 with equal to, it's a R4, that means reduce. So what we have to do, reduce with production 4. What's the production 4? What's the production 4? L tends to id. L tends to id. So with this production we have to change. With this production we have to change it. So what it will be changed? $0 id can be replaced with L. But now you can see the top of the stack is a non-terminal, and we can't able to access the non-terminal with a terminal in the parsing table. So compulsory we have to map the state with a terminal or non-terminal. That should be a state number. So here, if in this case, what we have to do, so go with the previous top of the stack and fill with the appropriate state number. So 0 upon L. So 0 upon L, it is 2. Now it will be 2. What's the remaining stack? So equal to id $. And now compare 2 with equal to. 2 upon equal to. Shift 6. Shift with 6. So what we have to do? So $0 L 2 and shift equal and 6. And what is the remaining here? id and $. Now 6 upon id. 6 upon id is S12. Again shift S12. So what we have to do? So again $0 L 2 equal to 6 and again shift id 12. And what's the remaining? $. Itself. So now compare with the 12 with the $. 12 with a $. It's a R4. 12 with the $. is R4. So reduce with a production 4. So what is here? $0 L 2 equal to 6 and L. Okay, L. And here there is no number. What we have to do? So we have to go with the previous top. That means that 6 upon L. 6 upon L. It is 10. So give the number. It is at 10. Now the remaining input string is $. And now check with the 10 with the $. So 10 upon $, it is a R5. So reduce with production 5. What's a 5th production? R tends to L. So L can be replaced with the R. So $0 L 2 equal to 6 and R. So L10 is replaced with the R. L is replaced with the R. Now again we are not having the top of the stack as a state number. So what we have to do, move on with the previous top of the stack. 6 upon R. 6 upon R, it is a 9. 6 upon R, it is a 9. And again it is a $. Now what is a 9 upon $? 9 with a $. R1. So reduce with production 1. So what is the production 1? S tends to L is equal to R. L is equal to R. So you can replace this $0 and this L2 equal to 6 R N 9. So that completely replaced with yes. And here it is a $, and now yes. So there is no number, state number. So move on with the previous top 0 upon yes. It is 1. So I take it as 1, and the remaining input string is $. Now check 1 upon $. So 1 upon $, is an accept. So it has been accepted. So that means the given input string id is equal to id has been parsed successfully by using these productions, using CLR parsers. See, all are dependent. So this parsing table comes with help of this numbering of productions as well as these LR1 items, right? And with the help of parsing table, we are parsing the input string. Okay, yes. So the last step is only left over. What's the last step? If the input is successfully parsed, then the last step is generation of a parse tree. So we have to generate the parse tree using a bottom up. So for that, we'll see. So this is the input string we have parsed just right now, and coming to the parse string. let us construct the parse tree here. So so as it is a bottom up, okay, this is a bottom up and parse tree. So what we have to do, so we have to start from bottom. What's the bottom? It is S. So from S it was divided as L equal to R. So equal to means this one. So this is a terminal, it can't be expanded. Now L can be expanded, so R can be expanded to L. So R is again expanded to L, and now L is expanded to ID. So L is expanded to ID. So this is a terminal, it can't be expanded. And again, this L is expanded to ID. So this L is expanded to ID. This is also a terminal which can't be expanded. Now you can check in this parse tree, all the leaf nodes are terminals. So you can write all the leaf nodes from this left to right. So we can go with the ID equal to ID, which is our input string. So this is the bottom up parsing technique. So we have parsed the input, and then based upon the bottom up, we are constructing this parse tree. So this is a parse tree. Okay, so what we have done, so just recall the steps once again. So first we have created the augmented grammar by taking a additional production which points towards the starting symbol, and the second we are calculating the LR1 items, which is with the help of LR0 plus look ahead symbol, and the next one is the numbering the productions, and then construction of parsing table with the help of these LR1 canonical items and the production numbers, and then we are parsing the input string. We are considering one input string, and we are trying to parsing the input string with the help of parsing table. And finally, we are constructing the parsing tree once the input string has been parsed successfully. So this is what we have done here. So we have taken this example. So we have taken this input string, and finally we have constructed the parse tree for the given input string. LALR Parser. So in our previous session, we have seen a different categories of parsers, that is LR0 parser, SLR parser, CLR parser. So all these parsers will be comes under the bottom-up parsing technique, and similarly this LALR parser will also comes under the bottom-up parsing technique. And the working of LALR parser is almost similar to CLR parser. So the steps we followed in the CLR parser will be equal to the LALR parser. LALR means look ahead LR parser. So what's the difference among the CLR and LALR? So only one difference, that is we can reduce the parsing table in LALR when compared to the CLR. Right? So let me write down the steps. The first step, step 1, which is a creation of augmented grammar. And step 2, after creation of augmented grammar, we have to find out the LR1 parser, canonical items. So LR1 items, so which is equal to LR of 0 plus look ahead. So this is nothing but LR1 items. And the step 3, we need to numbering the productions. Whatever the productions we have taken, we have to numbering the productions. Numbering of productions. And then step 4, creation of a parsing table. Okay, so creation of parsing table. So in order to create this parsing table, that will be done with the help of step 2 and step 3. That implies the LR1 items as well as the number of productions. And coming to the step 5, after creation of parsing table, right? So in this creation of parsing table, we have to identify the items or the productions or the states which are having the same productions with a different look ahead symbols. So we have to reduce this parsing table with that one, right? So after that, input should be parsed. And once the input has been successfully parsed, then the 6th step is the construction of parse tree. The two bottom up. And in this, we have to combine states with same productions with different look ahead symbols. So this is the only difference among CLR parser and the LALR parser. And with the help of this one, we have to create this parsing table. So these are the steps we need to follow. And now we'll take an example, like here I'll take the productions. S tends to A tends to small a, capital A, and capital A tends to small b.
So I am erasing this one, and let us construct this parse tree for the same example which we have taken for the CLR parser. Okay, so the first step is a augmented. So s dash tends to dot a sorry s dash tends to dot s, and if it is dot s, we need to write down the productions of s also. So s tends to dot a sorry, and a tends to dot small a capital A, and a tends to small b. So this is the augmented grammar. Augmented grammar. Now what we have to do, we have to calculate the LR1 items, that means the LR0 along with the look ahead symbols. Now I'll draw here. So I'll take the first state dot s tends to dot a tends to small a capital A, and a tends to small b. So here initial state, the look ahead symbol will be dollar. Okay, for s tends to dot a, so this is the look ahead for s. So what happens here, s tends to dot s comma dollar, and now we have to find out the look ahead symbol for this dot a, right? Yes, production. For this after dot s, we need to find out the first in order to find the look ahead symbol. So what's the first of this one? Dollar. So this will be dollar. Now we have to find out the look ahead symbol for production a, which is small a capital A. So after dot capital A, and we have to find out the first of this one. So we need to find the first of these items. So a means small a capital B. Sorry, small a and small b. So you can write it as small a small b. So it is small a and small b. And there is a one more production for a. So simply you can write here also small a small b. So these are the productions with look ahead. So without these look aheads, that will be the LR of 0. Now the production along with the look ahead, we call it as a LR of 1. So this will be the initial state I0. So we need to expand each and every state such that for every production, the dot should be at the end of the production. For example, if you see here dot s, so this can be expanded. So next step, dot will be moved towards the right side, and we have to repeat the same process until the dot reaches to the end of the right hand side of the production. So here I write upon capital S. So after dot we are having S. So our capital S. So it will be s dash tends to s dot comma dollar. So check out whether any production is having s immediately after the dot. So no other production except the first production there is a dot s. So this will be the only one production in this particular state. Now the next one upon capital A. So what happens here? S tends to a dot a dollar. What is here? After dot we are having a non-terminal. If we are having a non-terminal after dot, we have to write down the productions of that particular non-terminal. So here after dot we are having capital A. So we have to write down the productions of capital A. So capital A is equal to a, and the look ahead symbol will be dollar. And similarly, a tends to dot a, and here also dot, and dot b dollar. So this will be our another state. So for every time we have to check whether these productions have been already generated or not. If not, that will be considered as a new state. If yes, the same state number will be given here. Now the next one upon small a. What happens? A tends to a dot a or b. So again after dot we are having a non-terminal. So what happens here? So again we have to write down the productions for capital A because it's a non-terminal. So capital A tends to, what happens? Dot a or b, and capital A tends to dot b and a or b. So this is the another state. So check whether it has been done with the any other production, any other state generated, right? So no, this was a new state. And upon b, we can say a tends to b dot comma a or b. See, and further we can't expand anything, right? So you can see in the productions after dot s is there, after dot a is there, after dot small a is there, and after dot small b is there. Now give the numbers. So this will be I1, I2, I3, and finally I4. Now whether I1 can be expanded or not? No, because in this production you can observe dot has been reached to the end of the production. So what about the second state? Yes. So from the second state there can be up to a, small b. After dot we are having a 3 terminal and non-terminal values. So capital A, small b. So we will be expanding this one with a capital A, which gives the production s tends to a dot comma dollar. So dot reaches to end of the production. So we need not go with any other production here. And coming to here with a small a, it will be a tends to a dot a comma dollar. And here you can observe after dot we are having a non-terminal, so we have to write down the productions of a non-terminal. So a tends to dot a with a dollar and a tends to dot b with a dollar. Okay, now this is another one. So I'm not giving any state number because we have to check whether the productions have already been generated or not. And next, upon B, there is a one more production, that is A tends to B dot comma dollar. This is a one more production. This is a one more production. Now you can check whether these productions has been generated. A dash, A dot. So there is nothing. So it will be a new state. We can state it as a I5. And A is equal to A dot AA dot B. Yes. See, I3 is similar to this one, but there is a difference upon the look ahead. Here the look ahead is A or B, here the look ahead is dollar. So what we have to do, so give a state, another state, and see A tends to B dot, and see here it is, look ahead is A by B, A or B, and here it is a dollar. So this is also a different, so give it is a I7. Now we have to expand this one. So upon A, what will be there? A tends to A dot, comma, A or B. So here also the dot reaches to the end of the state. And then the next one, upon small a dot, sorry, A tends to A dot A or B, and see A dot, after dot we are having a non-terminal. Again we have to write down all the productions of non-terminal A. So I'm writing all these things. A tends to dot B, which is again A or B. So this is a one more state. And upon B, it is A tends to B dot, comma, A or B. B dot, A or B. Now you can check whether this production has been generated or not. A tends to A dot. So you can check anywhere, no. So this will be I8. And you can check here, A naught dot A. Yes, A by B, dot A by B, dot B, A by B. Yes. So this is similar to our state I4. So you need not go with this one. It's not a new state, so it will go with the I4. So I3 upon A goes to I4. Then what about this one? A tends to B not A by B. This is also similar, which is similar to our, see, upon B it will be I4. Sorry, it is I3. It is I3 and it will be I4. Right? Now, what we have to do? Next, move on with another one. So we are not giving the new state numbers. Now what we have to do? Go with the I6. So whether I5 can be expanded? No. I4 can be expanded? No. I6? Yes, it can be expanded. So upon capital A, the productions will be A tends to A dot, comma, dollar. This is one production. And upon small a, it will be A tends to A dot A, comma, dollar. And A tends to dot A, capital A, dollar. And A tends to dot B, dollar. So this is a one more. And upon B, it will be A tends to B dot, dollar. So upon B. Now check whether it has been generated. A dot. So but the look ahead symbols are different. So we can give the new state. It is I9. And what about this one? A dot A dollar, dot B dollar. So I6 itself. So we need not draw this one. So simply we can give it as a I6. That means I6 upon A will still go with the I6 only. And now coming to this one, A tends to B dot dollar. Yeah, it is B dot dollar. So obviously it will be the I7. It will be the I7. Okay. So now check whether I7 can be expanded. No. I8, no. And I9, no. So everything has been done. None of the state can be expanded now. Now let us stop here. So these are all the LR1 items. LR1 items with a look ahead, right? So what we have to do, the next one is give the numbering for the productions. So let us give this as a 1, a 2, and a 3. So I have given the production numbering. Now what we have to do, we have to create the parsing table. So before creating the parsing table, identify the states which are equal in the productions but different in the look ahead. So I'll write here, identify states with same productions but different look ahead. So let us check. I1, that's a unit. I2, and is there any other states? No. I3, and you can see I3 and I6. Both are productions equal, but look at symbols are different. So I3 and I6. Any other? I4, A tends to B dot. Here A tends to B dot. Here A by B, here dollar. So I4 and I7. What about the next? I5. Is there any other? No. I7. Already we have done. I8. A dollar. See again here A dot, here dollar, here. So I8 and I9. Any other symbols? No. So because I9 is the last step. So this can be combinedly known as I36, and this can be combinedly known as I47, and this can be combinedly known as I89. So almost we are reducing the 3 different states. We are combining 3 different states. So with the help of this one, we have to create the parsing table. Now write on the parsing tables here. Sorry, right here. Same productions. Okay, same productions, but different look ahead. Now what we have to do? We have to write on the parsing table, construct the parsing table. So how we can construct the parsing table? So we have to write the actions here, and here we have to write it as a go to. So under the actions we have to write all the terminals. What are the terminals here? A, B, and dollar. And what are the terminals which we have to write on go to? Yes, A. Yes, A. Now what are the states we are having? Right on here? 0, 1, 2, and 3. We can write it as a 36. So 36. 4 can be written as 47. 47. 5. 6 already written. 7 already written. 8. So 8 and 9. So these are the only rows we are creating for parsing table. So obviously you can notice that we have reduced the parsing table. So previously, that means in CLR, what we have done, we have taken total 9 states. But coming to this LALR, so we are combining the states which are having the same productions, similar productions, but with a different look ahead, right? So we have combined the 3 different states: 3 and 6, 4 and 7, and 8 and 9. Now the procedure is common, the same procedure. What we have to do? I naught on yes. So for the actions, we have to write it as a shift and the state symbol, and for go to, we have to write only the state symbol. State number. I naught on yes, it goes to 1. I naught on yes, it goes to 1. And I naught on a, it goes to 2. I naught on a, it goes to 2. I naught on small a, it goes to 3. Small a, it goes to 3. Yes, 3. See, here 3 and 6 are combined. So instead of 3, what we have to write it as? Yes, 3, 6. Yes, 3, 6. So whenever we got a 3 or whenever we got a 6, we have to write it as a 3, 6. Then I naught on B, it is a 4. I naught on B, it's a 4. So here 4 and 7 combined. So we have to write it as 4 and 7. Right? Next, I1. There is no other production. It's not expanded. There's an end. And we can see this is the end starting symbol. Right? So we can say 1 on dollar is a accept. Accept. Okay, 1 on dollar will be the accept. Now, I2 on capital A goes to I5. I2 on capital A goes to I5. And I2 on small a goes to I6. I2 on small a goes to I6. But here 3 and 6 combined. So 3, 6. And I2 on B goes to 7. I2 on B goes to 7. So again we are combining both the states, 4, 7. And I2 on B, right, completed. Coming to I3. So I3 on capital A goes to I8. I3 on capital A goes to I8. So here we are taking it as a 3, 6. No problem. I3 on small a goes to I3. I3 on small a goes to I3 itself. That means again 3, 6. And I3 on small b goes to I4. Again it will be 4 and 7. And I4 is an end state. Here you can say I4 is an end state. So here we have combined both the 4 and 7 because the productions are equal. So what we have to do? We have to find out the numbering of this production. What number? It's a 3. So I4 upon A, B, and dollar. Okay, look at symbols A, B, and dollar. In all these 3, what we have to write? Reduce 3. R3. R3 and R3. Reduce. Okay. Now, I4 completed. I5. I5 is also end. So I5 is also end means check out the number of the production. Numbering of the production. What's the numbering of the production here? 8 A dot. That means 1. So what is the look ahead symbol? Dollar. So 5 on dollar it will be R1. 5 on dollar it will be R1. And then 6. 6 upon A it will be 9. Yes, here already we have written here. So we need not, yes. So 6 upon A, it is 9, which is a 8, 9. So already we have written there. Okay, so it is a 89. if we got 8, we have to combine both 8 and 9. So I6 on 8 is 9, which is a 89. So 89 I have written it. I7, it's an end. So already we have written R3 for both the dollar and the AB. I8, it is also end. What's the symbol number? Production number, it is a 2. Where we have to place A, B and 9 dollar. In all three cases, we have to go with the R3. Sorry, A dot, that means R2. So we have to write R2 and R2 and R2. So this is the parsing table. This is the parsing table. Okay, simple thing. Before creating the parsing table, what we are doing is we are identifying the states which are having the same productions but different look-aheads. So from this we are combining both the states into a single state called 36, 47 and 89. So 36 means state 3 and state 6 are having the same productions with a different look-aheads. 4, 7 means two states numbering 4 and 7 having the same productions with a different look-ahead. Similarly 8, 9 is two states with the numbering 8 and 9 having the same productions with a different look-aheads. So we are, with the help of all these things, we are creating the parsing table. Now what is the next step? Successfully we have created the parsing table. Now we have to pass the input string. Now we have to pass the input string. So how we can pass the input string? We have to take the input string. So I'm erasing this one. So I'm also erasing this one. We can pass the input string right now. Consider one input string. So whatever the input string we have taken in our earlier example, we'll take the same thing. So the input string is A, B, B. This is the input string. So we have to pass this input string. So what we have to do? So first, so first one is a stack. Next input, and the next one is a action. Next one is the action. So we have to start parsing the input. So the input is A, B, B, dollar, and stack is initially dollar, and we have to start with the 0. So 0 upon A. So 0 upon A. 0 upon A is a shift 36. Shift yes 36. What we have to do? We have to shift the input symbol here 0 A and give the number of state 36. State symbol, state number 36. And now what we have to do? Write down the remaining string A, B, B, dollar. A, B, B, dollar. I'm also erasing this one. Now what we have to do? 36 and A. 36 upon A, again shift 36. So again shift 36. So the same process which we have followed in our SLR Parser, right? So again we are shifting the input symbol towards the stack A 36, and we are shifting this one A, and again it is a 36. The remaining string is B, B, dollar. Now again 36 on B. 36 on B, it's a 47. Now again shift yes 47. So what we have to do? Again we have to shift B and give the number 47. So dollar 0 A 36 A 36 B 47. The remaining is B dollar. So 47 on B. 47 on B, which is a R3. That means we have to reduce. Okay. So reduce with R3. R3 means third production. What's the third production? A tends to B. Third production is A tends to B. So we have to replace this one with A. So 0, A36, A36, and this can be replaced with A. Now you can check, we have to compare the state number along with the terminal, state number along with the input symbol, but here there is no state number. So what we have to do? We have to move on with the previous stack, previous top of the stack. What's the previous top of the stack? 36. 36 upon A. 36 upon A, it is 89. Now it will be 89 and B dollar. Again check with 89 on B. 89 on B, it's a R2. Again reduce with R2. So what's the R2? A tends to AA. So if you observe, this is in the form AA. This is in the form AA. So what we have to do? We have to reduce. So what happens here? 0, A36, and everything can be reduced with capital A. Capital A. B dollar. Okay, B dollar. Now there is no number here. Again we have to repeat the same process. Go with the previous top of the stack. 36 on A. 36 on A is 89. Again it will be 89. Okay, now 89 on B. 89 on B, which is R2. Again reduce with R2. So again you can check 0 AA, that means a capital A. AA means a capital A. So capital A, that implies there is no number. So we can go with the A, 0 upon A. 0 upon A, it is a 2. And it is B dollar. What we have to do? Again check with the 2 with B. 2 with B, it's a shift. Shift yes 47. What we have to do? We have to shift B and write down the state number 47. Dollar 0 A 2 B $47. So check with $47 on dollar. 47 on dollar. Reduce R3. Reduce with R3. R3 is A tends to B. Okay. Now what we have to do? We have to replace this B with capital A. So 0 A 2, and this will be replaced with a capital A. There is no number. Again, move on with the previous top of the stack. 2 upon A. 2 upon capital A except 5. 5. It's a dollar. So 5 upon dollar. So 5 upon dollar. It's a R1. So you can check reduce R1. So what's the first production? A, yes. So this is like in the same way. So dollar 0, yes. A to A5 can be replaced with yes. And dollar. You can check yes on dollar. So there, sorry. Yes, there is no number. So we have to go with the previous top of the stack. 0, 0 upon yes. 0 upon yes, it is 1. So 1. And now you can check 1 with a dollar. So 1 with a dollar, it's an accept. Accept. So that implies the given input string can be parsed with the given grammar or given productions. Okay. So we have to draw the parse tree from the bottom. So yes is the last one, and that can be expanded with a and capital A. And this A is expanded with a B, so which is a terminal which cannot be expanded further. And this A is again A, and this cannot be expanded further. And this can be again expanded with A, and this cannot be expanded. And A is replaced with a B, so this will be B, which cannot be expanded further. So if you observe all the terminals, that means the leaf nodes. So we got the input string A, B, B. So we are approaching bottom-up approach. So in this way, we have to solve the LALR parser. We can parse the input string and we can derive the parse tree by using the LALR parser. Okay, so only difference we have seen is, so before constructing the parsing table, after calculating the LR1 items, we have to identify the states which are having the same productions but at different look aheads, and we have to combine both the states. So that is the only thing we have done here, and rest of the procedure is similar to our CLR. Syntax directed definition, and this is also called as syntax directed translation. Okay, so whatever it may be, let's see what is exactly the syntax directed definition, right? So in our previous session we have discussed about the different types of parsers, right? So that is the second phase output where we'll be getting the parsers. So we have seen a lot of parsers: LR parser, SLR parser, CLR parser, etc., etc. And also we have seen some YACC tool which will generate these parser, right? Now, so the output of that parser is a parse tree. Okay, so parse tree. For all the types of parsers, the output will be the parse tree. So either it may be a bottom-up parser or the top-down parser. And now we have to improvise this parse tree. We are supposed to improvise the parse tree. Right? How to improvise the parse tree? And this is called as SDT or SDD. Means syntax directed translation or syntax directed definition. Okay. Now, how it will be improvised, the parse tree, how it will be improvised. So for every symbol, so here we are supposed to discuss about two types of symbols. We are calling them as, see, terminals and similarly non-terminals. Terminals and non-terminals. And we have seen these non-terminals can be expanded and terminals can't be expanded, right? So terminals can be expanded. And also we have seen these terminals will be the leaf nodes. So that's why these terminals can't be expanded. That will be the last one. And if it is a non-terminals, that can be expanded until it reaches to the leaf nodes. So particularly for these non-terminals, okay, for these non-terminals, there will be an attributes. Right? Like properties. We can say them as a properties. So for every non-terminal, that there can be 0 or more number of attributes. For every non-terminal, there can be 0 or more number of attributes. Okay, so one such attribute is a value. So value. Okay, every non-terminal will be having some value. Okay, and leaf nodes, for leaf nodes there will be no attributes directly. We can have the lexical value, direct value, right? For example, see, there is a productions like E plus T, E tends to T, T tends to T into F, T tends to F, and F tends to I. So already we have seen these kind of productions while generating the parsers, right? So here you can see E, T, F, all these are the non-terminals, and whereas ID is a terminal. So how we can write it? So for example, if you want to give ID plus ID into ID. So if you want to pass this particular input string, what we are doing simply, so we are first we are taking this production, we are starting from the initial production. So E tends to E plus T. So where this E can be, okay, E can be considered as a T, right? E with a T, and this T can be considered as a T into F, T into F, because so this is similar with this one, okay, ID plus ID into F, and this T can be expanded with F, and this T can be expanded with F, and this T is already F, so plus and star. Now it will be ID, it will be ID, it will be ID, star and plus. So this input string can be passed by using these productions, right? So that means every non-terminal will be having an attribute, so that should be evaluated. So for every production there will be some sort of rules. For every production there will be some semantic rules will be applied, and that semantic rules and this kind of productions combinedly call them as a syntax directed definition. For example, see what we are doing here. So E is equal to T. What we are doing here, T is equal to T star F. And again, what we are doing here, T is equal to F. What we are doing here, T is equal to F. That means for every production there will be some formula. So here I write it. So this can be written as E is equal to E plus T. And this can be written as E is equal to T. And this can be written as T is equal to T star F. And this can be written as T is equal to F. And this can be written as F is equal to I. Right? So all these are called semantic rules, and these are called productions. We know that productions, and we are usually calling it as context-free grammar. We are calling it as a context-free grammar. So what is this SDT? SDT or SDD? Okay, syntax directed transition or definition is equal to context-free grammar. That means these kind of productions plus some sort of semantic rules. Some sort of semantic rules. So semantic rules is called as a SDT, syntax directed definition or syntax directed transition. Syntax directed transition. Now, see, hope you understood this one, right? So these are the productions. We call these as a productions, and these as a semantic rules. Okay. So in order to evaluate this kind of expression, what we have to do? So with the help of these productions and with the help of the corresponding semantic rules, we have to calculate the expression. We have to calculate the expression. So this is what happens here. Now, here for applying the semantic rules on the productions, what we have to do? So we have to find out the attributes. There are different categories of attributes. Okay. So for every, see, one thing I will tell you, the symbols will be having attributes. Productions will be having semantic rules. Remember this one, definitely you'll be understanding everything. For symbols there will be an attributes, the properties. Okay. For example, capital T. So capital T is having some attribute called value. So if any value should be taken, that will be T dot value. So here you can write it as E dot val, E dot val, T dot val. So these are all the semantic rules. Okay, so rules are associated to the productions and attributes are associated to the symbols. That two particularly are non-terminal symbols. Non-terminal symbols. Right? Now, see, these kind of attributes are two categories. Okay, so two category of attributes. One is synthesized attributes, inherited attributes. Synthesized attributes, inherited attributes. Synthesized, inherited. Okay, how the, so both comes with the non-terminals only. Okay, both comes with the non-terminals only. But coming to the synthesized attributes, those are the non-terminals on the left hand side. Okay, so non-terminals on left hand side. And inherited attributes, these are the non-terminals on right hand side. Non-terminals on right hand side of production. For any production. So where we are having these non-terminals means in productions itself, right? So in productions, so on LHS, whatever the non-terminals we are having on LHS, those comes with the synthesized attributes. And the non-terminals which are available on the right hand side of the production are called as inherited attributes. See, we'll take an example for synthesized attributes and the inherited attributes, and then we'll move on with the different categories of SDDs, syntax directed definitions. Okay, yes. Let us consider. See, synthesized attributes. Synthesized attributes. So as I said, the non-terminals on LHS of production. Okay. So example, I'll write an example. For example, some A tends to B, C. A tends to B, C. Now, how will we get the value of A? So, coming to the semantics rule for this one is A dot value is equal to B dot value and C dot value. Okay, A dot value is equal to B dot value into C dot value. So, how we can get this A dot value? So, that A dot value will be getting from either B dot value or C dot value. So, here B dot value is again expanded because B is a non-terminal, C is also a non-terminal. So, A dot value, so the value of A will depends on children like B and C. Okay, so this is one more point. Value of A will depends on children. So here only remember the non-terminals on left hand side. So don't consider B and C. Don't consider B and C. Okay, it will also follows the bottom-up parsing. Bottom-up parsing. Okay. Next, the second category is inherited. The second category is inherited. So here, just now we have seen these are the non-terminals on right hand side. So non-terminals on RHS of production. So you need not worry about the left hand side. Okay, you need not worry about the left hand side. So inherited attributes are the non-terminals on the right hand side of the production. So here example S tends to A, B and C. X tends to A, B, C. Now which one will be the inherited attribute? So A, B, C will be the inherited attributes. Okay, so here the inherited attributes are A, B or C. For example, consider some B. Okay, consider some B. Now a value of B depends on parent. So what is the parent here? Yes, or siblings. Who are the siblings here for B? A and C. So if you want to calculate the value of B, okay, the attribute value of B, then it depends upon parent or the siblings A and C. So such kind of attributes we call it as an inherited attributes. Such attributes we call it as an inherited attributes. And usually it will be following the depth first parsing. Okay, so these are the two categories of attributes: synthesized attributes and inherited attributes. Right? Now, we'll see the different categories of SDTs, syntax directed transitions. So here SDT is also categorized with two different categories: S attributed SDTs, L attributed SDTs. So right here SDT, S attributed, L attributed, S attributed SDT, L attributed SDT. Okay, so the name itself indicates here S attributed SDT will be using the synthesized attributes, and L attributed SDTs will be using the inherited attributes with some constraints, some sort of constraints. Now we'll see what is the S attributes and L attributed SDTs, the categories of SDTs. See, simple example. S attributed SDT. So first it uses synthesized attributes synthesized attributes, and it will be using the bottom-up parsing. Just now we have seen bottom-up parsing. And then, see example, you can say A tends to B and C. So the A value will be depends on B and C. Now next one, L attributed SDT. What is this L attributed SDT? See, this L attributed SDT uses inherited attributes. It uses the second category, inherited attributes. So what is meant by inherited attributes? So here with some constraint, very important, with some constraint. So we have to focus on this constraint. What is the constraint here? Okay, so example, let us take some A tends to B, C, D. Now, see, value of C depends on if it is an inherited attribute. What we have said, it depends upon the parent and siblings. Parent or siblings. So here the constraint is only left sibling. Okay, so here C depends on A, parent, and what's the left sibling of C? B. It's a left sibling. Only this one. So the value of C doesn't depend upon D because it's a right sibling. So this is the only constraint. This is the constraint. Okay, this is a constraint of L attributed SDT. Right? So hope you understood this one. Right. Now we'll see one parse tree. Okay, we'll see one parse tree, and let me explain the improvised parse tree. Okay, what is the parse tree? And I'll write here the productions E tends to E plus T, and E tends to T, T tends to T into F, F tends to, T tends to F, and F tends to I. So these are the productions. Then what about the rules? So coming to this one, E dot val is equal to E dot val plus T dot val. Similarly, E dot val is equal to T dot val. Next, T dot val is equal to T dot val into F dot val. And T dot val is equal to F dot val. And F dot val is equal to ID. See. So these are all semantic rules. And these are all productions. Okay, the semantic rules and the productions. Now the input is ID plus ID into ID. So how it can be represented here? First start with the starting one, E, which can be expanded with the three terms, that is E plus T. Right? Now this T can be, so this E can be expanded to T, and this can be expanded to T into F. And this can be expanded to F, and this can be expanded to F, and this can be expanded to ID. And this can be expanded to ID, and this can be expanded to ID. So the leaf nodes are all terminals. Now what? This can be improvised in this way. See, E plus T, and the same thing, T star F ID. So this can be written as, see, what is this one? From bottom up, go with the bottom up. So this is the ID. So ID dot lex val, that means a direct value. It's a value, right? ID dot lex val, that value. Here F. So in this, here what happens? F dot val is equal to ID dot lex. F dot val is equal to ID dot lex. what happens here? Here also f dot val is equal to id dot lex. What happens here? Here it is t dot val is equal to f dot val, and here also t dot val is equal to f dot val, and here what happens? E dot val is equal to t dot val. Okay, and here t dot val is equal to t dot val into f dot val. Okay, and this E dot val is equal to E dot val plus T dot val. So like this, it can be improvised with the help of the attributes and semantic rules. So here there is a direct value, and here f becomes, we are getting the value of f with the help of a children, and here we are getting the value of t from its children, and we are getting the value of t from its children t star f. So like that, this SDT will be formed. So the productions plus the semantic rules, the productions plus the semantic rules is called the SDT. So the attributes, we have seen the attributes as two categories: synthesized and inherited. Similarly, SDT, syntax directed, L attributed, S attributed. Right? So this is all about our syntax directed definition. So the value, so whenever you are drawing the parse tree, that can be improvised with the help of the semantic rules given for each and every production. So once again I'm saying, every symbol, every non-terminal will be having 0 or more attributes, and every production is associated with some semantic rule. And these are called as the semantic rules, and dot val is one of the property or attribute of the particular non-terminal. So here YACC stands for yet another compiler, which is a parse tree generator tool. So this is a parse tree generator tool, and it stands for yet another compiler, right? So this is called a YACC tool, yet another compiler. So this will be acting as a parse tree generator tool, so which indicates that the output of this particular tool is parse tree. So the output of this tool is parse tree. Okay, there's also particularly LALR parser, right? So which generates the LALR parser. So LA means look ahead, and the input string parsing from left to right, and uses the rightmost derivation with one look ahead. And see, here we'll be having some YACC specifications, and that YACC specifications will be having a file name with a dot extension .y, right? And these specifications are divided into 3 categories or 3 divisions. So the first one is definition, and this should be in between the modular symbol, that is the percentage symbols. And this definitions means it defines all the tokens. Token information will be there. Similarly, the declarations will be there, and some header files will also be here, header files, and the constant declarations, okay, variable declarations, everything will be comes under this definition phase. And the next one is rules, and that should be included in between 2 modular symbols. So this is most important. So this section specifies the actions to be done or actions to be taken when the token is matched with the grammar. See here, these particular specifications will be having some grammar, and after processing this particular grammar, we'll be having some parse tree, so where it will take tokens as an input. Okay, so let me explain in detail, right? So this will be the second section. So second section is a rules section, where the actions, it specifies the actions to be taken when the token is matched with the grammar. And the last section is auxiliary routines. So this section specifies the function definitions. The routines means subroutines or functions. So whatever the functions we are writing inside the main function, including the main function, so that will be executed, and that will return the result.
okay, as a 0 or 1. If it returns 1, that implies the parsing is unsuccessful. And if it returns 0, that implies the parsing is successful. That means the execution of subroutine is successful. So here, the main function will be executed and also the functions will be done. So function definitions will be done. Okay, and if return 0, that is successful. So successful execution. If it returns 1, it is unsuccessful. So this information will be given in this particular auxiliary routines. So these are the 3 different sections available in the YACC specifications. Okay, so first one is the definition, so where all the declarations will be done. Second one is the rules, where the actions to be taken, what type of actions to be taken if there is a match. And the next one is the auxiliary routines, where the normal main function or any function definition will be get executed and it will return some value. So if the return is either 0, it is successful, and if it is 1, it is unsuccessful. Now, after specifying this one, right? So this complete information will be available in this YACC specifications, which is of a .y. For example, let us take it as a sample.y, which consists of the YACC specifications. Now what happens after specifying this one, right? This complete grammar. Okay, after specifying all the grammar according to the specifications. So we will be saying that it has a .y, right? So I'll take sample.y will be taken as an input, and to which we have to give to the YACC compiler, to the YACC compiler. So if this file is given to the as an input to the YACC compiler, it will produce some y.tab.c. So that means C file, C programming file will be returned as an output. Now, in order to execute this, we require some C compiler. So the next step, so this is the step 1. And step 2, what is the step 2? So whatever the output we got from the YACC compiler, there is a y.tab.c will be given to the C compiler now. C compiler. So which will produce a.out. Here a.out is a analyzer, right? Syntactic analyzer or a parser generator. So the next one, for this particular a.out, we are supposed to give the tokens as an input, and these tokens will be coming from the program. That means this is the output of the first phase of a compiler, that is a lexical analyzer. So we have discussed about the Lex tool, so which produces all the tokens of the program, smallest individual units of a program. So those tokens will be given as an input for this particular parser generator, and finally the output will be the parse tree. The output will be the parse tree. So this is how we can get the parse tree from this YACC specifications. YACC specifications. So I'll write here. Okay. So first YACC specifications. This file will be given to the YACC compiler, which will produce a C file, and C file will be given to the C compiler, which will create the parse generator. So this will be the parse generator. We can simply write it as a parse generator. So we need to pass the tokens as an input here in the second phase. So what we have discussed in the earlier session, there's a first phase is a lexical analyzer, the next one is a syntactic analyzer, right? So whatever the input we are, whatever the output we are getting from the lexical analyzer, that will be given to the next second phase. So that's what we are saying. So tokens are the output of lexical analyzer, which we are giving as input to the a.out, which is a parse generator, which will generate the parse tree. So this is how the parse trees will be created by using this parse tree generator. So this is a tool. This is a tool which will generate the parse trees. That's also particularly LALR parsers. LALR parsers. So we have seen these LALR parser and different types of parsers in our previous session, right? So once you have that, annotated parse tree. So here the parse tree is completely different with the annotated parse tree. All right. So from the first phase we'll be getting the lexings, and then in the second phase we'll be getting the parse tree, and the third phase in the semantic analysis we'll be getting the annotated parse tree. So we have seen for every non-terminal there will be an attribute or a value. Okay, so the parse tree which will be having only the non-terminals and the terminals, where leaf nodes are the terminals and intermediate nodes are the non-terminals. So annotated parse tree means for every non-terminal, that means for every internal node, it will be represented with the attribute. So the attribute can be anything. It can be a value, or it can be a type, or it can be a reference, anything. Okay, now we'll see one example for this annotated parse tree. So let us take an example, annotated parse tree generation for some 10 into 5 plus 3. So we know what is the evaluation of this one. So the result will be, the multiplication will be done first because the highest precedence will be there for the multiplication among the into and plus. So 50 plus 3. So it becomes 50 plus 3, which is a result called a 53. So if the expression, I mean, this is represented with id into id plus id. So we need to construct the parse tree for this particular expression, where for every non-terminal will be representing the value. So once executing this one, we should get the result as 53, where first id is replaced with the 10, second identifier is replaced with the 5, and the third identifier is replaced with the 3. Now we need to construct the annotated parse tree for this one. So parse tree for this one and annotated parse tree for this one. Okay, so the productions, first let us see the productions. What are the productions which satisfies this particular expression? So E tends to E plus T, E tends to T, T tends to T into F, T tends to F, and F tends to ID. So these are the productions which satisfies this particular expression. So for this one, we need to write the semantic rules. Semantic rules. So we know the SDD, syntax directed definition, is a combination of production and the semantic rules. So here everything is a value. Okay, everything is a value. We are not using any kind of data types or a memory, right? So for everything is a value. So semantic rules will be E dot value, the attribute we are representing with a dot value. So E dot value is equal to E dot value plus T dot value. And this one, E dot value is equal to T dot value. And for this, T dot value is equal to T dot value into F dot value. And for this, T dot value is equal to F dot value. And for this production, F dot value is equal to, so this is an identifier. This is an identifier, not a non-terminal. So this will be directly having id dot lex value. Lex value means a direct value. Lex value means a direct value. So for these semantic rules, first we will need to draw the parse tree. Parse tree. So parse tree means deriving this particular definition. So we have to start from start symbols. For production, we know E is a start. So E, it can be expanded with E plus T. So the second one is a addition, first one is a multiplication. So this can be changed to T, which further can be expanded with T star F, and T can be expanded with F, which is an ID, and F, which is an ID, and T F, which is an ID. So this is a parse tree. Okay, this is a parse tree for the given string. So you can observe these are all internal nodes. These are all internal nodes, and all the leaf nodes are the terminals. You can see. So all the leaf nodes, what are the leaf nodes? ID, which is a terminal, ID, which is a terminal, star, terminal, plus, terminal, ID, terminal. So leaf nodes are the terminals, and intermediate nodes are non-terminals. Now, what is an annotated parse tree? Annotated parse tree. So if you represent, so what we are saying, so you can observe here, every non-terminal will be having a different attributes. See, for example, if you take E, so E can have a value, E can have a data type. Okay, E means a memory variable, so it can also be have a memory. So like that, there will be a lot of attributes. But in this particular example, we are showing that every non-terminal is having only a value. So if you want to get this one, that depends upon E dot value and T dot value. So if the LHS part is completely depends upon RHS part, that we are calling it as synthesized attributes. So this is a completely example for the synthesized attributes. Okay, now annotated parse tree. This is a parse tree which we need to represent each and every non-terminal with its attribute. That may be either value or type or memory, whatever it may be. But in the annotated parse tree, every non-terminal should be represented with a corresponding attributes based upon the semantic rules. So here we will write here. I will write once again a parse tree. First we will write the parse tree, then we will convert into annotated parse tree. So this one is a T, which again further divided as T star F, and again F, ID, F, ID, F, ID. See here you can observe some productions like this one and this one, we are having some left recursion. But we don't worry about the left recursion because we are using the bottom-up approach. So if you are using the bottom-up parsing, we have studied that there will be no problem with the left recursion and left factoring. So no need to worry about that one. So here we are using the bottom up approach. So bottom up approach means we need to travel to the bottom first. So this is a leaf node. So what happens? ID. So what is the value of this ID? Okay, so it is id dot lex value. So this becomes id dot lex val. Okay, and coming to this f, so you can observe the last one, id dot lex value can be represented with a f dot val. So the f dot val depends upon its child. So here f dot val is equal to id dot val, lex val. Okay, sorry, is equal to id dot lex val. And see, you can observe, and this particular t, value of t, depends upon its child f. So here it will be t dot val is equal to f dot val. So what happens? This value will be occupied in this position and this value will be occupied in this position. And if you want to consider this particular non-terminal t, that depends upon the child t and f. So we need to travel in this way. So id, again we are getting id is equal to id dot lex val. So f dot val is equal to id dot lex val. Okay, now what about this value? So this value is t dot value is equal to the value of left child and the value of a right child. So this becomes t dot value is equal to t dot value into f dot value, because here we are having an into operation. And this value can be replaced with this one. So e depends upon its child. E depends upon its child. So here e dot value is equal to t dot value. So what happens? Here it is id dot lex value, the first one, it is a 10, and id dot lex value, it is a 5, and here we'll be getting 10 into 5, 10 into 5 is equal to 50. The value is 50, and here we are getting the value 50. Here we are getting the value 50. Now again, see what happens? So it moves upwards, and again it comes here id. So again it is id is equal to id dot lex val. id dot lex val. id dot lex val is the third one, that is a 3 here. Now f depends upon id. According to the productions, f is equal to id lex value. id dot lex value, yes. So f dot val is equal to id dot lex val. So what happens here? 3 will be getting. And here again t dot val is equal to f dot val. So what is f dot val? It is again 3. So what happens here? E. So e dot val is equal to e dot val plus t dot val. So what is the value of here? E dot value is a 50 plus here it is a 33. So which gets 53. So is equal to 53. So 50 is equal to, here we'll be getting a 53. Okay. So this E depends upon these two attributes. I mean these two children, E and T. So hope you understood. This is a parse tree. Okay. So this representation is a parse tree, but this representation is an annotated parse tree. So annotated parse tree means for every non-terminal should be represented with its attribute. That may be either value or type or memory. That depends upon the semantic rules and the example. So also this will give you the order of evaluation, how it will be evaluated. You can see in this example, first the 10 into 5 has been done, and that is added to the rest of the id. That means a 3 in this example. Okay, so this is a difference among the parse tree and annotated parse tree, right? So parse tree is an output of syntax analysis, and annotated parse tree is the output of semantic analysis. Okay, and the implementation of this particular SDD, we call it as a syntax directed translation. So as here all the productions are synthesized attributes. Here you can see in the semantic rules, every attribute, I mean every non-terminal is represented with a value. So, and also the LHS is completely depends upon the RHS. The parent completely depends upon the children. So how we are getting the parent value from the children value. So that's why we are calling it as a synthesized attributes, and this is a synthesized SDT. Yes, attributed SDT. And finally, this is the annotated parse tree. You can feel the difference among parse tree and annotated parse tree. Annotated parse tree. So today we'll see the example for int a comma b. So the input string is int a comma b. So for this particular input, we'll see the parse tree. First, let us see the productions. What are the productions? The productions to validate this particular string is d tends to t l and t tends to int and L tends to L comma ID, and L tends to ID. So these are the productions which satisfies this particular input string. And also we have to write the semantic rules first. Semantic rule. So as we said that only the value is not the attribute, okay, for the non-terminals. There will be a lot of things. So here you can see int is a data type. Int is a data type. So for this, the attribute will be t dot type. T dot type is equal to integer. And for this also, okay. And here see, A and B are identifiers. We know A and B are the identifiers. And what is the meaning of this particular statement? So declaration of two variables or two identifiers which are of integer data type. So here you can see T and L. T and L. So we have seen two types of attributes, that is a synthesized attributes as well as inherited attributes. So synthesized attribute means the value of the parent value will be depending upon the child values. So D value will depends upon T and L. But here you can see what is the L value? ID. So this L value is ID, and before reading the input, before reading the identifier, that should be of integer data type. So this completely depends upon the siblings. Okay, so here we are saying D as a parent, D tends to TL, and T comma L are siblings. So here L is an ID, so L that is of integer. So L completely depends upon T. T is a data type, integer or a float or a double, whatever it may be, but it depends upon here. So you can also write T tends to int or float. Now you can say if you consider identifier that depends upon the data type, which is T. So T dot type is equal to integer or float, whatever it may be. And here L depends upon sibling, not a parent. So this is an inherited attribute. So we can say L dot inherited is equal to T dot type, because whatever the data type we are taking here, for that particular data type only the identifier should also be taken. So here the L value will be completely depends upon the sibling, not on the parent. So if the attribute depends upon the sibling, that we call it as an inherited attribute. So this is an inherited attribute. So inherited attribute. So in our previous example, we have seen the synthesized attributes. So in this example, we are seeing the inherited attribute. So here what happens? L dot in will also be depends upon the same thing. So T dot type, and we can simply add entry of ID. Okay, add entry of ID. And now we'll see the parse tree, how the parse tree will be. Okay, so parse tree. So what first we need to start from the first production, D, T and L. Okay, and T is integer based upon this particular input string, and L again you can expand L comma ID and L ID. Okay, and this will be A and this will be C. Oh, sorry, B. So int A B. So this is the parse tree. Now coming to the annotated parse tree. Annotated parse tree. So annotated parse tree means giving the attributes to each and every value. So we'll write here once again D, T, L, L, comma, ID, ID, int. Right? So now you can see we need to give the attribute values. So here int is nothing but a type. It's a data type, right? And T, the value of T becomes, so T dot type is equal to integer. T dot type is equal to integer, because here we are writing the data type. So we are giving the attribute as a type. And coming to here, so int is a normal int. The value of int is int. Okay, it's a keyword. Now coming to the ID is nothing but A, and L. See, L depends upon T. So L depends upon this one. So in order to differentiate this one, I'll give L1. Okay, I'll give L1 instead of L. Both are equal, but just in order to differentiate that, I'm giving it as a L1. L1. So here you can see L inherited attribute is equal to L dot in is nothing but a type, because if you are giving any value to the identifier A or B, so that depends upon the data type, which is this one. So L dot in is equal to T dot type. So this depends upon this one. Okay, so the value of L is getting from its sibling. So the same thing happens here also. L1 dot in is equal to integer. So because it's coming from its parent. Okay, it's coming from its parent. So L1 is also the integer. Okay, hope you understood. So this is a simple example for generating the annotated parse tree for this kind of input string. Okay, this is also an example for inherited attributes. So once again I'm saying, so here L is an identifier and the input string is a declaration part. So the declaration part means if you are declaring some variables, that should be done only with respect to the data type, what data type it was. So it totally the A value and B value depends upon the data type. So L value depends upon the data type T. T here is a sibling. So this is an inherited attribute. Okay, so previous example we have directly taken the values, that there is no data type there. Okay, but here we are having the data type, so it is an inherited data type. So in the annotated parse tree also, L value is getting from its sibling, so this is an inherited attribute, and this L1 value is coming from its parent. So this is a T dot type, this is nothing but integer, and this is a ID is equal to, simply we can write ID is equal to lex dot value, and here also ID is equal to lex dot value, which is a here, which is B, right? So hope you understood. This is a simple concept, construction of annotated parse tree with the inherited attributes. So in our previous sessions, we have seen how to draw the parse tree as well as an annotated parse tree. So from that annotated parse tree, the next concept is a dependency graph. So here the graph means it is a nodes and corresponding edges. So here the nodes represents the statements. Statements means the production rules. Okay, so we'll be having a lot of production rules. So LHS and RHS. So RHS can be replaced with the corresponding LHS. So that particular LHS will be considered as a nodes here. Okay, the substitution. And edges represents the dependency. So what exactly means the dependency? If we are having a two statements, then one statement can be depends on another statement. So for example, let us take a statement like A is equal to B plus C and D is equal to A plus E. Okay, so if consider these two statements, if you want to execute this one, that means if you want to compute this one, it depends upon this particular A value, because in this expression A is included, but A will be calculated in the first statement. So this depends upon A. This depends upon A. So this can be represented as A arrow mark D. That implies this D value depends upon A value. Okay, so this is called as a data dependency. This is called as a data dependency. So one statement depends upon another statement. So if you want to compute one statement, that should be depends upon another statement. So this is a data dependency. There's a one more major kind of dependency is there. There is a control dependency. Control dependency. So what is this control dependency? This is the first one, this is the second one. Control dependency. Control dependency means in our program we are supposed to write some control statements like conditional statements, right? So we will be writing like this: if A greater than B, then some statements, right? So these statements depends upon this particular condition. So if condition becomes true, these statements will be executed. If the condition becomes false, these statements will be skipped, will not be get executed. So such type of dependency we call it as a control dependency. And two more dependencies are there, like anti-dependency and equal dependency. So these are the major things: data dependency and the control dependency. In order to represent these kind of things, we will be using this dependency graph. We will be using this dependency graph. So which statement depends on another statement. Okay, and the major importance why we are using this dependency graph, we are representing the graph means to reduce similar computations, and one major thing is order of evaluation. So for example, if any expression is having a multiple operators, so which operator should be executed first? So that depends upon the operator precedence, and that will be represented by using this dependency graph. And also this will be used in representing the DAG model. DAG means directed acyclic graph. So in our further sessions we'll be learning about this DAG. Okay, directed acyclic graph. So this dependency graph will be used for these things. Now we'll see one example. We will take some productions and also the semantic rules, and then we will represent the dependency graph. Yes. So the name itself indicates dependency graph means the statements, dependency among the statements. So here statements means the productions, right? Example productions. Let us take the previous example. E tends to E plus T, T tends to, sorry, E tends to T, T tends to T into F, F tends to T tends to F, F tends to some ID. Okay, and let us represent this dependency graph for the expression like 10 plus 4 into 3. So we need to write the dependency graph for this one. So first we'll see the semantic rules for this one. So all these are the synthesized attributes. So what synthesized attribute means? The value of a child depends upon the parent. Sorry, yes. So the value will be depending upon the child. So here E value depends upon this E value and this T value. Okay, it's not a inherited, it is a synthesized. So this can be written as E dot value is equal to, so we, in order to give the difference, we can write it as E1 dot val plus T dot val. Similarly, this one can be represented as E dot val is equal to T dot val, and here T dot val is equal to T dot val into F dot val, and this can be written as T dot val is equal to F dot val. Val means value, attribute. Okay, and this one F dot val is equal to ID dot lex value, directly the value. Okay, because it's a term, it's a terminal. Okay, terminal means directly LX value. Now we'll see the parse tree. Okay, parse tree for this one. So in order to represent this one, so this will be like ID plus ID into ID. So this is in this form. So we need to construct the parse tree for this particular expression. So how we'll be writing? So E can be expanded with E plus T, and again here E can be represented with T, T can be represented with F, F can be represented with ID, and here T can be represented with E star, sorry, here E, yes, T can be represented with a T star F. So here T is a F. So this T can be represented with F, F can be represented with ID, and this F can be represented with ID. So this is a parse tree for this particular expression. So now the dependency graph means, so as we said that A arrow mark B means B value depends upon A. B value depends upon A. So F value here ID value doesn't depends upon anything, because ID is a terminal, directly will be having the lex value. So here what happens? F value depends upon ID. So you can write it here. So F dot val is equal to, so here ID is equal to lex val. So which is nothing but ID1. ID1 is 10. So 10. So is equal to 10. So the arrow mark will be in this way. Okay, so that means this F dot val depends upon ID dot lex value. Okay, now see, always the parse tree can be evaluated from bottom up and left to right. So you need to remember this one, bottom up, left to right. You can see simply, so E can be, E value depends upon this E value and this T value. And here E value depends upon T, T value depends upon F, F value depends upon ID. ID is a terminal, so directly we can have a value. So the first execution will be this one. Second execution, this one. What happens? Now this one, T, the relation among F value and T value, you can see this one. T value is equal to F value. So T value is equal to F value, which is a 10. So this value depends upon F value. So this one, sorry, I'll write here and I'll keep arrow mark in this way. So arrow mark means T value depends upon F value. So this is the third step executed. And the dependency between E and T value, is there any relation among the E and T? So E tends to T. Here you are having the production, E tends to T. So E value is equal to T value. So here we can write E value is equal to T dot value. T dot value is a 10. So there is a one more dependency and it is a 4. Now what about the value of E? And this particular E value depends upon this E value and this T value. So we don't know about this T value. So again it comes down and here it is ID is equal to some lex value. So this is ID2, which is nothing but a 4. So this is a 4. So this will be the fifth process execution. This is the first execution, second execution, third one, fourth step, and fifth step. Sixth step, F and ID, the relation among F and ID. So F tends to ID, F dot value is equal to ID dot lex value. So F dot value is equal to lex dot value, that is a 4. This is the sixth step to be get executed, the arrow mark. And T and F, the relation among the T and F. T tends to F, T dot value is equal to F dot value. So T dot value is equal to F dot value, which is a 4. And this is the seventh step to be get executed, and there is a dependency. So the T dot value depends upon this F dot value. Then this T value depends upon this T dot value and F dot value. So here F dot value was not executed. So instead of calculating this one, this will be executed. So id3 is equal to lex dot value. So the value of id3 is 3. So this is a 3. So this is a eighth step to be get executed. So this depends upon f, because the relation among f and id is f tends to id, f dot value is equal to id dot lex value. So here it becomes f dot value is equal to 3 because id is 3, f dot value is equal to 3. So this will be the ninth step to be get executed. Okay, ninth step to be get executed. Now this t value depends upon this t value and f dot value. What is the relation among this t and f? So this is the t tends to t into f. So t dot value is equal to, what is the 4 into 3, which is a 12. Okay, 4 into 3, which is a 12, because this depends upon these two things. Okay, this is the 10th step to be get executed. So this depends upon here and this depends upon here. Okay, then okay, now see here, this e dot value will be depending upon e dot value and t dot value. The relation among this one, e is equal to e plus t, e value is equal to e1 plus e1 value plus t value. So this will becomes, what's the value of this one? 10 plus 12, so which is nothing but a 22, and this is the 11th one. So here we are getting dependency comes here in this way, right? So hope you understood. So the order of execution representing in the graph is nothing but a dependency. So because we can't compute this particular thing the first time, because it depends upon this value and this value, and we can't compute this one first because this depends upon this value. So this dependency graph will be showing the order of execution, the order of statements which are being executed, right? So this is the dependency graph, and you can draw this. See, first, second, third, fourth, next, 7th, 6, 5, next, 8, 9. This is a 10, and this will be the 11. Okay, this is a dependency graph. The first evaluation, second evaluation, the second statement depends upon the 1, 3 depends upon 2, 4 depends upon 3, and 11 depends upon 4 and 10, and 6 depends upon 5, 7 depends upon 6, 9 depends upon 8, and 10 depends upon both 7 and 9. Okay, and 11 depends upon 4 and 10. So this is the dependency graph. So this will be used for showing the order of evaluation as well as to represent the directed acyclic graph. So just remember these 2 points. So in this syntax tree, this is a logical structure of a program. So it represents logical structure. So in the instructions of a program, it will eliminate all the symbols, spaces, and etc. Right? So it removes spaces and unwanted grammar, comma, spaces, etc., will be removed from the instructions. And this is a simplified version of a parse tree. Simplified version of parse tree. And as we are saying, this is a tree structure, so it will be having both nodes and edges. So here, nodes represents operators or operands. So in this syntax tree, always a leaf node. So leaf node means the node which can't be expanded further. Okay, that's the end node, right? Last node. So the leaf node represents operands, or we can say them as identifiers, both constants as well as variables comes under this identifiers. And similarly, all the internal nodes of a tree. So internal nodes means other than the leaf nodes. So even a root node will be a part of the internal node. So all the internal nodes will be operators. So the operators will be representing the internal nodes. So this is a complete view of the syntax tree, which is a logical structure and leaf nodes, internal nodes, and it's a simplified version of a parse tree. And mainly 3 functions will be used while constructing the syntax tree. So the first one is make leaf. If it is a leaf node, so what we are saying, leaf nodes are nothing but operands or identifiers, right? So whenever we say the operands, so that will be make leaf. So it will be identifier comma entry of that particular identifier in the symbol table. So it will take 2 arguments. And the next make node. So make node will be So what are the internal nodes? Internal nodes are nothing but operators. So if it is an operator, that operator can have the operands. Okay, the operands. The operation can be performed on operands. So make node will be having the three arguments. One is an operator and next one is the operands. So here we can write operator, left operand and right operand. So we are saying it is a tree structure. So left operand and the right operand. And similarly, if there is a number, okay, number is also an identifier. For example, see, let us take some a is equal to some 10 plus 2 into 3. So we are calling this as an identifier and this as a number. Okay. So if expression is having both identifiers and number, so number is also a leaf node. So for that particular thing, we can write it as mk leaf node, the same thing. But here instead of id, we will be writing it as a number, comma, it's a value, whatever the value it was taking. Okay, so these are the three functions we'll be using while constructing the syntax tree. While constructing the syntax tree, right? So we need to remember all these three functions. Okay, and apart from these, we will be using the semantic actions also. Semantic actions. Okay, so by using both these two, we'll be using, we can construct the syntax tree. Now let us take one example and we will see how the syntax tree will be constructed. So very easy thing. So let us check it out. So remember all these points, particularly the functions as well as the semantic. So example, let us take one example. So id into id plus id. So let us convert it to numbers, right? So 10 into 2 plus 20 or plus 5. Okay, 10 into 20 plus 5. So let us take this particular thing. So what are the productions we can use here are e tends to e plus t, e tends to t, e tends to, sorry, t tends to t into f and t tends to f and f tends to id. Okay, so for this, the actions, see, we can make use of the functions. Okay, so here we are having an operator. Okay, consider the RHS of the production, and in the RHS, if you are having the operator, we have to use a function called make node. And if the RHS of any production doesn't have any operator and it is having only the identifier, that means the terminals, then we have to use a make leaf function because it's a leaf node. So this will become, see, we are having operator, so we can say e dot pointer. So in order to represent this syntax tree, we can use a double pointer. It will be easy for implementation. Okay, we can, if you use a double pointer, it will be easy for implementation, right? So pointer is equal to, so this can be written as mk node. Mk node means a make node, three arguments, which is a, first one is an operator, next left and right, so plus left and t right. So e dot pointer, t dot pointer. Hope you understood how we have written this one, right? So on the RHS, consider, identify whether it is having any symbols or not. That means operators or not. If it is there, we have to use a make node. And for the second production, there is no operator. So simply we can write e dot pointer is equal to t dot pointer. So directly we can assign the pointer value, t dot pointer value to the e dot pointer. And the third one, again, we are having a star. So simply we can write t dot pointer is equal to, so the result of t into f. So here into is an operator. So we need to use the same thing, mk node. First one operator, next t dot pointer, next f dot pointer. And the next one, there is no operator. So simply we can write t dot pointer is equal to f dot pointer. The next one is an id. id, it's a terminal. So what we have to do, f dot pointer will be leaf node. This is a leaf node. Okay. So mk leaf, but we have to write id and entry of id on symbol table. So these are all semantic actions. These are all semantic actions. Now we will write the parse tree. Parse tree. So parse tree means, so expanding this one, right? So let us take e, which is expanded with e plus t. And now to get the multiplication, again this will be considered as t, which can be expanded as t star f, which can be considered as f, and it is id. It is id. T to f, f is id. So you can see id into id plus id. So the parse tree for this particular thing is this one. Now how to construct the syntax tree? So for everything we are using the double pointer. So double pointer means, so the pointer, the node will be having, so node or data, we can simply write it as the data, left pointer, right pointer, this one. So what we are doing, id, okay, the last one. So you can go from bottom to top, left to right. So id, so just to create one id. So this is a syntax tree. I'll write here the syntax tree. First one is a id. So id means it can be f dot pointer is equal to make dot leaf. So we can here write, so id which is null, and it is null. Why we are writing null means it is a leaf node. So the next pointers will be null automatically. And then you are having a star. Okay. So before going to star, again id is there. So again give id which is of null, left pointer, right pointer, null. So why we are taking one more id means, so here we are having an operator which can be performed on two identifiers here. So here we have written, so the address of this one is, let us take 1000 and it is at 2000, the address of this particular node. Now what we have to do, so star means you can see t dot pointer will be t dot pointer into f dot pointer. So here it will be id, so it will be 1000, the pointer f dot pointer is equal to make leaf of id of entry. So whatever the pointer it is having 1000 will be given to f dot pointer, so it is 1000. And here f dot pointer is equal to again id, so it will be a 2000. Now you can see t, so expanding this f to t, okay, the substitution of f to t, so t is equal to f, t dot pointer is equal to f dot pointer, so this is also 1000. Now you can see this t which can be applied multiplication on the 1000 node and 2000 node. So you need to draw one more node, we have to take one more node, so which is a star. So left is 1000, right is 2000. So this is a, okay, then so this will be some 3000 address. Just imagine it is an address 3000, address 3000. Now you can see expand. So e and t, relation among e and t, e dot pointer is equal to t dot pointer. So this becomes 3000. And here again one more node is there, that's a leaf node. So create one more node. It is a leaf node. So that will be a null, and here also null. It's a leaf node. So let it be some 4000 is the address. So f and id, f dot pointer is equal to make leaf of id entry id. So this will be some 4000. Next f and t relation. So t dot pointer is equal to f dot pointer. This will be also 4000. So now we have to apply the addition operation in between the 3000 and 4000. So one more node is created here, that is plus. So left pointer is 3000, right pointer is 4000. So it becomes here and this becomes here. Okay, so this is one more address, that is a 5000. So this will be the 5000. So you can see e dot pointer is equal to make node plus. So this pointer will be the e dot pointer. So this is nothing but our syntax tree. And convert this, you can convert this. So first one is plus, and left child is star, right child is id. So you can replace the ids. So the first one is 10, second one is 2, third one is 5. So star in between 10 and 2, and plus in between the result of this one and 5. And this is the syntax tree for this particular expression. And you can see the result 10 into 2, the result is 20. So 20 plus 5, it will be 25. So the same thing applies here. And you can also observe the leaf nodes are the operands or values. So 10, 2, 5, these three are leaf nodes which are operands. What about the internal nodes? That means which are not a leaf nodes. So here two nodes are there, internal nodes. One is a star and another one is a plus, which are operators. So the same points we have discussed in the starting session. Okay. So the leaf nodes will be the operands, and root node or internal nodes will be the operators. So this is the syntax tree for this particular expression, and this is the parse tree, and this is the syntax tree. So the simpler version of the parse tree will be the syntax tree. So in order to construct the syntax tree, we require the functions make node, make leaf, as well as the semantic actions, right? So hope you understood this one. It's a very simple thing. So we are using a double pointer simply for making the syntax tree construction easier. Okay, or directly you can also construct the syntax tree. So let us take one more thing. So let us take some a plus b into c plus d. So let us take this one. Okay, so you can apply star as a center, and here plus, and here a, and here b, and here again plus, this is a c and this is a d. For simpler expressions we can directly draw the syntax tree, so without using all these things. But the procedure is first write the semantic actions and then construct the parse tree, and from that construct the syntax tree by using the double pointer and simply use the operator and operands to represent the perfect syntax tree. So which is a simpler version of parse tree. So the fourth phase of a compiler, which is an intermediate code generation. So already we have seen the different phases of a compiler. So which starts with a lexical analyzer. So the output of a lexical analyzer will be the lexemes, and that will be given as an input for the second phase, that is a syntax analysis, which will be producing the parse tree. And that parse tree will be given as an input for the third phase, that is a semantic analyzer. It will check all the rules, whether the productions are perfect, that fits the program, and also type checking. Okay, also type checking will be done. So that's why we can also call it as a checker, right? And the output is a modified parse tree, or we can also say annotated parse tree. So that will be given as an input for the next phase, that is a intermediate code generator, which will be generating the intermediate code, right? So see, the first one is a lexical analyzer. So the next one is semantic checker, sorry, syntax analysis, and from semantic analysis, and the next one is a intermediate code generator. See, this is the most important phase. This is the most important phase. So why? Because so among 6 phases, we have studied about the 6 phases, right? Lexical analyzer, syntax analysis, semantic analysis, intermediate code generator, uh, uh, code optimizer, and target code generator. So in this, the first 4 phases will be considered as a front end. Okay, front end, and the last 2 phases will be called as a back end. So we'll be using these words in every concept. I mean, nowadays we are able to listen these words like front end. What is a front end? What is a back end? Like that. So front end means this is a machine independent. Machine independent. So that means this can be used in any kind of machines. For example, let us take a different operating systems like Windows operating systems, Linux, or Mac, like that, different Android. So say different operating systems will be there. So if you want to design a compiler, okay, if you want to design a compiler, so you need to use all these phases. We know, so because our subject is a compiler design. So if you want to design a compiler, you need to work out on all these phases. Then only a compiler can be designed. So coming to this front end, the same, I mean, whatever the design we are doing so far, that can be used for both all the 3. The same front end can be used for different systems. But from here, whatever the code we are generating from this intermediate code generator, that will be given to the next phase, which is a starting phase of a backend. These 2 are machine dependent. These are all machine dependent. That means, so whatever the things we have learned so far, that is a common to design the compiler for any kind of operating systems. But from here, this is depends on the machine. The 2 phases, code optimization and the target code generator, will be depending upon the machine. So that will be different for Windows, different for Linux, and different for Mac, right? So we can make use of this front end for any kind of compiler, but this back end is a crucial. So whatever the output we are getting from this intermediate code generator, that we are calling it as a intermediate code. Intermediate code. So the output, so this is the output. This is the output. Okay, the output of intermediate code generator is the intermediate code. So intermediate code, that implies it will be the bridge between the front end and the back end. So that will be the input for the first phase of a back end. So that's why we are calling it as a very crucial Okay, it's a crucial. So it will the definition of intermediate code generation is it's a fourth phase of a compiler which will convert the high level program. So the input for this lexical analyzer is high level program, or we can also call it as a source program, source code. The source code, the conversion of source code to intermediate code. So what is the, I mean, what is the output of this compiler means high level to machine code. So in between high level and a machine level, so there is a intermediate code which is the output of this intermediate code generator. Now, how many ways we can represent this intermediate code generator? Different types of intermediate code generator. Okay, so what are the types of intermediate code generator means? See, types of intermediate code generator. So I'll shortcut it as ICG. Okay, so this can be done in different ways. One is postfix notation. Postfix notation. So I think you might be studying this postfix notation in your data structures, right? And another one is three address code. Three address code we can also call it a tag. The next one is a syntax tree. And the next one is directed acyclic graph, which can be called as DAG. So these are the three different types of intermediate code generators. Okay, so these are postfix notation, three address code, syntax tree, and directed acyclic graph. So among all these four, we have already studied about this postfix notation and also the syntax tree. Now we need to focus on three address code and directed acyclic graph. So what is the next phase of this one? So the next phase of this intermediate code generator is a code optimization. Code optimization. So that means with respect to the memory, okay, and also time, space complexity and time complexity, the code can be reduced, right? So the code can be optimized. So among all these four, the best type of intermediate code generator to generate the code optimization, to make the code optimized, is this three address code. Hope you understood. There are different types of intermediate code generators. So these code generators will be generating the intermediate code, which is in between the high level and a machine code. But among these four, this three address code is perfectly suitable to generate the optimized code. So we'll be concentrating more on this one in our further classes, and also we will see what is a directed acyclic graph. Okay, so we know already the syntax tree. So reducing the memory of this syntax tree is called as a directed acyclic graph. So we know the postfix notation. So I'll give an example, simple example. So let it be a plus b into a minus b, or a plus b. See, if the expression is in this way, we know the postfix expression. What is the postfix expression? If the expression is in this way, this is an infix. Infix means the operator will be in between the operands. So postfix means the operator should be after the operands. So if a plus b, that the postfix of this particular thing will be ab plus. So you can consider this one. So ab plus and into ab plus. So just go with the priorities. Operator precedence. So in this case, operator precedence, brackets will be having the highest precedence. So first we will be converting these brackets. And now you can see already we have done, and among these, the star is having the highest precedence. So we can say ab plus star. So this will be the postfix notation for the given expression. So similarly the syntax tree, so already we have seen in the syntax tree, the operands will be the leaf nodes and operators will be the intermediate nodes. So we can say star and plus a, b plus a and b. So this is a syntax tree for this particular expression, right? So this already we have studied, and I'll post the complete compiler design playlist link in the description, so that just go through that. Okay, how to construct the syntax tree and everything. And in our further sessions, we'll focus more on first directed acyclic graph, and then we'll see what is the three address code and how we can convert this any expression in this three address code. Okay, because so this three address code is the most suitable for giving the input for the next phase, which is a code optimization, right? So these are the different types of intermediate code generators. So this is usually we can call it as a DAG, directed acyclic graph. And we know that directed graph means, first a graph means it will be having the nodes and corresponding edges. And directed means that edges will be having the direction. Okay, and acyclic means there should not be any cycles. That means if you start from one node, if you traverse all the nodes, it should not end with the same node. So that is called a cycle. So it should not contain the cycles, and it is a directed. And here the nodes in that leaf nodes, similar to our syntax tree, the leaf nodes are operands, and internal nodes. Internal nodes, that means which are not a leaf nodes, are operators. Operators. Okay. So for example, let us take here A, B, C, and D. So we can say this is a graph. Okay. Whether it is a cyclic or acyclic graph. So how to know that? So it is a undirected. Okay, it's an undirected. So undirected means if you travel from A to B, B to C, C to D, and D to A. So there is a cycle. So starting node is A, and we are traveling and we are coming to the same node. So that is that's nothing but a cycle. So it is not a acyclic graph. So if it is a directed, there will be the directions. Now you can observe. So this is a directed graph because each and every edge is having the arrow. Okay, and I mean each and every edge is having the direction, right? And also if you start with A to B and B to C, and there is no path from C to A, so this is a acyclic graph. So this is a acyclic graph. So in this we can say the leaf nodes. So we can also say a tree as a graph. Okay, so this directed acyclic graph is similar to a syntax tree. So a reduced memory of syntax tree. Okay, so we can say a tree is also a graph. A tree can also be considered as a graph. Okay, so reduced memory of a syntax tree. So how we can say the reduced memory? Main aim of this one is it will eliminate common sub-expressions and recomputational expressions. So the main reason of getting this directed acyclic graph is we can eliminate the common sub-expressions as well as recomputational expressions also, and also it will generate the optimized code. It will be used to generate optimized code. Okay, which is the next phase of a compiler. So example, in the last class we have seen an example like A plus B into A plus B. So we have drawn the syntax tree here. We have taken star on left hand side, we have given plus, and here again plus, which is A and B, A and B. So this is a syntax tree. So one thing you can observe here, this term is A plus B. This is a plus B, and this is also A plus B. You can observe here, this is also A plus B. So what happened? Here 2 times we are performing the same operation. So same expression is evaluated 2 times. So such type of things can be avoided in this directed acyclic graph. So how can we draw this one here, right? So first we'll take an expression A plus B, okay, and then you have to perform the multiplication towards the same thing. So we'll give one more node with a multiplication, and we'll be applying the same thing here. Okay, so this is a direct acyclic graph. So this portion is a plus B, which is multiplied twice. Instead of giving this one, we'll draw this one. This is a directed acyclic graph, and here you can observe there should be a direction on edges. So if we have to draw the directed graph, acyclic graph for A plus B, the plus will be the internal node and A and B will be the leaf nodes and directions towards the plus. So this implies A plus B. So for any kind of expressions we can perform this directed acyclic graph, and now we will see a few examples on how can we draw the directed acyclic graph for a few expressions. So one thing we need to remember for constructing this directed acyclic graph is operator precedence. So which operation should be performed first? Which expression should be performed first? For example, we can take A plus B into C. So in this expression, first highest precedence with a star. So first create one node for B, one node for C. So here rules are, whenever you are trying to create a new node, once check whether it already existed with the same value in the tree or not. If it exists, you can make use of that particular node, and if it doesn't exist, or if it changes the value, you can create a new node. So initially there are no nodes. I have created one node for B, one node for C, and I have created multiplication. So give the arrow marks, So this is a B into C. So which result should be further added to A? Okay, because the first operation is B into C, the result of B into C should be added to A. So I'll write a one more operator here plus, and that will be added with A. You can see. So this is a simple directed acyclic graph for the expression this one. For example, let us take one more thing, A into minus C. See, this is the expression, A into minus C. So here minus C, here we are having a two operators, one is a star and this is a unary minus. Minus C is a unary minus. So among these two operators, minus, that means the unary operators will be having the highest precedence. So first this should be given. So initially there is no node here, so we can give one node which is minus, that is a unary minus. So that should be multiplied with a A. So this should be multiplied with A. So this is the directed acyclic graph for this particular expression. So hope you understood. So for this, we need to know the operator precedence, which operator is having the highest precedence. Okay. So let us take one more example, and I'll stop. In our next session, we'll see a few more examples. So let us take this example. So A is equal to B plus C, D is equal to A minus E, F is equal to B plus C, and G is equal to F minus E. So starting with the first instruction. So initially there is no node here. Okay. We can create B and C and perform the addition operation. So I'll perform B and C. I'm creating two nodes, performing the addition operation in between them. So this is a directed acyclic graph, so you have to use a arrow marks, okay, directed arrows. And then D is equal to A minus E. So this is a, this is A, okay. So just for reference, I'm giving A, label A. So A means B plus C. So what happens? Next D is A minus E. So whatever the result we are getting with this, that should be applied in this expression. So E should be subtracted from this one. So once again, I'll use minus and I'll use E. Okay, A and E. So this is a and this is E and this is a D. Next, F is equal to B plus C. So what is a B here? B and C here. So already B and C is same. Okay, already B and C are same. And one more thing we have to remember, whether the values have been changed or not. And here you can see, so on RHS, A and D, that means B value, C values have not been changed. Okay, A value and B value and C value has not been changed. The same values we are adding and we are calling it as F. So you can give the same thing with F, label F. So A is B plus C and F is also B plus C. And G is equal to F minus E. G is equal to F minus E. So you can see F is nothing but this one minus E. So here you can say this is also G. It's also a G. So A is B plus C, F is B plus C, D is A minus E, and G is F minus E. So like this we can use, and this is a directed acyclic graph. So what we have done, we have avoided the repeated computations. Here you can see B plus C is repeated and B plus C is repeated, and here A minus E and F minus E is also same because A and F are equal. You can see A is equal to B plus C, F is equal to B plus C, A and F are equal. Okay, so here two computations are repeated. Okay, so there are repeated computations. We are avoiding that one in representing the DAG. So if you are drawing the syntax tree for every expression, we need to draw the syntax tree. So that's why we are calling the DAG is a reduced syntax tree, reduced memory of syntax tree, reduced memory of syntax tree. Okay, so hope you understood this one. Let's stop here, and in the next session, we'll see a few more examples of constructing the directed acyclic graph. So just remember directed acyclic graph, which is one type of intermediate code generator to generate the intermediate code, which gives as an input for the next phase, that is a code optimization. And this will be also useful to generate the code. And also it is a variant of syntax tree. We can also call it as a variant of syntax tree. So both are equal, but with a minimal modification. So DAG is a reduced memory of syntax tree. So variant of syntax tree. And let us take a few examples. So let us take this example, A plus B into A plus B plus A plus B. So one thing we have to remember, that is an operator precedence. So among all these operators, the operator precedence is highest for parentheses. So first we need to evaluate, or first we need to draw the directed acyclic graph for the expression which is in between the parentheses. So A plus B. So empty. So we can create a node for A and B, and which is a plus. I'll write here A, B plus. So this is a acyclic and directed graph. So A plus B, and here once again A plus B, once again A plus B. So the same values. Okay, same values. So the same will be A plus B, and again A plus B. First, after, so we need not create once again the nodes for these two expressions. Okay, the same thing can be used for these two. Now what we have to do among star and plus, this is having the highest precedence. So the star in between a plus b and a plus b, that means whatever the result we are having, so this is the result. So for this result only we need to apply the star. So what we can do, so you can apply the star here and one arrow this side and one arrow this side. So same value will be multiplied. Okay, same value a plus b multiplied a plus b, and once again then plus again a plus b plus a plus b. So what is this? You can observe. So the complete result of this expression will be added with this one. Okay, so what is the expression? So a plus b into a plus b, that is one expression. The result will be added to a plus b. So here the result is here. Once again you can use plus and that will be applied here. Sorry, the result should be applied with this one, right? This is the correct. This is the correct. Okay, so hope you understood. So first a plus b, which has been multiplied twice. So this one, which is again added with a plus b, so which is added with this result itself. So this is a directed acyclic graph. So here we are having a nodes. So the leaf nodes are the operands and internal nodes are operators, and we are also giving some arrow marks. Okay, because it's a directed. Now we'll see one more example. So these are all the expressions given, and now we need to construct the directed acyclic graph for this one. So let's start with the first statement. So b and c. So there is no node, so we can create a node for b and node for c, and the operation is multiplication. So multiplication will be done here. So this is the DAG for first one. Next, this is completed, and this is, let us give a labeling. So a is this one. Okay, a is equal to b into c, right? Next, d is equal to b. Sorry, yeah, d is equal to b. So that means whatever the b value we are giving, that should be assigned to d. So b value. So b is already there. Okay, b is already there. So the data has not been modified. So this node itself, we can treat it as a d also. Okay, d and b both are equal. Now e is equal to d into c. E is equal to d into c. So this is a d, this is a c, d into c, which is nothing but e. So e is also same. Hope you understood. So a is equal to b into c. B already created, b node was created, c node was created, and we are performing the multiplication. Now d is equal to b. So b is already there. We can make use of that particular node. So I am giving a label for d. Next, e is equal to d into c. Already d is available, c is available. So which is of a same value. So I have assigned d with b, and the same thing, d into c, which gives e. I am giving a label as e. Now b is equal to e. B is equal to e. Now b has been updated. So b has been updated. So what happens? So this value becomes b itself. Hope you understood. See, b is equal to e. What is the e value? E value is this one, right? D into c, which is equal to b. So this value is b. Now b has been updated, not this one, this one. Next, f is equal to b plus c. F is equal to b plus c. So here we should not consider this one, because in the previous statement b has been updated to e. That means b is equal to d into c. So now the b value is this one, not this one. So b plus c. F is equal to b plus c. So we can give it as plus, and again this one, b plus c. Next, g is equal to f plus d. So this is a f. This is a f. Okay. So g is equal to f plus d. F is this one and d is this one. So d has not been changed. So you can simply write it as this one. So this is a directed acyclic graph for these statements. Hope you understood. So here what we have said, before creating a node, we need to check whether the node holds the old value. So here what happens? So d is equal to b and e is equal to d into c. B is equal to e. That means the updated value has been assigned to b. Now the b value has been changed here. So in the next statement, whenever we are trying to compute the b plus c, we need to use the updated one, not the outdated one. So we are giving a branch, or we are giving a node the addition operation from this particular thing. Okay, because b is this one, not this one. So like that, we need to check whether the node, existing node, holds this previous same value or not. If it has been updated, then immediately we need to create a new node, or we need to use the updated one. Okay, so this is one more example, and we'll see one more example and we'll wind up. Okay, so let us take this example. Here also we are having the parenthesis, addition operator, subtraction operator, multiplication operator. So among all these things, which one is having the highest precedence? Obviously parentheses. So we need to create a node for parentheses, all the parentheses. So first one, this one. So what is the A and B? So initially I'm creating a nodes for A and B and performing the addition operation here. So this is the addition operation. Then C minus D. So C is not available, D is not available, and minus is also not available. So simply I will write here C D minus, C and D minus. Okay. Yes. Then A plus B. Again A and B. The values will not be changed. So A and B. Again C minus D. Done. And then we are having some multiplications and additions. So the first preference will be on multiplication. So multiplication in between A plus B and C minus D. So what we have to do? So we need to apply multiplication here. Okay, multiplication here, and also this one, right? Yeah. Then what we have to do? We need to apply the addition operation. Okay, addition operation. So the same thing, addition in this way. So this is the addition operation. Okay, so hope you understood. So A, B, this one, and C, D, this one, and this is also a repetitive. Okay, once again repetitive, and again we need to apply the addition among these two things. Okay, the same thing will be added once again. So the same thing will be added once again. So the multiplication, see, this is a one multiplication and this is one other multiplication. The same thing will be added twice. The same thing will be added twice. So hope you understood. This is a reduced version of syntax tree. It's also a variant of syntax tree. Okay, so main use is we need not recompute the same things multiple times. Here we can see A plus B and C minus D were appeared 2 times. We are not computing them 2 times. We are computing only 1 time, and we are just giving the arrow marks. That means directions towards the operators which will be performed. Right. So I'll stop here and hope you understood about the directed acyclic graph, and just practice a few more so that you'll be good at drawing this, constructing this directed acyclic graph. So one type of intermediate code generation is a 3-address code. So the compiler makes the complex instructions to a simple statements, simple instruction or statements by using this 3-address code. And also it will be used for code optimization, and easy to generate machine code from this particular 3-address code. These are all the different advantages of 3-address code, and now we'll see what exactly the 3-address code means. So here the statement should have at most 3 operands. That means the expression can have, or the expression or a statement can have either 1 operand, 2 operand, or 3 operand. That means at max only 3 operands will be there. So example, or this particular 3-address code, we can also call it as a TAC. It will be in the form as result is equal to operand 1, operator, operand 2. So the statement in 3-address code will be in the form of this one. So you can observe at most 3 operands will be there. So one is a result, operand 1 and operand 2, and this is an operator. And you can also see on the right hand side of the statement, it should have only 1 operator. Right hand side only 1 operator. So that also you need to remember. Okay, so such statements we call it as a 3-address code. So 2 points. One is at most 3 operands. The expression should have 3 operands at most, and the right hand side should have only 1 operator. See, I'll tell you an example so that you can understand more clearly. So let us take an instruction like A is equal to B plus C into D minus E. Let us take this particular expression. So it might be very simple for us, but this kind of expression will be more difficult for the machine to understand. Right? So the first evaluation will be done is a multiplication, and then addition, and then subtraction. So same order it should multiply. So such a type of complex, according to the machine, this is a complex instruction or complex expression. So what it will be to using? So it will be using some temporary variables in order to generate the 3-address code. Temporary variables will be used. So what is the first expression need to be executed? C into D. So let us take one temporary variable T naught is equal to C into D. Then addition operation. You can see T1 is equal to B plus T naught. Next, subtraction. T2 is equal to T1 minus E. Next, assignment. A is equal to T2. You can observe this is the code we can construct from this particular expression. So this is a complex expression according to the system. Okay, complex expression, and this is the 3-address code. So you can observe in any statement. So we are having at most 3 operands. First one T0 C D, only 3 operands. On right hand side only one operator, that is a multiplication. Here also T1 is equal to B plus T0. So 3 operands and only one operator on the right hand side. And here T2 T1 E, 3 operands, and right side we are having only one operator. See, A is equal to T2. So only 2 operands are there. Okay, so it will be having 3 operands and right hand side only one operator. So this is a 3-address code. 3-address code. So like this, the complex expression will be reduced into simpler statements. Now we'll see the types of 3-address codes. Types of 3-address codes. Types. So first one is an assignment. Assignment. So assignment means, so this is the last one. So A is equal to some B, which is an assignment. Right hand side value will be stored in A. And the second type is unary operator. Unary operations. Unary operations, we know A is equal to minus T1. So here T1 is one operand, so minus is a unary minus. Unary minus. And the next one is a binary. Binary means the operator can be performed on 2 operands. So simply we can say A is equal to some B plus C. So this one, all these 3 are binary statements. And the next one, conditional jump. Conditional jump. So before jumping the statement, we need to check the condition. So we know condition A greater than B, then go to some label. So based on the condition, the control will move towards this particular label. So there's a conditional jump. And the next one is an unconditional jump. Unconditional jump. So without any condition, simply we can use a go to statement and give the label, so that towards that label the control will be jump. So these are different types of 3-address codes. Assignment, unary, binary, condition, and unconditional. So you can observe in all these cases. So particularly the binary operations. So what we have said, result is equal to operand 1, operator, operand 2. So always the 3-address code will be in this particular format. Okay. Now let us see a few examples so that you will be clearly understand. Say, let us see this example. A is equal to B into C plus D divided by E minus F. So this is a complex instruction when for the machine to understand, right? So such case we need to convert into 3-address code. So here also we need to remember the operator precedence. So based upon the operator precedence, we need to assign the temporary variables. Okay. So among these, star and division are having the highest precedence. So if one expression is having this operators with the same precedence, we need to follow the associativity, which is a left to right. So in which way the execution should start? The execution should start from left to right. Left to right means first B into C. So T0 is equal to B into C. So that means temporary variable. Next, which one will be executed? Division will be executed. So T1 is equal to D divided by E. Next, addition will be executed. So T2 is equal to T0 plus T1. Next, subtraction will be done. So T3 is equal to T2 minus F. Next, assignment will be done. So A is equal to T3. So this is a 3-address code for this kind of expression. Okay. So hope you understood. Whenever you are assigning some expression to the temporary variables, you need to remember the operator precedence and associativity. So based upon that, you need to write the 3-address code. So we'll see one more example. So let us take one more example. So this is one more expression, a little bit complex because there are a lot of parentheses. So among all these operators, the first precedence will be the parenthesis. So initialize the expression to one temporary variable. So let us take t0 equal to the first one a plus b, and similarly t1 is equal to some c minus d. You need not write this one because already we have assigned some temporary variables to these two things. Now what we have to do, so you need to multiply this one. So t2 is equal to t0 into t1, t0 into t1, and similarly this is also t0 into t1. Then t3 is equal to t2 plus t2, and so this is the 3 address code for this particular expression. Okay, the same thing we are reusing. Okay, reusing, we are assigning some expression to the temporary variables and we are reusing it. So here a plus b and c minus d are repeated, so we are just giving only two temporary variables to assign both the a plus b and c minus d. And again we are performing the multiplication for these two t0 and t1, and we are assigning it to t2, and the same thing will be added twice. So t2 plus t2, that's it. Okay, and one more example, we'll see the last example. So let us see one more example. A is equal to minus b into c plus d. So here we are having a different operators. Among these, the highest precedence will be the unary minus. So this is a unary minus because the operator applied on only one operator. So unary minus is the first precedence. So let us take one temporary variable and assign this particular unary operator to this one. Next, multiplication will be done. So t1 is equal to t0 into c, and next addition will be done. t2 is equal to t1 plus d, and next assignment will be done. So a is equal to t2. So this is the 3 address code for this particular expression. Okay, and last, let us see this one also. A is equal to b plus plus. This is an increment operator. Increment operator. So the value of b will be incremented and stored in the same variable itself. So here we can see, let us take a is equal to b, and t0 is equal to b plus 1 incremented and then assigned. So t1, sorry, b is equal to, you can see, t0. So we are assigning b, and t0 is equal to b plus 1 and b is equal to t0. Okay, or else you can also write it here, t0 equal to b, t1 equal to t0 plus 1, okay, and b is equal to t1. Simple. So you can write in any one of the way. Okay, this is the 3 address code for this one. Okay, this is the increment operator, and this is a parenthesis, and this is the unary operators, and this is a complex expression. So we have seen 4 examples how we have written this 3 address code. Okay, hope you understood this one, and in our next session we'll see what are the different representations of 3 address code. So 3 address code is one type of intermediate code generation, so which will be used for code optimization, and next session we'll see the representations of this 3 address code. Representation of 3 address code. So we'll take an example and we'll see, and that mainly 3 ways we can represent this 3 address code. So one is a quadruples and triples and indirect triples. Indirect triples. So these are the 3 ways we can represent any 3 address code. So we'll take one example, then we'll see how that example, that expression can be represented using quadruples, triples, and indirect triples. This is also a very important concept. So let us take an example. A is equal to b plus c into d minus e. So let us take this example. So in our previous session already we have seen how this expression can be written in a 3 address code. So let us take among all the operators, the parenthesis will be having the highest precedence. So the first temporary variable stores the expression inside the parenthesis, and there is one more parenthesis. So t1 is equal to d minus e, and t2 is equal to, so you need to multiply these two. So t0 into t1, and a is equal to t2. So this is a 3 address code. So far we have discussed, right, in our previous sessions. So now, how can we represent this particular 3 address code using quadruples, triples, and indirect triples? So first, let us start with the quadruples. So here the name itself indicates quadruples means the 4 parameters. So here it will be using the 4 parameters. So 4 parameters. So the first one is result operator argument 1 argument 2. So here what we have discussed in our previous session, every statement will be in the form of result is equal to operator operand 1 operator operand 2. So we can call these as a arguments, argument 1 operator, argument 2 result. So if any 3 address code statement represented by using all these 4, that is called as a quadruple. So here we'll use temporary variables, and these quadruples representation will be very easy for code optimization, easier for code optimization, or we can say for machine code generation or target code generation. This is best suitable. Okay, and one disadvantage of using these quadruples means it requires more number of temporary variables, because every statement will be having the temporary variables, and so it requires more temporary variables to store the expressions. So let us see this particular 3 address code in a quadruples. So I'll erase this one and let us see. 4 parameters, that is a result, operator, argument 1, argument 2. So let us take this one. See, result, temporary variable t0, and see, this is an addition between b and c. Result t1 minus, this is a minus, subtraction, arguments d and e. Next t2, so operator is a star, t0 and t1. Next result is a, and operator is equal to argument 1 is t2, and there is no second argument. So what we have seen, so you can observe this one, this is an assignment type of this 3 address code. So in our previous session we have seen already types of 3 address codes. So in that, this is an assignment. So that statement, the 3 address code statement will be having at most 3 arguments. That means the statement can have only 1 argument or 2 arguments or 3 arguments, at most 3 arguments. So here we can have only 1 argument, and this is a hyphen, this is an empty. So if the 3 address code is represented in quadruples, this is the form. Okay, the main advantage is it is very much suitable for generating the target code, and disadvantage is, so we are using a lot of temporary variables. Right? So in order to avoid these temporary variables, we are moving towards the second category, that means second type of representation, that is a triples. So here it will be having only 3 arguments. One is a operator, argument 1 and argument 2. So I'm erasing this one. So these are quadruples. So it will be having only 3 parameters. So the first one is operator, second one is argument 1, and third one is argument 2. So what about the result? So here you can see the complete results are in temporary variables. So in this triples we are avoiding the temporary variables. So avoiding result, which mean temporary variable, a temporary variable. So we are not using any temporary variables, but instead of using the temporary variables, we are using the, so instead of temporary variable, we are going to use previous triples value or result. Whatever the result we are having previous triple, so that will be directly using in this particular thing. Okay, so here we'll be using some index. Okay, so here the advantage is no temporary variables, but disadvantage is difficult to generate target code. So when compared to the quadruples, it will be somewhat difficult to generate the target code, but there are no temporary variables. So in this case, there are no temporary variables. So let us see what are these things. Okay, I'll write here. So the first one is an index and operator, argument 1, argument 2. So let it be index 0, 0th index, operator plus, and this is B and this is C. Index 1 minus, this is D and this is E, second statement. Third index will be star, and here we are not using any temporary variables, but the result is at index 0, result is at index 1, right? First triple, second triple. So we are using the same thing. This is the first tuple and the result of second tuple. So the multiplication to be done in between the first tuple result and first triple result and second triple result. And 4, which is an operator, so which is the result of this one, the 3, and here there is nothing. So this is the representation of triples. Okay, so here we are not using any temporary variables, but instead of using the temporary variables, we are making use of the previous tuple results directly. So it will be very easy because I mean there is no temporary variables, but it is difficult to generate the target code. And there is one more representation that is called indirect tuples. Indirect triples. So here the name itself indicates indirect triples, which is similar to the concept of triples, but it maintains a pointer list of statements to the triples. So whatever the triples we are using, so one more pointer will be there. Okay, see, let us take, this is a 10, 11, 13 and 14. So it will maintain a one more pointer. So here it is a index and the statement. So 0th index 10, was first index 11, second index 13 and third index it's a 14. So one more table will be there other than the triples concept. Other than the triples, one more variable will be there. See, so 0th index, the first 10. So first statement is at 0th index. Second statement is at first index. Third statement is at second index. Fourth statement is at third index. So this particular list of pointers, this is a list of pointers, will be additional along with the triples concept. So this is an indirect triple, and this is also somewhat difficult to generate the target code. Here also there is no use of, I mean, we are not using any temporary variables, but difficult to generate the target code. Okay, so among these three, the quadruples will be easy for generating the temporary, I mean, easy for generating the target code, but it will be using the temporary variables. So hope you understood. These are all the representations of 3-address code. So 3-address code is a type of intermediate code generator, and these three are the representations of 3-address code. So hope you understood this one, and I'll stop here. In our next session, we'll see how we can write the 3-address code for conditional statements as well as iterative statements. So our program will be having both normal expressions as well as the conditional statements as well as the iterative statements. So we will see how to write the 3-address code for the conditional statements and iterative statements in our next session. 3-address code for control structures. So we can call them as a control structures. So here the control structures means conditional and iterations. So I'll write here conditional and iterations. So in both the cases, here we'll be using the two things, that is a conditional jumps and unconditional jumps, because here we are supposed to check the condition, and based upon the result of the condition, we need to go to the other steps. So in both the cases, we are writing some conditions, so there will be conditional jumps and unconditional jumps. See, we'll see. So example here, we know the conditional statements. If some a less than b, simply we can write sum is equal to sum plus 1. Okay, let us take this a simple if statement. So how it can be written? The 3-address code for this kind of things will be, write down the same thing. If a less than b, then what have to do? Go to, and in the false case again go to. And here you need to give some labels. Okay, so go to some label we need to give. So let us take L1 and here L2, and here we'll be writing L1 means, so if it is true, what happens? We need to take sum is equal to sum plus 1. So you can see this also in a 3-address code format. If it is not in a 3-address code format, we need to change it in the 3-address code format. And then go to L2 means whatever the things we will be writing here, that means else case should be writing here. So this is the 3-address code for a simple if statement. So let us take one more. If a less than b, simply write a is equal to a plus 1, else b is equal to b plus 1. So let us take this statement. Okay, so for this the 3-address code will be, if a less than b, then go to, and else go to. Okay, so here let us take L1. So I'll write L1 as a is equal to a plus 1, and here I'll be writing L2, and see L2 b is equal to b plus 1, and after a is equal to a plus 1, okay, it should not execute this one because this is a conditional, I mean if else statements. So only the true block or else block will be executed, but not both. In this case, see, if this condition is true, go to L1, that means control comes here and immediately it will execute this one. Okay, so here once again we should write one more go to statement L3 after completion of the thing. So you can now see if the condition is true, it will execute this L1, okay, and go to L3, directly it goes here. If condition is false, go to L2, directly it goes to L2 and followed by L3. So in this way, we need to write the tree address code for conditional statement. So all these are the simple conditions. Okay, so in our next session, we'll see the compound conditions, means using the logical operators. Multiple conditions will be compared using the logical operators. Such type of conditions we'll see in our next session. But as of now, if any conditional statement is given, the tree address code should be writing in this way. Okay, so hope you understood this one, right? Now we'll see the iterative statements. For example, let us take some y, a less than b, some a is equal to a plus b. Okay, let's take this one. Okay, and also a is equal to a plus 1. Let us take these statements. Now, how can we write this one? So here also the same thing. So when these statements will be get executed, whenever the condition becomes true, these statements will be executed. Whenever the statement becomes false, the condition becomes false, it will go out of the loop. The same thing we have to write here, tree address code. So if a less than b, okay, then if it is true, what should be done? These should be executed. So okay, yes, go to, and here I'll write L1. Okay, L1, what's the L1? Here we can write a is equal to a plus b. That means if a is less than b, that means if condition is true, it should execute a is equal to a plus b, as well as a is equal to a plus 1. So after this one, what should be done? So it have to again check the condition, and if the condition is true, again it will enter into the loop. Hope you understood. So in the iterative statements, so the same set of statements will be continuously executed until the condition becomes false. So every time the condition should be checked. So what happens if a less than b? That means if a condition is true, the inner statements, the statements of the body will be executed, and after completion of this execution, again the control will check the condition. So what you have to do? Again, go to, see here I'll write L1, and here I'll write L2, and here I'll write L2. So here I'll write L3. So go to L1. So this implies, so whenever this condition is true, it will execute, and again it will go to L1. So this will be repeated. And if the condition becomes false, it goes to L3. So here we can write L3. Here we can write L3. Okay, so the same thing, similarly for while loop, how we have written, in the same way we can write in the for loop also. The same code we can write in for loop for some I is equal to 0 and I less than or equal to, or simply we can write it a, and here we can write it a less than b and a plus plus. Okay, and here we can write a is equal to a plus b and a is equal to a plus 1. So the same thing we can write here also. The same code, the same tree address code can be written for this particular for loop also. Okay, so if a greater than b, go to L2. That means it comes here and it will execute all the statements, and immediately it will again go to L1. So this is called a loop. Okay, this is called as a loop. And here you can see this statement, that means condition followed by go to, it can be called as a conditional jump. Conditional jump, because we are jumping towards another location. And see, these cases, go to L3 and go to L2, go to L3 and go to L2, and these are unconditional jumps. Unconditional jumps, because here we are not using any condition, and without depending upon the condition, we are simply moving the control towards another location. So these are called as unconditional jumps. So what I said is, if you are writing the tree address code for the control structures, particularly for iterative statements and conditional statements, here we are supposed to use the jumps called conditional jumps and unconditional jumps. So here there is only one problem, that is to identify the address. Okay, L1, L2, L3. So there will be a little bit confusion among these addresses, where to jump. Okay, so for that purpose, there is one more concept called backpatching in our compiler design. So first it will fill all the details except the addresses, and later it will fill the addresses. So that will cover in our further sessions. Okay, so as of now, the tree address code means by using this conditional and unconditional jumps, and also we need to follow the rules of a tree address code. So any kind of expression should be having at most 3 variables, and right side of the expression should be having only one operator. So we need to follow the same thing. Okay, for example, if there is an expression like this, instead of a is equal to a plus b, if there is an expression called b into c plus d, so then what we have to do, we need to convert it. So t0 is equal to b into c, and t1 is equal to t0 plus d, and a is equal to t1. So this code should be written in the place of a is equal to a plus b. So like that, we need to follow the tree address code rules, and we need to write the tree address code with the help of these conditional and unconditional jumps. Okay, so hope you understood this simple concept. So how we can write the 3 address code for the control structures. So here we are once again I'm saying here we have written for only the simple conditions. So in our next session we'll see for the compound conditions. Compound conditions means whenever we are using the logical operators, so multiple simple conditions, comparing the multiple simple conditions. So that concept we call as a short circuit evaluation. So that we'll see in our further sessions. Example, so here we are having two more expressions in the condition, right? So first we need to calculate these expressions and then we have to find out the condition. So the 3 address code for this particular code snippet is, let us take a temporary variable t1 is equal to a plus b and t2 is equal to c into d. Now we need to use a condition. So if t1 less than t2, go to some L1, else go to L2. So this is a conditional jump and this is an unconditional jump. So what is the L1 here? What's the label 1? So if the condition becomes true, we need to execute this one. So x is equal to a plus b, and finally it have to skip this else statement. Again you need to write a go to some L3, and then L2, if the condition becomes false, go to L2. So what is the L2 here? So you can simply write here, so x equal to a plus b, you can replace this one a plus b with the temporary variable t1. Already we have calculated t1 is equal to a plus b, and here in the else case y is equal to c into d. So y is equal to c into d we have computed for t2, y is equal to t2 and L3, and the statements continued. So whenever this condition becomes true, it will execute x equal to a plus b and it will skip this else. So t1 less than t2, go to L1, directly goes to L1, it executes this one and go to L3, directly the control comes here L3 out of the conditional statement. And if the condition becomes false, it goes to y is equal to c into d. So if condition becomes false, go to L2, directly it comes here and it continues its sequential execution. So coming to the second one, nested if. So this is an example for the nested if. So let us write here. So if a less than b, then go to L1 and or else go to L2. Simply directly write the true case and a false case. Now label L1. So if the condition becomes true, we have to execute this one. Okay. So again in the L1 we need to execute. We need to check if c less than d, then go to L3. Go to L3, else go to L4. Label here L3. What's the L3 here? L3. What's the L3? If the condition becomes true, this should be executed. So x equal to c plus d, and after this one it have to skip this else. So we need to write a go to L2, and then L4. That means if this condition becomes false, it should execute. So x equal to c minus d, and then L2. This is a simple thing. So if this condition becomes false, what happens? It comes out of this particular thing, right? Out of this one. So if a less than b is false, go to L2, directly it comes here. If this becomes true, this statement will be executed. So go to L1, we are writing again, we are checking the condition, and if this condition becomes true, it should execute c plus d. So go to L3 label c plus d, and this else part will be skipped. So directly we are going go to L2. So the control comes here. Okay. So like this, we need to execute. Now, what about the do while? So one more example on do while statement. So here, first the statements will be executed, then at the end the condition will be checked, right? So first x equal to x plus 1, y is equal to y minus 1, and now the condition checks if y greater than 0. So let it be L1. Y greater than 0, go to L1, else go to L2. So L2 is here. So simple code, right? So first the statements will be executed even though the condition becomes false, because it is a do while, it's an exit control. So these conditions will be executed first. These statements will be executed first, then this condition becomes, this condition is checked, and if this condition becomes true, it will repeat the same statements once again to get executed. Otherwise it comes out of the loop. So go to L2. So this is out of the loop. So hope you understood these 3 examples. Now let us take one more example. Okay. So let us take one more example. This is a for loop. Okay, inside the for loop again some condition has been written. So now let us write the 3 address code for this one. So initially I is equal to 0. So this will be executed only once, and then what's the next one happens? It checks the condition. If the condition is true, it enter into the body. So it will be executed, and after that the increment will be done, and then the condition will be checked. So here we need to label 1. So remember, for all the iterative statements, either it is a while or a do while or a for, the starting statement itself we have to give the label, because it should form a loop. Okay, so L1, and if I is less than n, then go to L1, else go to L2. So we need to write here already L1 is there, L2 and L3. So let us write L2 here. If the condition is true, it will come here. So if I less than 5, simply go to Yes. So if if I is less than 5, go to L4, else go to L5. So let us take L4 here. Okay, if this condition becomes true, we need to write sum is equal to sum plus I. Okay, go to L6. Next L5, what's the L5 here? Else case. So if this condition becomes false, L5. So sum is equal to sum minus I. What happens after this? The increment should be done. So even if this is executed after this statement, increment should be done. Even if this case is executed, then also the increment should be done. So go to here, we are giving L6. L6 we can write I is equal to I plus 1, and after increment it will have to check the condition itself. What's the condition here? I less than n, so L1. So you can simply write it here, go to L1. And finally, if the condition is false, go to L3. So L3 is out of the loop. Hope you understood. So here first, so this will be executed only once, and the condition will be executed. Next, this condition will be executed. If the condition is true, this will be executed, and if this is true, this will be executed, and then increment will be done. If this is false, this will be done, and increment will be done. So in both the cases, we need to do the increment. So here, after executing this particular statement, it have to skip the else case and it have to increment. So I have skipped the else case and go to L6, which is an increment. After increment, again it have to check the condition. After increment, we are giving the control to L1. So this is how we have to write the for loop. Okay, let us see one more example of nested loops. Okay, and then we'll close. So let us take this example. This is a nested while loop. So how can we write this one? So how the execution is done? So in the same manner, we need to write the 3 address code. So let us write the 3 address code here also. First, the condition will be checked. If the condition is true, then only it will enter into the loop. So first, let us take the label, because every looping statement should start with the label itself. So L1. So if I less than 3, then let us write go to L2, else give a label L3. Okay. So what is the L2? If the condition is true, it enters, and here j is equal to 0 will be executed. Once again, this loop will be executed. So L4, we can write a one more. L3 is else case. So L4, if j less than 2, go to L5, else go to L6. So what is the L5? If this condition is also true, this should be executed. So x equal to x plus I, and then j is equal to j plus 1. Okay, after this one, again it have to check the condition. So what we have to write? Go to this condition. So j is equal to 2. So L4, this should be happens. If it is false, else, that means L6. That means if this condition is false, this one I is equal to I plus 1 should be executed. After this, the control should go to this particular condition. So here we can write go to, what is this? L1. Okay, and then simply we can write L3, which is an out of loop. For example, here let us take some a is equal to a plus b. So L3 will be a is equal to a plus b. So out of the loop. So once again we'll analyze. So first this one will be executed. So if I less than 3, go to L2. If this is true, it should start execution this one. So L2 is this one, right? J is equal to 0, and immediately once again the condition. If it is false, go to L3. So that means out of the loop here. So L3, right? This is correct. And L2, j is equal to 0, and L4, which is another condition, go to L5. So if this becomes true, it will enter into the loop. Else I should be executed. So L5 means these statements will be executed, and immediately after this one, again it have to check the condition because it's a loop. So j is equal to j less than 2, which is a L4. So we have written go to L4. If it is false, this should be executed. So go to L6. I is equal to a plus 1, and again this condition should be executed. So go to L1. So this is a loop. So you can observe this is a one loop, and this is another loop. Okay, nested loop. And immediately after that, go to L1. So it goes up, and again it will check all the things. Otherwise, go to L3. So this is how we can write the 3 address code for any kind of code snippet. Okay, so you need to know the flow of execution. If you know the flow of execution, immediately it will be very easy for you to write the 3 address code for any kind of code snippets. Okay, so hope you got a clear understanding about the 3 address code and how can we write the 3 address code for different control structures. Okay, nested loops, or conditional control structure, or iterative control structure. Short circuit evaluation for Boolean expressions. So one of the important concept. first let us know what is a Boolean expression. So Boolean results, you might be listening about the Boolean results, right? So Boolean result means the result either 1 or 0, which is called as a Boolean result. Now Boolean expression means the expression which gives the result as a 0 or 1 is called as a Boolean expression. So simply we can say A less than B. So this is an expression, right? This is an expression. So expression means the group of operands and the operator. So here we are having a 2 operands and 1 operator. So this we can call it as an expression. And what is the result of this one? Either 0 or 1. That means either false or true. So this type of expressions we can call it as a Boolean expressions. Now see, even A greater than B or B greater than C, this is also a Boolean expression, because the result of this one is either 0 or 1. The result of this one will be either 0 or 1, and the result of these two things will be OR operation. Again the result will be either 0 or 1. So this kind of things is also called as a Boolean expressions. Now what is meant by short circuit evaluation of Boolean expression? So this particular short circuit evaluation can be done for logical AND and logical OR operations, particularly for the logical AND and logical operations. Okay, so this short circuit expressions can be done for logical AND operation, so which can be represented with the 2 ampersands, and another one is logical OR operation, so which is a parallel lines. Okay, this short circuit evaluation, both are Boolean expressions. Okay, see, let us take this one first. Let us take this one. If I am writing a small syntax, so A greater than B and A greater than C. Let us take this one. Okay, let us take this one. So the complete result of this expression, so we can call this as a Boolean expression. Okay, because the result will be either 0 or 1. So the complete result of this one will be either 0 or 1. So this result depends upon the first expression and the second expression. Let us take this one as a Boolean expression 1 and Boolean expression 2. Okay, and the result between B1 and B2 will be either 0 or 1. So the result of B1 will be again 0 or 1, and again the result of B2 will be either 0 or 1, and you need to apply AND operation for these two things, which gives 0 or 1. So that you understood. Now see, what is the property of AND? What is the property of AND? So this logical AND, if the two operands are true, then only the result will be true. Okay, so you can write the truth table. Okay, for better understanding, I'm writing the truth table. So the input will be true, 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 false, false, true, and false, false. So this is for AND. This is for AND. So what is the result of this one? So if both are true, it will be true. True, false, it's false. False, true, it's false. False. So you can see, if one of the input is false, the result is false. If one of the input is false, the result is false. Now, if B1 is false, the result will be false. If B2 is false, the result will be false. Now, what is meant by short circuit evaluation? That means, if you compute this B1, if the result of B1 is 0, that means if it is false, okay, if it is false, you see, if any one of the input is false, the result is false. So if the input of B1 is false, I mean the output of B1 is false, you need not compute the B2, because one is false among these two, the result will be false. So the result will be always false. If the B1 result is 1, now the result depends upon B2. So B2 should be computed, because if B2 is 1, the result will be 1. If B2 is false, the result will be false. So the complete result of this expression, this kind of expression, the complete result of this kind of expression depends on B1. If B1 is false, B2 can't be computed. If B1 is true, then only B2 can be computed. So if B1 is false, B2 need not be computed or evaluated. If B1 is true, so B2 should be computed. That means evaluated. So this is called as a short circuit evaluation. So here logically, and that evaluation always done from left to right. So this thing can be evaluated from left to right. So in both the cases, AND and OR. So this explanation is completely with the logical AND, and the same thing applies for logical OR also. See, I'll give you. If it is a logical OR. So the same thing, if you write A greater than B or A greater than C. Okay, so this is a B1 and this is a B2. So what's it? Okay, once again I'll write here OR operation. So T, F, T, F, and F, and the result will be true, 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 false. So you can observe here, if any one of the input is true, the result becomes true. If both the inputs are false, then the result is false. Here, if B1 is true, then automatically you need not compute B2, so the result will be true. Okay, and if B1 is false, then B2 should be computed, because the result of whole expression will be depending upon this one. Okay, if B1 is false, the whole expression will be depending upon the result of B2. So if B2 is true, the result will be true, and if it is false, the result will be false. Okay, so mainly this kind of thing we call it as a short circuit evaluation. It always done with a left to right, and it will be evaluated for logical AND and logical OR, particularly logical AND and logical OR. So it depends upon the first expression, and the result of, based on the result of first expression, the second expression will be evaluated. Okay, now we will see one example, and we will write the 3 address code for this particular short circuit evaluation by using the short circuit evaluation. Okay, so example, for both cases we can see. So I'll write the same thing. If A greater than B and A greater than C, let us take some x equal to 0 and else x equal to 1. So let us take this example, the three address code for this one. Okay, the 3 address code for this one will be, so this is not an iterative statement, so you need not start with a label. So first check this particular expression. If A greater than B, if A greater than B, if it is true, this can't be executed. Okay, this can't be computed, need not be computed, directly you can go here. So simply write go to L1. If it is false, then it should be executed. Okay, if it is false, it should be executed. So simply you can go to L2. Okay, go to L2. So here you can write L1. Okay, L1 as, go to L1 means x equal to 0. Okay, and again go to some L4 and L2. What is a L2? If this is false, it should be computed, because if it is true, okay, if it is true, I'm extremely sorry, if it is true, then it should be evaluated. Okay, it should be evaluated. If it is false, the complete expression is a false, right? So if it is true, then go to L1. L1 will be this, it should be computed here. Okay, if A greater than C, okay, go to L3, else go to L2. So what is a L2? If this is false, the complete expression is false, so automatically it should be executed. L2 is x equal to 1. Okay, so what is a L3? If this becomes true, okay, this becomes true, go to L2. Here it is L3, right? If this is also true, yes, sorry. Yeah, go to L2, and L3 means if this is true and this is true. Okay, this is true and this is true, then x equal to 0. Simply you can skip the else part. So go to L4. Go to L4. And here also, if it is false, then yes, this one. Okay, I'll write here. You can write here L2 x equal to 1. L4, right? Simply. So you can see once again, just think A greater than B. If it is true, then you need to evaluate this one. So go to L1. L1 it will be evaluated, and if it is also true, this should be executed. Go to L3. So here, and immediately after this, it should skip, and it will be L4. So directly it comes here out of the conditional statements. And if it is false, so directly this should be executed, and L4 here. So directly it comes here. If it is true, okay, and if it is false, and here also it is L4, directly it comes here. Yes. So this is a simple 3 address code for this particular short circuit evaluation of a conditional statement and logical OR. So hope you understood. Okay. Now same thing we can apply for OR. So here there will be a lot of confusion among giving the labels. Okay, So as of now, just try to understand this one, and these kind of problems we can solve by using one more concept called a backpatching. So that we'll see in our further session. Okay, how can we manage the labels for a conditional and unconditional jumps? Okay, yes. So for this example, let us take if A greater than B, if it is true, what should be executed? This cannot be evaluated directly. This can be done, right? So go to L1. Okay, go to L1. And if it is false, If it is false, okay, it should be executed. So once again we can write if a greater than c, if it is a false, this will be executed, right? So if it is true, again go to L1, go to L1. If it is false, go to L2. So what is a L1 here? L1 means if this is true, or means if any one of the input is true, the result will be true. So this should be executed. So x equal to 0, and L2, and it should skip this one. So here once again we need to give a label. I'll wait for the label. And if this is false, this will be executed because this is a false case. So if it is also false, go to L2. That means this one, x equal to 1, x equal to 1. So immediately we can write L3. So go to L3. Okay, simple. So if you understand the flow control of, the control flow of execution, so simply you can write the 3 address code for all these things. So once again, let us check whether it is right or wrong. So if this is true, this is OR, so you need not compute this one, directly this will be executed. So if a greater than b, if it is true, go to L1, L1 is x equal to 0, and you need to skip this and come out from this one. So we are writing go to L3, so directly it comes here. And if it is false, this should be computed. So if this is false, this should be computed. So again, if a greater than c, go to L1. That means if this is true, okay, this case means a greater than b is false and a greater than c is true, then go to L1. So same thing. If again this is also false, go to L2. That means this part will be executed. Go to L2 and directly L3, right? So this is the short circuit evaluation for Boolean expressions. So mainly this short circuit evaluations will be applied for logical AND and logical OR, because here we are comparing two different Boolean expressions. So the result will depends upon either one of the Boolean expressions. Okay, so this is the 3 address code generated for the simple Boolean expression here. So backpatching. So it is a technique in a compiler to generate code with placeholders. That means it will leave some blanks to give correct address in jumping instructions, jumps that may be both conditional and unconditional. So here let us take an example. So if a greater than b, some x equal to 0, else y is equal to 0, right? So let us take this example. And what is the 3 address code we have written? So if a greater than b, if it is true, we are simply saying here go to some statement, some label. So here what happens means in backpatching, it will leave some placeholder in order to fill that with a correct address later. Okay, later, this is important. And if it is false, go to another. If a, yeah, see, let us write here the address is 100 and this is 101. Okay, address 101, and it will be x equal to 0, 102, and go to dash, and this is 103, and 104 is y equal to 0 and 105. Okay, so these are the steps. Actually we have studied the representation of 3 address code, right? Representation of 3 address code in quadruples, triples, and indirect triples. So whatever the lines we are writing here, everything will be stored in that particular table. So among the 3, we have studied that quadruples will be the best suitable for generating the 3 address code, right? So using some temporary variables. Okay, so every line will be there in the quadruples, so it will be retrieving one line after another. So here you can see if a greater than b, what should be executed? X equal to 0 should be executed. So where we have written x equal to 0 here, so the address of this one is 102, so you can fill this one later. And if it is false, it should move on with the y equal to 0. Okay, it should move on with y is equal to 0. So y is equal to 0 address is 104, so it will fill 104. And after completion of this one, 102, x equal to 0, it should not execute these statements, it should skip this one. So immediately it should go to 105, so it will be 105. Okay, so like this, the 3 address code will be generated first, leaving the place to give the correct address of a jumps later. Okay, so this is called as a backpatching. So already previous sessions we have seen, we have experienced a lot of confusion. So regarding the addresses, we have given some labels L1, L2, L3 and so on. So while writing the instruction itself, it seems it will be difficult to write the label unless you know the address. So this is a solution for that particular thing. So here the code is very simple, so we can simply write it, but when compared to the large and complex expressions, Boolean expressions, so that will be different. There will be more number of conditional jumps and unconditional jumps, so that will be very difficult until you know the addresses of that particular statements. Okay, so this is called a backpatching, and before applying this backpatching into the code, so we will see there will be a two list should be maintained. So one is a true list, another one is a false list. See, this backpatching will also be suitable for the short circuit evaluation, that means a complex instructions or complex expressions. So true list will be maintaining all the list of instructions to jump if the condition is true, and this is a list of instructions. This is a list of instructions to jump if the condition is false. So for every expression it will be maintaining two lists, one is a true list and false list. So this will be represented as TL and this will be represented as FL, TL and FL. For every Boolean expression there will be TL and FL. So which statements should be executed, which statement should be, I mean when the condition becomes true, and which statement should be executed when the condition becomes false. And apart from these two lists, there will be three more functions mainly it will be used. So functions, one is a make list. Make list is a function, okay, which will create a list, and merge function, merge, so B1 and B2, so two conditions, so it will combines the two list. And next one is a backpatch, so B and a target. So what should be executed if B? Okay, so look at correct address. So these three functions are very important in the concept of backpatching. Now by using these three functions, let us see the translation rules. Okay, so before applying this to our example, so you need to know the translation rules. So the translation rules, let us see. So first one, B implies B1 ampersand M B2. So M is nothing but a instruction that to be executed before B2. Okay, starting of the instruction. So let us take it as a starting of the instruction. So we know the short circuit evaluation. For example, B1 is a one conditional expression and B2 is another conditional expression. So if B1 is true, so this is an end operation. End operation means if any one of the input, if any one of the output is false, the result will be false. So if B1 is true, then only it start, the B2 will be started. Okay, that is a M. B2 will be started. And if B1 is false, what happens? Whole expression will be false. Whole expression is false. Whole expression will be false. So here you can see backpatch, the backpatch function. Okay, backpatch function for this particular thing. So if B1 dot true list, that means B1 dot true list means the true list contains B1, that means the Boolean expression is true. So when B1 is true, then it start M. That means M is a starting address of B2. For example, let us consider. So M will be the thing. And see, for every expression there will be two lists. Just now we have seen. So B dot true list and B dot false list. True list and false list. So when this B dot true list will become true list, this is a true, when becomes this B becomes true if B2 is true. So if B2 is in true list, automatically B1 will be true, because until and unless B1 is true, B2 will not be get executed. So if B1 is false, B2 will not be computed. Okay, automatically that comes end. So whenever, I mean when the B becomes true, the Boolean expression becomes true whenever B2 becomes true. Okay, and whenever B false, when the B becomes false, the Boolean expression becomes false. Either B1 is false or B2 is false. So it will be merge function. If B1 is in false list, B2 is in false list. Anything. If anyone is in the false list, automatically the result will be false. whenever the B2 is true, immediately the B becomes true. Okay, so this is the first thing, which is a end operation. And the second one, so you need to remember these three things. Okay, so these things will be useful while drawing the annotated parse tree for any example. Okay, so just remember this one. And the second rule, B1 or MB2, the same thing. Okay, previously we have seen the end operation, and now we are seeing the end OR operation. OR operation means if B1 is false, then B2 will be started, because if any one of the input is true, automatically the result will becomes true. So if B1 becomes false, it have to check whether B2 is true or not. So if B1 is false, B2 will be started. If B1 is true, you need not compute the B2, because B1 is already true, the result will be true. So B1 is false, sorry, here B1 is true, the whole expression will be true. Hope you understood. And here backpatch, B1 is in a false list, then M will be started. And when the B dot false list comes, if B2 is in a false list, and when it will be true, either so merge, either B1 is in true list or B2 is in true list. Hope you understood. So if any one of the thing is in a true list, automatically that will be true. If B2 is false, so when the B2 is computed, if B1 is false, then only B2 will be computed. So whenever B2 becomes in a false list, automatically B becomes a false, the result will be false. So this is the second one, translation rule. And the third one, B tends to not B1, not. So obviously if when the B becomes a true, if B1 becomes false list, because it's a not. If it is true, the result will be false. If it is false, the result will be true. Similarly, when it will be false list, whenever it is in true list, whenever the B1 is in true list, the result will be false. And the next one, B tends to B1. So when this is similar to assignment, okay, when the B becomes in a true list, if B1 is also in true list, automatically the result is B true list. When it will be in false list, whenever the B1 is in false list, automatically that will be. So like this, there will be a lot of translation rules. Okay, there are a lot of translation rules, but these are very important for any Boolean expression. So we are talking about the Boolean expressions. So Boolean expressions means this one, right? So in our previous session also, we have seen the short circuit evaluation just for logical AND and logical OR. That becomes more complex. Okay, if the condition is having the logical operations, that expression becomes complex to write the code. So for that purpose, we are doing this translation rules. These are the translation rules. So before applying the backpatching or before going to the examples, you need to learn all these translation rules. Okay, so these rules will be applied for generating the annotated parse tree of any kind of example. So one thing remember, so in our last session we have seen the 3 address code will be represented in a quadruples for code optimization. So every address will be stored in a quadruples. So one after another it will be it will be evaluated. Okay, so I'll stop here. Just remember all these rules, translation rules and functions. So in our next session we'll see one example, and we will generate the code, and later we will give the addresses, and later with the help of all these translation rules we will draw the annotated parse tree. So backpatching. So let us take an example. So before going to the example, let us see the 2 translation rules mainly. So one is B1 ampersand B2. So where we will be writing the backpatch function for this. So backpatch. So when the backpatch, whenever the B1 is in true list, then immediately the next instruction will be started. So we can simply write it as a MB2. So M is a initial instruction of B2. Similarly, B dot. So let us take this one. B dot true list will be when this becomes true, whenever the B2 dot will be in the true list. B2 will be in the true list. And B dot false list, when it will be false. So merge function, if one among these two, that means B1 is in false list or B2 is in false list. If any one of these condition is false, automatically the result will be false. And one more thing, B tends to B1 or B2 backpatch function, which gives the address, perfect address. So if B2 is in if B1 is in false list, then the next instruction will be executed, because if any one of the function is, output is true, the result will be true. and when it will be in the true list, if any one is true, then automatically it is true. So it is b dot true list. Merge b1 dot true list, similarly b2 dot true list. If any one among these two is true, the result will be true. And when it will be false, so whenever the b2 is false, then automatically it will be false. So when the b2 will be executed, if b1 is false, then only b2 will be executed. So that we have seen in the short circuit evaluation. I post the link in the description. So go through all those things. Now let us take an example: a less than b and c less than d. This is a logical expression, right? Logical expression. As we've seen, these kind of logical expressions will be more complex for a system, right, to generate the operations. So 3 address code. So let us write: if a less than b, simply go to. So we don't know where to go, so we need to give a placeholder. So let us take the address of this one is 100 and 101. So if it is false, then go to. Next 102 address. So this one, if c less than d, go to. Else, go to. So here we are not giving the addresses, just giving the placeholders. So 104 is a true statements, and 105 it will be the false statements. So what are the statements we can write here? Okay, so now you can write, you can fill up the blanks, okay, giving the correct address. So whenever this becomes true, you need not sorry, this is an AND operation. If it is true, then this should be evaluated. Okay, this should be evaluated. So what is the address of c? That is 102. So if it is true, immediately the control should execute this c less than d. If it is false, what happens? So the complete expression is false. You need not compute this one, because if any one of the output is false, the result will be false. So a less than b is false, go to directly 105. And here, if this is true, 1 or 2, the control comes here. And if this is also true, then it goes to 104. And if this is false, if any one of the output is false, the result will be false, so directly goes to 105. So this is the 3 address code for this particular thing. So now we have to generate the annotated parse tree. So simply we can write a b. So b can be divided. So this is a b1, and this is the operation here. What's the operation here? End operation. And let us take m as a starting instruction of the second b2, and this is a b2. So what is a b1? So b1, which is a less than b, c less than d. So what we have said, so for every node, for every expression, there will be true list and false list. So you can write here, so b1 dot true list, similarly b1 dot false list. Here also b2 dot true list, b2 dot false list. And here also we have to find out b dot true list, b dot false list. So how we can fill this one? So b1 dot true list, where the address where it has started, the true list started. So a less than b have started here. So 100 is the statement, true list statement, and false list is 101. So if it is true, it goes to 102, the starting of the instruction. So m will be 102. So the starting instruction of the next condition. And here b2 started, true list is 102 and false list is 103. Okay, hope you understood. This is the address where the true statement is written. So here this is the true statement written, because here we are writing the go to statement, right? So this is the true statement of b1. This is the false statement of b1. This is the true statement of b2, false statements of b2. Here we have written. Now how we can write when the b becomes true? So b means complete. So this is a b. Okay, this is a b1 and this is a b2. So when the b becomes true, so you can apply this rule. So when the b becomes true, whenever b2 dot true list is true, then automatically b becomes true. So here b2 dot true list, so that means 102. Simply you can find out and you can write it. And when the b becomes false list is equal to merge b1 dot false list, b2 dot false list. b1 dot false list is 101, b2 dot false list is 103. So you can observe here, see b1 dot true list 102. So whenever this becomes true, then automatically it comes with a true statement, because when this executed, whenever a less than b is true, then only it will be evaluated. If a less than b is false, it will not be evaluated. So the complete true of this particular expression depends upon b2. So 102. And false, when it will become false, even a less than b is false, the result is false. C is less than d is false, result is false. So 101, if it is false, it will be false. 103, if it is false, it will be false. So 105 is false. Okay, like this we need to construct the annotated parse tree. So hope you understood this one. So let us make it a much complex. Okay, we'll see one more example with a few complex things. see, I will write complete this one, and I'll give R and E less than F. E less than F. Okay. Now see, 104 it will be if E less than F, go to, and this is another go to, and 106 it is a true, and 107 it will be a false. So here there are placeholders. We need to fill all these placeholders. Okay. So this is complete in the, sub expression, right? So this will be one expression, and if this is true, the result will be true. If this is false, the complete expression is false. This will becomes executed. I mean, it will be executed. So if A less than B, if it is true, automatically it have to check this one, right? C less than D. So it will be 102. If it is false, okay, if it is false, this complete expression is false. This should be executed. So it goes to 104 now. Hope you understood. If this becomes false, this complete expression is false. If it is false, the result of B will be depending upon this one. So let us rename this one. So this as a B1 and this as a B2. Okay, and this will be B11 and this will be B12. Okay, now if this is true, it will execute 102. So if it comes here, if it is also true, what happens? It directly goes to 6 because this expression B1 becomes true. So if B1 is true, B2 need not be executed because it is a OR function, right? So this will be directly moving on to this. If it is false, again this should be executed because this expression will be false. So if B12 is false, this complete expression is false. So the value of B depends upon B2. So it start executing B2. So here it will be 104. Now if this happens, okay, when the control executes B2 means whenever B1 is false, then only B2 will be executed. So if it is true, then automatically this will be true, and if it is false, this will be false. So this is the complete generation of 3 address code for this example. Okay, hope you understood. So we need to remember the short circuit evaluation while filling up all these addresses. Now let us give the annotated parse tree for that. So let it be B1. So this is a B1 OR operation, and this will be M1. So which is a this one, right? And this is a B2. Now B1 again having, so this is a B11, and this is an AND operation, this is a M2, and this is a 1-2. So this is again A less than B, C less than D, E less than F. So we need to fill all these things. Okay, we need to fill all these things. So I'll write here B11 dot true list. Similarly, B11 dot false list. Similarly, B12 dot true list, B12 dot false list. Similarly, B2 dot true list, B2 dot false list. Okay, now where it has been started B1 A less than B, so it is 100. 100 is a true list, and false list is 101. So if this becomes false, if this becomes true, it will start executing C less than D. So that means 102. So the first instruction of next one is a 102. So everything will be retrieved from the quadruples. So we have seen the representation of 3 address code quadruples, right? From that, what is the next instruction will be taken from that. Okay, this is 102, and B12 dot true list starts at 102, and false list is 103 here, false list. And coming to this B2 means E less than F, 104 and 105. So this is 104 and 105, this one. Okay, now we need to write B1 dot true list and B1 dot false list. I'll write here. So B1 dot true list, what is this? And B1 dot false list, what is this? So based upon the translation rules, see here. So B1 means end operation. End operation means this one. B1 dot true list will be B2 dot true list. So B1 dot true list will be B2 dot true list. That means this one. So 102. What about the false list? Match B1 dot false list and B2 dot false list. B1 dot false list is 101 and false list is 103. Okay, and similarly, now we got a B1 dot false list, B1 dot true list. Now we need to find out B dot true list, B dot false list. Okay, so what is the B dot false list, true list and B dot false list? Here we need to apply this one or this one. Okay, because B1 or B2. So B1 or B2. So or means here we need to write true list is merge. If any one of the statement is true, the result is true, the result will be true, right? So merge, we need to merge B1 dot true list and B2 dot true list. So 102, 104. So here we need to write 102, 104. So this is the thing. And false list is B2 dot false list. Whenever the B2 becomes false. So if the control executing B2 means that implies B1 becomes false. So it totally depends upon the B2. Right? B2 dot false list. We need to write only the B2 dot false list, which is 0, 1, 0, you can see 105, so which is a false, and 102 and 104, so which is a true statements. 102 and 104, these are the true statements. So we need to construct the parse tree with the help of these translation rules, and first we need to give the addresses, and then you need to draw the parse tree, and you need to fill the true list and false list. Hope you understood. True list, we are maintaining true list and false list, and we are using the three functions mainly. One is a create list, backpatch, and merge. Backpatch means which instruction should be executed next, and merge means combining two lists, true list and false list. So I'll post the link of this translation rules in the comment section and also in the description. So go through that so that you'll be understanding these translation rules. If you understand the translation rules, then only you can easily construct or generate the tree address code as well as construct the annotated parse tree. Issues in designing code generator. So the first issue is, so this is the next phase of intermediate code generators. So we are having some intermediate representation of the code. So first we will start from the source code, and now we are at the intermediate representation of source code. And our next, the next output and the next generator is the code generator. See, the first design issue is input for the code generator. Input for code generator. So already we know what is the input for code generator. So the first one is a tree address code. So actually we can call it as a intermediate representation. So we have studied about the intermediate representation. The code can be represented in different ways. That is a postfix notation, tree address code, syntax tree, as well as a directed acyclic graph. So there are a lot of representations. Among that, we are saying this tree address code will be the optimized one to generate the code, okay, target code. So the first input is a tree address code, and also the symbol table. So in our first sessions of compiler design, we have seen the complete phases of compiler design. In that, the two things are common for each and every phase, that is a symbol table and error handling. Okay, so these two are the inputs for the code generator, and if this tree address code is not correctly written, automatically that will be reflected on the code generator. So the tree address code representation is most important. And the second one is a target machine instructions. So here we are generating the code for a target machine. So the different machines will be having a different architectural styles. Okay, so whether it is a RISC instructions or CISC instructions, so reduced instruction set or complex instruction set. So we need to focus on this one. So whether the target machine is having the following the reduced instruction or the complex instruction. So based upon this, the code should be generated. And the third one is a memory management. So we know that there will be different kinds of memories. So in that we'll be using a normal memory, similarly heap memory, and the registers. Okay, so our source code will be using a different identifiers, functions, etc. So which should be stored in which memory. Okay, so that should be very careful, because the accessing should also be very fast. Okay, so when compared to this one, we know that registers are very fast to access. So when we have to use the registers and what kind of variables we can store into the registers, so that we need to focus before generating the code. Next, register allocation and assignment. Register allocation. So we know that when compared to the memory, registers will be very less in size but very fast accessing. Okay, so less in size, fast in access. So we need to, and also the registers are limited. The registers will be in a limited number. So we need to take care which variables should be assigned to the registers and which variables should be allocated in the memory. So in order to get the fast access. So usage of registers. Because these are less in size, fast in access, and also limited number of registers will be available. And the next one, instruction selection. So as we discussed it just now, the target machine will be having a different architectures. So which kind of instructions should be selected? For example, so let us take, if you want to implement this one, a is equal to b plus c. Okay, so you can implement this one by using simple add instruction, add a comma b comma c. Okay, and the same thing, see this kind of instruction, if you are using this kind of instruction, we can use add a comma b. So here we are using 3 addresses instructions, and here we are using 2 addresses instructions. So this we are calling it as reduced instructions and complex instructions. Okay, so if it is a complex instructions, the number of instructions will be reduced. If it is a reduced instructions, that means simple instructions, number of instructions should be more. So the selection of instruction should be based upon the target machine. So we need to take care about that. Next, instruction ordering. Instruction ordering means here we need to reduce unnecessary load and store operations. So if you want to perform the same thing, a is equal to b plus c, so what we can do, so we can use a load operation, load, we can load b to register 1 and load c to register 2, and then we can add r1 comma r2. So the same thing can be written as, so load a comma r1, sorry, here we can write it a b comma r1, and load, or simply add c comma r1. So whatever the result we are having in r1, so for that c will be added, and now store the result r1. So here some sort of reduction is there here. So we have to remove the unnecessary load and store operations. We need to reduce the number of operations, the number of instructions. Okay, so that is the instruction ordering, which instruction should be implemented so that unnecessary instructions can be removed. Next, handling control flow. This is the most important in our source code, because the control structures means the if statements, if else statements, similarly while loop, for loop. So in all these cases we are using Boolean expressions. So the result of these Boolean expressions will be either true or false. So that means we need to give the addresses. So unconditional and conditional jumps we are using in this. So we need to give an appropriate and correct addresses to in the jump instructions. So if the condition becomes true, so the control should go towards which address. Okay, we need to give that appropriate and correct address. So that is the thing, handling the control flow, control structure. Okay, that is most important. And the next one, code optimization. So this is also very important, because every code should be written in a optimized results, which we should give the optimized results. So here we need to reduce the number of memory or in terms of time also. So in this case, let us see an example. Let us take 2 instructions, like t1 is equal to a plus 0 and t2 is equal to t1. So this can be reduced, because we know that this instruction is completely not required, because if you add anything to 0, that will be the same value. The value doesn't change if you add with the 0, right? So we can remove this one and directly we can write t2 is equal to a. So you need not compute this step, and again you need not compute this step. So directly you can write t2 is equal to a. So in such case we can optimize the code. Okay, so this is also one design issue we need to concentrate while generating the code. Okay, next, handling data types. So we know there will be a lot of data types. Okay, so the type conversion will be done. So sometimes the implicit conversion will be done, and sometimes the explicit conversion will be done. So we need to take care about that thing also, right? So for example, let us take a is equal to some 5 and b is equal to some 2.5. So you know this is an integer value and this is a float value, and if you want to perform the addition on these two, c is equal to a plus b, so what is the data type of c? So if the data type of c is a float, obviously there will be a type conversion of a, type conversion on a. So there will be a type conversion, because the data type of a is integer, so e integer should be converted into float and then it will be added into the p. And if c is in an integer, c is declared in integer, then automatically some sort of data will be lost, because the result will be in integer itself. So some data will be lost. So there will be a lot of issues here. So we need to take care about of all these data types, whether the data types are properly defined or not. Okay, next, calling conventions. calling conventions. So calling conventions means mainly this is used in functions concept. So we'll be writing a lot of user-defined functions in our programming. So while you write the user-defined functions, what happens whenever the control executes the function call, the address of that particular thing will be moved into the stack. Okay, and then the control will move towards the function definition, and after completion of function definition, again the control will resume its execution by getting the value from the stack, by pop the value from the stack. So whatever what is the value available in the stack, that is an address, so that will be popped and the control will move towards that particular address. So the moving of calling function to called function and called function to calling function, as well as giving the input parameters from the calling function to called function, and so that is most important, and that should be taken care while designing the code generator. So the parameters, if there are any parameters, that should also be moved into the function definition. So how they can be moved, where they can be stored, everything comes here in the calling conventions. And the next one is error handling. Error handling. So this is the most important thing. So this is the output of any phase we have seen. So we have seen the lexical analyzer, semantic analysis, and syntax analysis, intermediate code generator, target code generator, and code optimizer. So these are all different phases of a compiler which we have studied in our earlier sessions. And one input for everything is a symbol table, and one common output from all these stages is an error handler. So because in each and every phase, whenever there is an error, automatically that error should be reflected. So this error handling means identifying and reporting the errors. So if there are any error occurred, automatically that should be reported, and these errors we call them as a syntax errors. So we have studied in our programming language, the syntax errors are identified by the compiler. So whenever the code was not written properly, so then immediately the syntax error will be raised. Okay, the error will be raised, and that will be called as a syntax error. So all these are the issues need to be concentrated while generating the code, target code. Okay, so this is the last but one phase in the compiler design. So the input for this one is the intermediate representation, that can be either 3-address code, syntax tree, direct acyclic graph, or the postfix notation, anything, but we are representing an intermediate, 3-address code as an intermediate code. First we will see the basic blocks. So very simple and important concept. So here a block represents a group of statements. Okay, so here a block means sequence of statements. So consider any program. So in that program we need to form a different blocks. That means we need to group a number of statements. So with a few constraints. So what is the constraints means? Every block should have single entry point. That means the control should enter from the beginning only, and single exit point. That means the control should leave the block only at the end of the statement, and no branching in the block except at end of block. That means, so what we are saying, block here, sequence of statements. Among these sequence of statements, so there should no branching in between the statements except the end of the block. So for example, if there are 4 statements in a block, so there should be only one entry and only one exit. Only one entry, one exit, and in between no branch. But here one clause, except the last statements. That means end of the block. So this end of the statement can be a block. Can be a branching, but in between there should not branching. So we need to create a blocks by following these characteristics: single entry, single exit, as well as no branching in the block except at the end of a block. And this will be mainly used for code optimization. So the code optimization also specifically local optimization, because we are saying a block, so local optimization, only local optimization. So it will also give the structure of a program. So we'll take one example and I'll show you how to prepare the blocks. So far hope you understood this one. So you need to remember only these 3 points: single entry, single exit, and no branching in the block except at the end of a block. Yes, now we will see what is the procedure to form a block for a given example. So I'll write the procedure, then we'll see an example, right? So procedure to form blocks, you can call it as an algorithm also. Okay, so only 2 steps will be there. Step 1, what's the step 1? Identify leaders. So first we need to identify the leaders in the program. Now what is the leader? Okay, which statement we can call it as a leader? So this leaders means the first one, the starting statement. The starting statement can be considered as a leader, the starting statement of a block, okay, of a program, not a block, because so we are having only a program. Now we are trying to divide that program into blocks. So the first step is identify the leaders. So in this, the first one whom we are considering as a leader means first statement. Next, target of jumping statements, either it can be conditional jumps or unconditional jumps. So target of a jump statement, so if you are writing any branching, so we are supposed to write a jump statement. So jump L1 or L2 will be giving some labels. So those targets, whenever the control executes the jump statement to where the control moves, so that statement will be the leaders. And then third one, immediate statement after jump. Immediate statement after jump. So these 3 things we can consider as a leaders. So we'll be identifying the leaders. That's the first step in order to form a blocks. Okay, hope you understood. Next, step 2. So what we have to do in a step 2? Now the actual thing, form blocks. So we need to divide into a blocks. So with some constraints. First one, so every leader is starting statement of a block. The first one is every leader is a starting statement of a block. Next, so all the statements until the next leader forms a block. Okay, only two steps. Two steps. Every leader is a starting statement of a block, and the second one, all the statements from the current leader to the next leader. Okay, just before the next leader. Okay, until we can write it here, just before next leader forms a block. Okay, so these 2 are the steps. One is identify the leaders. A leader can be a starting statement, target of jump, and immediate statements after jump. And step 2, form the blocks. By following this one, every leader will be the starting statement of a block, and all the statements until the just before the leader forms a block. Now we will see an example and we'll form the blocks. Okay, so let us take an example, a simple example. So let us take this example. So I is equal to 1, sum is equal to 0. If I greater than 5, go to L2. Sum is equal to sum plus I, and I is equal to I plus 1, go to L1. And L1 is if I less than or equal to 5, go to 4, the line 4, and print sum is a L2. So this is a program, and we have given some numbering. Okay, so we need to form a block for this particular example. First step, identify the leaders. So I am writing here identify, or simply we can write leaders. What are the leaders? So what's the thing? Starting statement is a leader. So here I will be writing the line 1 is a leader. Starting statement means line 1. Target of jumps. So here where are the jumps? Here it is jump. Go to L2. What is the target? L2. What is L2? Line 8. So line 8 is another leader. And any other jump? Yes. Here again it is jump. Go to L1. So line 7 is also leader. Next, here also we are having go to 4. So what is the target? Go to 4. So line 4 is also a leader. See, first one is a starting statement. Second one means target of jumps, means L2. Here it is a 1, go to second. Okay, so go to L2. L2 means line 8. L2 means line 8. Okay, next, here also one more. Go to L1. L1 means line 7. go to 4. 4 means line 4. So these are all the leaders. Next, immediate statement after jump. Immediate statement after jump. So let us see, there are 3 jumps here. First one, so immediate statement means line 4. Already we have written here. Okay, see, immediate statement after jump. So here it is a jump. Immediate statement is line 4. Yes, we have written already. And here line 6 is a jump. Immediate statement will be line 7. Already we have written. And here one more jumping statement. Immediate is line 8. Already we have written. Okay, 1, 8, 7, 4. So you can rearrange the order like line 1, line 4, line 7, line 8. Okay, hope you understood. So there are 4 leaders here. That's the first step. Now we need to identify. Once again, we will repeat. Starting statement, that is a line 1. Target of jumps means L2, line 8. Next, L1, go to L1, line 7. Next, go to 4, line 4. Yes. Immediate statement after jump. After jump, line 4, already written. Immediate after 6, 7, already written. 8, already written. Yes. Now we need to form the blocks. Blocks. Okay. So what we have said, every leader, starting statement of a block. Every leader. So line 1 is a leader. Similarly, line 2 is a leader. Line, sorry, not 2, it's a 4. Line 4, line 7, and line 8. Now, so we need to continue the statements until just before the next leader. What is the next leader? Line 4. So line 1, line 2, line 3. Because next leader is line 4, just before the line leader we need to stop. Line 4, the next leader is line 7. So line 4, line 5, line 6, line 7, line 7. The next letter is line 8. So only one statement here. Line 8 is the last statement, and here also it is. So how many blocks we have formed? 4 blocks. So let us represent it as B1, B2, B3, and B4. So instead of writing line 1, it's better to write the programming concept. So what is a line 1? What is a line 2? What is a line 3? Similarly, line 4, line 5, line 6, and line 7, and line 8. Okay. Now I'll erase this one. So here we have created a blocks. Okay, we have created a blocks. Hope you understood this one. So I'll write here B1. What is the line 1? I is equal to 1. Sum is equal to 0. And if I greater than 5, go to L2. So this is a one block. Okay. Next. B2, line 4, sum is equal to sum plus I is equal to I plus 1, go to L1. This is a B2. What's a B3? B3 is a line 7. If I less than or equal to 5, go to 4. Next B4, print sum. So these are all different blocks. Okay, so this is how we are framing the blocks. Okay, so I'm just, yes. Now we will see what is a flow graph. Hope you understood about the basic blocks. This is the building of basic blocks. Okay, generation of basic blocks. Next, a flow graph. Flow graph means, a graph means it will be having a nodes, edges. So nodes represents blocks and edges represents connection between these blocks. That means a flow, control flow. And this connection can be sequential, conditional, or unconditional. Anything it can be. Okay, the relation between one block and another block. Okay, different blocks. So here, in order to create a flow graph, we need to remember the 3 things. Okay, so if block doesn't have branch, connect to next block. Similarly, if block have conditional jump, then we need to give true and false connections. So two paths will be there, true and false. And if block have unconditional jump, connect to target, directly target. Okay, there will be no true and false, so only one thing. So example, I'll tell you. So if you observe the line 3, so here we are having a condition and we are giving a jump. So this is a conditional jump. So it will be having either true or false. Okay, two paths. And coming to this line 6, here you can observe, go to L1. So here there is no condition, this is an unconditional jump. So directly we have to go to the target, that means L1. Okay, so this is the procedure to give a connection to flow graph of blocks. So this complete flow graph is connecting the blocks. Okay, and this will be used for global optimization. Okay, it will give the control flow and also the global optimization. So it shows control flow, and it is used in global optimization. Okay, now instead of writing everything, I'll be writing B1, B2, B3, B4, 4 nodes. Okay, now you need to observe these 3 things: branch, conditional jump, and unconditional jump. So doesn't have a branch, have the conditional jump and unconditional jump. So observe B1 is having, doesn't have a branch. No, it is having a branch. You can observe B1, it is having a conditional jump. So if it is a conditional jump, we need to connect true and false. So if this condition true, go to L2. So where is the L2? L2 means print sum. So this is a L2. This is a L2. Okay, and L1. So this is a L1. So if condition is true, go to L2. L2 is in B4. So if condition is true, it should go to L2. Okay, if it is false, it should go to next further. So if it is false, it continues the statement. So this is the case, false case. Now B2. So B2, there is a conditional jump. Unconditional jump. Directly go to L1. What is L1? B3. So there will be a direct connection to this one. It's not a true or false. Okay. Next B3. It's again conditional. So if it is true, go to 4. Where is the 4th line? It is in B2. If condition is true, it goes to B2. So this is a true path. And if it is false, it goes to B4. It is a false case. So this is the flow graph for these blocks. Okay, now hope you understood. So first one, mainly these building blocks, blocks and flow graphs, basic blocks and flow graphs are mainly used for code optimization and better generation of machine code. Okay, so 2 things. One is forming the blocks and then connecting these blocks. So forming the blocks, we need to find the leaders and then we need to form the blocks. And coming to the connecting the blocks, we need to check whether each and every block is having either conditional or unconditional, or it doesn't have any branch. If it doesn't have any branch, then it will be a sequential. If it is having any conditional statements, then it will be a conditional flow. So that there will be a true and false cases. And if it is an unconditional jump, there will be no true and false. Directly you need to connect to the next one. The target one, target block. Okay. So this is how we need to construct a basic blocks, form the basic blocks and construct the flow graphs. So code optimization means how the code is efficiently developed. So in terms of both the memory and also time complexity. So the main reason is, so fast execution. The execution will be very fast and it will reduce the memory usage. Okay, reduce the memory. So this is a time complexity and a space complexity. You might be learning about these 2 things, time complexity and space complexity. Time means fast execution, within a very less time we need to get the result, and the space complexity, we need to use the variables or memory very efficiently. That means we can reduce the memory usage, and also if these 2 things happens, automatically the efficiency will be improved. So it improves the efficiency. So in order to achieve all these things, the target code should be optimized. Okay, so we'll see what are the optimization techniques. Okay, so when the code will be optimized and how the execution becomes fast and how the memory will be reduced. Okay, so we'll see the optimization techniques, so which we need to take care to generate the optimized code. So optimization techniques. The most important thing, the first technique is algebraic expression. So we need to take care about all these expressions, algebraic expressions. So we need to simplify this one. We need to simplify the algebraic expressions. So example, we know a simple algebraic thing, anything multiplied with 0 will be getting 0 as a result, and anything addition with a 0 will give the same content. So we can replace these things by eliminate these terms. So we can avoid the multiplication, we can avoid the addition. Instead of that, we can directly take the result as 0 and a in this case. So we can simplify the algebraic expressions. Okay. Next, common subexpression elimination. So we need to eliminate the common subexpressions. So the reusability we need to add. Okay, so we need not compute the same thing multiple times. Okay, so we can remove such type of subexpressions. So the same thing we have learned in directed acyclic graph, DAG. Okay, so let us take some a is equal to b plus c, and there is a one more expression called d is equal to b plus c. Okay, so here you can observe b and c has been added here to get a result of a, and once again we are adding the same variables and we are storing the result into d. That means the addition operation between b and c has been duplicated multiple times. We are computing the same thing. So instead of this, what we can write, we can compute only once b plus c and store the result in a, and then same store the a value in d. So instead of recomputing this b plus c, we can use the variable where stores the result of b plus c here. So these kind of things we can eliminate. So common subexpressions can be eliminated. Next, constant folding. Constant folding. So here we can evaluate some computations in compile time. Evaluate expressions in compile time itself. So we know the compile time and runtime. Okay, for example, you can see some a is equal to b plus c. If the same expression we need to compute, then the result will be depending upon b value and c value. So usually we are writing the program where we are reading the values of b and c during runtime. We are using some scanf in C language, right? So unless you use a scanf, we can't know the values of b and c. Okay, that's called a runtime. Runtime, we are taking the inputs. So this we can't do anything. So we need to take the inputs and we need to compute the addition. But if the same thing happens in this manner, 5 plus 6. So here what happens? Here we are not taking any variables. We are taking directly values, 5 and 6. So in order to perform the addition between 5 and 6, we need not wait till the runtime. So during the compile time itself, we can compute and we can store the result. So this can be done at a compile time. So during the compile time, some sort of expressions, so these kind of expressions can be evaluated and we can replace this as a is equal to 11. So this is called as a constant folding. Constant folding. Next, similar, constant propagation. Constant propagation. So here substitute the values. Substitute the values. Already whatever the values, we know that those values can be substituted here. Okay, so for example, take a is equal to 5 and b is equal to some a plus 6. So what we can do, so these type of expressions can also be calculated at compile time. Okay, so because here you can observe this expression. So the addition is dependent on variable a, where the variable a is having the value 5. Already here 5 is there. So automatically the result can be stored as a is equal to 11. So this can also be computed at a compile time. So this is also one form of constant folding itself. Okay, we are supposed to substitute the values in the variables. And next, copy propagation. Copy propagation. So here the copy propagation means, and you can see some a is equal to, this is also similar to our constant propagation, but here what we have to do is, if it is a is equal to some 5 and b is equal to some a plus c. Okay, So in this case, what we are doing, so we are just copying. So here you can replace this with b is equal to 5 plus c. We can simply copy this constant to this particular variable and we can replace the statement in this way. So these kind of things we call it as a peephole optimization. Peephole optimization. So whatever the things we have seen, constant propagation, copy propagation, or constant folding, all these three can be considered as a peephole optimization. So reducing the instructions to make the computation in a faster manner. So in here also, instead of writing this one directly, we are replacing it with this one, and here we are just replacing the variables, and here we are copying the constant to the variable. So all these three comes under the peephole optimization. So reducing the number of instructions by making with the instruction which executes faster. Okay, so that's a peephole optimization. So I'll write here reducing multiple instructions with one instruction which executes faster. So multiple instructions can be reduced with only one instruction. Okay, one or very two instructions. So reduction of instructions, that's a peephole optimization. And the next one is a dead code elimination. So this is also most important. Dead code elimination. Dead code means if we are having a multiple instructions and if one instruction is not being used so far, or then for the further instructions, so simply we can eliminate that particular instruction. So for example, let us take some a is equal to 5 and we are calculating c is equal to some 10 plus 4, and we are simply writing printf %d c. So what happens here in this code? So c is already computed and we are just printing the value of c. So where we are using this a value? So a value is not used in the program, but we are using the variable. We have declared some variables and we are initializing that variable with some value which is not used in the program. So this is called as a dead code. So these kind of instructions should be eliminated. So if you use all these techniques, automatically the code will be optimized. Okay, so first one, algebraic expressions. So simplifying the algebraic expressions, and then common sub expressions should be eliminated, and constant foldings, constant propagation, copy propagation, which we call them as a peephole optimization, as well as the dead code elimination. So we need to follow all these things to make the code optimized. Okay, so let us see a small example so that you can understand all these techniques. So let us take this example. So if our code is having these many instructions, we can reduce these instructions by using the techniques so far we have discussed. So these instructions can be written in the same way, a is equal to b plus c. And coming to the second one, already b plus c is evaluated and it was stored in a, so we can reuse that one. So this can be written as d is equal to a. And see here, this is simplifying the algebraic expressions. So anything plus 0 will be the same variable. So it can be written as e is equal to d. And here anything is multiplied with 1, that will become the same number. So f is equal to e into 1. So whatever the number it may be, the value will be 1 itself. So f is equal to e. And here, so this is a constant folding. So this can be evaluated during the compile time itself. So g is equal to, it can be written as 8. And here we are having, we can copy the variables. So h is equal to 8 plus f. So this is optimized. This is optimized by using all the techniques which we have seen, right? And next, it can also be simplified, right? More optimized. We can also make this more optimized. You can observe here, more optimized. So which is the first statement, a is equal to b plus c. And what we are doing, a is stored in d, and d is stored in e, and e is stored in f. Okay, e is stored in f. So obviously, what happens? So f consists of e only. F consists of a value only. Okay, f consists of a value. So if a is 4, you can see d is equal to 4. So e is equal to d means e is equal to 4. Yeah, e is equal to 4 means f is equal to 4. So that means a is equal to 4 means here f is equal to a. So that can be replaced in this one, right? So second one, h is equal to 8 plus, what we can write? Instead of f, we can write it as a. So the entire instructions can be written in only 2 instructions. Okay, which makes it faster. So this is also called as a peephole optimization. So we are reducing the multiple instructions and making only a few instructions which will execute faster. So this is called as a peephole optimization. And here you can see whatever the techniques we have so far learned. So we have used everything to reduce the code. Okay, so these many instructions can be written in a simple 2 instructions. So this is an optimized code. So hope you understood what is a code optimization and why we are using this code optimization. So in order to make the execution fast and reduce the memory, and which improves the efficiency. The 3 points are most important. So this is an algorithm which generates the code for the target machine. Simple code generator algorithm. So we need to follow some rules, and see, this is a code generator. The name here specifies generates target code from a simple 3 address code, because so the output of previous phase, that is the intermediate code generator phase, is the 3 address code. So that will be giving input for the code generator. So for the target code, we are taking the 3 address code as an input and we are generating the code. So here mainly the 2 things are very important for this simple code generator algorithm. So one is register descriptor, and another one is address descriptor. So these 2 things will be used in our simple code generator algorithm in order to know the memory of the variables which are being used in our 3 address code, right? So where the values have been stored, either in the registers or in the memory. So here the register descriptor, the name itself indicates, it will be keep track of variables which are being stored in registers. So we know that register is a one sort of memory with a limited size and a fast access. But the main limitation of the using of registers is very limited number of registers will be available. So this register descriptor will be keep tracking of the variables which are being stored in registers. So some variables will be residing in the registers and some variables will be residing in the memory. Okay, so whatever the variables which are being stored in the registers will be tracking by the register descriptor. And coming to the address descriptor, keeps track of location where the value of variable are stored. So the location where the variables will be stored. Here the term location. So here the location can be either register or memory. Okay, so this is completely register, but here this address descriptor keeps tracks of location, so the variable can be either in the register or in the memory. So these 2 things will be used in generating this target code by taking 3 address code as an input. Okay, so in order to save the time, I'll write the steps here of this particular algorithm and I will explain the steps, and then we will see a simple example. So this is a 3 steps, mainly the 3 steps involved in the simple code generator algorithm. So what we are saying, so what is the input for this code generator algorithm is a 3 address code, and we have studied that the 3 address code statement will be having at most 3 addresses, that means 3 operands. So any 3 address code statement will be in this format: A is equal to B operator C. So here every statement operator will be represented in a target language operator. Okay, there will be a separate target language. Okay, so here we'll be calling it as a plus. Okay, so that can be represented as add in this instruction. Similarly, minus can be represented as a sub. Similarly, multiplication can be represented as a mul. Okay, and assignment. So assignment operator, that means is equal to, can be represented as a load. So like this, so every operator in the statement will be having the corresponding target language operator. So these are called the target language operators. So these are all operators which are available in this statement. So we need to use all these things in order to represent the target code generator. So what's the first step? So here we are saying there is a 2 descriptors, address descriptor as well as a register descriptor. Register descriptor will be having it will keep track of all the registers where the variables have been stored, right? So here first we will be invoking a function called get registers. So we need to know whether the registers are available to store the variables or not, because for example let us consider we need to perform the operation like A is equal to B plus C. Okay, we need to perform this operation, so we need to store these variables, okay, into the registers or some memory. So for that we need to find, because why we are selecting only the registers means here by using the registers there will be a very fast accessing. Okay, so for that purpose we are going with the registers rather than the memory. Okay, so here first step is get register function should be called, so that it will be used for identifying whether there are any available registers or not. So if there are any available registers, there will be no problem, we can make use of those registers, and if the registers are not available, automatically we need to find whether there are any variables stored in the registers which are not available, I mean which are not in a use. So if such variables are there, you can just switch that variable values from the registers to the memory, and we can use those registers. So see, invoke the get register to determine the location where B operator C should be stored. That means, so here we need to perform B plus C. So we need to find the location, so where the result is to be stored. That can be either memory or thing. So this will be performed in a location. So we need to find out that location by using get register function. So this location can be either a register or memory. Anything it can be, right? Anything it can be. But the first preference will be with the register because of fast access. Next, step 2. So if value of B is not in L, so here L is the result. You can see this is the thing. Okay, so where the operation has been stored. So if value of B is not in L, right? So B is the first operand in the statement. If B is not available in that L, what we have to do? So we need to generate the move function. So we need to move the value of B to the register. Okay, so if already B is available in L, you need not use this one. Okay, you can skip. And if B is available in both location, that means available in both address and memory and register, you need to consider the register only. Okay, so if the value of B is not in L, generate move B comma L. So move B comma L means, so B will be stored in L. Okay, L is the location. Next, generate the instruction operator C comma L. C is the second operand. So here in this example, what we are using, this is a addition. Okay, now what we have to do, we need to add second operand, that is a C comma L. So always remember, if you use this one, so this will be the destination where the value has been stored. Okay, so this implies B value is stored in L. The second parameter or second operand is the target operand where the result is stored. For example, if you use add C comma L, so already L is having B. Okay, in the previous step, B is stored in L. So whatever the value available in L, that will be added with this C, and the result is stored in L itself because this is the destination. Okay, so we need to perform operator C comma L, operator C comma L, and immediately you need to update the address and register descriptors. So which register, that means the register, I mean the way which variables are stored in the registers and which variables are stored in the addresses. So here we are maintaining two descriptors, register descriptor as well as the address descriptor. We need to update them. Okay, and next, if these values B and C values are not in next use, immediately you need to again update the register descriptor and the address descriptor, and we make it ready to switch to the memory because some other variables can be stored in the register because the registers are limited, only limited, but the access will be very fast. Okay, so these are the main steps involved in this code generator algorithm. So first we need to find the location where the operation should be computed, and the second, if B is not in L, so here there is an option, if B is in L, we can make use of that one. If B is not in L, we need to move that value to the L because we need to find the register, empty register. Okay, and we need to move it. If the register is not empty, so we need to find the variables or the registers which are having the variables which are not in use. So such type of variables we need to move into the memory, and we have to make the registers available for the operations. So if B is not in L, generate move B comma L. We need to move the B to the location. And next, generate the instruction operator C comma L. So actual operation will be done, and we need to update both address registers and the register address descriptor and register descriptors. Okay, so hope you understood the 3 steps. So just remember these 3 steps. We'll see one example and we'll understand. See, let us say take these examples. So these are the statements. So we need to generate a code for these statements. So first we can see all these are a 3 address code based statement because every statement is having at most 3 operands. Okay, so we need to generate the code here. So initially, just imagine the register descriptor is having the registers, all the registers are empty. Okay, there is no variable stored in the registers. So actually that doesn't happen because number of processes will be running in the computer. So obviously the registers will be occupied with some values itself. But here in this example, let us assume that, imagine all the registers are empty. All registers empty. So here how many variables are there? So that many memory addresses will be there, and initially all the variables are stored in the memory itself. Okay, so here A, comma B, comma C, comma D, E, F. So all these resides in the memory. Let us consider M as a memory. Okay, M as a memory, and registers are empty. There are no values or variables stored in the register. Right, now coming to the first statement. So we have seen all the registers are empty. Now what we have to do? So invoke get register to determine the location L where B operator C should be stored. So here registers are empty, so we can get the register, one register. Now if value of B is not in L, so let us take R naught. Okay, R naught is a register. So B is not available in the register because all the registers are empty. What we have to do? Move this second operand to L. So we need to write move the second operand B to R naught. So we are moving the value of B to R naught. Okay, what happens? Immediately generate the instruction operator C comma L. So now R naught is having a B. Next we need to apply the operator. What is the operator? Addition. So you can simply write add the operand C comma R naught. So already R naught is having a value of B. So that will be added with C, and the result is in R naught. Okay, hope you understood. The result is in R naught. So here the result is in R naught means what is the result here? A. So what is the value available in register R naught? It is A. Now in a memory, the rest of the variables will be residing in the memory. Hope you understood, right? So here add C comma R naught. R naught is having B. C comma B. Addition of C comma B will be stored in A. So here the result is stored in R naught. So R naught is having the value of A. So this happens here. Okay. So I'll write here E is equal to A plus F. D is equal to D minus B. Okay. So now you can see D. Check whether D is available. So first check whether register. So the next register is available, and initially the register is empty. So we have to do move, because move the first operand to register. So move here D to R1. Okay. Next immediately we need to apply the operator. So here subtraction. So sub what is this? B with R1. So we are subtracting B with R1, and the result is stored in R1. So R1 consists of, previously R0 is having the A, and now R1 consists of the result D. So except that one, the remaining variables are available in memory itself. Now the third one, similarly. Okay. So E is equal to A plus F. A is already available in R0. Okay. F is a new thing. So what we have to do? So we can simply move R0 to R2, another register. We are moving just a variable to another register, and addition. So add F to R2. F to R2. Add F to R2. So we should not use the same thing for addition. So we are not using this one, because we add simply F to R0. Okay, F to R0, because the value of A will be overwritten. So now R0 will be having E, not A. Okay, so we should not write this. We are using one more register, that is R2. So we are moving R0 value to R2, and we are adding F with R2. So now you can see R0 is having A, R1 is having a D, R2 is having E. Okay, here the code is generated, and here C, D, and F. Sorry, here also D is there. So B, comma C, comma E, comma F. Here also B, comma C, comma F will be in a memory. Now what happens? So in the reverse process, now R0 is having a value of A, R1 is having a value of D, R2 is having a value of E. But when coming to this one, the result should be stored in A, the result of this statement should be stored in D, not in registers. The result of this value should be stored in E. So simply we can use a move operations, move R0 value to A, move R1 value to D, move R2 value to E. Okay, so here you are just finally you are storing the results to from the registers to variables A, D, E. So if you use here R0, F comma R0, A value will be overwritten. So the value can't be stored in A here. Okay, so that's why we are using one more register here. So we need to take care about all these things. So this is how we can generate the target code from the 3 address code statements. So here this is a simple example. So any kind of expression, first we need to convert into a 3 address code and then use this code generator, register descriptor and address descriptors to update the variables and to generate the code. So this is a code generator, and we are at every step we are updating the register descriptors and address descriptors. Okay, so here not only the memory, here we need to use this one also, a in register. So here we need to write a comma d in registers, because here we are using a location. Address register means location, right? So here also we need to write a comma d comma e will be in registers. Okay, so that should be updated. So these two should be updated for each and every step. Symbol table. As I said, it is an input for all phases. For all phases of a compiler. So 6 phases we have studied. So for all phases, the common input is a symbol table. So here the name itself indicates table. Table means it stores some information. So what kind of information? So this symbol table, it is a data structure used to store, update, and retrieve the information. So table means storing the information of identifiers in a program. So the complete information about the identifiers will be stored in the symbol table. So now what comes under this identifier? Okay, I hope everyone know that, but I'll recall it. So what comes with the identifier? So all user defined names given for programming elements. So in our programming, while we are writing the program, so whatever the thing we are giving out a user defined names, that comes under the this identifiers. So example, variables. So for variables we are supposed to give the name. Okay, so we know the rules to be followed while giving the name. But variables, that means user gives the name for a variables. Similarly, constants, so user will give the constant names. Next, function names. So even the user defined function also will be supposed to give the names. Similarly, classes, coming to the object oriented programming, objects, etc. So like that, for any programming element, if the user gives the name, that comes under this identifier. So the keywords, operators, such type of symbols, those will not come under the identifier. So this symbol table will be storing the information regarding all these things, only the identifiers. Now we'll see what are the fields of a symbol table. That means what kind of information we'll store regarding this identifier. Hope you understood this introduction. So information or entries of a symbol table. So the first one is a name of an identifier. So for every identifier there will be one name. Okay, so that name will be stored here. So it can be a variable or a constant or a function or classes or objects, any kind of the identifier, the name should be given. And also some identifier will be having the values. So if you consider any variables or constants, definitely that will be having the values. So the next entry is a value. Next, type. So the data type. So if comes with the functions, so the return types. If comes with the variables and constants, the data type. Next, scope. So where it can be used. Okay, in which part it can be used, the scope. Memory. So where it is saved, the location. Okay, and line number. So line number in the program. So in a program, in which line the information, the identifier information, I mean the identifier belongs to, right? So declared. And function information. So function information means it will be having some parameters. Okay, so parameters, return types. So all that information comes under this function. Okay, and also storage classes. So there are different storage classes like auto, extern, register, right, static. So it also gives the storage class, what storage class it is. So it doesn't mean that for every identifier the complete information, all the entries will be there. consider one variable, a variable or a constant. So a constant can have a name, value, type, scope, memory, line number. There is no function, storage class. Okay, so like that, depends upon the identifier, the information will be stored. So for example, let us take int a is equal to 10, main function, int x equal to 20, float y is equal to 3.5. For example, let us consider this code. So the symbol table will be having name, type, value, memory, line number, storage class, or you can also consider scope. I'll write it. Okay, so scope, line number, etc., etc. So for example, name is a, type, it is an integer, value, it is a 10, scope, so it was declared above the main function, so the scope will be global. Okay, global. Line number, so let us take the line numbers. So what's the line number? It was declared at 1. Next, x, it is of integer, value is 20, scope, so within the local, so local scope within the function, and line number, it's a 4. Similarly, if you use a storage class, what is the storage class? Extern. Here it will be extern, here it will be auto. Okay, this here also auto. So like that, every information will be stored here. Why? So it is a float, it's a 3.5, and this is also local, and the line number is 5. So these are different entries. Okay, like this, the storage table will be stored. I mean, the information about the identifiers will be stored in this storage, in the symbol table. So this is called as a symbol table. So here the symbol, it seems those are the identifiers. Those are the identifiers. Now, whatever the operations that can be performed on this particular symbol table. Operations that can be performed. Okay, what kind of operations that can be performed? Operations. So initially the symbol table will be empty. So we need to insert the new entries. So the first one, insert operation can be done. So it will insert the identifier information into the symbol table. Next, after insertion, so we can retrieve the data. So lookup means searching the entries, searching the variables, and then update. So sometimes the value of the variables can be updated. So then it should be updated in the symbol table also. Next, after completion of the scope, it will be removed. So delete operation. So operations that can be performed on a symbol table are insert, lookup, update, and delete. Okay. Now, how many ways we can implement this symbol table? So implementation steps, implementation types. How many types we can be implemented? So it can be implemented by using hash tables. So different data structures that can implement the symbol table, right? Hash tables. Similarly, linked list, and then trees. Sometimes the trees. So in these 3 ways also, the data, I mean the symbol table can be implemented. Okay. So we have seen what are the entries of a symbol table and example, and then what are the operations that can be performed on a symbol table, and how many ways, what are the different data structures that can implement the symbol table. Now we will see what is the importance of symbol table in each and every phase. So we have studied around 6 phases. So in each and every phase, what is the importance of that symbol table? So role of symbol table. So what is the first phase? It is a lexical analyzer. So in that lexical analyzer, so symbol table will be empty. So entries will be done. So all the initial entries of identifiers will be done. Because in this lexical analyzer, the complete program will be divided into different tokens. So in that, the tokens will be considered as a lexemes, right? We have studied that one. So initial entries of identifiers will be done in the symbol table. So this is the role of a symbol table for this lexical analyzer. Next, syntax analysis. In the syntax analysis, so it will update the structure and relationship of the identifiers. Update structure and shifts. So it will update the complete structure and relationships of our identifiers. So that is the role of a symbol table in syntax analysis. And coming to the semantic analysis. The role of this symbol table is a type checking. So it will check all the type checking information. So whether all the variables has been declared or not. So if there are any variables which are undeclared, so then immediately some syntax error will be raised. Next, intermediate code generator. Intermediate code generator. So in this phase, the symbol table will be used to generate the address calculation. Okay, so the role of this symbol table is used for calculating the address calculation for identifiers. Okay, next, code optimization. So we have discussed about this code optimization means in order to reduce the delay, that means making fast the execution time and reduce the variable usage. Okay, so the role of symbol table in code optimization is efficient usage of identifiers, particularly the variables and the constants, efficient usage. And the last one is a target code generation. And in this target code generation, this particular symbol table is used for mapping and generating the instructions. So what is the final step? That is the generation of instructions for a target machine, right? So target machine. So mapping and generation of target instructions is the role of symbol table in target code generation. So I think you remember the phases of a compiler. So we have written all these phases. And right side of this one will be the symbol table. So it will be the input for every phase. This will be input for every phase. And here also we have written one thing, that is error handling. So if any error occur in any one of these phases, automatically some error will be raised by the compiler, that we are calling it as a syntax error. So this is a most important in a compiler designing. So that is a symbol table, which is a common input for every phase of a compiler. So finally we can say the symbol table stores and updates the information regarding the identifiers. So storage, organization. So here the name itself indicates storage organization means it is completely related with the memory. Okay, so that deals with how the memory was structured, and used to store programming elements. So I am generalizing this one, programming elements in the sense everything of a program. Okay, so we are going to use different variables, constants, and also local variables, global variables, static variables, okay, dynamic variables, any kind of the thing, right? So all these comes under this programming elements. So how the memory was structured and used to store the programming elements during program execution. So program execution. So what we are calling program execution means this is a runtime environment. Okay, runtime environment. So now the complete memory is divided into 4 parts. The first one is code segment, data segment, stack, and a heap. See, the complete memory is divided into 4 categories. So code segment, data segment, stack, and heap. Okay, so whatever the variables and whatever the programming elements we are going to use, everything will be stored in these 4 divisions. Okay, so coming to the code segment, what kind of things will be stored in the code segment? So here the name itself indicates is a code. So all the compiled instructions, so whatever the instruction that is being compiled, all those compiled instructions will be stored in this code segment. So compiled instruction in the sense, we are supposed, for example, let us take a C language. So we are supposed to write the main function. So whatever the instructions written in main function, okay, and in the main function, if you are using any user defined function called add, so whatever the statements of add, we are going to use some predefined functions like printf, scanf. So printf statements, scanf statements, etc., whatnot, all the compiled instructions will be stored in this code segment. Okay, and coming to the data segment, in this data segment, okay, all the static variables and global variables which are being declared in the program will be stored in this one. So static variables and global variables. Static variables and global variables. Apart from these, it will also store all initialized data and uninitialized data also. You might be knowing about this initialized data and uninitialized data. For example, if you consider int a, so this statement is just a declaration of variable a. So what is the value of a? So a, we have not initialized any value, so this is an uninitialized variable. And what is the value of a means a garbage value. So for example, int b is equal to 20. So here both the declaration and initialization was there. So we have initialized some value to the variable. So the value of b will be 20. So these kind of variables can also be stored in the data segment. That means both the static variables and the global variables. Consider static and global variables. That too initialized or uninitialized data will be stored in the data segment. Coming to the stack. So working of functions, the function call. So whatever the parameters given in the function call, everything function call as well as a local variables, So these two will be stored in the stack, because see, for example, we say that we are writing some main function here. And after some instructions I have written some add, one more function and some other functions. And here we are writing the function definition. What happens here? So the control will always start execution from the main function. So it will start the sequential execution, and whenever the control executes this add, immediately the address will be stored in the stack. So the address of add will be stored in the stack, and immediately it doesn't move to the next instruction, it moves to the function definition, and here it will start again executing in a sequential manner. So whenever there is a return or this closed curly brace, immediately it will pop the address from the stack, and it will again go back to the position from where it came here. So this is the position address of add, right? So this happens. So this is the use of a stack. That means that whenever there is a function, so the information will be stored in the stack itself. Similarly, whatever the local variables we are using, those local variables are also used in the stack. So whenever there is a function call, immediately it will create one activation record, and that activation record will be pushed into the stack. So usually we are saying that some address will be stored in the stack, but that's not the thing. Activation record will be pushed into the stack. So in that activation record, the address will be there. So we'll see about the activation record in our further session. Okay. So mainly the function call and the local variables will be stored in the stack. And coming to the heap, all the dynamic allocation variables. So whatever the variables that are allocated dynamically. So we might be knowing the dynamic memory allocations like malloc, calloc, and realloc. So usually we will be allocating the memory during the runtime, okay, by using either malloc or calloc. So those kind of variables will be stored in this heap. Okay. So these are the four data segments which are being used to store the different programming elements during the program execution. Okay, so hope you understood this one. I will quickly, I'll give you one example and I'll close it. Okay, so I'll write the example here itself so that you can understand. So I'll write some int a is equal to 10. Int a is equal to 10, and I'll write a main function here. Main function. Int b is equal to 20, and some add a comma b, and int star p is equal to int star malloc function. So I'm not writing the syntax, malloc function. So I'll, and then close, and again add int x comma int y, int z is equal to x plus y. So I'm writing this one, right? So hope you understood this program. So int a is equal to 10, and inside the main function int b is equal to 20. So I'm giving parameters. I'm passing the parameters to the add function a comma b, and I have taken one pointer variable. So it was declared here, and I'm giving the size here, size of int. Okay. So I'm not writing the complete thing, but I have used some malloc function to create a memory, allocate the memory to the variable, and in the function definition I'm taking two variables here. See, main function instructions, add function instructions will be stored in the code segment. Okay, main function, add function. And in the data segment, so what's this data segment? Static variables, global variables. So A is in a data segment. A is stored in the data segment because A is a global variable. And coming to the stack, function call and local variables. What is the function call? This add is a function call. So add will be stored here, as well as the local variables. Here the local variable is B. So here the local variable is B, and here you can see X, Y also local variables, and even Z is also a local variable. And add, everything will be stored in the stack. Both function as well as the local variables. And coming to the P, which is a malloc function, which where the address, the memory is allocated using the malloc function. So P will be stored in the heap. So first let us see static allocation. So here the name itself indicates the static allocation means the memory will be allocated during compile time. Only. So before execution, the memory will be allocated to the variables in the static allocation. And here the memory is fixed memory. So memory is fixed throughout the program. So we can't change the memory. Okay. So because it was already allocated during the compile time, so it cannot be changed. And it is very fast access. So all the variables which are allocated using the static allocation will be accessed very fast and also easy for implementation. So it doesn't require any runtime allocations. So example, let us take this example. So for example, int x equal to 10, okay, and main function, and let us do this one, right? So the memory will be allocated for integer data type. So this is an integer data type with a name x, we have given x, and it will give some 10. So here it will be some 4 bytes of data. It occupies some 4 bytes of data. So before execution, this particular memory will be allocated, and which cannot be changed. So here memory cannot be changed. Okay, once allocated, the memory can't be changed. So one limitation of using this static allocation is, so this doesn't support recursion. Very, very important. It doesn't support the recursion, the static allocation. So why? Because let us take this one. See, I'll write int main function, and inside the main function, or let us write recursion means a function calling itself. So I'll write here some function name, and again I'll write some function. So let it be some x equal to 10, and let us take this one. Okay, this is an example for recursion. I think hope everyone understand, because in the function we are calling the same function, right? So once the function is called, immediately the control enters into the function, and it will create a variable x with a value 10. And once again there is a function call. Again the same function will be executed. So again one more memory will be created with a name x. So once again it was executed. One more memory will be executed with a value of x. That means multiple blocks of memory will be executed. Multiple memory blocks will be executed. So also there will be memory wastage in using this static allocation. So one more limitation may be wastage of memory. So these two are the limitations of static allocation. So it doesn't support the recursion. Okay, every time a new memory should be allocated. So every time a function calls, a new memory will be allocated. So this is the main reason why it doesn't support the recursion. Okay, and also, so multiple blocks of memory will be created with the same value, so there will be a wastage of memory. So for this reason, we are moving on with another allocation strategy called a stack allocation strategy. So hope you understood. Static allocation, memory allocated during the runtime. Yes. So now we'll see the stack allocation policy. Static, stack. Remember those terms. So the next one is a stack allocation strategy. Stack allocation. So here the stack allocation, the memory can be allocated and deallocated. Both can be done. Okay, allocated and deallocated during runtime, during runtime. So this is most important. So previously the static allocation, the memory will be allocated during compile time. Okay. So here the memory can be allocated and deallocated by you in the runtime itself, runtime. Okay. So variable memory, it can be using the variable memory. So it is not fixed memory, variable memory. Okay. So it is best for recursion. It is best for recursion. Why it is best means, so the recursion will be using the stack data structure in order to store the function calls. Okay, so it will be using stack data structure. Stack data structure. So stack, all of you know about the stack data structure, right? So here the last in first out, last in first out. Okay, so here what happens? See, let us write a small function. So I'll write a main function here. Some statements and function, some statements, close, and again we will write the function definition, and again some statements, function, some statements, and close. So this is a recursion. This is a recursion. So whenever there is a main function, okay, so whenever there is a function call, whenever there is a function call, see, most important this one, whenever there is a function call, then the stack frame will be created and it will be pushed into the stack. So stack frame, say new term, okay, stack frame will be pushed into stack, right? So that means whenever there is a function, immediately what happens, it will search for the function definition and the control moves towards the function definition, and once the function definition has been completed its execution, again it will come back to the calling function. So that's the concept of a function, either it can be a recursion or a normal function. So here we are using a stack data structure. What happens, whenever there is a main function, immediately one stack frame will be pushed into the stack. So this is a stack, this is a stack, okay, and this is called a stack frame. Stack frame, okay. So stack frame is also called as activation record. So in our previous session we have discussed about this activation record. So whenever there will be a function call, once the activation record will be created and that activation record will be pushed into the stack. Now immediately the execution of function will be started, and again here we are having a one more function. So again one stack frame for that function will be created. Okay, one more function for that particular stack will be created. So now the control goes here, the control moves here, right? Again there is a function definition, so it will be keep on executing. Again we are having a function call, so again a function definition, function call will be recorded. That means one activation record will be created and that will be pushed into the stack. So once it was completed, again what happens, so it will be popped. So once the function call executes, it will be popped and the control moves to that particular calling function. Okay, so whenever this function is created, this will be popped and immediately it will comes to here, and once immediately whenever this completed, again it goes to here. So again this will be popped, next time this will be popped and it will start execution, and again this will be popped and again it will be started its execution. So once this function is completed and this function will be popped and the control will move towards that particular address. So which will be stored in the stack, not the address, that is a activation record or a stack frame. We can call it as a stack frame. So whenever there is a function call, one activation record will be created and that will be pushed into the stack. So what exactly available in the stack frame? What exactly available in the stack frame? So stack frame or activation record, what exactly there? So there will be a local variables. So we can use the local variables in the function, subfunction, and also we may have the parameters that are passed from function call to function definition, and once it was completed, automatically it should return the value to the calling function. So it is a return address, So these three are the some of the fields, main fields of a stack frame. That's an activation record, right? So that's why this is a best for recursion. So we are using some stack and we are using the same memory. See, allocation and deallocation at runtime. So whenever there is a function call, one memory will be allocated. So that is the main function will be pushed into the stack. Once it was completed, we are popping. That means we are applying the pop operation. That means removing. Removing is nothing but a deallocation of a memory. So once everything is completed, the stack becomes totally free. So that means the stack is empty, the memory is empty. So this is the advantage of stack. So one is best for recursion. It's a best for recursion. Okay. So coming to the data structure, there is no data structure used in static allocation. So we'll write a small differences among the stack allocation and the static allocation. So hope you understood about the stack allocation, right? It's a runtime. It's a runtime. So the first one is a static allocation and another one is a stack allocation. So coming to the allocation time, it's a compile time allocation. The allocation time will be compile time, and here the allocation time will be runtime. Okay, and also here what we have seen, the limitation of a static is not suitable for recursion. So not suitable for recursion, and this is best option for recursion. So it's the best for recursion because we saw that allocation of, the memory will be allocated and deallocated during the runtime for every function call. And here we have seen memory wastage. Memory wastage will be there because multiple blocks of memory will be created here. But here memory can be used efficiently. Efficient use of memory. Efficient use of memory. So what is the data structure used here? So the data structure is fixed memory. So there will be no particular data structure. So memory is fixed here. It cannot be changed. But in this case, the stack data structure will be used. The stack data structure will be used. And here, no overhead. No overhead. Why there is no overhead means before executing the program itself, the memory will be fixed here. So there is no overhead. But here we are using a runtime environment. Okay, runtime. The memory is allocated and deallocated at runtime. So some overhead will be there. Some overhead will be there in this allocation. Okay, so these are a few differences among static allocation and dynamic stack allocation. Static allocation and stack allocation. So this is allocation time. This is allocation time. Okay, this is a limitation and memory based upon the memory and the data structure and overhead. Okay, and this is also fast, very fast. Somewhat overhead will be there. Okay, it's also fast, so no overhead. So the fast access will be done in the static allocation, right? So hope you understood what exactly mean the static allocation strategy and the stack allocation strategy, and also we have seen the differences among the static allocation and stack allocation. Activation record, simple and important. So here this activation record, also known as stack frame. So what we said is, whenever there is a function call, what happens? Immediately stack frame is created. Stack frame. So whenever I am saying it as a stack frame, imagine it is an activation record. Stack frame is created to store the complete details of function call. So what we said means, whenever there is a function, for example, let us take some main function. Inside the main function we are calling some function. Okay, and whenever the control comes here, the function call, whenever the control comes or executes this function call, immediately an activation record will be created and it will be pushed into the stack. So this is the activation record. That means here the activation record means information about the call, function call, information about function call. This is most important because once the function is executed, function completes its execution, definitely the control should go back to the calling function. So here the calling function is a main function. So whenever the control executes the function call, immediately this one activation record will be created for this particular function call, and that activation record will be pushed into the stack. So imagine this is a stack, and once the function activation record is pushed into the stack, immediately the control moves on to the function definition, and immediately whenever there is a function definition, executes the function. Now this particular stack, so the function will be popped from the stack. So whatever the function it is there, that will be popped from the stack, and immediately the control go back to this particular position. The control will move back to this particular position. So and again it will start its execution, sequential execution. So that is the most important thing of activation record, or we can call it as a stack frame. Both are equal. Now what are the fields or what type of information does the activation record maintains? So activation record contains, what are the different fields? The first one, parameters. So we are saying this activation record will be created whenever there is a function call. So obviously some sort of parameters, in some cases the parameters can be passed from function call to function definition. So if there are any parameters that are being passed from function call to function definition, so those parameter information should be available in the activation record. Then local variables, similar to the parameters, sometimes the function definition may also declare some variables. Okay, those are called as the local variables. So such type of local variable information also should be maintained in the activation record. And next, once the function completes its execution, that means once the function definition completes its execution, immediately the control should come back to the calling function. So return address, return address, return address, and then saved registers. If there are any registers to store the temporary data, so saved registers, the register information also to be maintained. And finally, control link, the link to the previous function, the link to the previous function, control link, or we can also call it as a dynamic link, dynamic link. So these are all the parameters, or what we can say entries which will be maintained in the activation record. So where this activation record is stored, so this activation record is stored in, just now we have seen, that is a stack, stored in a stack data structure. So last in first out, so it follows the last in first out. So the recently inserted activation record will be executed first, right? So let us take an example so that you can understand. So this is best suitable for recursions and nested functions. Recursions, nested functions, even functions can also be implemented using this activation record. For example, let us take, I'm taking a main function, and here I'm writing some function A and function B, and inside the A function I am writing function C, and inside the B function I am writing the D. So you can see. So first, sorry, I'll write here. So first the stack is empty. So whenever this executes, so a main function will be executed. That means the activation record for main will be stored here. And immediately whenever control executes the A, what happens? The activation record will be created for A and it will be pushed into the stack. What happens next? The control moves towards A. Now again it starts executes, again we got a C. The third step, already main is available, A is available. Now there is again function call on C. So C will be pushed into the stack. That means the activation record for C will be pushed into the stack. Once it was completed, what happens? Once it was completed, its execution, it will pop. Okay, sorry, I'll write here. So it will move towards this one, and whenever it completes, it comes here, right? So for this, C will be popped and it will reach to the same position. Okay, this is a stack. So what happens here? C is popped. Pop. Now it will execute up to here, and now after completion of this one, what happens? Again, it will pop the top of the stack and it will go. So what is the top of the stack? A. So A will be popped and the address will move to the, see, here, and it will start again the execution. Now B is there. So once again, already main is here. Again the function call executes the B. So activation record of B will be stored here, and now the control moves towards B, right? Next again D is available. So next case, the main is here, B is here, and again the activation record of D is stored in a stack, and it start executing the function D. Whenever it completes its execution, it will pop and it will return back here. So the next case is a main function and B. So D is popped from here, and once it completes its execution, B completes its execution, again it moves towards the main function. So that means again there will be a pop on B and it will move, the control moves towards the place where it came. Again it completes its execution, main. So again main will be popped. Main will be popped. So obviously there is an empty stack. So this is the order how the activation records will be maintained. Okay, so when there is a function call, definitely we have to maintain the complete information about the function call. So that will be done with the help of the stack data structure. Okay, so if you, I think you understand the complete thing. So from the starting itself, I have given the complete information. So if you represent the same thing in a hierarchical structure, that is called as an activation tree. So this is an activation record. So first main function, next A is pushed, record activation record if A is pushed, so the control moves to A, and again there is a function called activation for record of C is pushed into this stack, and again the control moves to the function definition of C. There is no function call. After completion of C, it will pop the top of the stack, that is a C, and it get back to its positional correct position, and it continues its execution, and whenever it comes to end of the A, again it will pop A from the stack and it will move to the main function. Again it is here, it is a B and follow the same procedure. So considering the same procedure in a hierarchical fashion is called as a activation tree. So let us check that one. Okay, so hope you understood this one, and I'll erase this one. I'll erase this. See, main function, the first it executes the main function. So when there is a main function, there will be a function call, and immediately in this function call again C will be created. There is one more function call of C, and there is no functions completed. So it come back to A. So it come back to A. It come back to main, and then B will be created, and then it moves to the B, and again there is a D function call. So D will be executed. It goes to the D procedure. So there is no other function call. It completes its execution. It comes back to B, and it comes back to main. So this process. So here A, B, C, D are nothing but activation records. So we can consider them as activation records. So whenever there is a function call, this record will be created. So this is called activation tree. The working of function or the working of activation records in a tree structure. Okay, you can represent that in a tree structure. So this is called as an activation record and activation tree. So hope you understood about this one. So very simple and important thing, because everywhere we are using the functions concept. So if there is a function concept, the compiler will create these activation records, and also known as a stack frame. So we have mentioned what are the entries available in the stack frame. So local variables, parameters, return address, control link or dynamic link, and one more thing, that is a control link, dynamic link. Okay, and also saved registers. So these are all the content which are available in the activation record.